All right, let's take a look at the practice test. For the instructions, we're asked to find the exact value. All right, let's take a look at the first problem. So here we have the inverse sine of negative square root of 3 over 2. Before we answer this, I want to revisit the graph of y equals the inverse sine of x. So what's the domain? Looking at the graph, we can see that it's from -1 to +1. Let me just write this out. So this is the domain. It's going to be from -1 to +1. -1 and +1 are included. Now for the range, which is really what we're going to focus on here, you see it's from -pi/2 to pi/2. Both are included. So from -pi/2 to pi/2. Okay, so now that we've established that, let's go back up, and I'm just going to copy this. So we have the inverse sine of, and we have negative square root of 3 over 2 as the argument. What you want to do is you want to think about that range. So in other words, the result of this guy right here is going to be from -pi/2 to pi/2. So if this guy is positive for the argument, you want to work in this first quadrant here. If this guy is negative, you want to work in this fourth quadrant here, but you're going to be rotating clockwise. So in other words, if I think about where the sine value is negative square root of 3 over 2, well, looking at my unit circle, you're going to see that right here. That's at 4pi/3. And then you're going to get that again right here at 5pi/3. So we're not interested in this guy right here because it's in quadrant 3. So I'm just going to delete this, and I'm going to focus on this one right here. So this right here is what we want to think about. But again, we can't use 5pi/3 because that is not within the range of the inverse sine function. So what you can do, the slow way is to say you have 5pi/3, and you're going to subtract away 2pi. So minus 2pi, so that's 6pi/3. So that gives you -pi/3. So that would be the answer there. And what you're basically doing is you're saying, okay, if I started here and I rotate, so if I rotate to this 5pi/3, well, to correct for the fact that with the inverse sine function, you're rotating clockwise, I really want this guy right here. That's the angle I want, which is -pi/3. So what you would have to do is start from here and rotate by -2pi, so by -2pi, and then come back to right there. So essentially you have the 5pi/3 minus 2pi or minus 6pi/3, which gives you that -pi/3. Now, that's the slow way to do it. What's the fast way to do this? You just realize that this guy right here has a reference angle of pi/3. So basically, if I want a clockwise rotation, this angle right here is going to be -pi/3, right? So this would be -pi/3. It's just that simple. So the answer here, let me just erase this and I'll just put is equal to -pi/3. So that's going to be for the inverse sine of negative square root of 3 over 2. All right, for problem 2, we have the inverse tangent of 0. Now, most of you know this is pretty easy. It's just going to be 0. But let's look at the graph for y is equal to the inverse tangent of x. And we're just going to think about it for a moment in case it comes up again. So basically, we know that the domain from the lesson is the set of real numbers. So in other words, it's from -infinity to +infinity. So I can plug in any real number that I want for x and there's no problem. Now for the range, this is again where you have to be careful. So it's going to be from -pi/2 to pi/2, but -pi/2 and pi/2 are excluded. When we looked at the inverse sine function, they were included, but here they're excluded. And that's because the tangent of -pi/2 is undefined, as well as the tangent of pi/2. They're both undefined because at -pi/2 or pi/2, the cosine value is 0, so you get division by 0, which is undefined. So for the range, we get from -pi/2 to pi/2, and those are excluded. Now, if we come to the unit circle, again, just like with the inverse sine function, if we have something that's positive, we're working here in this first quadrant. If you have something that's negative, you're working in this quadrant. Again, you're rotating clockwise for the negative argument. Now, in this case, you have 0. So I'm thinking about a tangent value of 0, and of course, that's not on the unit circle. We all know that it's going to end up right here with this angle of 0, but let's just think about this for a moment. The tangent of 0 is equal to the sine of 0 over the cosine of 0. And the sine of 0 is 0, and the cosine of 0 is 1. So the tangent of 0 is equal to 0. So in other words, when I go the inverse tangent, so the inverse tangent of 0, that's going to get me back to 0, which is this angle right here. All right, let's take a look at problem 3. So here we have the inverse secant of -2. So we're going to end up converting this over into an inverse cosine function problem. But before we do that, let's just look at the graph again for the inverse secant function. So y is equal to the inverse secant of x. So the graph looks something like this. And essentially, what you'll see is that for the domain, what we have here is x can be -1 or anything less. So the way you would write that is coming from -infinity, going up to and including -1. So you have a parenthesis with -infinity, and then a bracket with -1 to show it's included. And then you have the union with from 1 out to positive infinity. So 1 is included, so again, we're going to use a bracket there, and this goes out to positive infinity. So the problem was the inverse secant of -2. So is that within the domain? Yes. If you come over here to an x value of -2, well, if I go up, I'm going to have a point right there, and this is going to end up being -2, 2 pi over 3, and we'll find that in a moment. For right now, let's just look at the range and think about this in case we have another problem. So we have the range, and what is that going to be? Well, if I look, it seems like the y values start at 0 and go up to pi, with an exception of this value right here, which is going to be pi over 2. So this line in orange, this dashed line, this is a horizontal asymptote. And so basically that's the line y equals pi over 2. So the range, if you want to write it in interval notation, you could say from 0 and including 0, going up to and excluding this pi over 2. So you want to use a parenthesis here with pi over 2 and a bracket here with 0 because 0 is included and pi over 2 is excluded. And the union with, you're going to, again, exclude this pi over 2. So that's why you're using a parenthesis there. And then you're going to go up to and include. This value right here is going to be pi. And that, again, is included. So you're using a bracket. Okay, so that's the range. What we would do is actually convert this into an inverse cosine function problem. So you can say that the inverse secant of -2 is equal to the inverse cosine of, you're just going to take the reciprocal of this. So this is -1/2. You're going to end up getting 2 pi over 3. But let's think about where that's coming from with this inverse cosine function graph. So let's write that this is y equals the inverse cosine. Let me move this stuff out of the way. So of x. So here, the domain is going to be from -1 to +1. So from -1 to +1, both are included. And then your range, this is the one you really have to pay attention to. It's going to be from 0 to pi. So both of those are included. So from 0 to pi. So let's think about this problem real quick. I'm just going to grab this and come to the unit circle. So thinking about the inverse cosine of -1/2, again, I said that the range is from 0 to pi. So if this argument here is positive, you're working in quadrant 1. If it's negative, you're going to be working in quadrant 2. So this is negative. So I'm going to be working in quadrant 2. And I'm just asking, where is the cosine value -1/2 in quadrant 2? So that's going to be right here at 2 pi over 3. So to answer this question, the inverse secant of -2, that's going to be equal to the inverse cosine of -1/2, which is going to be 2 pi over 3. All right, let's take a look at problem 4. So here we have the inverse cotangent of -1. All right, this problem is a little bit tricky because if you try to use the inverse tangent function in order to solve that problem, you have to make a bit of a correction. So although it may be different in your textbook, most trigonometry textbooks will show this as the inverse cotangent graph. So y equals the inverse cotangent of x. Now, the domain is the same as the domain from the inverse tangent function. So it's just all real numbers. So that's not going to change. So the domain is the set of real numbers, so from -infinity to +infinity. But the range, this is where we have to be careful. So if you look at this, you're going to have from 0 to pi, where both are excluded. So basically 0 to pi, both are excluded. And obviously, if you took the cotangent of 0, it would be undefined, and the cotangent of pi would be undefined, because in each case, the sine of 0 is 0, and the sine of pi is 0, so you'd have division by 0, which is undefined. Let's come to the unit circle and think about this. We have the inverse cotangent of -1. So based on what I just told you, you're looking in quadrants 1 and 2, and you're thinking about, well, where am I going to get a cotangent value that's -1? A lot of you know that's going to happen right here at 3 pi over 4. Because if I think about the cotangent of 3 pi over 4, well, this is the cosine of 3 pi over 4, which is negative, so negative square root of 2 over 2, divided by the sine of 3 pi over 4, which is square root of 2 over 2. So I'm going to multiply by the reciprocal, so times 2 over the square root of 2. So these would cancel, and then these would cancel. So your result here is going to be negative 1. And I know most of you know that the cotangent of 3 pi over 4 is negative 1. So that means the inverse cotangent of negative 1 is going to give me 3 pi over 4. Again, it's got to be within the range of that inverse cotangent function. Now let's talk about what you could do if you didn't have a unit circle handy, or maybe you didn't know this stuff, and you're trying to use your calculator. So your calculator probably only has an inverse tangent button. So we could say that the inverse cotangent of negative 1 is equal to the inverse tangent of, you take the reciprocal of this, so this is negative 1, but there's a problem. You need to do a little bit of a correction here because you're not going to get to 3 pi over 4. Again, with the inverse tangent function, if you have a negative argument, you're going to be in quadrant 4 rotating clockwise. So we talked about that earlier. Basically, you would be right here. Again, you would rotate clockwise by pi over 4. So right there, that would give you negative pi over 4. So how can I correct for that and get back to here? Essentially, when this happens, you're going to have to add pi to get to the correct angle. So what I would do is start at negative pi over 4, and I would add pi. So add pi, and that's going to get me right here. So I'm going to put plus this pi over here, and that's going to give me a correction. So if I key this into my calculator, essentially I'm going to get negative pi over 4, and then I've got to add pi to make that correction to get myself where I want to be in quadrant 2. So that's going to be me adding 4 pi over 4. That's just pi with a common denominator. So that gets me to that 3 pi over 4 that I'm looking for. All right, let's take a look at problem 5. So here we have the inverse cotangent of the square root of 3. So for this one, because the argument is positive, let me write this out. So the inverse cotangent of the square root of 3, you can just key this into your calculator by saying you have the inverse tangent of, you're going to take the reciprocal of this, so 1 over the square root of 3. Of course, if you want to rationalize the denominator, you can. It's not necessary with your calculator. It would just be something you want to do if you need to show your work to your teacher. So this would be square root of 3 over 3. So square root of 3 over 3. And most of you know this is going to be pi over 6, because again, the tangent of pi over 6, let me write this out for clarity, the tangent of pi over 6 is going to be the sine of pi over 6, which is 1/2, and then divided by the cosine of pi over 6, which is square root of 3 over 2. So you multiply by the reciprocal, so times 2 over the square root of 3. The 2's cancel, and you get 1 over the square root of 3, which again, if you rationalize the denominator, you get square root of 3 over 3. So the answer here is just going to be pi over 6. And again, it does not require a correction here because with the inverse cotangent function, if I have a positive argument, I'm working in quadrant 1. That's where I'm looking. And then with the inverse tangent function is the same thing. If I have a positive argument, I'm going to work in quadrant 1. That's where I'm looking. All right, let's take a look at problem 6. So here we have the inverse cosecant of a negative square root of 2. Now, if I look at my inverse cosecant function, so this is y equals the inverse cosecant of x, we think about the domain. So this is going to be, let me write out the domain here. This is going to be from negative infinity coming up to negative 1, and negative 1 is included. So from negative infinity going up to negative 1, and that's included. And then union with positive 1 is included, and then anything out to positive infinity. So that's your domain. But more importantly, we're thinking about the range. So you're going to go from negative pi over 2 to pi over 2, but you're going to exclude 0. So for the range, and this is the important one here, so for the range, we're going to say that we're coming from this right here, let me put is negative pi over 2, and this right here, let's say that's pi over 2. So for the range, you're going to say from negative pi over 2, and then you're going to go to 0. 0 will be excluded. And then the union with, you're going to cut 0 off, so it's excluded. And then basically up to pi over 2, and that's going to be included. So anything from negative pi over 2 to pi over 2, where those guys are included, we're just going to exclude 0. Now we're good to go. If I plug in negative square root of 2 in for x, I don't have a domain violation, so everything's okay. So I'm just going to come down here and write the inverse cosecant of this negative square root of 2. And I'm going to change this over and say it's the inverse sine of, again, you're just going to take the reciprocal of this, so negative 1 over the square root of 2, and I would rationalize the denominator, so times the square root of 2 over the square root of 2. So this would be negative square root of 2 over 2. So negative square root of 2 over 2. Okay, so for this one right here, if you think about where is the sine value negative square root of 2 over 2? So I'm just going to go on the unit circle where sine is negative. Again, that's in quadrants 3 and 4. So we're looking at this guy right here, so at 5 pi over 4, and then this guy right here, that's at 7 pi over 4. Now again, with the inverse sine function, if the argument is negative, I'm working in quadrant 4. So I'm going to get rid of this one right here. We don't need that. And we're looking at this right here. But again, I don't want 7 pi over 4 because I've got to rotate clockwise. Again, the shortcut here is to think about the fact that this has a pi over 4 reference angle, so this rotation here would just be negative pi over 4. Again, that's the quick way. The long way is to take the 7 pi over 4 and then subtract away 2 pi, so subtract away the 8 pi over 4, and that gives you negative pi over 4. So however you can get that straight in your mind, the other way is a little bit longer, but it's still going to get you to the right answer. So this is going to be negative pi over 4 for the answer. Okay, let's take a look at problem 7. So here we have the inverse sine of the sine of 3 pi over 4. So the inverse sine of the sine of x is equal to x only if x is greater than or equal to negative pi over 2 and less than or equal to pi over 2. Why is that the case? Let's come back up here and think about this. I'm just going to write y is equal to the inverse sine of, let's just say, x. We know when we look at this that the range is from negative pi over 2 to pi over 2, with both of those values being included. So in other words, what we're doing here is we're taking this guy right here and we're plugging it in right there, and we're saying, should I get 3 pi over 4 as the answer? That's what a lot of people do. They just try to cancel this with this and say it's 3 pi over 4. Well, no. The result of taking the inverse sine of something is going to give you something that's between negative pi over 2 and pi over 2, with those two values being included. 3 pi over 4 is not in that interval, so you cannot answer that way. So what you'd have to actually do is say that for the inverse sine of the sine of 3 pi over 4, you would first say that you want the sine of 3 pi over 4. So what is that? Well, we come to 3 pi over 4. The y-coordinate is square root of 2 over 2, so that's your sine value. So let's go ahead and say that this is the inverse sine. So the inverse sine of the square root of 2 over 2. Now, when I key this into my calculator, I'm not going to get 3 pi over 4. Because again, how the inverse sine function works, if this is positive, I'm getting something in quadrant 1. So I'm looking in quadrant 1 for a sine value of square root of 2 over 2. So that's going to be right there at pi over 4. So this would give me pi over 4 as an answer. All right, let's take a look at problem 8. So we have the inverse cosine of the cosine of 2 pi over 3. For this particular one, you can actually use the cancellation property. So the inverse cosine of the cosine of x is equal to x if x is greater than or equal to 0 and less than or equal to pi. So coming back, if we think about this, is 2 pi over 3 greater than or equal to 0 and less than or equal to pi? Well, yeah. 2 pi over 3 is greater than 0 and it's less than pi. So we can just answer right away that this is 2 pi over 3. If you went through this the long way, so you have the inverse cosine of the cosine of 2 pi over 3, and you can always do this the long way if you want. So the cosine of 2 pi over 3, that's going to be right here. So your x value is negative 1/2. So this is going to be the inverse cosine of negative 1/2. And again, with the inverse cosine function, you're working in quadrants 1 and 2. Right? So basically from 0 to pi, and if the argument is negative, you're going to be in quadrant 2 where cosine is negative. So you're looking for a cosine value of negative 1/2. So that's right here, again at 2 pi over 3. So this just reverses what you just did. So you're right back to the 2 pi over 3. All right, let's take a look at problem 9. So here we have the inverse tangent of the tangent of 11 pi over 6. So if you want to use your cancellation property, in other words, if you want to say the inverse tangent of the tangent of x is equal to x, well, that's only true if x is greater than negative pi over 2 and less than pi over 2. We have 11 pi over 6, so that is not going to be in this interval. So if I come back up here, I need to do some additional work. So I need to evaluate this first before I can take the inverse tangent. So let's go ahead and write the inverse tangent of the tangent of 11 pi over 6. Let me grab this real quick. And I'm just going to come to the unit circle. And basically, the first thing you'd want to figure out, well, what is the tangent of 11 pi over 6? A lot of you know that's negative square root of 3 over 3. But again, if you don't know that, you can still use the values here from the unit circle to get it. So you can say, what is the tangent of 11 pi over 6? Well, that's the sine of 11 pi over 6, which is negative 1/2, divided by the cosine of 11 pi over 6, which is square root of 3 over 2. So you'd multiply by the reciprocal of that, so times 2 over the square root of 3. And so these 2's would cancel, and you get negative 1 over the square root of 3. I'd multiply by the square root of 3 over the square root of 3 to rationalize the denominator. So I get negative square root of 3 over 3. I know a lot of you already know that. When you evaluate this right here, tangent of 11 pi over 6, you get negative square root of 3 over 3. So now I'm going to say that this is equal to the inverse tangent of the negative of the square root of 3 over 3. Okay, well, when I look at that, again, this tangent value, I'm working in quadrants 1 and 4. When I'm in quadrant 4, when I have a negative argument here, I want to rotate clockwise. So again, I'm thinking about this angle right here, but I'm not thinking about it as 11 pi over 6. There is a pi over 6 reference angle there, and I'm rotating clockwise. So this right here is going to be negative pi over 6. So I want to give that as the answer. So this would be equal to negative pi over 6. All right, let's take a look at problem 10. So here we have the cosecant of, we have our inverse sine of 12 over 13. So for this type of problem, I'm going to make a little substitution. I'm going to let something like, let's say u, be equal to this guy inside, so the argument for the cosecant function. So that'll be equal to the inverse sine of 12 over 13. So once I do that, I can say then the sine of u is equal to 12 over 13. Because again, if the sine of u is equal to 12 over 13, well, the inverse sine of 12 over 13 will get me to u. Now, once you've done that, you can basically say that this guy is going to be the cosecant of u. Because again, u is equal to the inverse sine of 12 over 13, so this guy right here. So the cosecant of u, by definition, is 1 over the sine of u. And here, the sine of u is 12 over 13, so just take the reciprocal, and you're going to get 13 over 12. So my answer here would just be 13 over 12. All right, let's take a look at problem 11. So we have the tangent of the inverse cosine of 3/5. All right, for this problem, just like in the last problem, I'm going to make a little substitution. So I'm going to let something like, I'm just going to use u. I typically use that. If you want to use theta, that's fine. Use whatever you want. But I'm going to let u be equal to the argument for the tangent function. So what's inside here? So basically this inverse cosine. So this inverse cosine of 3/5. So once we've done that, we can say then the cosine of u is equal to 3/5. Again, if the cosine of u is 3/5, then the inverse cosine of 3/5 is going to be u. Well, since the inverse cosine of 3/5 is u, now I just want to say that I have the tangent of u. So I'm going to put that the tangent of u is equal to what? So this is what I'm trying to find. So in order to do that, let me slide down a little bit. We'll come back up in a little while. I'm going to go back to what we did at the beginning of trigonometry. So if I have something like the cosine of u is equal to 3/5, and I know the quadrant of u, well, then I can find the tangent of u. First, let's identify what is the quadrant. So we know that the cosine of u equals 3/5, and cosine is positive in quadrants 1 and 4. But in this particular situation, think about the fact that you have the inverse cosine of 3/5. So if this guy right here is positive, so a positive 3/5, that means I'm getting something back in terms of u in quadrant 1 because of the range of the inverse cosine function. So that tells me right now that u is in quadrant 1. Let me make that q a little bit better there. So once I know that, then I'm just going to go through and say, okay, based on the definitions for my trigonometric functions, the cosine of u is equal to x over r. Remember, x is your adjacent, r is your hypotenuse, and then the sine of u is equal to y over r. So y is the opposite, r is the hypotenuse, and then the tangent of u is equal to y over x. Okay, well right now I have 3 over 5 for this cosine of u, So that tells me that x is 3 and r is 5. So let me write that x is equal to 3 and r is equal to 5. Now, most of you know that y is going to be 4 because this is a 3, 4, 5 right triangle. But let's just go through and figure that out. Let's just pretend we didn't know it. Of course, you could sketch a triangle if you needed to. You can pause the video and do that on your own. I think this problem is easy enough to where we don't have to do that. So we would just use our Pythagorean theorem. We know that x squared plus y squared is equal to r squared. So just coming straight from the Pythagorean theorem, something we did earlier in the course. And basically you would take your 3, so 3 squared, plus, again, let's pretend y is unknown. So let's put y squared is equal to r, which I need to plug in for that. So that's known, so that's 5 squared. So 3 squared is 9, and then 5 squared is 25. And then essentially you would subtract 9 away from each side of the equation, and this would go away. And 25 minus 9 is 16. So at this point, you would use your square root property and say y is equal to plus or minus the square root of 16. Now, we know that we are in quadrant 1. Again, we established that earlier. So in quadrant 1, y values are positive, so I don't need the plus or minus here. I just want the principal square root of 16, and that's going to be 4. And of course, we already knew that because this is a 3, 4, 5 right triangle. But again, if you didn't realize that, then that's how you can go through and figure it out. So at this point, I know that x is 3, y is 4, and r is 5. Now, I don't actually need r in this particular case. I just needed it to figure out what y was. But I'm just going to plug in a 4 for y, and I'm going to plug in a 3 for x. And so the tangent of u, what I was trying to figure out over here, is going to be 4/3. Let me actually erase everything and put this in terms of the original problem. So just coming back up here, the tangent of the inverse cosine of 3/5, that's going to be 4/3. All right, let's take a look at problem 12. So here we have the cotangent of the inverse sine of 3/4. So again, I'm just going to use a little substitution. I'm going to let u be equal to the argument for the cotangent function. So basically it would say this is equal to the inverse sine of this 3/4. And once we do that, we can then say that the sine of u is equal to 3/4. Now, we're going to end up just replacing this, again, with u. So we want to find the cotangent of u. So that equals what? Let me slide down here. I'll come back up in a little while. Remember from earlier in the course that, again, if you know the sine of u is 3/4 and you know the quadrant of u, well, then you can find the cotangent of u. The cotangent of u is going to be x over y. It's the reciprocal of the tangent of u. So what quadrant is my angle u going to lie in? Well, again, this is positive here, so a positive argument for the inverse sine function, that's going to give me an angle in terms of u that's going to be in quadrant 1. So I know that u is in quadrant 1. Now that we've established that, again, we're going back to that basic exercise from the beginning of trigonometry. The sine of u is equal to y over r. So this is your y, that's your opposite. This is your r, that's your hypotenuse. So all you really have to do here is say that x is equal to, I'm just going to put a question mark, y is equal to 3, and r is equal to 4, and just use the Pythagorean theorem. So remember, we have x squared plus y squared is equal to r squared. So x is unknown, so let me write x squared, plus we know y is 3, so 3 squared is equal to r squared. R is known, that's 4, so this is 4 squared. So 3 squared is 9, and 4 squared is 16. And so basically what you would do here is subtract 9 away from each side of the equation. And so this is going to cancel away, and you're going to get that x squared is equal to, if you look at 16 minus 9, that's going to be 7. So by the square root property, you could say that x is equal to plus or minus the square root of 7. Okay, let me actually erase this. When we think about our x values, again, we know that u is in quadrant 1, and so the x values are positive. So I just need the principal square root of 7 there. I don't need the negative, so let's put that in there. And maybe this doesn't fit so well, so let me rewrite this. So x is equal to the principal square root of 7, and then y is equal to 3, and then r is going to be equal to 4. So the cotangent of u is x over y. So what is my x value? Again, that is going to be the square root of 7. And then what is my y value? That's going to be 3. So the cotangent of u is the square root of 7 over 3. Now let me erase all this, and I'll just come back and answer in terms of the original problem. So the cotangent of the inverse sine of 3/4, that's going to be the square root of 7 over 3. All right, for the next problem, we're going to change things up a little bit. For the instructions, we want to write as an algebraic expression in u. All right, let's take a look at problem 13. So here we have the secant of the inverse sine of u over the square root of u squared plus 4. So this problem is actually pretty easy overall. You just need to make a sketch and go back to your SOHCAHTOA. And what I'm going to do first is just make a little substitution like we've made in the previous problems. So I'm going to take the argument for the secant function. So this guy right here, this inverse sine of u over the square root of u squared plus 4. And I'm going to set that equal to a variable. Normally I would use u, but since u is taken, I'm just going to use w. So you see here that I have let w be equal to the inverse sine of u over the square root of u squared plus 4. So then we can say that the sine of w is equal to u over the square root of u squared plus 4. So once I make this little substitution, now I'm just trying to figure out what is the secant of w. Because again, w is this. So let's say this equals what? Now going back to the SOHCAHTOA, remember that if we think about our cosine function, it's going to be the adjacent over the hypotenuse. For the secant function, we take the reciprocal. So this is by definition the hypotenuse over the adjacent, and normally we write that as r over x. Now before we continue, what can we plug in for the inverse sine function? We have this expression here, and we really want to think about, am I going to be able to plug in something that's going to violate the domain of the inverse sine function? And then, is something going to happen where I'm going to violate the domain of the secant function? So you really want to think about that if you're not given any restrictions. So the first thing is, we know that the domain, so the domain for the inverse sine function, so y equals the inverse sine of x, this right here is going to be from -1 to +1, with both being included. So the question would be, is there anything that I can plug in here for u that's going to result in me getting a value that is outside of this domain? Well, to answer that question, I think the fastest way is to look at a graph. You can go to Desmos and just sketch this. What you'd want to do is sketch the graph of y is equal to, let's just say it's x over the square root of x squared plus 4. So you would notice immediately that the domain of this guy right here is going to be all real numbers. So the domain is the set of real numbers. So from -infinity to +infinity. So that tells me if I go back up, I can plug in anything for u. So I can plug in a negative, a positive, 0. And so that is the first part. Now, I need to focus on the result of this, or the range, because the range of this, or the output values here, that's going to become the domain for the inverse sine function. In other words, I plug in something for u, I go through this guy, and I get a result, and then basically I'm taking the inverse sine of that. So looking at the range here, what you're going to see is it's going to work out quite nicely. Looking at the range, it's going to be from -1 to +1, with those guys being excluded. The way you can see it's excluded is that you have a horizontal asymptote at y equals 1 and also y equals -1. So those are those horizontally dashed lines. Let me actually arrow to these and say that this right here is y equals -1, and then this right here is going to be y equals +1. So for the range, let's go ahead and write this is from -1 to +1, with those two values being excluded. So that's why I wrote a parenthesis here and a parenthesis here. Now, let's come back up and let's think about this. So no matter what I plug in for u, again, the domain is all real numbers, the result of this guy right here will be from -1 to +1, with those guys being excluded. So I will never violate the domain of the inverse sine function. Okay, so we've established that, so we're good to go there. Now, let's think about this in terms of the secant function now. I want to go to the unit circle, and I want you to remember, if you have something like the secant of w, this is going to be undefined, so is undefined. Where? Well, basically at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so basically pi over 2 plus pi n, where n is any integer. So I'll say is undefined for pi over 2 plus pi n. Now, This would also include something like negative pi over 2. So in other words, if I started here and I rotated clockwise by pi over 2, so this would be an angle of negative pi over 2. Let me get rid of this real quick. So remember, if you take the inverse sine of positive 1, you get pi over 2. And if you take the inverse sine of negative 1, you get negative pi over 2. So if we were able to do that, we would see that our secant function is undefined. But remember, 1 and negative 1 are excluded. So we're not going to be able to get to that. So when we're working in our problem, in terms of that expression, our inverse sine function is going to be working this right here. So basically from negative pi over 2 to pi over 2, with those guys being excluded. So you could really say that w is greater than negative pi over 2 and less than pi over 2. So thinking about that, we're not going to encounter a situation where the secant of w is undefined, because it would need to be pi over 2 or negative pi over 2 for that to happen in this particular case. All right, coming back here, let me just paste this in so this is clear. You could write that down for your notes. Again, like we just talked about, we know the secant of w is not going to be undefined because w is greater than negative pi over 2 and less than pi over 2. Now, looking at this guy, we're going to make a little sketch. If u is positive, so just think about this for a moment. If u is positive, this whole thing's going to be positive. So the inverse sine of something that's positive is going to give me something in quadrant 1. Remember, this is not going to be positive 1. That's excluded, so we're good on that. We already covered that. So basically, if I look at my sketch, I'm just going to cover this part for right now. This is if u is positive. So I know I'm going to get something in quadrant 1 in terms of w. Now let's go back up. The other scenario is, what if u is negative? So if u is negative, well, this whole thing is negative. And again, the inverse sine of something that's negative, you're going to get something in quadrant 4 rotating clockwise. Again, we're not going to have negative 1 here. That's going to be excluded. So you're not going to get a negative pi over 2. So let's go back down and let's look at that. So this is where u is less than 0 or negative. So that's this angle w here rotating clockwise. So now that we've set that up, let's go ahead and say that the secant of w is equal to, again, it's just going to be the hypotenuse. So the hypotenuse over the adjacent. So the hypotenuse is the square root of u squared plus 4. Again, we're getting that from this sine of w equals u over the square root of u squared plus 4. So the hypotenuse is down here. It's opposite over hypotenuse. So that's labeled here as square root of u squared plus 4. So this is your hypotenuse here. It's also labeled here. So this is the square root of u squared plus 4. So remember, the hypotenuse is always positive. In terms of u, it would be positive here and then negative here. So we've already established that. But when we think about the adjacent, because we're either in quadrant 1 or quadrant 4, where x values are positive, well, this is always going to be a positive 2. And the way you work that out mathematically, let me just slide down here a little bit. You can just say that u, again, whether it's positive or negative, it's not going to matter because we're going to square it. So let's go ahead and say that it's u squared plus, you would have, this guy is unknown. Let's just call it x. So x squared, it's going to end up being 2, but you'll see that in a moment. This would be equal to the hypotenuse squared. So let me come down here and say that this would be the square root of u squared plus 4, and this guy would be squared. Okay, well, if I square this, this is going to cancel with this, and I'm going to have the radicand. So I would have u squared plus x squared is equal to, the radicand is u squared plus 4. Well, look at how this is going to work out pretty nicely, because I can subtract u squared away from each side of the equation. This is going to cancel, and this is going to cancel. So this is going to give me x squared is equal to 4. Now I know that I'm either in quadrant 1 or 4, and x values are positive there, so I want the principal square root here. So I would just say x is equal to the principal square root of 4, which is 2. So let me erase all this, and let me come back here. So that's how I get this right here for the adjacent. That's going to be 2. So to answer this problem, finally, after all that work, the hypotenuse is the square root of u squared plus 4. Now we already knew that. And this is over the adjacent, which is what we just solved for. That's going to be 2. So that's going to be the solution for this problem. The secant of w is the square root of u squared plus 4 over 2. Again, where w is greater than negative pi over 2 and less than pi over 2. Let me go ahead and grab this real quick. And I'll just come all the way back up here and answer in terms of the original problem. So let me paste this in right here. And I don't need two equal signs there. So the secant of the inverse sine of u over the square root of u squared plus 4 would give me the square root of u squared plus 4 over 2. All right, for the next few problems, we're going to change the instructions back to say we just want to find the exact value. All right, let's take a look at problem 14. So I'll just tell you in advance, this one's pretty tedious. So you have the cosine of the inverse tangent of 5/12 minus the inverse tangent of 3/4. So the first thing I would do is make 2 different substitutions. I think that's the easiest way to solve this problem. There's other methods you could use. It's really up to you. I'm just going to let something like u be equal to this right here. So this is equal to the inverse tangent of 5/12. And so from that, I can say that the tangent of u is equal to 5/12. And then I'm going to let w be equal to this other guy. So the inverse tangent of 3/4. And then we can say that the tangent of w is equal to 3/4. So first off, I know that if this argument is positive and this argument is positive, then both these angles are going to be in quadrant 1. So I could say that u is in quadrant 1. So I'm just going to do it like this, and then I'll put w that's also in quadrant 1, just as a reminder. So let me actually just grab this real quick, and I'm going to paste this in here. We need a lot of room to work. Let me come back up. So this is u, and this is w. So I'm going to write this as the cosine of u minus w. So let me grab this. So let me paste this in here. Now, most of you have this memorized, some don't. So for your difference identity for cosine, we're going to have the cosine of the first guy times the cosine of the second guy plus the sine of the first guy times the sine of the second guy. So here it's the cosine of the first guy is u times the cosine of the second guy is w, and then plus you have the sine of the first guy, which is u, times the sine of the second guy, which is w. So this is what I need to figure out. I need to get the cosine of u, the cosine of w, the sine of u, and the sine of w. So let's go back up to this right here, and this is where you have to put the work in. So we have that the tangent of u is equal to 5/12, and I know I'm in quadrant 1. For the tangent, it's going to be your opposite over your adjacent, or you could say your y over your x. Okay, so that tells me that x is equal to 12 and y is equal to 5. Now, a lot of you know that r here is 13 because it's a 5, 12, 13 right triangle. But again, you go through the work and you say that this is x squared plus y squared is equal to r squared. Again, r is the length of the hypotenuse. So when we think about this you plug in a 12, you get 12 squared, which is 144. This you plug in a 5, you get 5 squared, which is going to be 25. So that equals your r squared. So 144 plus 25 is 169. So you get r squared. So r squared is equal to 169. So r is equal to plus or minus the square root of 169. But again, your r is always positive. So this is going to be positive 13. Again, we already know that because of the special right triangle. But let's go ahead and say that for the sine of u, it's equal to your opposite over your hypotenuse. So that's going to be y over r, or 5 over 13. And then your cosine of u is going to be equal to your adjacent over your hypotenuse. So x over r, or 12 over 13. Come down here and paste this in. And let me go get the other ones. We'll come back up. So let me erase this. We're going to work in terms of the other one now. So we're thinking about w. So we have the tangent of w is equal to 3/4. So again, this is y, and this right here is x. So this is going to be a 3, 4, 5 right triangle. Again, a lot of you already know that. If you get this on a test, just skip ahead and say, okay, well, r is 5. But for the sake of the tutorial, let's write that x is equal to 4. Let's write that y is equal to 3. And r, let's just put 5 for right now. But again, this was x squared plus y squared equals r squared. If you don't know what it is, x is 4, so 4 squared is 16, plus y is 3, so 3 squared is 9, and this equals r squared. So this becomes 25 over here. 16 plus 9 is 25. And you want the principal square root of 25, which is 5. So r is equal to 5. Let's get rid of this. And now let's write that the sine of w is equal to, again, this is going to be y over r, so 3 over 5, or 3/5. And then the cosine of w is going to be x over r, so that's going to be 4/5. Okay, let's come down here and paste this in and put a little border there. And hopefully this all fits on the screen. So the cosine of u is 12 over 13. So let me put that this is equal to 12 over 13. And then times the cosine of w, that's going to be 4/5. So 4/5. And then plus the sine of u is 5/13. And then times the sine of w, that's going to be 3/5. Now you could cancel this 5 with this 5, but notice that you're going to have a common denominator if you leave it alone. So I'm not going to touch that. So I'm just going to go through and say 12 times 4 is 48. And then plus 5 times 3 is 15 over the common denominator of 13 times 5, which is 65. So this right here, 48 plus 15, that's going to be 63. So this is 63 over 65. So coming back up, I'm going to say this equals 63 over 65. All right, let's take a look at problem 15 now. So we have the tangent of, we have 2 times the inverse sine of 2/5. So let me slide down here a little bit. I'm just going to make a little substitution. So let u be equal to this part right here. So we're going to say the inverse sine. So the inverse sine of 2/5. And again, that tells me that I'm going to have the sine of u is equal to 2/5. And u is going to be in quadrant 1 because this guy is positive. Again, if you have a positive argument for your inverse sine function, you're getting something back in quadrant 1. So let me just write here that u is in quadrant 1. So what I'm going to do is replace this and say it's tangent of 2u that I'm trying to figure out. So the tangent of 2u. So let me grab this and come down here and paste this in. And let me put this in there that got erased. So at this point, if we want to find the tangent of 2u, remember we have a little formula for that. Let me actually grab this and come up here. I have the formula already written out. So the tangent of 2 theta equals 2 tangent of theta over 1 minus tangent squared theta. Okay, so the tangent of 2u is equal to 2 tangent of u over 1 minus tangent squared u. So the first thing is you need to find the tangent of u. How do we do that? Well, at this point, we have the sine of u. Again, we know it's in quadrant 1. So this right here is going to be your y value, or the opposite. And this right here is going to be your r value, or the hypotenuse. So you need to find x, or the adjacent. So if I know that x squared plus y squared is equal to r squared, I can just plug in. So plug in a 2 for y, and then plug in a 5 for r. And then basically you're going to get x squared plus 2 squared is 4 is equal to 5 squared is 25. Subtract 4 away from each side. So x squared would be equal to 21. So x squared is equal to 21. Again, we're in quadrant 1. So x is equal to the principal square root of 21. Again, you don't need the plus or minus because you know you're in quadrant 1. X values are positive. Okay, so that tells me that the tangent of u is equal to, again, it's y over x. So this is 2 over the square root of 21. If you rationalize the denominator, you multiply by the square root of 21 over the square root of 21. This gives me 2 times the square root of 21 over 21. Okay, let me get rid of this. And I'll just write this in here more cleanly. So 2 times the square root of 21 over 21. Okay, let me get rid of this. Now, all you have to do is take this right here and plug in everywhere you see tangent of u, and basically you're home free. So I'm going to replace this tangent of u with 2 times square root of 21 over 21. And then this is tangent squared u. So what I want to do is plug in for the tangent of u. So 2 times square root of 21 over 21, and this would be squared. Okay, let's say equals. We're going to come down here. I'm going to do this in a slightly different way. So this is just multiplication. So 2 times 2 is 4. So I'm just going to write this as 4 times the square root of 21 over 21, and this is over. For this one, let me first write 1 minus. This is 2 times the square root of 21 over 21. So this would be 2 squared times the square root of 21 being squared over 21 squared. Now I'm doing that for a specific reason, and you'll see that it's going to make it easier. We can do this without a calculator. So first off, we know that this would just be 21. So I'm just going to erase that and say that this is 21. Now this would be 4, so you can write that in, so 4 times 21 like that. Now, before I do anything else, notice that you have 21 here and 21 squared here. And to make that crystal clear, you can write this as 21 times 21. So of course, this would cancel with this. So I'm just going to erase it, make it a little bit quicker for us. So this is 4 over 21 here. So I'm going to write this as 21 over 21. I can go through and say that this is equal to 4 times the square root of 21 over 21, and then over 21 minus 4 is 17, and then over the common denominator of 21. So this equals, you're going to have 4 times the square root of 21 over 21 times the reciprocal of this. So this is 21 over 17. So this right here would cancel. And what I'm left with is, let me write this down here. So 4 times the square root of 21 over 17. So let me copy this real quick, and we'll come back up here and just give our answer in terms of the original problem. Let me paste this in here. That color really doesn't show up well, so let me change it to green. So our answer here is 4 times square root of 21 over 17. All right, let's take a look at the practice test. For the instructions, we're asked to solve each equation for theta is greater than or equal to 0 and less than 2 pi. All right, let's take a look at the first problem. I'm just going to tell you in advance, these problems are very, very straightforward and easy. They're just meant to give you an introduction into solving trigonometric equations. So here we have negative 3 minus 7 times sine of theta. This equals 4 times square root of 2 minus 3 plus the sine of theta. So the goal here is to isolate the sine of theta on one side and then to have a single number on the other. So you want sine of theta equals some number. So how are we going to do that? Well, you have a sine of theta here and a sine of theta here. So let's get this guy over here. I'm just going to subtract the sine of theta away from each side of the equation. And if you want to make that crystal clear, you can always say that this is 1 times sine of theta, and this is negative 1 times sine of theta here. So I'm subtracting away 1 times sine of theta over here. So let's go ahead and show this as canceling. And then the other thing I would want to do, you notice you have a negative 3 here and a negative 3 here. Well, you can just cancel that away because, again, you could just add 3 to both sides of the equation. And so negative 3 plus 3 is 0. So let's just cancel this away. All right, so now what I would have, negative 7 times sine of theta minus 1 times sine of theta is going to be negative 8 times the sine of theta. And this equals 4 times the square root of 2. Now, again, I'm trying to isolate the sine of theta. So I want to get rid of this negative 8 that's multiplying the sine of theta. So I'm going to divide both sides of the equation by negative 8. So this right here is going to cancel away. And I'll have that the sine of theta is equal to, we know this is a positive over a negative, so it's negative. Now let's think about 4 and 8. So 4 divided by 4 is 1. So this would be the square root of 2 over here. And then this is over. 8 divided by 4 would be 2. So this is the negative of the square root of 2 over 2. So this is not our solution. We have the sine of theta equals the negative of the square root of 2 over 2. We have to do some detective work to figure out the values for theta that are going to work. In other words, I want to find all the angle measures, in this particular case from 0 to 2 pi, where 0 is included and 2 pi is not, that I can plug in there and get a true statement. So let me grab this real quick, and I'm just going to come over here to the unit circle and paste this in. So the first thing I would notice here is that your sine of theta is equal to a negative square root of 2 over 2. So where is sine negative? We know it's negative in quadrants 3 and 4. That tells me that I'm looking for a y-coordinate of negative square root of 2 over 2 in quadrants 3 and 4. Well, easily we can find that right here. So this is negative square root of 2 over 2, and this is negative square root of 2 over 2. So this is in quadrant 3, and this is in quadrant 4. And you just look for the corresponding angle measure. So here it's going to be 5 pi over 4, or 225 degrees if you want to work with that. And then here it's going to be 7 pi over 4, or 315 degrees if you want to work with that. So that basically tells me that theta is equal to, we would say 5 pi over 4, because again, sine of 5 pi over 4 would give me negative square root of 2 over 2. And then it can also be 7 pi over 4, because again, sine of 7 pi over 4 would give me negative square root of 2 over 2. Now, this is one way to do this. This solves our problem. But you could have also used your inverse sine function. Maybe you don't have this committed to memory and you don't have a unit circle handy, but you do have a calculator. So what you could do is say, well, I want the inverse sine of, and I would just make this positive. So I get a reference angle. So the square root of 2 over 2. And I think we all know that this is going to be pi over 4. Again, you can look at this on the unit circle and see that for pi over 4, the sine value is square root of 2 over 2. All right, so what I would want to do is find an angle in quadrant 3 and also an angle in quadrant 4 where sine is negative, where the reference angle is pi over 4. So that's pretty easy to do. So what I would do in quadrant 3 is I would say that, let me put quadrant 3 here so this is clear. You would want to go, well, I have pi plus my reference angle of pi over 4. So for this, I would just multiply by 4 over 4, and you would get 5 pi over 4. So that's this solution here. Now in quadrant 4, let me just change this up. The procedure is a little bit different. So we would say that we have 2 pi. I would start with that, and I would subtract away my reference angle, which is pi over 4. So let me come over here and just multiply this by 4 over 4. And so this would end up being 8 pi over 4. And if I do this subtraction here, this is going to give me 7 pi over 4, which is this one right here. So two different strategies to do this. I personally know all the unit circle values off the top of my head, but if you're newer to trigonometry, maybe you haven't memorized that yet. And again, maybe you don't have a unit circle handy, so you can always use your inverse sine function. All right, now, although it didn't ask for it, let's write out a general solution. So let me put, this will be our general solution here. So what you want to do is think about this first solution that we got, which was 5 pi over 4. Now remember, this 5 pi over 4 is a solution because if I plug it in for theta there, it gives me a true statement. Sine of 5 pi over 4 is equal to the negative of the square root of 2 over 2. Again, we can see that from the unit circle. Now, what if I added 2 pi to this? So in other words, what if I swung myself around 2 pi and I ended up with 13 pi over 4? So in other words, if I had 5 pi over 4, and I added 2 pi. So if I added 8 pi over 4, well, that's 13 pi over 4. Well, the sine of 13 pi over 4 is still going to be equal to the negative of the square root of 2 over 2. So basically what's going to happen is this solution right here is going to repeat itself every 2 pi. And that's also true if I went the other way. So in other words, if I went clockwise, so if I subtracted 2 pi away, so let's show that. So 5 pi over 4, and then minus, again, 8 pi over 4. Well, this would be negative 3 pi over 4. So the sine of negative 3 pi over 4 is still going to be negative square root of 2 over 2. So all you really have to do is realize that the period of sine is 2 pi, and then you'll just take that solution that you got. Let me put some braces in here. So we'll put 5 pi over 4, and then I'll go plus 2 pi, so that's the period of sine, and then times n, where you would say n is any integer. So it could be something like -1 or -2 or +1 or +2, or it could be 550. Whatever you want to put in there, it's just any integer that you're working with. Then I'm going to put a comma here, and then I'm going to list this guy, so 7 pi over 4. And again, it's the same reasoning here. I can just add 2 pi n, where n is any integer, and let me just close that down. So this would be the general solution. All right, so let me give you one more approach to this. This is not practical, but it's good if you want to visualize the solutions. So I would think about the graph of y is equal to the sine of x. Then you could also graph, this right here is a horizontal line. It's y is equal to the negative of the square root of 2 over 2. The reason you put this in, first off, on Desmos, it's going to give you these little points that you can click on with your mouse. But ideally, you're trying to figure out, well, where are the y values for this y equals sine of x going to be equal to negative square root of 2 over 2? So basically, everywhere this guy intersects this horizontal line, that's going to be true. And then you can just look at the x values, and that's going to be the solution for that equation you were working with. Remember, if we go back to this, it was the sine of theta, but I'm just going to use the sine of x, is equal to the negative of the square root of 2 over 2. So it's just like I'm taking this right here, and I'm plugging it in for y, and I'm saying, what are the x values or the angle measures where this is going to be true? Where I can take the sine of that, and I'm going to get the negative of the square root of 2 over 2. Well, on the unit circle, we found right away in quadrant 3, 5 pi over 4. So the sine of 5 pi over 4 would give me negative square root of 2 over 2. So that's why this point is on the graph of y equals sine of x. You've got 5 pi over 4, comma, negative square root of 2 over 2. We also found 7 pi over 4. So 7 pi over 4, comma, negative square root of 2 over 2. That's going to be on the graph of y equals sine of x as well. So those are two solutions you could find on the unit circle immediately. The other solutions are found by adding multiples of 2 pi. That's why we said when we got to the general solution, it was 5 pi over 4 plus 2 pi n, where n is any integer. And then we have 7 pi over 4 plus 2 pi n, where n is any integer. Let me draw that differently there, and let me close that down. So thinking about this on this graph, let's say I started here, and let's say that I subtract away 2 pi from this x coordinate. So in other words, let me do this over here because this is getting really busy. I have 7 pi over 4, and I subtract away 2 pi. So I subtract away 8 pi over 4. So this is negative pi over 4. So basically, if I decrease this by 2 pi, I'm going to get to an x value that's another solution. So that's negative pi over 4. So negative pi over 4, comma, negative square root of 2 over 2. So basically, from this point right here, I went 2 pi to the left. So let me trace that out. So I'm going 2 pi to the left. So I'm at that point right there. And if I took that point right there, which has an x value of negative pi over 4, so let me just continue this process. So negative pi over 4, and I subtracted away another 2 pi, so 8 pi over 4. Well, this is going to give me negative 9 pi over 4. So let's go over here. This would be negative 9 pi over 4 for the x value, comma, negative square root of 2 over 2 for the y value. So I would just go 2 pi units to the left along this guy, and then that's going to put me right there at that point with negative 9 pi over 4, comma, negative square root of 2 over 2. So you see how this works. Basically, I could have started here and just went 2 pi units to the right, and I'd end up here at a solution, 2 pi units to the right, I'd end up here at a solution. Now, similarly, if you want to work with that other solution, which is this guy right here. So if you had, let me get rid of this scratch work here. If you had 5 pi over 4, and I subtracted away 2 pi, which is 8 pi over 4, well, this right here is negative 3 pi over 4. And you can see that right here, this point. Again, if I move 2 pi to the left along this graph, so 2 pi to the left, I'm going to end up right there. So negative 3 pi over 4, comma, negative square root of 2 over 2. And then if I do that again, so negative 3 pi over 4, and then minus 8 pi over 4, this is going to be negative 11 pi over 4. So that's going to give me this point right here, negative 11 pi over 4, comma, negative square root of 2 over 2. So that's me moving along this graph 2 pi to the left. So that's going to put me right there. So hopefully this makes sense visually. You can go to Desmos and just play around with this. I recommend this when you first start solving trigonometric equations so you fully understand what's going on. It's a way to really visualize these general solutions and the fact that they're going to repeat forever and ever and ever. Okay, let's look at problem 2. So now we have negative 3 minus 9 fifths times the tangent of theta. This equals negative 16 fifths minus 2 times the tangent of theta. What I would do in this situation is, because we have fractions involved, you have a denominator of 5 and a denominator of 5. I would clear those first before you do anything else. So just multiply everything by 5. So negative 3 times 5 minus 9 fifths times 5 times the tangent of theta. This equals negative 16 over 5 times 5 minus 2 times 5 times the tangent of theta. So all I did was multiply everything by 5, and that's basically going to clear these denominators. Now looking at what we have, negative 3 times 5 is negative 15, and then minus, these 5s would cancel, so 9 times the tangent of theta, and this equals, these 5s would cancel, negative 16, and then minus 2 times 5 is 10, and then times the tangent of theta. Again, what we're trying to do is isolate the tangent of theta. So you have it there and you have it there. So what I'm going to do is add this 10 times the tangent of theta to both sides of the equation. And also, I'm going to add 15 to both sides of the equation. So this would cancel and this would cancel. Negative 9 times the tangent of theta plus 10 times the tangent of theta is going to be 1 times the tangent of theta, or just the tangent of theta. And this equals negative 16 plus 15, that's going to be negative 1. Once you have it in the form of tangent of theta equals some number, now it's time to do some detective work. Now, a lot of you probably know that if I use the inverse tangent function with negative 1 as the argument, I'm going to get negative pi over 4, or negative 45 degrees. But I like to use positive numbers for the argument so that I just get a reference angle and I don't have to go through and think about this too hard. So inverse tangent of 1 would be pi over 4, or 45 degrees. So this would be my reference angle in any quadrant where tangent is negative. So tangent is negative where? In quadrant 2 and quadrant 4. So let me put a little border here. And first, let's think about quadrant 2. So we know in quadrant 2 that theta prime, so theta prime, which is the reference angle, is basically pi minus your theta. Well, I want to figure out what theta is. I already know what theta prime is. So basically, I'm going to add this to both sides and say this is theta is equal to, I'm going to subtract this away from each side. So I'm going to say pi minus theta prime. Okay, so that's all I'm doing. So basically, in order to find theta, I'm going to say that I have pi minus theta prime. I know it's pi over 4. That's my reference angle. So this is pi over 4. Let me scooch this down so it fits. So this is 4 pi over 4. And so 4 pi minus pi would be 3 pi. So this is 3 pi over 4. So that's in quadrant 2. So this is 3 pi over 4. Actually, let me put theta is equal to this. And let me move this down here. So in quadrant 4, now we have to use a different formula. So remember, for that one, it's 2 pi minus your angle. So minus theta, and that's going to give you your reference angle, theta prime. Again, I have the reference angle. I want to find theta. So I'm going to add this to both sides. So I would have theta is equal to, I'm going to subtract this away from each side. So I'm going to say 2 pi minus theta prime. So my reference angle here is going to be pi over 4. So this would be 8 pi over 4. So 8 pi minus pi is 7 pi. So in quadrant 4, theta would be 7 pi over 4. Okay, let me get rid of this. So this gives me the two solutions that I'm actually looking for in terms of what the practice test asked for. It wanted theta that's greater than or equal to 0 and less than 2 pi. We have that. So theta would be equal to 3 pi over 4, and then also 7 pi over 4. Now, in terms of the general solution, again, this is where you have to think a little bit. So for the general solution, let me set this up. So the first thing is I'm going to put in 3 pi over 4. This is where students get tripped up because they're used to the period of sine being 2 pi. Remember, the period for tangent is pi. So if we go back to the unit circle, I want to go to this point right here, which is 3 pi over 4, and to basically think about the fact that if I swing around another pi radians, or 180 degrees if you want to work with degrees, that's going to put me right there. So that's that 7 pi over 4 that we found as a solution. What's going to happen is, as I keep swinging around by pi, or 180 degrees, I'm going to get back to another solution. So that would be a solution, another solution, and you can go clockwise as well. So coming back, what I would actually do is just list this and then go plus pi n, where n is any integer. And that's all you have to do. You don't need this one here because pi times 1 is pi, and 3 pi over 4 plus pi would be 7 pi over 4. Let me show that so nobody's lost. So 3 pi over 4 plus, you would do 4 pi over 4. That's 7 pi over 4. So using this, I can get to this second solution here, and any other solution that's available, again, where n is just going to be any integer. So let me get rid of this, and let me show you this one other way. I'm not going to keep doing this in the interest of time because it just drags the video out, but if you graph y is equal to the tangent of x, you're going to get this guy in red. So we already know how to graph this. Again, you can just go to Desmos. And then here you could graph y equals -1. Again, all I'm doing is I'm going back to the fact that we have the tangent of theta. I'm just going to say the tangent of x is equal to -1. So basically, I'm just taking this and plugging it in there. So everywhere where it hits this horizontal line, I know the y value is -1. And so I'm just looking at the x values there. Those are going to be solutions for my equation. Now, if I start right here with something we know, tangent of 3 pi over 4 is going to give me -1. So the point 3 pi over 4, comma -1. If I add 4 pi over 4, or just pi, to this x coordinate, basically I'm moving down to the right by pi, right? So I'm going to be at this point right here. So this is 7 pi over 4, comma -1. The y value is not changing. I want the y value to always be -1, so it solves this equation right here. If I add another 4 pi over 4 to this x coordinate, I'm going to be at 11 pi over 4, so that's going to get me right here. And you can do this as much as you want. If I start with the 3 pi over 4 again, and I subtracted 4 pi over 4 away, I'm going to get this negative pi over 4 here, so that's going to give me this point right there. I'm just moving to the left by pi. All right, let's take a look at problem 3. So here we have 1 minus 12 times cosine of theta equals -8 times square root of 3 plus 1. So I want to isolate the cosine of theta. I notice that I have a 1 here and a 1 here. Again, if you see something like that, the same number on each side of an equation, you can just cancel it away, right? So I can just subtract 1 away from each side of the equation. This cancels and this cancels. So I have -12 times the cosine of theta is equal to -8 times the square root of 3. So let me slide down here a little bit. I'm going to divide both sides by -12 so I can isolate the cosine of theta. So this right here is going to cancel with this. You get the cosine of theta is equal to negative over negative is positive. 8 divided by 4 is 2. So this is 2 times square root of 3 over 12 divided by 4 is going to be 3. So what I get is the cosine of theta equals 2 times square root of 3 over 3. Let me grab this real quick. And you can go to the unit circle, but I think it's easier to see this with a graph. So 2 times square root of 3 over 3, that's about 1.15 if you round to the nearest hundredth. So this right here is y is equal to 2 times square root of 3 over 3. And again, that's approximately, let's say 1.15. Do you see a problem? Yes. we can't plug in anything there for theta and get a true statement because we know the range for the cosine function is from -1 to 1. So there's no possible value that you can plug in for theta that would give you something that's greater than 1 or a value of about 1.15 or 2 times square root of 3 over 3. So for that reason, you can go ahead and say that there's no solution for this particular equation. All right, for problem 4, we have -3 minus 3 times the sine of theta equals 1 minus 11 times the sine of theta. So I want to isolate the sine of theta. So I have it there and I have it there. So what I'll do is add 3 to both sides of the equation. That will cancel. And then I'm going to add 11 times the sine of theta to both sides of the equation. So this would cancel. So -3 times the sine of theta plus 11 times the sine of theta is 8 times the sine of theta. And this equals 1 plus 3 is going to be 4. All right, let's divide both sides of the equation by 8 so we can isolate the sine of theta. That will cancel away. So we have the sine of theta is equal to, we know 4 over 8 is 1/2. All right, this one's really easy. A lot of you have memorized this. Again, you can use the unit circle. You can also use the inverse sine function. So you can say the inverse sine of 1/2, well, that's going to give me pi over 6. Now, I would have another solution because, again, sine is positive in quadrant 2 as well as quadrant 1. In quadrant 2, I would want to take pi and subtract away my reference angle, which is pi over 6. So this would be 6 pi over 6. And so this would give me 5 pi over 6. A lot of you know this. This is 30 degrees and this is 150 degrees. So those would be the solutions here, or where sine is going to be 1/2 at pi over 6 and then also 5 pi over 6. Let me get rid of this and I'll just write it more formally. And we'll say that theta is equal to pi over 6 and then comma 5 pi over 6. Again, if you want a general solution, I'm not going to graph things anymore. I think it's a bit time consuming and you can just do it on your own. So for a general solution, if you want it, remember the period of the sine function is 2 pi. So I would start with pi over 6 and I would add 2 pi n, where n is any integer, and then I would have 5 pi over 6 and then plus 2 pi n, where n is any integer. All right, let's take a look at problem 5. So here we have 3 minus 5 times sine of theta is equal to 4 minus 3 times the sine of theta. All right, I want to isolate the sine of theta, so I've got it there and there. So let's add 3 times the sine of theta to both sides of the equation. And let's subtract 3 away from each side of the equation. So this would cancel, this would cancel. So you have -5 times sine of theta plus 3 times sine of theta. That's going to be -2 times the sine of theta. And this equals 4 minus 3 is going to be 1. And we divide both sides by -2. So we can isolate the sine of theta. So that's going to cancel. And what you're going to have is the sine of theta is equal to -1/2. So basically in the last problem, we had the sine of theta equals 1/2. And we found that theta was going to be pi over 6, or it could be 5 pi over 6. Sine is positive in quadrants 1 or 2. You have a pi over 6 reference angle in quadrant 2. That's how you get the 5 pi over 6. Well, this one is negative. So it's negative in terms of sine in quadrants 3 and 4. You would still have that pi over 6 reference angle. Again, you can always do this in your calculator. So the inverse sine of, just make this positive, 1/2. That gives you pi over 6. And you're just going into quadrant 3 and you're saying, well, what angle in quadrant 3 would have a reference angle of pi over 6? Well, you could start with pi and you could just add pi over 6. And that would give me, let's go 6 pi over 6. So that would be 7 pi over 6. So that would be in quadrant 3. And then in terms of quadrant 4, what you would do is you would take your 2 pi and you would subtract away your reference angle of pi over 6. Let's say that this is 12 pi over 6. So this would be 11 pi over 6. And a lot of you know this stuff off the unit circle, but if you don't, this is how you can figure it out. You don't always have a unit circle handy. So let me put the solution up here. I'll say that theta is equal to, the first one we found is 7 pi over 6. So that's in quadrant 3. And then in quadrant 4, you would have 11 pi over 6. Let me get rid of this. And I'll go ahead and write the general solution just in case you want it. So down here, I'll put the general solution. That would be, you have your 7 pi over 6 plus 2 pi n, where n is any integer. Again, 2 pi is the period of sine, so that's why I'm using that. And then this guy would be 11 pi over 6 plus 2 pi n. Again, 2 pi is the period of sine. That's where that's coming from. N is any integer. So let me close that down. And that would be the general solution. All right, for problem 6, we have 5 plus 2/5 times the tangent of theta. This equals 25 plus square root of 3 over 5 plus the tangent of theta. All right, let me get rid of these denominators first. You have a 5 here and a 5 here. So just like before, you could just multiply both sides by 5 and clear those denominators. So I don't think we need to show this. I'm just going to speed this up just a little bit. So 5 times 5 is 25. And then plus 2/5 times 5 would be 2. And then times the tangent of theta. And this equals, if I multiply this by 5, the denominator there would get canceled away. And so you just have the numerator. So 25 plus the square root of 3. And then plus, if I multiply the tangent of theta by 5, it's 5 times the tangent of theta. So hopefully I did not lose anybody. I just multiplied everything here by 5 to clear those denominators. Now, you have 25 over here and 25 over here. Again, if you have the same thing on each side of an equation, you can just cancel it away. So my goal is to isolate the tangent of theta. And so I have that there and there. So let me go ahead and subtract 5 times the tangent of theta away from each side of the equation. So that would cancel away. And so 2 times tangent of theta minus 5 times tangent of theta would be negative 3 times the tangent of theta. And this equals the square root of 3. Now to get tangent of theta by itself, I'm just going to divide both sides of the equation by negative 3. And so this would cancel. And you have the tangent of theta is equal to the negative of the square root of 3 over 3. Again, some of you know this by heart. What I'm actually going to do, again, is just use the concept of a reference angle. So I'm just going to say that the inverse tangent of, I'm just going to make this positive. So the square root of 3 over 3. I'm going to get my reference angle, and then I'm going to go into quadrant 2, where tangent is negative, and quadrant 4, where tangent is negative, and figure out my solutions. So for this one, if you punch this into the calculator, you're going to get pi over 6. So this would be my reference angle in quadrant 2 and 4. Okay, so in quadrant 2, again, what you'd want to do is go pi minus your reference angle, which is pi over 6. So let's say this is 6 pi over 6. So this would give me 5 pi over 6. And then in terms of quadrant 4, you would want to say 2 pi minus pi over 6. So this is 12 pi over 6. So this basically is 12 pi minus pi. That's 11 pi over 6. So those would be my two solutions. Let's say theta is equal to, you'd have 5 pi over 6 and then comma 11 pi over 6. Now, if you want the general solution, again, I'm just going to list it even though we weren't asked for it in case you're curious. So we would say the general solution. When you think about this, remember the period of tangent is pi. This often gives students trouble because they're so used to the period being 2 pi. So you have to keep that in mind if you're solving an equation with tangent or cotangent. So you're going to take this first solution, this 5 pi over 6, and just add pi n. Not 2 pi n, but pi n. And then just close that down. If you add pi to this guy right here, you're going to get this guy right here. So you don't have to worry about listing this one and this one with this guy right here. You would just put 5 pi over 6 plus pi n, and you're basically good to go. All right, let's take a look at problem 7. So here we have 4 plus the square root of 3 over 2 plus 2 times the cotangent of theta. This equals 2 plus 1/2 times the cotangent of theta. I would clear these denominators here first. So just multiply both sides of the equation by 2. It'll just make your life a lot easier. So if I multiply this by 2, I'm going to have 4 plus the square root of 3. The denominator would cancel away. Plus 2 times 2 is 4, and then times the cotangent of theta. And this equals 2 times 2 is 4, and then plus 1/2 times 2 would be 1. So this is just the cotangent of theta. So I just multiplied everything here by 2. Now, if I look at this, you notice you have a 4 here and a 4 here. You can subtract 4 away from each side of the equation, and that's just going to go away. So looking at what we have now, I want to isolate the cotangent of theta. So I've got it there and I've got it there. So what I'll do is subtract the square root of 3 away from each side of the equation. So let me see if I can fit that over here. And I'm going to subtract the cotangent of theta away from each side of the equation. And that C could be a lot better there. So this would cancel away. So 4 times cotangent of theta minus the cotangent of theta, this is 3 times the cotangent of theta. And this equals, over here, this canceled away. We have the negative of the square root of 3. So what I'll do here is divide both sides of the equation by 3. So I can isolate the cotangent of theta. This cancels. You have the cotangent of theta is equal to the negative of the square root of 3 over 3. The majority of us do not have calculators where you have an inverse cotangent function. If you're using an online calculator like Mathway or something like that, then you can just use the inverse cotangent function that they have built in, and it's going to do all the work for you. Essentially, what you could do here is say that, remember, the cotangent of theta is equal to 1 over the tangent of theta. Okay, so we know that identity. So you could say that I'm going to plug in the tangent inverse of, take the reciprocal of this, and actually I'm going to make it positive. So I'm just going to work with 3 over the square root of 3. Don't worry about rationalizing the denominator here. I'm just trying to get a reference angle. So I end up with pi over 3. Now for tangent or cotangent, they're negative in quadrants 2 and 4. So that's all the information I really need. If I come down here and I think about, okay, in quadrant 2, I would say that I have pi minus pi over 3. So I can write this as 3 pi over 3. And so this would be 2 pi over 3. So that's one solution. Then if I go into quadrant 4, I can say, well, this is 2 pi minus pi over 3. So let's multiply this by 3 over 3. This would be 6 pi over 3. So this would end up giving me 5 pi over 3. So 2 pi over 3 and 5 pi over 3, those are the solutions where theta is greater than or equal to 0 and less than 2 pi. So let's say theta is equal to 2 pi over 3. Or let me actually just rewrite it. So 2 pi over 3. And then you could also have, let me just put a comma here, 5 pi over 3. Now for the general solution, again, if you want to write that out, the general solution, you could just say this guy right here, 2 pi over 3 plus, again, when you think about cotangent or tangent, the period is pi. So you want to just put pi n. You do not need to list this guy right here, because if you take 2 pi over 3 and you add pi, or you can think about it as adding 3 pi over 3, you're going to get to 5 pi over 3. So just list this one for your general solution. So 2 pi over 3 plus pi times n, where n is any integer. All right, for problem 8, now we have negative 8 plus the square root of 2 over 2 minus the secant of theta. This equals negative 4 minus 3 halves times the secant of theta. All right, I would clear the denominators. You have a 2 here and a 2 here. So just multiply everything by 2. So you can have negative 8 plus the square root of 2 minus 2 times the secant of theta is equal to negative 4 times 2 is negative 8. So negative 8. And then minus, basically 3 halves times 2 is just 3. So this is going to be 3 times the secant of theta. Okay, so just multiplied everything there by 2. So we have another situation where we have negative 8 and negative 8. So you could just add 8 to both sides. But again, if you see the same thing on each side of an equation, just cancel it away. All right, so looking at this now, I want to isolate my secant of theta. So we would say that we could add 3 times the secant of theta to both sides of the equation. And then we could subtract the square root of 2 away from each side of the equation. So let me show this as canceling away. And let me slide down here a little bit. This is going to cancel. Negative 2 times secant of theta plus 3 times secant of theta. That's just going to be the secant of theta. And this equals, over here I just have the negative of the square root of 2. So the secant of theta is a reciprocal of the cosine of theta. Remember, the secant of theta is equal to 1 over the cosine of theta. So because most of us do not have an inverse secant key on our calculator, I would just go through and say, I want to take the inverse cosine of the reciprocal of this. Again, don't use the negative. I'm just going to use the positive. I'm just going to go 1 over the square root of 2. Don't worry about rationalizing the denominator there. I'm just going to key it into the calculator, and we get pi over 4. So pi over 4. And I know most of you already know this, but again, going through the exercise of keying it into the calculator for people who don't know is necessary. All right, so that tells me that the reference angle is going to be pi over 4, and secant is going to be negative where? Well, quadrants 2 and 3. Because cosine and secant are negative in quadrants 2 and 3, they're positive in quadrants 1 and 4. So I want to go into quadrant 2 and find an angle with a reference angle of pi over 4. A lot of you already know that's going to be 3 pi over 4, or 135 degrees. That one's pretty easy to know. But again, if you don't, you could just say, okay, well, I have pi minus the reference angle of pi over 4, and you could write this as 4 pi over 4. So this is going to give me 3 pi over 4. So that would be in quadrant 2. If you were in quadrant 3, then you would want to go pi plus the reference angle, which is pi over 4. A lot of you know already that's 5 pi over 4, or 225 degrees. But let's write 4 pi over 4 like this. So this is 5 pi over 4. And so these would be the two solutions where theta is greater than or equal to 0 and less than 2 pi. So we'll say theta is equal to, we have 3 pi over 4, and then I'll put a comma, and then 5 pi over 4. Now, if you want the general solution, let me just write that out. So the general solution, well, you take this one, 3 pi over 4, and you add 2 pi n, where n is any integer. Again, 2 pi is the period for cosine and also secant. And then the other one would be 5 pi over 4 plus 2 pi n. Let me close that down. Again, n is any integer. All right, let's take a look at problem 9. So here we have 12 minus square root of 2 over 3 minus 2 times cosecant of theta equals 4 minus 7/3 times cosecant of theta. So you have a denominator of 3 and a denominator of 3. So before I do anything, I would want to clear those denominators. So we would multiply everything by 3. So this denominator would cancel. You'd have 12 minus the square root of 2, and then minus 2 times 3 is 6. So times the cosecant of theta, and this equals 4 times 3 is 12, and then minus 7/3 times 3. The denominator is going to cancel. That's just a 7, and then times the cosecant of theta. So once again, you have this 12 and 12, the same thing on each side of the equation. You can show this as canceling by subtracting 12 away, but if I was doing this on my own, I would just scratch it out, right? So just quickly cancel it out and save yourself some time. All right, so let's come down here, and we're trying to isolate, again, the cosecant of theta. So what I want to do is just add 7 times the cosecant of theta to both sides of the equation. That would cancel. I'm going to add square root of 2 to both sides of the equation. That would cancel. And so negative 6 times cosecant of theta plus 7 times the cosecant of theta is just going to be 1 times the cosecant of theta, or the cosecant of theta. So this equals the square root of 2. The cosecant of theta, this is 1 over the sine of theta. Again, a lot of people are not going to have an inverse cosecant key on their calculator. Some of you might, but it's unlikely, especially if you're using a TI-83 or 84. So I would say we want the inverse sine of 1 over the square root of 2. Again, a lot of you already know this is going to be pi over 4, but in case you don't, you can use your calculator, and so this would give you pi over 4. Now, because this is positive, this square root of 2, I know I'm looking for something in quadrant 1 or 2. That's where sine and cosecant are going to be positive. So I already have my answer for quadrant 1. I'm good to go there. So I can say that theta is equal to pi over 4. But basically, I have to go into quadrant 2 and get my solution there. Again, a lot of you already know it's 135 degrees, or 3 pi over 4. So you can also say it's 3 pi over 4. If you don't know that, go into quadrant 2 and say, okay, well, I want pi minus the reference angle, which is pi over 4. So this is 4 pi over 4. So this becomes 4 pi minus pi, which is 3 pi over 4. So that's how we get that. In terms of the general solution, again, the period here for cosecant is 2 pi. So for the general solution, you would just say you have pi over 4 plus 2 pi n, and then comma, 3 pi over 4 plus 2 pi n. And again, I would just note that n is any integer. All right, let's take a look at problem 10. So we have negative 6 plus the square root of 3 over 3, plus you have 3 times the cotangent of theta. This equals negative 2 plus 8/3 times the cotangent of theta. So what I would do in this situation, you have a denominator of 3 and a denominator of 3. I would clear those fractions out just to make your life a lot easier. So just multiply everything by 3. So for this guy right here, the denominator would cancel away. You just have the numerator. So negative 6 plus the square root of 3. And then plus 3 times 3 is going to be 9. And then times your cotangent of theta. And this equals negative 2 times 3 would be negative 6. And then plus 8/3 times 3, the denominator would cancel. So that's just 8. And then times your cotangent of theta. So at this point, our goal is to isolate the cotangent of theta. So you have it there and you have it there. So let's think about what we can do. Well, first off, you have negative 6 here and negative 6 here. So the same thing on each side of an equation, you can just get rid of it. I would just show this by adding 6 to be complete for the tutorial. But again, if you're doing this on your own, you don't need to do this. You can just scratch it out. So now that that's gone, let's think about how we can move this over here. So I would subtract this 8 that's multiplied by the cotangent of theta away from each side of the equation. And then also I would subtract this square root of 3 away from each side of the equation. So let's see. We're going to be able to cancel this away and this away. Let me slide down here and see what we have. So we have 9 times the cotangent of theta minus 8 times the cotangent of theta. That's just going to be 1 times the cotangent of theta or just cotangent of theta. So cotangent of theta is equal to, over here, it's just negative square root of 3. Now, again, like we talked about before, most of us do not have an inverse cotangent function available to us on our calculator. You might, but most of us don't. So what you would do is say that the cotangent of theta is equal to 1 over the tangent of theta. And then you can use your inverse tangent function on your calculator. So I would say that the inverse tangent of, I'm going to make this positive just so I can get a reference angle. And I'm going to take the reciprocal of the square root of 3. So that's 1 over the square root of 3. Again, you don't need to rationalize the denominator. It would be the square root of 3 over 3, but you don't need to do it. Just key it into your calculator like that. A lot of you already know that this is going to be pi over 6 or 30 degrees. So this would give me pi over 6. Now again, this is going to be your reference angle in the quadrants where cotangent is negative or tangent is negative. So that's quadrants 2 and 4. Remember, tangent and cotangent are positive in quadrants 1 and 3. So in quadrant 2, I think most of you know that this is going to be 5 pi over 6. But again, if you don't, you can say, okay, well, I have pi minus my reference angle, which is pi over 6. Let's write this. Let me scooch this down. Let's write this as 6 pi over 6, which is just pi, and then minus your pi over 6. So again, this is 5 pi over 6, or 150 degrees. Again, a lot of you will know that. So the other one would be in quadrant 4. So in quadrant 4, the formula would change a little bit. So for quadrant 4, you would have 2 pi, and you would subtract away your reference angle, so pi over 6. Again, you could say this is 12 pi over 6 to have a common denominator. So 12 pi minus pi is 11 pi. So this would be 11 pi over 6. So this is my quadrant 2 solution. This is my quadrant 4 solution. So the cotangent of 5 pi over 6 or the cotangent of 11 pi over 6 would give me the negative of the square root of 3. Let me get rid of this and let's write our solution. So theta is equal to, we want 5 pi over 6. I'm going to put a comma and then 11 pi over 6. Let me get rid of this. So once again, if you want the general solution, even though we're not asked for it, all you need to do is think about the period of cotangent. So that's going to be pi, not 2 pi. So that's where everybody gets confused. So you're going to take this first solution here, which is 5 pi over 6, and add pi, which is the period, times n, where again, n is any integer. And I didn't mention this in previous videos, but a lot of students get confused about n because some books use k. Like if you're using like a Stewart pre-calculus, they use k, but a lot of books do use n, so it just depends on what book you're using. You could use n or k or whatever you want there. I forgot to mention that when we started out the video. So we have 5 pi over 6 plus pi times n, where n is any integer. Again, you don't need to list this because 5 pi over 6 plus, if you did 6 pi over 6, which is just pi, that would get you to 11 pi over 6. So this is how you would list your general solution. All right, let's take a look at the practice test. For the instructions, we're asked to solve each equation for theta is greater than or equal to 0 and less than 2 pi. All right, let's take a look at the first problem. So here we have negative 4 secant of theta plus 4 plus 2 secant squared theta. This equals secant squared theta. Again, the idea here is to get secant of theta equals some number. So how can we do that? Well, if I look at this, you basically think back to solving quadratic equations. Let's say, to completely see this, I replace secant of theta with x and secant squared theta with x squared. So negative 4x plus 4 plus 2x squared equals x squared. So if you see this type of problem, you know it's a quadratic equation, and you would solve this either with a quadratic formula, or in some cases, if you're lucky, you can solve it using factoring in the zero product property. So here you could subtract x squared away from each side. We'll cancel that and say it's 0. So 2x squared minus x squared, that's x squared. So x squared minus 4x plus 4 equals 0. So on the left-hand side, you could factor this. This is actually going to be a perfect square trinomial. So this is x and this is x. Give me two integers whose sum is negative 4 and whose product is positive 4. So that would be negative 2 and then negative 2. So again, this becomes x minus 2 quantity squared. Let me erase this and just send this down here. And you can solve this using the square root property. You would say x minus 2, so x minus 2, is equal to plus or minus the square root of 0. Of course, the square root of 0 is 0, and you don't need the plus or minus there, so it's just equal to 0. Add 2 to both sides of the equation, and you get x is equal to 2. Well, basically, you're going to do the same thing here. You're just going to find that secant of theta equals 2. Sometimes if you're struggling for how to start a problem, just replace things with a variable like x or u or whatever you want to use, and then you can go back to things that you learned in algebra. You don't have to do that forever. Once you solve enough of these, you'll understand what to do. But if you're struggling to get started, I recommend that. So let's go ahead and solve this without using that. So I'm just going to subtract secant squared theta away from each side of the equation. This will cancel and become 0. And so 2 secant squared theta minus secant squared theta, that is secant squared theta. And then minus 4 secant of theta, and then plus 4, and this equals 0. So we know the left side is factorable. So this is secant of theta, and then this over here would be secant of theta. And of course, when we say what are two integers that sum to -4 and have a product of positive 4, that's -2 and -2. So -2 and -2. So this becomes secant of theta minus 2, quantity squared is equal to 0. And again, you solve this using the square root property, and you say the secant of theta minus 2 is equal to 0. Add 2 to both sides of the equation, and you end up with, as we said before, the secant of theta is equal to 2. So secant of theta equals some number. That's what we need. So let's come to the unit circle. And we have that the secant of theta is equal to 2. Now again, the cosine of theta, which we can get from the unit circle, is equal to 1 over the secant of theta. So the cosine of theta here is equal to 1 over 2, or 1/2. Now you can get rid of this and get rid of this and bring this up here. Now where is the cosine of theta equal to 1/2? Well, first off, cosine is positive in quadrants 1 and 4. Where's the x-coordinate going to be 1/2? Well, that's going to be right here in quadrant 1, and that's going to be right here in quadrant 4. So in quadrant 1, it's pi over 3. In quadrant 4, it's 5 pi over 3. Notice the reference angle for 5 pi over 3 is pi over 3. So again, if you didn't have a unit circle, you could say inverse cosine of 1/2. That would give you the pi over 3. And then you say, well, cosine is also positive in quadrant 4. So give me an angle in quadrant 4 with a reference angle of pi over 3. And so that's going to give you the 5 pi over 3 solution. So theta is equal to pi over 3. And then put a comma, and then 5 pi over 3. And then that's in the interval where theta is greater than or equal to 0 and less than 2 pi. If you want the general solution, then I'm basically just going to have pi over 3 plus 2 pi n. Remember, 2 pi is the period for cosine. And then the other one would be 5 pi over 3 plus 2 pi n. Let me close that down. All right, let's take a look at problem 2. So here we have the square root of 2 times the sine of theta cosine of theta plus 3 cosine of theta equals 4 cosine of theta. The first thing I would do to solve this problem is subtract 4 cosine of theta away from each side of the equation. So over here, this would cancel away, and I'll put a 0. On the left, let me write the square root of 2, and then we have sine of theta, and then cosine of theta, and then 3 cosine of theta minus 4 cosine of theta would be negative cosine of theta. So let me write minus cosine of theta. And actually, let me put this as plus -1 times the cosine of theta, because we're going to factor in a moment. I want this to be crystal clear. And then let me put equals 0. So let me slide down here a little bit. And what I'm going to do is factor out the cosine of theta. So you see that's here and also here. So let's pull that out in front of some parentheses like this. And so we'll say that we have the cosine of theta times the quantity. Inside you would have the square root of 2 times your sine of theta. And then we have this -1 here. So you could put plus -1, but I think it's easier to just put -1 here and then close down the parentheses, and this equals 0. So the reason we're setting this up this way is so that we can use the zero product property. I would say that this guy right here, the cosine of theta, is equal to 0. Then or I take this guy right here, the square root of 2 times your sine of theta minus 1 equals 0. So for this one on the left, we really don't need to do anything other than to go to the unit circle. On the right, we need to clean up a little bit. So let's add 1 to both sides of the equation. That would cancel away. You would have your square root of 2 times the sine of theta is equal to, over here this is 1. Let me divide both sides of the equation by the square root of 2. So this is going to cancel. And basically, let me write this as the cosine of theta is equal to 0. then I'll put or. We'll have our sine of theta is equal to, you have 1 over the square root of 2. If you rationalize the denominator there, you can multiply this by the square root of 2 over the square root of 2, and that would give you the square root of 2 over 2. So the square root of 2 over 2, this is what we're going to see on our unit circle, so that's why I'm doing that. So let me go ahead and grab this real quick. All right, let's start off with cosine of theta equals 0. So we're looking on the unit circle for an x-coordinate of 0. So that's going to be right here at pi over 2, and then also right here at 3 pi over 2. Then we're looking for the sine of theta being equal to square root of 2 over 2. So you're looking for a y-coordinate of square root of 2 over 2. Remember, sine is positive in quadrants 1 and 2. So you're going to come right here to pi over 4. That's going to be square root of 2 over 2 for the y-coordinate, or the sine value of pi over 4. And then go into quadrant 2. You're looking for an angle with a reference angle of pi over 4. And you're going to see that y-coordinate is square root of 2 over 2. So that's the sine value of 3 pi over 4 as well. All right, so we have our solutions. We'll say that theta is going to be equal to, we would have pi over 4, and then pi over 2, and then 3 pi over 4, and then we would have 3 pi over 2. So 3 pi over 2. So this is in the interval from 0 to 2 pi, where 0 is included and 2 pi is not. Now, if you wanted to write the general solution, so let me write G period S period for general solution. Let me slide down a little bit. This is going to probably go off the screen, so I'll just scroll over. I'm going to start with this pi over 4, so pi over 4. And then, of course, I can just add 2 pi, which is the period for sine, and then times n, where n is any integer. Then the next guy here, we have pi over 2. Now notice that there's a little pattern here. So if you start here and you add pi radians or 180 degrees, you come to another solution. So you're going to be right there at 3 pi over 2. Add pi radians or 180 degrees, you're going to be back to another solution, and so on and so forth. So really for this one, you can just put pi over 2 plus pi times n, where n is any integer. Let me put a comma here, and then I'm going to work on this 3 pi over 4. So let me get rid of this and this and this and this. Let me just list that. I'm just going to slide way over. So 3 pi over 4 plus 2 pi, again, the period for sine, and then times n, where n is any integer. All right, before we move on to the next problem, in the lesson, we talked about the fact that as a general strategy, we don't want to divide both sides of an equation by a trigonometric function, such as the cosine of theta. We saw in the lesson that we would potentially remove some of our solutions. So these solutions that would be removed are ones that make the divisor 0. So in other words, you might have looked at this problem and said, I can divide everything by cosine of theta. So I'm just going to note that this is the wrong way to solve this. So I'm going to divide everything by the cosine of theta just to show you what could go wrong. So what's going to happen is this cancels, and this cancels. So now the equation becomes the square root of 2 sine of theta plus 3 is equal to 4. Okay, well, we solved this earlier. If you subtract 3 away from each side of the equation, this cancels. So you'd have the square root of 2 times sine of theta is equal to 1. You would divide both sides of the equation by the square root of 2. And so now you'd have the sine of theta is equal to 1 over the square root of 2. And we know if we rationalize the denominator, the sine of theta would be equal to the square root of 2 over 2. Well, you know that from the unit circle, the sine of theta equals square root of 2 over 2, that theta there would be pi over 4. We just looked at that a moment ago, and then we went into quadrant 2, where sine is also positive. We found an angle with a reference angle of pi over 4, so that's 3 pi over 4. So if you solve this equation this way, well, you're only going to get part of the full solution. You would get pi over 4 and 3 pi over 4 only in that interval where theta is greater than or equal to 0 and less than 2 pi. Well, what happened to these solutions here? So this one where we have pi over 2 and 3 pi over 2. Well, those make this divisor here 0. Cosine of pi over 2 is 0. Cosine of 3 pi over 2 is 0. So that's what's going on. So you don't want to do this as a general strategy. You want to use factoring like we saw earlier. And so that's going to lead to the full solution here, where we say theta is equal to pi over 4, pi over 2, 3 pi over 4, and 3 pi over 2. And again, you can even check this if you want with something like pi over 2. you could plug that in there, and also there, and also there, and also there. So we know cosine of pi over 2 is 0. So basically, this right here is going to be 0, and then this is going to be 0, and then this is going to be 0. So you would get 0 is equal to 0, which is a true statement. The same thing would happen with 3 pi over 2, because cosine of 3 pi over 2 is also 0, so you would have 0 equals 0 in that case. So those are valid solutions. So generally speaking, you want to use factoring and not divide both sides of an equation by a trigonometric function such as the cosine of theta, because you could potentially remove some of your solutions. All right, let's take a look at problem 3. So here we have 3 cosine theta is equal to 1 plus 2 cosine squared theta. So in this particular case, I'm going to think about putting this in terms of ax squared plus bx plus c equals 0 and try to factor the left side and see if I can use my zero product property. So I think it would be easiest to subtract 3 cosine of theta away from each side of the equation. That cancels, we'll have 0. I'm just going to write this on the left. So let's put 2 cosine squared theta first, and then minus 3 cosine of theta, and then plus 1. And of course, this would be equal to 0. Let me slide down here. And let's try to factor this. So let's put this like this. So this is a 2 here. That's a prime number. So I'm going to put 2 cosine of theta, and then cosine of theta. So if this right here is a positive, I know the signs are the same. This right here is a negative, so I know it's got to be a -1 and a -1. So the outer here would be -2 cosine of theta, and the inner here would be minus cosine of theta. And so -2 cosine of theta plus negative cosine of theta would be -3 cosine of theta. Okay, so this is the correct factorization. So at this point, you could just use your zero product property. So 2 cosine of theta minus 1 is equal to 0. Then or cosine of theta minus 1 equals 0. Add 1 to both sides. Let me cancel that. We would have 2 cosine of theta is equal to 1. Divide both sides by 2. And so this would cancel. You get cosine of theta is equal to 1/2. And then over here, let's add 1 to both sides. This would cancel. So I'll say or cosine of theta is equal to 1. All right, so coming to the unit circle, let's start out with cosine of theta equals 1/2. We know that cosine is positive in quadrants 1 and 4. So we're just going to look on the unit circle in quadrant 1 for an x coordinate of 1/2. So that's going to be right here at pi over 3 or 60 degrees. If we go into quadrant 4, again, you can ask the question, what angle has a reference angle of pi over 3? So that's going to be 5 pi over 3. Or again, you could just say, well, where's the x coordinate going to be 1/2? So that's going to be right here. So 2 ways to do the same thing. So we have our solutions for cosine of theta equals 1/2, again, in the interval where theta is greater than or equal to 0 and less than 2 pi. Now we're looking at cosine of theta equals 1. For this one, you're just looking for the x coordinate to be 1. So that's going to be right here at 0 in terms of radians, or in terms of degrees, you could say 0 degrees. All right, let's just write out the solution. So first we'll say that theta is equal to, let's start with 0, and then I'll go ahead and go to pi over 3. And then I'll finish up with this 5 pi over 3. And then if you want the general solution, so the general solution, not too bad. Let's start with 0. So I'll say 0 plus, again, the period for cosine is going to be 2 pi. So 2 pi, and then times n, where n is any integer. Notice that you can make that a little bit simpler, because if I have 2 pi n plus 0, well, that's just 2 pi n. So you can get rid of this 0 plus here and just slide this down, make it a little bit simpler. And then I'll list this pi over 3. So pi over 3, and then plus my 2 pi, and then times n, where n is any integer. And then lastly, let me slide over. We're going to have this solution here, which is 5 pi over 3, and then plus 2 pi n, where n is any integer, and let's just close that down. Okay, let's take a look at problem 4. So we have 1 plus 3 cosine squared theta plus 3 cosine of theta equals cosine squared theta. So let me just subtract cosine squared theta away from each side of the equation. This will cancel and give me 0. And so 3 cosine squared theta minus cosine squared theta, that would be 2 cosine squared theta, and then plus 3 cosine of theta, and then we'd have plus 1, and this equals 0. Okay, let's factor the left side. This would be 2 cosine of theta. And then this would be cosine of theta. And then this one and this one, let's think about this. Everything is a plus here, and this is a 1. 1 can only come from 1 times 1 or negative 1 times negative 1. And in this case, again, everything is positive. So let's put plus 1 and then plus 1. So this would give me 2 cosine of theta, and this would give me cosine of theta. And 2 times cosine of theta plus cosine of theta would give me 3 cosine of theta. So this is what we want. All right, so now I'm going to use my zero product property. So 2 cosine of theta plus 1 equals 0, or cosine of theta plus 1 is equal to 0. Subtract 1 away from each side of the equation over here. This becomes 2 cosine of theta is equal to negative 1. Divide both sides by 2. This cancels, and you get cosine of theta is equal to negative 1/2. Over here, if I subtract 1 away from each side, this cancels. You'll say, or cosine of theta is equal to negative 1. Okay, so where is cosine of theta going to be equal to negative 1/2? So again, cosine is negative in quadrants 2 and 3. So I'm looking for an x-coordinate of negative 1/2. So that's going to be right there and also right there. So over here in quadrant 2, that's going to be for 2 pi over 3. In quadrant 3, that's going to be for 4 pi over 3. Now also I want cosine of theta being equal to negative 1. So that x-coordinate of negative 1 is going to be right there, and that's going to be for pi. So I could say my solution, again, if I'm thinking about theta being greater than or equal to 0 and less than 2 pi, I could say it's 2 pi over 3, and then pi, and then 4 pi over 3. For the general solution, let's go ahead and say that it's 2 pi over 3 plus 2 pi n, and then we're going to have pi plus 2 pi n, and then we're going to have 4 pi over 3 plus, let me slide down so I can fit this, 2 pi n. So n is going to be any integer, and again, 2 pi is the period for cosine. All right, let's take a look at problem 5. So here we have 3 cosecant of theta equals square root of 3 cosecant of theta tangent of theta plus 2 cosecant of theta. So my strategy here is going to be to factor and then use the zero product property. So I'm going to first subtract 3 cosecant theta away from each side of the equation. This is going to cancel and put a 0 there. And so over here on the right, I'm actually going to flip this and put it on the left. We have the square root of 3 cosecant of theta tangent of theta, and then 2 cosecant theta minus 3 cosecant theta, and that's negative cosecant theta. So then this would be equal to this 0 over here. I'm just going to put that on the right. All right, so at this point I can factor. So I have this cosecant theta here and this cosecant theta here. And if you want, you can really write this as plus negative 1 times cosecant theta, if that helps you with the factoring. So coming down here, this is going to get pulled out. So you're going to have the cosecant of theta outside here. And then inside the parentheses, you'd have the square root of 3. And then tangent of theta. And then you have this negative 1 here. So you can go plus negative 1 or just minus 1, whatever you want to do. I just want to make it crystal clear when you pull that out, you're going to have that negative 1 that's left there. So let's close this down and say this equals 0. Now at this point, you can use your zero product property. So you can say the cosecant. So the cosecant of theta is equal to 0. Most of you know that does not have a solution, but I'll talk more about that in a moment. And then you can say, or you have the square root of 3 tangent of theta minus 1 is equal to 0. Now let me discuss this one right here first, and then I'll go to this one. So the first thing is you could come to a graph. You could use Desmos or something like that. I think we've all seen the graph of y equals cosecant of x or cosecant of theta or whatever you want to use there. Basically, you can see from the graph that the range is where the y values are going to be negative 1 or anything less, and then or it could be positive 1 or anything greater. But there's nothing you can plug in for x that would give you a y value of 0. So in other words, you're never going to see this graph impact the x-axis where y equals 0. So clearly, that equation would not have a solution. So I'll just put for this part, no solution. So I'm just going to come over here and work on this part. So I'm going to add 1 to both sides. This cancels. You would have the square root of 3 tangent of theta is equal to 1. Let's divide both sides of the equation by the square root of 3. This would cancel. you're going to get the tangent of theta is equal to 1 over the square root of 3. If you rationalize the denominator there, you're going to get that the tangent of theta is equal to the square root of 3 over 3. So the tangent of theta is equal to the square root of 3 over 3. Come back to the unit circle, and I'm thinking about this. Again, you can't directly get the values for the tangent of theta from the unit circle, but most of us know that this is going to be at pi over 6 or 30 degrees, right? So you could key this into your calculator as inverse tangent of square root of 3 over 3, and that's going to give you pi over 6 or 30 degrees. Now, alternatively, you can go through and say that, well, the tangent of pi over 6 is equal to the sine of pi over 6 over the cosine of pi over 6. So the sine of pi over 6 is 1/2, and then the cosine of pi over 6 is square root of 3 over 2. So this would be 1/2 times the reciprocal of square root of 3 over 2. So 2 over the square root of 3. The 2's cancel, so you get 1 over the square root of 3, which again, if you rationalize the denominator, you're back to that square root of 3 over 3. So one solution for theta is going to be this pi over 6. Now the other solution is going to be in quadrant 3, where tangent is also positive. And again, to find that, you could add pi radians. So you could add pi radians, or 180 degrees. That's going to be your period for tangent. You could also go into quadrant 3 and say what angle has a reference angle of pi over 6, and that's going to be 7 pi over 6. So let's list that as the other solution. So this is in the interval where theta is greater than or equal to 0 and less than 2 pi. Now again, if you want the general solution here, it's very easy. So we would say for the general solution, basically you would list pi over 6 and then plus pi, which is the period for tangent. Again, start here, rotate by pi radians or 180 degrees. And you could do that again from here. Just keep adding 180 degrees or pi radians. And you could do that forever and ever and ever. So let's put pi over 6 plus pi times n, where n is any integer. All right, let's take a look at problem 6. Here we have the negative square root of 3 secant of theta tangent of theta plus 4 secant of theta equals 3 secant of theta. Again, my strategy is to factor and use the zero product property. So I'm going to subtract 3 secant of theta away from each side of the equation. This right here is going to cancel and give me 0. So on the left, I now have negative square root of 3, and then secant of theta, tangent of theta, and then 4 secant of theta minus 3 secant of theta. That's going to be secant of theta, or you could put plus 1 times the secant of theta. And I'm just doing this because we're going to factor the secant of theta out. So I want it to be crystal clear that there's going to be a 1 there. So this would be equal to 0. Let me go ahead and highlight the secant of theta in each case, and let's pull that out in front of some parentheses. So you would have the secant of theta times the quantity. Inside, we're going to have the negative square root of 3, and then tangent of theta. And again, if I pull this out, I have this plus 1 here. Let me close that down, and this equals 0. At this point, we can use our zero product property. So we can say the secant of theta equals 0. So that has no solution. Then, or you could say the negative of the square root of 3 tangent of theta plus 1 is equal to 0. So for this one, let me cover that real quick. Again, for the secant of theta being equal to 0, if you think about the graph, y equals the secant of theta, again, you see that this never impacts the x-axis where y equals 0. So there's nothing I can plug in for x or theta or whatever you're working with there such that the y value would be 0 or the function value would be 0. So there's no solution there. So let me come back up here and just say this right here is no solution. Okay, over here I'm going to subtract 1 away from each side. This cancels. You get the negative of the square root of 3. Tangent of theta is equal to negative 1. Divide both sides by negative square root of 3. So this cancels. You're going to get tangent of theta is equal to negative over negative is positive. So you have 1 over the square root of 3, which again, if you rationalize the denominator, that would be the square root of 3 over 3. We know we're going to have the exact same solution we had last time. So basically, we know that this guy is going to occur at pi over 6 in quadrant 1, and then also 7 pi over 6 in quadrant 3, where tangent is also positive. So let me put that theta is equal to pi over 6, and then also 7 pi over 6. So this is in the interval where theta is greater than or equal to 0 and less than 2 pi. And then for the general solution, Again, just like last time, we'll just put pi over 6 plus the period for this guy is going to be pi, right? So if I add pi radians, add another solution, and then add pi radians, back to a solution, so on and so forth. So plus pi times n, where n is any integer. So let's close that down. All right, for problem 7, we have -1 minus 2 cotangent squared theta equals negative cotangent squared theta plus 2 cotangent of theta. All right, the idea here is I'm going to add 2 cotangent squared theta to both sides of the equation, and then I'm going to add 1 to both sides of the equation. So this is going to cancel, and this is going to cancel, so the left side is 0. I'm going to flip this over here and basically take this and write it on the left. So negative cotangent squared theta plus 2 cotangent squared theta, that would be cotangent squared theta. And then you have plus 2 cotangent of theta, and then plus 1. And so this would be equal to, this guy right here would be on the right now, so 0. So basically, let me set up some parentheses. I'm going to put a cotangent of theta here and a cotangent of theta here because this is a 1, right? So cotangent of theta times cotangent of theta, that's cotangent squared theta. Then I need 2 integers whose sum is 2 and whose product is 1. Well, everything here is a plus, so I can just put a plus here and a plus here. And in terms of 1, it's either 1 times 1 or -1 times -1. And we know that this is going to all be positive here. So basically, it's going to be a 1 here and a 1 here. And if you check that, it does work out. 1 plus 1 is 2. 1 times 1 is 1. So this can be written as cotangent of theta plus 1 quantity squared is equal to 0. So lots of ways to think about this. Typically, I just use the square root property and say that this right here, the cotangent of theta plus 1, would be equal to plus or minus the square root of 0, which is just 0. So subtract 1 away from each side, and you're going to get that the cotangent of theta is equal to -1. So let me grab this real quick. So we should know at this point that if the cotangent of theta is equal to -1, that means the tangent of theta is also equal to -1 because the tangent of theta is equal to 1 over the cotangent of theta, and 1 over -1 is -1. So let me work on it like this and think about this for a moment. We know the tangent of theta is going to be +1 at pi over 4, right? Because essentially when you think about the tangent of pi over 4, it's the sine of pi over 4 over the cosine of pi over 4. And so you have the same non-zero number being divided by itself. Square root of 2 over 2, that's the sine value. Square root of 2 over 2, that's the cosine value. So the same non-zero number divided by itself is going to be 1. The issue here is that tangent is negative in quadrants 2 and 4. So you're going to go into quadrants 2 and 4 and find an angle with a reference angle of pi over 4. So in quadrant 2, that's going to be 3 pi over 4. And in quadrant 4, that's going to be at 7 pi over 4. Notice that here you would be dividing opposites. So you would say the sine value is square root of 2 over 2, and the cosine value is negative square root of 2 over 2. So when you divide opposites, you get -1. So let me get rid of this, and let me actually get rid of this highlighting here so nobody's confused. Essentially, you would say that your solution is that theta is equal to, we'll put 3 pi over 4, and then we'll have 7 pi over 4. So this is where theta is greater than or equal to 0 and less than 2 pi. And then if you want the general solution, well, again, the period for tangent and also cotangent is pi. So starting here, I can add pi, and I'll get to the next solution. And then if I add pi, I get to another solution, and so on and so forth. So I can just have that 3 pi over 4 plus pi, again, that's your period for tangent or cotangent, times n, where n is any integer. All right, let's take a look at problem 8. So here we have the negative of the square root of 3, cotangent of theta, plus 2 cotangent of theta, sine of theta, minus 3 sine of theta equals -3 sine of theta. So you have the same thing on each side of an equation, so of course you can just get rid of it. To show it for the sake of the tutorial, let's add 3 sine of theta to both sides of the equation. So this right here is going to cancel away. Let me write a 0 over here. So now on the left, we have the negative of the square root of 3, and then cotangent of theta, plus 2 cotangent of theta, sine of theta, and this equals, over on the right, we have 0. So at this point, I'm going to factor out the cotangent of theta. So let's pull that out in front of some parentheses. So we'll say we have the cotangent of theta times the quantity. Here you would be left with the negative of the square root of 3, and then plus over here, notice you have this 2 and you have this sine of theta. Okay, so if I pull out the cotangent of theta, I'd be left with 2 times the sine of theta. So 2 times the sine of theta. Let's close that down and set this equal to 0. Now from the zero product property, we can now say that the cotangent of theta is equal to 0, or this guy right here, so the negative of the square root of 3, and then plus 2 sine of theta is equal to 0. So on the left, I really don't need to do anything else to clean this up. On the right, let's add the square root of 3 to both sides of the equation. This will cancel away. We'll say that we have 2 sine of theta is equal to the square root of 3. Let's divide both sides of the equation by 2, and so this would cancel. And so you can basically say that the cotangent of theta is equal to 0. Let me write or. I'm going to put the sine of theta is equal to, this would be the square root of 3 over 2. So let's grab this. Okay, so first off, let's start with the sine of theta equals square root of 3 over 2. It's a little bit easier to think about. So first off, sine is positive, again, in quadrants 1 and 2. So go into quadrant 1 and just look for a y-coordinate of square root of 3 over 2. So that's going to be right here. So that's at pi over 3. And again, if we go into quadrant 2, I'm looking for the same thing. So a y-coordinate of square root of 3 over 2. So that's right there at 2 pi over 3. Again, I can't stress this enough. If you don't have a unit circle, just do your inverse sine function with square root of 3 over 2 as the argument. You're going to get pi over 3. Then go into quadrant 2 and say, what angle has a reference angle of pi over 3? And that's going to be 2 pi over 3. So that's how you can get your solutions without a unit circle and with a calculator. All right, so the cotangent of theta equals 0. So let's think about that for a moment. So the cotangent of theta is by definition the cosine of theta over the sine of theta. Well, if we want something like this to be 0, you would need the numerator to be 0 and the denominator to not be 0, because again, we don't want to divide by 0 that's undefined. So we would want to ask the question, where is the cosine of theta equal to 0? Well, you're looking for an x-coordinate of 0, so that's going to be right here at pi over 2, and then right here at 3 pi over 2. So notice that the x-coordinate is 0 and the y-coordinate is not 0. So you would have 0 divided by something that's not 0, which gives you 0. So for the solution, where again theta is greater than or equal to 0 and less than 2 pi, we'll say that theta is equal to, let's go pi over 3, and then let's go pi over 2, and then let's go 2 pi over 3, and let's finish this up with 3 pi over 2. All right, so for the general solution, let's go ahead and put some set braces in there. I'm going to start with pi over 3, so pi over 3, and then plus 2 pi, so that's going to be the period for sine, and then times n, where n is any integer. Then when I come to this solution here, I'm going to write pi over 2, but notice that if you started here and you rotate by pi radians or 180 degrees, you're back to another solution. Okay, so we know that the period for a cotangent is going to be pi or 180 degrees. Again, if you add pi, you're back to another solution, and so on and so forth. So for this one, I could just put plus pi times n, where again, n is any integer. And then for the last one, let's put 2 pi over 3. Let me get rid of this and this and this and also this. Let me slide way over, and I'm just going to put plus 2 pi n, where n is any integer. Okay, let's take a look at problem 9. So here we have negative 2 is equal to negative secant squared theta minus secant of theta. So all I'm going to do here is just add 2 to both sides of the equation. This would cancel and give me a 0 over here. I'm just going to rearrange things and put negative secant squared theta, and then minus secant of theta, and then plus 2 equals 0. To make this easier to factor, I'm just going to multiply everything by negative 1. So this sign would change, this sign would change, and then this sign would change. No change to 0. So this became positive, positive, and then negative. Again, no change to 0. Now it's very easy to factor this. Again, this is just a 1 right here. So you could say that this is the secant of theta, and then this is the secant of theta. Let me make this a little bit cleaner here. Now, this is a 1 here, and this is a negative 2. So two integers that sum to 1 and have a product of negative 2, well, that's going to be positive 2 and negative 1. So now you can use your zero product property and say the secant of theta plus 2 is equal to 0, or the secant of theta minus 1 is equal to 0. Let me subtract 2 away from each side. This cancels. You get the secant of theta is equal to negative 2. Then or, you're going to get the secant of theta is equal to, let me add 1 to both sides over here, positive 1. So since we can get the cosine values from the unit circle, it's easier just to convert this over into cosine. So we can say the cosine of theta is equal to 1 over the secant of theta. So for cosine of theta, it's equal to 1 over. The secant of theta is negative 2. So 1 over negative 2 is just negative 1/2. Let me move this down over here so this fits. So again, negative 1/2. Let me get rid of this. And then let me slide down here a little bit. Then we'd say or. The other one for cosine of theta is equal to, well, 1 over 1 is just 1. So let me grab this. So where is the cosine of theta equal to negative 1/2? Again, cosine is going to be negative in quadrants 2 and 3. And you're looking for an x-coordinate of negative 1/2. So that's going to be right here. So at 2 pi over 3, the reference angle is pi over 3. And so if I go into quadrant 3, again, I can look for an x-coordinate of negative 1/2, or I can just say, what is the angle with the reference angle of pi over 3? Well, that's going to be 4 pi over 3. Then for the other one, we have cosine of theta equals 1. So I'm looking for an x-coordinate of 1. So that's just going to be right there at 0. So let me go ahead and write out the solution. So basically, where theta is greater than or equal to 0 and less than 2 pi, theta would be equal to, let's put 0, let's put 2 pi over 3, and then let's put 4 pi over 3. Now for the general solution, I want you to notice that if you start here and you go to here, well, you're going to basically add 2 pi over 3 or 120 degrees. Then if you start here and you go to here, you're going to add another 2 pi over 3 or 120 degrees. Then if you start here and go to here, you're going to add another 120 degrees or 2 pi over 3 radians. So this would continue forever and ever and ever. So for the general solution, let's go ahead and say we're going to start with 0, and then we add 2 pi over 3, so that's 120 degrees in terms of radians, times n, where n is any integer. Now you can make this a little bit cleaner because adding 0 to something does not change it, so you can really get rid of that and tighten this down a little bit and say for the general solution, let me just put this over it like this, it's 2 pi over 3 times n, where n is any integer. All right, for problem 10, we have square root of 3 secant of theta plus 3 secant of theta cotangent of theta equals 0. So immediately I can factor out this secant of theta. So from here and here, let me slide down here a little bit, and I'm just going to pull that out in front of some parentheses. So let me write the secant of theta. So inside you would have the square root of 3 plus you're going to have 3 cotangent of theta, and this equals 0. So at this point I can use my zero product property. So I can say the secant of theta equals 0. So this has no solution. We talked about that earlier. So let me just write that out, and we'll put or. Over here we have the square root of 3 plus 3 cotangent of theta is equal to 0. So for this one, let me go ahead and subtract square root of 3 away from each side of the equation. So this would cancel away. You would have 3 cotangent of theta is equal to the negative of the square root of 3. And then let me divide both sides of the equation by 3. And so this would cancel. And so what we have is the cotangent of theta is equal to the negative of the square root of 3 over 3. And what I'm going to do is put this in terms of tangent. So I'll say that the tangent of theta is equal to, again, 1 over the cotangent of theta. So that's basically me just taking the reciprocal of this. So the negative of 3 over the square root of 3. If you rationalize the denominator, so multiply by the square root of 3 over the square root of 3, you're going to get the negative of 3 times the square root of 3 over 3. The 3's would cancel. So this is the negative of the square root of 3. So the negative of the square root of 3. Let me make this a little bit cleaner there. So let's grab this real quick. Now again, we can't directly get the tangent values from the unit circle, but we can use it to think about things. I would just use my calculator and say, well, what is the inverse tangent of the square root of 3? And if you key that in, you're going to get pi over 3. And that's coming from the fact that at pi over 3, you have your sine value of square root of 3 over 2 and your cosine value of 1/2. So basically, the tangent of pi over 3 is coming from the square root of 3 over 2 times the reciprocal of 1/2, which is 2. So this cancels, and you get the square root of 3. So now what we need to do is go into quadrants 2 and 4, where tangent is negative, and we need to find an angle with a reference angle of pi over 3. So coming into quadrant 2, that's going to be at 2 pi over 3. And then coming into quadrant 4, that's going to be at 5 pi over 3. And again, if you don't know that, you can always say, well, in quadrant 2, it's going to be pi minus my reference angle, which is pi over 3. So this is 3 pi over 3. So this gives me 2 pi over 3. And then in quadrant 4, you could do 2 pi minus your reference angle of pi over 3. So this would be 6 pi over 3. So this gives me 5 pi over 3. So if you don't have a unit circle handy, you can always do that. It's really up to you what you want to do. Lots of different ways to come up with these solutions. So I'm going to say that theta is equal to 2 pi over 3, and then 5 pi over 3. So that's where theta is greater than or equal to 0 and less than 2 pi. And then for the general solution, again, if I started here, well, I'm just going to rotate by pi radians, or 180 degrees, to continually get to additional solutions. So I'll say for the general solution, it's going to be starting with 2 pi over 3, and then plus pi times n, where n is any integer. All right, let's take a look at the practice test. For the instructions, we're asked to solve each equation for theta is greater than or equal to 0 and less than 2 pi. All right, for the first problem, we have a negative cosine squared theta is equal to 3 minus 5 cosine squared theta. So your goal here is to get cosine of theta equal to some number, and then we can go to the unit circle, or we can use our inverse cosine function to get all of our answers, where theta is greater than or equal to 0 and less than 2 pi. So the first thing I would do is add 5 cosine squared theta to both sides of this equation. And so over here on the right, this is going to cancel away. Negative cosine squared theta plus 5 cosine squared theta would give me 4 cosine squared theta, and this equals 3. Again, I want to isolate the cosine of theta. On the left, I have 4 times cosine squared theta. So I'm going to first get rid of this 4 by dividing both sides of the equation by 4. And so this would cancel away. You're going to have cosine squared theta is equal to 3/4. Now, we can solve this using the square root property. Let me put a little border. I know most of you know this, but if you have x squared is equal to k, then x is equal to plus or minus the square root of k. So we're just going to use that here. Cosine squared theta is equal to 3/4. So that tells me that the cosine of theta is equal to plus or minus the square root of 3/4. We can simplify this. We can say that this is the square root of 3 over the square root of 4. And the square root of 4, if you wrote that out, is going to be 2. So now we have that the cosine of theta is equal to plus or minus the square root of 3 over 2. So let me write this out as the cosine of theta is equal to the square root of 3 over 2. And then let me put or the cosine of theta is equal to the negative of the square root of 3 over 2. So let me grab this real quick and let me paste this in right here. So again, you can use your unit circle or you can use your inverse cosine function. So I'm just going to use the unit circle because it's going to be a little bit quicker here. So if the cosine of theta is equal to square root of 3 over 2, first off, this is positive, and cosine is positive in quadrants 1 and 4. So I'm going to go into quadrants 1 and 4 and look for an x-coordinate of square root of 3 over 2. So that's going to occur right here, where we have pi over 6, or 30 degrees. And that's also going to occur right here, where we have 11 pi over 6, or 330 degrees. Now, in terms of cosine of theta being equal to negative square root of 3 over 2, cosine is negative in quadrants 2 and 3. So if I go into quadrant 2, and I'm looking for negative square root of 3 over 2 for the x-coordinate, so that's going to be right here, and that's going to be for 5 pi over 6, or 150 degrees. And then coming into quadrant 3, I'm looking for negative square root of 3 over 2 for the x-coordinate. That's going to be right here at 7 pi over 6, or 210 degrees. So at this point, we have our solution in terms of what the practice test asked for. So where theta is greater than or equal to 0 and less than 2 pi, well, you would basically say that theta is going to be equal to, let's just start with pi over 6, or you could do 30 degrees if you want, and then let's go to 5 pi over 6, or you could put 150 degrees, and then let's go to 7 pi over 6, or you could put 210 degrees, and then let's finish up with 11 pi over 6, or 330 degrees. If you don't have a unit circle handy, then what you want to do is you want to use your inverse cosine function, and you want to plug in the square root of 3 over 2, and that's going to give you pi over 6. So that gives you one solution in quadrant 1. What you're going to have to do is go into quadrants 2, 3, and 4 and look for an angle with a reference angle of pi over 6, and that's how you're going to get these other solutions of 5 pi over 6, 7 pi over 6, and 11 pi over 6. So you can do that if you have to, if you don't have a unit circle handy, or maybe you just prefer to use the calculator. Let me get rid of this. And now let's talk about the general solution. So I'm just going to write G period S period for general solution. And let me put some set braces in here. Now we know that the period for sine and then also cosine is 2 pi. So normally you do something like this. You'll say, okay, well, here's a solution. It's pi over 6. And then you add 2 pi, that's your period for cosine, and then times n, where n is any integer. Now that does work. You could keep going through and saying, okay, well, I have 5 pi over 6 plus 2 pi n. But what's going to happen is you're going to actually make this longer than it needs to be. Let me get rid of this. And actually, let me get rid of this. So first off, I want you to notice that if you start here and you add pi radians, or 180 degrees, you're going to come to this point right here, which is another solution at 7 pi over 6. Then if you add another pi radians, or 180 degrees, you're going to get to another solution. So we're swinging around right there. So at that point, you'd be at 13 pi over 6. And I just got that. Let me just do this off to the side so nobody's confused. I just did 7 pi over 6 plus pi, which is 6 pi over 6. So that's 13 pi over 6. So that's another solution. And this would keep going on forever and ever and ever. So really all I have to do is say pi over 6 plus pi times n. Now similarly, if I started with this guy right here, 5 pi over 6, and I swing around by pi radians, or again 180 degrees, I'm getting to this next solution. And then if I swing around by another pi radians, or 180 degrees, I'm back to another solution, and so on and so forth. So I'm just going to put a comma, and I'm going to take that 5 pi over 6 and then add pi n. So that right there would be my general solution. So pi over 6 plus pi n, and then also 5 pi over 6 plus pi n. All right, for problem 2, we have 1 plus 3 tangent squared theta is equal to 4 tangent squared theta. The idea here is we want tangent of theta equals some number. So I would start by subtracting 3 tangent squared theta away from each side of the equation. Let me go ahead and cancel that away. On the left, you just have 1, and this equals 4 tangent squared theta minus 3 tangent squared theta would just be tangent squared theta. Now let me just rearrange this and say it's tangent squared theta equals 1. And I'm just going to use my square root property and say that the tangent of theta is equal to plus or minus the square root of 1. Now the square root of 1 is 1, so the tangent of theta is equal to plus or minus 1. Let me write this as tangent of theta is equal to 1, and then or the tangent of theta is equal to negative 1. All right, so you might find it helpful to use a unit circle even though you can't directly get your tangent values from the unit circle. What I would start off with is this top equation. So the tangent of theta equals 1. So let's think about it for a moment, and then we'll use our inverse tangent function. First off, the tangent of theta, by definition, is the sine of theta over the cosine of theta. So where would this be equal to 1? Well, you're looking for the same sine value as you have for the cosine value. In other words, the same non-zero number divided by itself would give you 1. Well, that's going to occur at pi over 4, or 45 degrees. Notice that your sine value is square root of 2 over 2, and your cosine value is square root of 2 over 2. So in other words, the tangent of pi over 4 is equal to the sine of pi over 4 over the cosine of pi over 4. And of course, this would be 1 because you have square root of 2 over 2 divided by square root of 2 over 2, which gives you 1. Now, I think all of you know that at this point, but it's nice to get a little refresher when we think about this. So if you did the inverse tangent of 1, you would get pi over 4, or 45 degrees. So this would give you your solution in quadrant 1. if you want to think about the other solution for tangent of theta equals 1, again, the period for tangent is pi, so you would just swing yourself around by 180 degrees or pi radians, and that's going to put you right there at 5 pi over 4 or 225 degrees. So notice here, you have the same non-zero number that would be divided by itself. So the sine value of 5 pi over 4 is negative square root of 2 over 2, and the cosine value of 5 pi over 4 is negative square root of 2 over 2. So again, the same non-zero number divided by itself is 1. So that would be another solution for tangent of theta equals 1. So let me get rid of this, and let me just write that theta is equal to, I'm going to put pi over 4, I'm going to put a space, and then I'm going to put 5 pi over 4 here, and then let me leave that blank there. I'm going to list this solution and this solution in those positions, but I want to explain where those are coming from. So let me get rid of this and get rid of this. And now we have tangent of theta equals negative 1. So most of you know that you can just go into quadrant 2 and find an angle with a reference angle of pi over 4. So that's going to occur at 3 pi over 4. But again, if you didn't know that, you can go in and look for, well, here I have a sine value of square root of 2 over 2, and I have a cosine value of a negative square root of 2 over 2. So if I divide basically opposites there, I'm going to get negative 1. And the same thing would happen, again, if I swing myself around by pi radians, or 180 degrees, I'm going to end up right here at 7 pi over 4. Notice you'd have a reference angle of pi over 4 there, but again, you'd be dividing opposites here to get your tangent value, so you'd end up with tangent of 7 pi over 4 being equal to negative 1. So let me list those solutions here. So you have 3 pi over 4, and then you have 7 pi over 4. So let me scooch this down here. This would be for the interval where theta is greater than or equal to 0 and less than 2 pi. Let me get rid of all of this, and I want you to think about the general solution. So this is one where, again, you have to maybe write it out for a moment and then think about how you can make it a little bit better. The period for tangent is pi, so we know that at this point. So in other words, I could start at this guy right here, and I could swing around by pi radians, or 180 degrees, and end up there. And then again, I could swing around by pi radians, or 180 degrees, and it'd end up at another solution. So you could start by saying that you have pi over 4 plus pi n. And then you could put a comma, and then you can go, okay, well, the other guy, let me get rid of this, is at 3 pi over 4, and then I'm going to swing around by pi radians. So that's going to put me right there at 7 pi over 4, so that's another solution. Swing around by pi radians, and again, you can continue this forever and ever and ever. So you might be tempted to say, okay, well, this is 3 pi over 4 plus pi n. But the problem is you can make that a little bit better or a little bit more concise. So let me get rid of this, and let's think about this again. You have a solution that's going to be right here, and then right here, and then right here, and then you're going to have one right there. So notice that actually this right here is going to be pi over 2 radians, and then this right here is going to be pi over 2 radians, and then this right here is going to be pi over 2 radians, and then this is going to be pi over 2 radians. So basically you can keep adding pi over 2 radians or subtracting away pi over 2 radians to get to your next solution. So let me get rid of this. Let me make this a little bit better. So pi over 4 plus pi over 2 times n, where n is any integer. So that would be your general solution. All right, let's take a look at problem 3. So here we have 7 is equal to 4 sine squared theta plus 4. So I want sine of theta on one side and a number on the other. So let's subtract 4 away from each side of the equation. That would cancel. 7 minus 4 is 3. So you're going to have 3 is equal to 4 sine squared theta. You can divide both sides of the equation by 4. So let me cancel this with this. And I'm just going to rearrange this and say it's sine squared theta is equal to 3/4. So what you'd want to do is use your square root property. So we're going to have the sine of theta is equal to plus or minus the square root of 3/4. So again, we saw this earlier. You can simplify this. So this would be plus or minus the square root of 3 over the square root of 4. The square root of 4 would be 2. So let me write this out as the sine of theta is equal to the square root of 3 over 2. Then I'll put or the sine of theta is equal to the negative of the square root of 3 over 2. All right, so I'm just going to come to the unit circle. It's going to make it a little bit quicker for us to get a solution. So for the sine of theta being equal to the square root of 3 over 2, I'm looking in quadrants 1 and 2 for a y value of square root of 3 over 2. Remember, sine is positive in quadrants 1 and 2. So that's going to happen right here. So that's going to be at pi over 3. in terms of radians or 60 degrees. And then in quadrant 2, that's going to happen right here. So that's going to be at 2 pi over 3 or 120 degrees. Now, if I want to find sine of theta being equal to negative square root of 3 over 2, again, I'm going into quadrants 3 and 4 where sine is negative, and I want to look for a y-coordinate of negative square root of 3 over 2. So it's going to be right there. So this is going to be at 4 pi over 3. And then also that's going to be right here. So that's going to be at 5 pi over 3. So for 4 pi over 3, again, that's 240 degrees. And for 5 pi over 3, that's going to be 300 degrees. All right, so to go in that interval that we were given, so theta is greater than or equal to 0 and less than 2 pi, we'll say that theta is equal to, let's say, pi over 3. And then we'll put 2 pi over 3. And then we'll put 4 pi over 3. And then lastly, we're going to put 5 pi over 3. Now, again, what you could do, if you didn't want to use the unit circle or you didn't have one, you could have started by saying, what is the inverse sine of square root of 3 over 2? That would give you pi over 3. So that's your solution in quadrant 1. And then you just go into quadrants 2, 3, and 4, and you say, what is the angle with a reference angle of pi over 3? So that's going to be 2 pi over 3, 4 pi over 3, and then 5 pi over 3. Now, when we think about the general solution, so the general solution, again, we can do a little bit better than just listing each one of these and saying plus 2 pi n. I'm going to start with pi over 3, and then I'm going to think about, well, if I go from right here and I swing around by pi, I'm going to end up right there at a solution. If I swing around by pi, I'm going to go back to a solution. So really, I could just add pi n, where again, n is any integer, and then I'm going to put a comma. And let me go to this other solution over here. So this guy right here, again, if you look at that one and you look at that one, I could just add pi or 180 degrees to get there, and then add pi to get there. I'm just swinging myself around by pi radians each time. So let's say that we would have 2 pi over 3 plus pi n. So my general solution is pi over 3 plus pi n, and then also I would have 2 pi over 3 plus pi n. All right, let's take a look at problem 4. So here we have negative 2 is equal to cotangent squared theta minus 3. So I want cotangent of theta equals some number. So let's start by just adding 3 to both sides of the equation. So this is going to cancel. And so I would have negative 2 plus 3, that's going to be 1. And this equals cotangent squared theta. So we could flip this around and say it's cotangent squared theta is equal to 1. Makes it a little bit easier to think about it. Let me slide this up here. And basically, you're just going to use your square root property and say that the cotangent of theta is equal to plus or minus the square root of 1. And of course, the square root of 1 is just 1. Let me slide down here and I'll write this as the cotangent of theta is equal to 1, or the cotangent of theta is equal to negative 1. Now remember, when you think about the relationship between cotangent and tangent, we can say that the tangent of theta is equal to 1 over the cotangent of theta. So here I could say that the tangent of theta is equal to 1 over 1, which is 1, and then or the tangent of theta is equal to 1 over negative 1, which is negative 1. So basically you could solve this, which we solved earlier in problem 2, right? So we already know what the solution for this is. And again, if we think about the tangent of theta being equal to 1, well, that's going to occur at pi over 4, and then also 5 pi over 4. And then if we think about the tangent of theta being equal to negative 1, well, that's going to occur at 3 pi over 4, and then 7 pi over 4. So in other words, you just use your inverse tangent function with 1 as the argument. Let me get rid of this. We don't need this anymore. You could say that the inverse tangent of 1, again, is pi over 4, and then you can use that as the reference angle in quadrants 2, 3, and 4. So what angle in quadrant 2 has a reference angle of pi over 4? Well, it's 3 pi over 4. Then when you go into quadrant 3, it's 5 pi over 4. When you go into quadrant 4, it's 7 pi over 4. So you can basically just move this up here. Let me get rid of this. Let's move this up here and say that for theta being greater than or equal to 0 and less than 2 pi, well, your theta is going to be pi over 4. And then you're going to have 3 pi over 4. And then you're going to have 5 pi over 4. And then you're going to have 7 pi over 4. Now for the general solution, again, we found this earlier. We said that to go from here to here is going to be 90 degrees or pi over 2 radians. And then to go from here to here, again, that's going to be pi over 2 radians. And then to go from here to here, that's going to be pi over 2 radians. And then from here to here, that's pi over 2 radians. So basically just start with pi over 4 and then add pi over 2 times n, where n is any integer. All right, let's take a look at problem 5. So we have secant of theta plus 1 equals tangent squared theta. In this particular case, you'll notice that you have secant of theta and you have tangent squared theta. So our strategy when this occurs is to use a little identity. Remember, from the Pythagorean identities, we have tangent squared x plus 1 equals secant squared x. So you could say that tangent squared theta is equal to, I'm just going to subtract 1 away from each side, so secant squared theta minus 1. So let me grab this real quick, come back up here and paste this in. And the idea here is that you have tangent squared theta and you have tangent squared theta. Now, tangent squared theta is equal to or the same as secant squared theta minus 1. So I can just take this right here and plug it in for tangent squared theta right here. So let's see what that looks like. Let me slide down a little bit so we have some room. I'm going to have secant of theta plus 1 is equal to, instead of, again, tangent squared theta, I'm going to plug in this secant squared theta minus 1. So now what we want to do is put this in terms of secant of theta equals some number. So in order to do that, notice you have secant squared theta here and you have secant of theta here. So I'm just going to subtract secant squared theta away from each side of the equation. So over here, this is going to cancel away. I'm also going to add 1 to both sides of the equation. So this would cancel away. So on the right side, this is now just 0. So on the left, let's go ahead and say we have negative secant squared theta. And then you're going to have plus secant of theta. And then plus 1 plus 1 is 2. And of course, this equals 0. So what I would do at this point to make it easier to factor is multiply everything by negative 1. So this would become positive, negative, negative, and of course there's no change to 0. So now it's very easy to factor this. So I'm going to open up some parentheses here. And if this is hard for you, like I know for most students it is, you could just think about, well, what if I was factoring u squared minus u minus 2 is equal to 0? What would I do? Again, thinking about this, this is a 1 here, so I know I would put a u here and a u here. Okay, well, this is secant squared theta. So this is a 1 here, basically. So you could say that this is secant of theta and that this is secant of theta. So just matching what we're doing there. It's the same exact thing. Now think about it. This is negative 1 and this is negative 2. So I want two integers whose sum is negative 1 and whose product is negative 2. Well, that's going to be negative 2 and positive 1. So again, it's the same thing up here. So this is going to be negative 2 and positive 1. So if you get stuck on factoring with something like this, just stop for a minute and say, okay, well, what if secant of theta was u? Well, then I could write this as u squared minus u minus 2 and set that equal to 0 and solve. And then when you're done, just go back and say, okay, well, this is u minus 2, this quantity times the quantity u plus 1, and this equals 0. We'll just plug in a secant of theta for u, and you're basically good to go. So let's get rid of this. Just using that as a little guide. And now we can use what we call the zero product property. So we can say this is the secant of theta minus 2 is equal to 0, or the secant of theta plus 1 is equal to 0. For this one, you could add 2 to both sides and say the secant of theta is equal to 2. And then or over here, you could subtract 1 away from each side. So the secant of theta is equal to negative 1. So I'm going to put this in terms of cosine. That way we can use the unit circle. So remember that the cosine of theta is equal to 1 over the secant of theta. So here, if the secant of theta equals 2, then I can say that the cosine of theta is going to be equal to, just take the reciprocal of this, it's going to be 1/2. Then or, over here, if the secant of theta is equal to negative 1, well, basically the reciprocal of that is also going to be negative 1. So we'll say that the cosine of theta is equal to negative 1. Okay, so where is cosine of theta equal to 1/2? So this is positive 1/2. So remember, cosine is positive in quadrants 1 and 4. So if I look in quadrant 1, I'm looking for an x-coordinate of 1/2. So that's going to be right here. So that's going to be with pi over 3 in terms of radians, or 60 degrees. And then going into quadrant 4, again, I'm looking for this 1/2 for the x-coordinate. So that's going to be with 5 pi over 3 or 300 degrees. Again, the other way to do that is to say, what is the inverse cosine of 1/2? That's going to give me pi over 3. And then I could say, well, cosine is positive also in quadrant 4. So what's the angle in quadrant 4 with a reference angle of pi over 3? And that's going to be 5 pi over 3. So those are the solutions for cosine of theta equals 1/2. Now, what about cosine of theta equals negative 1? Well, that's only going to be where the x-coordinate is negative 1, and that's going to be over here at pi. Okay, so that's right there. So I have my solution, again, when we're thinking about where theta is greater than or equal to 0 and less than 2 pi, I would say that theta is equal to, we're going to say pi over 3, and then we're going to say pi, and then we're going to say 5 pi over 3. So let's think about the general solution. With the period for cosine, remember it's going to be 2 pi. So if I think about this solution right here, again, if I swing around by 2 pi, of course I'm going to get to another solution. But I want you to notice that if you go from this solution to this solution, that's me swinging around by 120 degrees, or 2 pi over 3 if you want to think about that in terms of radians. Then to go from this solution to this solution, it's another 120 degrees, or 2 pi over 3. And then you get from this solution to this solution, it's another 120 degrees, or 2 pi over 3 in terms of radians. So I can greatly simplify things by just saying that it's going to be pi over 3, and then plus, you're going to have 2 pi over 3. Again, that's going to be 120 degrees in terms of radians, times n, where n is any integer. All right, for problem 6, we have 2 plus sine squared theta is equal to cosine squared theta plus 3 sine of theta. So here you have sine squared theta, you have cosine squared theta, and you have 3 sine of theta. So think about replacing this using your Pythagorean identity. So sine squared x plus cosine squared x equals 1. You could say cosine squared theta, I'm just going to replace x with theta, is equal to this 1, and then subtract sine squared, again, I'm just going to use theta, away from each side. So minus sine squared theta. Okay, let's grab this, come back up here. So let's think about this and this. Those are the same, cosine squared theta. Well, we're saying that cosine squared theta is equal to this 1 minus sine squared theta. So I can take this and plug it in right there. Okay, so that's all I'm going to do. And so I'm going to have 2 plus sine squared theta, and this equals, again, this is being plugged in for this. So 1 minus sine squared theta, and then plus 3 sine of theta. Now, the idea here is that you want to get sine of theta equals some number. Let me start by subtracting 1 away from each side, so that will cancel away. Let me add sine squared theta to each side. That will cancel away. And let me subtract 3 sine of theta from each side. So that's going to cancel away here. We're going to put the right side as 0 because everything has canceled away. And on the left, let me just stack this up. So minus 3 sine of theta. So it's a little bit messy here, but let me clean it up with you. So I'm going to start with sine squared theta plus sine squared theta. That's going to be 2 sine squared theta. And then I'm going to go minus 3 times sine of theta. And then 2 minus 1 is going to be 1, so plus 1, and this equals 0. Don't forget about this 0 over here. This is something you can actually factor. So let me go ahead and do this like this and say that this is 2 sine squared theta. So 2 is a prime number, so I'm going to put 2 sine of theta and then sine of theta. Now this one right here is pretty easy because this guy right here is a minus and this guy right here is a plus. So I know that comes from a negative times a negative. And then just think about 1. Well, that's 1 times 1. So let me put a 1 here and a 1 here. So basically this would work itself out because the outer would be negative 2 sine of theta, and the inner would be minus sine of theta. So negative 2 sine of theta minus sine of theta is negative 3 sine of theta. So this is basically what we want. Let me get rid of this, and let me come down here. So now we can use our zero product property. We can say 2 sine of theta minus 1 is equal to 0, or sine of theta minus 1 is equal to 0. Let me add 1 to both sides of the equation. We have 2 sine of theta is equal to 1. And then or we could say the sine of theta is equal to 1. Let me divide both sides of the equation by 2. So here this would cancel. And so we'll say the sine of theta is equal to 1/2. And then or the sine of theta is equal to 1. So let's start with sine of theta equals 1/2. So again, I'm looking for a y coordinate of 1/2. So that's going to be right here. That's in quadrant 1 with pi over 6. Remember, sine is also positive in quadrant 2. So going into quadrant 2, I'm going to have 1/2 right there for the y coordinate. So that's going to be at 5 pi over 6. You could have also said the inverse sine of 1/2 is going to give you pi over 6, and then say, well, sine is positive in quadrant 2 as well, so go into quadrant 2 and find an angle with a reference angle of pi over 6, and that's 5 pi over 6. Okay, so those are two solutions. Now you also have sine of theta equals 1, so that's going to occur at pi over 2. So notice that that is 1 there, so that's at pi over 2, or 90 degrees. So thinking about the solution, so theta is greater than or equal to 0 and less than 2 pi, we'll say that theta is equal to, well, you have your pi over 6, and then you have your pi over 2, and then you have your 5 pi over 6. Now thinking about the general solution, this one's going to be a bit long. There's really not a shortcut here. If you look at going from this guy to this guy, well, that's going to be 60 degrees or pi over 3. And then to go from this guy to this guy, that's going to be 60 degrees or pi over 3. But the problem is, to get to the next solution, you realize that you have to rotate. So this right here is going to be, well, you could first say 360 degrees minus 150 degrees. That's 210 degrees. Then you need another 30 degrees. So it's 240 degrees or 4 pi over 3 in terms of radians. So really, there's not a consistent jump. So you can't really do anything there. Let me get rid of this. You have to just go back to the standard way when you think about the general solution. So I'm going to say the general solution here. I'm going to start with pi over 6. And of course, I can add 2 pi n, where n is any integer, then pi over 2, and then plus 2 pi n, where n is any integer, and then lastly, 5 pi over 6 plus 2, let me slide over a little bit so this fits, pi n, where n is going to be any integer. All right, let's take a look at problem 7. So here we have cotangent squared theta minus 3 cosecant theta plus 3 equals 0. Remember, you have this Pythagorean identity as well. So you have 1 plus cotangent squared x equals cosecant squared x. So I'm going to solve this for cotangent squared x. And let's just call it cotangent squared theta is equal to, I'm going to subtract 1 away from each side. So let's go cosecant squared theta minus 1. Let's grab this real quick. Come up here and paste this in. So this right here, again, is the same as this right here. So all I'm going to do is take this and to plug it in right there. That's all I'm doing. Let's come down here and let's say that we have cosecant squared theta minus 1. Again, this got plugged in right there. Then minus 3 times cosecant of theta, and then plus 3 is equal to 0. You have negative 1 plus 3, that's going to be 2. So let me erase this from here and just put this as a 2. Let's go ahead and set this up. This right here is a 1, right? So I can just say this is cosecant of theta, and then cosecant of theta. And then now I need two integers whose sum is negative 3 and whose product is positive 2. Well, you could do negative 2 and negative 1. So negative 2 and negative 1. So let's say cosecant of theta minus 2 is equal to 0, or cosecant of theta minus 1 is equal to 0. So just using the zero product property. On this one, I would add 2 to both sides of the equation. That cancels. You get cosecant of theta is equal to 2, and then I'll put or. Over here, let's add 1 to both sides of the equation. That cancels. You get cosecant of theta is equal to 1. Okay, I'm going to put this in terms of sine. Remember that sine of theta is equal to 1 over the cosecant of theta. So basically, I can say for this one that the sine of theta is equal to 1 over 2 or 1/2. And then I'll put or. Over here, the cosecant of theta equals 1. So that tells me the sine of theta would also be 1. So coming to the unit circle, we have sine of theta equals 1/2 or sine of theta equals 1. So the exact same setup from the last problem. So we're going to have the same solution. Basically, to go through this, again, if sine is positive, it's going to be in quadrants 1 or 2. So this is positive 1/2. So in quadrants 1 and 2, I'm looking for a y coordinate of 1/2. So that's going to be right here. And that's going to be at pi over 6, so that's in the first quadrant. And then going into the second quadrant, here's my 1/2 for the y coordinate, so that's going to be for 5 pi over 6. Okay, then sine of theta equals 1. You're just going to look for a y coordinate of 1, and that's going to occur right here at pi over 2. So if we're in that interval where theta is greater than or equal to 0 and less than 2 pi, I'm going to say that theta is equal to, let's start with pi over 6, and then we also have pi over 2, and then we're going to have 5 pi over 6. So this is in that interval. If you want the general solution, so the general solution, really this is quite long, and I talked about this in the last problem, so you can rewatch that if you want to see the reasoning. We really can't do any better than this long statement here. Let me slide over because this is pretty hard to fit. Let me come down a little bit. So I'm going to put some set braces here, and I'm just going to start with pi over 6, and I'm going to say plus 2 pi, which is the period for sine, times n, where n is any integer. Then I'm going to put a comma, and I'm going to go to this solution, so pi over 2, and just plus 2 pi n, again, where n is any integer, and then I'll put a comma. We're going to have 5 pi over 6. Let me slide down so this fits on the screen. And then plus, again, the 2 pi n, where n is any integer. And let me just close that down. All right, let's take a look at problem 8. So we have 3 sine squared theta plus 2 is equal to cosine squared theta minus 4 sine of theta. So once again, you have this cosine squared theta that you're going to make a replacement for. Let me come down here. So sine squared x plus cosine squared x equals 1. Again, you can say cosine squared theta is equal to 1 minus sine squared theta. This right here and this right here are the same. So I can take this and plug it in right there. So let's go ahead and say we have 3 sine squared theta plus 2 is equal to, again, for this, I'm plugging in this. So 1 minus sine squared theta, and then minus 4 sine of theta. Let me slide down a little bit here. What I want to do is add sine squared theta to both sides of the equation. So that's going to cancel. I'm going to subtract 1 away from each side of the equation. So that's going to cancel. Let me add 4 sine of theta to both sides of the equation. So that's going to cancel. So the right side is 0. Everything canceled away. So let me come down here a little bit. And it's a little bit tough to read this, but let's start with 3 sine squared theta plus sine squared theta. That would be 4 sine squared theta. And then we would go plus 4 sine of theta. And then 2 minus 1 is obviously 1, so plus 1. And of course, this is equal to 0. All right, so I'm going to factor the left side here. And so what I would do is set up some parentheses. And this is 4, so that's tricky because it could be 4 times 1 or it could be 2 times 2. But luckily, this last guy here is a 1, and all the signs are positive, so I know this is not going to be that hard to check. So really, all I would have to do is say this is 4 times sine of theta, and then sine of theta, and then plus 1 and plus 1, because again, this is plus 1 here, and this is a plus here, so I know this has to be a positive and a positive. So if you check this, this first guy would work, but if you look at this guy and this guy, it would not work. 4 sine of theta times 1 is 4 sine of theta. And then 1 times sine of theta is sine of theta. If you add those guys together, you're going to get 5 sine of theta, which is not correct. So this is wrong. So you'd have to switch it over and try the other one. So 2 sine of theta and then 2 sine of theta there, and this will work. Right? So if you look at the outer, this is 2 sine of theta. If you look at the inner, this is 2 sine of theta. And so 2 sine of theta plus 2 sine of theta would be 4 sine of theta. So this is what you want. So really, you could write this as this guy being squared and saying this equals 0. So you could say from the square root property that this would be 2 times sine of theta plus 1 is equal to, again, you go plus or minus the square root of 0, that's just 0. So you would just subtract 1 away from each side. This cancels, and you would have 2 sine of theta is equal to -1. Divide both sides of the equation by 2, and this would cancel, and we'll end up with sine of theta is equal to -1/2. So let me come down here and just write sine of theta equals -1/2. So sine is negative in quadrants 3 and 4. So in quadrant 3, I'm looking for -1/2 as the y-coordinate. So again, that's going to be right there, 7 pi over 6. And then I'm looking for -1/2 in quadrant 4 for the y-coordinates. So that's going to be right there. So this is 11 pi over 6. Again, if you don't have the unit circle handy, do the inverse sine with 1/2. That's going to give you pi over 6. And then you know that sine is negative in quadrants 3 and 4. So go ahead and go into quadrant 3 and 4 and say, what are the angles with a reference angle of pi over 6? And you're going to get 7 pi over 6 and 11 pi over 6. So let's say that for theta being greater than or equal to 0 and less than 2 pi, we'll say that theta is equal to 7 pi over 6 and then 11 pi over 6. And then for the general solution, so the general solution, let's go ahead and say that it's going to be 7 pi over 6 plus 2 pi n, where n is any integer. And then you'll have 11 pi over 6 plus 2 pi n, where n is any integer. All right, let's take a look at problem 9. So we have 1 plus secant of theta minus 2 tangent of theta equals negative tangent of theta. In the previous problems, we were able to look at a little identity and make a substitution. Here, you think about tangent squared x plus 1 equals secant squared x. That's a Pythagorean identity. But if you come back, so what you'd have to do is a little bit of cleanup and then some squaring in order to use that. So what I'm going to do is add 2 tangent of theta to both sides of the equation. So let's go ahead and do that. So this would cancel away. So now I have 1 plus secant of theta is equal to negative tangent of theta plus 2 cotangent of theta is going to be 1 times the tangent of theta, or just the tangent of theta. So the tangent of theta. Okay, so at this point, hopefully you can see if I squared both sides, I would have tangent squared theta on this side, and on this side I'd have something that I have to expand, but I could immediately replace this using my identity. So let's go ahead and square both sides. So we're going to square this side and square this side. Now remember, when you square both sides of an equation, you have to go back and check all your solutions in the original equation. So let's expand this. This would be 1 squared plus 2 times 1 times the secant of theta plus the secant of theta squared, so secant squared theta. And then this would be equal to tangent squared theta. Let me slide down here. So this right here, I'm just going to clean this up. So this would be secant squared theta. Maybe the E could be a little bit better there. And then let's go ahead and say plus 2 times 1 is 2. So 2 times the secant of theta. And then plus 1 squared is going to be 1. And this equals tangent squared theta. Again, for tangent squared theta, if we come back down, you could say tangent squared theta is equal to secant squared theta minus 1. So let me grab this real quick. Let me paste this in. And again, this is the same as this. So I'm allowed to take this right here and plug it in for this right here. So I'll say this is secant squared theta minus 1. I can subtract secant squared theta away from each side. So that's going to cancel away over here and cancel away over here. And so what I'm going to do is subtract 1 away from each side. So that's going to cancel away over here. So in this case, I have 2 secant of theta. And this equals, over here, -1 minus 1 would be -2. Let's divide both sides of the equation by 2. Cancel this away. We'll have the secant of theta is equal to -2 over 2 is -1. All right, so I'm going to put this in terms of cosine. Remember that cosine of theta is equal to 1 over the secant of theta. So here, the cosine of theta would be 1 over -1, which is -1. So I'll go ahead and just say that the cosine of theta is equal to -1. If we go to the unit circle, where's the x-coordinate -1? Well, it's going to be right here at pi. So before I write my solution, let me come back up here and let's check this. So basically, we said that theta is equal to pi. So I'm going to plug in a pi there, and also there. So remember that the secant of pi and also the cosine of pi is -1. So this is 1 plus -1, or you could say 1 minus 1, and then minus 2 times. When you think about the tangent of pi, if we come back to the unit circle, the tangent of pi is equal to your sine of pi over your cosine of pi. Well, the sine of pi is 0, and the cosine of pi is -1, so 0 over -1 is 0. So coming back, this would be minus 2 times the tangent of pi is 0, so times 0, and this equals the negative of the tangent of pi. Well, the tangent of pi is 0, so this is the negative of 0, which is 0. So this right here is going to work itself out because here -0 is just 0, and then this one, 2 times 0 is 0, so you're subtracting away 0, you can get rid of that, and 1 minus 1 is 0, so you get 0 equals 0, so this is a valid solution in terms of pi. For theta being greater than or equal to 0 and less than 2 pi, we'll say that theta is equal to pi. And then again, with the general solution, this one's really easy, we'll go ahead and say that it's just going to be pi plus 2 pi n. Let's take a look at problem 10. We have negative cosecant theta plus 1 equals cotangent theta plus 2. So you want to use this identity here. This is a Pythagorean identity, but you can't use it immediately. So what I would do is subtract 2 away from each side of the equation. Let's cancel that away. And let's say this is negative cosecant of theta. And then 1 minus 2 is going to be -1. And this equals cotangent of theta. Now, what I would do to make this a little bit easier, I would actually multiply everything by -1. So this would be positive, this would be positive, and this would be negative. And the reason I'm doing that is because I'm going to end up squaring both sides. And so the negative will go away here. It's just going to make it a little bit easier when I use my formula. All right, let me come down here and let's think about cotangent squared theta would be equal to cosecant squared theta and then -1. So let me grab this and let me paste this in here. So I'm just going to first square both sides like this. So this right here would be cosecant squared theta plus 2 times, so 2 times cosecant of theta times 1. So that's just 2 cosecant of theta, and then plus 1 squared, which is 1. And this equals, if I square this, the negative will go away. That's like -1 being squared, that's 1. And then cotangent of theta being squared is just cotangent squared theta. Now I'm going to make a replacement because, again, this right here matches this right here. So I'm going to take this and just plug it in right there. So let's say we have cosecant squared theta plus 2 cosecant of theta plus 1 is equal to, again, this is getting plugged in for this. So cosecant squared theta minus 1. Let me get rid of this. So I can subtract away cosecant squared theta from each side. This is going to cancel, and this is going to cancel. I can subtract 1 away from each side, so that's going to cancel. So you can have 2 cosecant of theta is equal to negative 1 minus 1 is negative 2. Let's divide both sides of the equation by 2. This cancels. You're going to have cosecant of theta is equal to negative 2 over 2 is negative 1. Now again, when you think about this, I would put this in terms of sine. So sine of theta is equal to 1 over the cosecant of theta. So basically 1 over negative 1 is negative 1. So I could say the sine of theta, so the sine of theta is equal to negative 1. And if we go to the unit circle, that's going to be right here. So the y-coordinate's negative 1. So that's at 3 pi over 2, or 270 degrees. Okay, when we square both sides of an equation, we have to check. You might get extraneous solutions. So let's go ahead and plug in 3 pi over 2. And let's plug in 3 pi over 2. And let's see what we get. So coming down here, you would have negative, let's just say negative 1 times, what is the cosecant of 3 pi over 2? Well, it's the same as the sine of 3 pi over 2, and we know that's negative 1. So this is negative 1 times negative 1, then plus 1, and this equals, what is the cotangent of 3 pi over 2? Let's go back to the unit circle. Remember, cotangent, so cotangent of 3 pi over 2 is equal to the cosine of 3 pi. Let me make that better. So 3 pi over 2 over the sine of 3 pi over 2. In other words, it's x over y. So it's going to be 0 over negative 1, which is going to be 0. So this right here would be 0 and then plus 2. So I think you can see this is going to work itself out. Negative 1 times negative 1 is 1, so you'd have 1 plus 1, which is 2, and this equals 0 plus 2 is 2. So this is a valid solution. So we'll say for theta is greater than or equal to 0 and less than 2 pi, that theta is going to be equal to 3 pi over 2. And then for the general solution, let's say it's 3 pi over 2 plus 2 pi n, where n is any integer. All right, let's take a look at the practice test. For the instructions, we're asked to solve each equation for theta is greater than or equal to 0 and less than 2 pi, and for all solutions. All right, for problem 1, we have the cosine of theta minus 1 is equal to the sine of theta over 2. All right, so I'm going to start this problem out in a different way. We're going to look at the solution graphically in terms of the general solution. And what that's going to do for us, it's going to allow us to think about how far out do I need to go to capture solutions, and then how often are those solutions going to repeat. So let's start off by graphing the left side of this. So you see you have the cosine of theta minus 1. So I'm going to graph that in blue here. That's y equals the cosine of x. You might need to wrap that depending on your graphing calculator, then minus 1. So this guy is the normal graph of y equals cosine of x, just shifted down by 1 unit. And you can see that the period is still going to be 2 pi. If you go over here and you start at 0 and you go to 2 pi, that's going to be 1 cycle. So this right here is 1 cycle for the cosine graph. And then let's say we start at 2 pi and we go to 4 pi. Well, that's another cycle for the cosine graph. And then obviously continuing this pattern, you could go from 4 pi to 6 pi, 6 pi to 8 pi, 8 pi to 10 pi, so on and so forth. So we can see the period is 2 pi. Now let me erase this and we'll think about the other side of that equation. So this is a little bit more complicated to think about. So here we have the sine of theta over 2. So I have graphed this in orange as y equals the sine of x over 2. So let's really think back to when we graphed these trigonometric functions for the first time. We said if we had something like y is equal to the sine of bx, what's going to happen is your period, so your period is going to be 2 pi over b. So here you could really write this as y is equal to the sine of, let's go 1/2, dividing by 2 is the same thing as multiplying by half, then times x like this. And so what's going to happen is your b is 1/2. So the period is 2 pi divided by 1/2, or 2 pi times the reciprocal of 1/2, which is 2. So 2 pi times 2 is 4 pi. So the period for this guy, let me just erase this. I'm just going to arrow to this and say that the period is going to be 4 pi. And we could label this one as well and just say that the period is just going to be the standard 2 pi. So we can see that clearly if we go to the graph here and I start at 0 and I go to 4 pi, that's now going to be one cycle for the sine graph. So it's been horizontally stretched by a factor of 2. So now we would go through one cycle from 0 to 4 pi. And of course, if we wanted to repeat that, you could go from 4 pi to 8 pi. So here's another cycle. So again, from 4 pi to 8 pi. And of course, from 8 pi to 12 pi, 12 pi to 16 pi, so on and so forth. Let's erase this. And now let's think about the solutions for the equation. When I solve my equation graphically, I'm looking for the points of intersection for this yellow graph and this blue graph. That's going to tell me the x values for which the y values or the function values are the same. So those would satisfy this equation. I know we're using theta here and x here, but it's basically the same thing. I'm just doing that for graphing purposes. Okay, so to think about, first off, how far out do we need to go to capture solutions? To answer that question, you're going to have to use the concept of the least common multiple that we learned a long time ago in pre-algebra. So let me write out that we want the LCM of these two periods. So you have a period of 2 pi and then a period of 4 pi. So let me put 2 pi here and then 4 pi here. And of course, this is going to be equal to 4 pi. So what is this telling me? Why did I say we need the LCM? Essentially, what you need is, let's say you start, to make this nice and simple, at 0. So at 0 for the x value. And basically, if you think about how far out do I need to go before these two guys are going to start again, so at the same time. In other words, they both start here. This cosine guy is going to have a period of 2 pi, so it's going to finish right here at 2 pi, and then it's done right here. But if you look at the sine graph, it's not done at that point, right? So right here, if you go to 2 pi, well, it's only halfway through. So how far out do I need to go to where they're both going to start again? Well, this guy needs to go all the way to 4 pi until it's going to start again. And then this guy right here needs to go through another cycle. So it needs to go to 4 pi before it's going to start again. So this is going to happen every 4 pi. And that's coming from the least common multiple of 2 pi and 4 pi. And so you can do this again if you wanted to trace it out. Let me use different colors. So let's say this is another cycle for this sine graph. So we're going to go from 4 pi to 8 pi. And then you can go through 2 other cycles for this cosine graph. So here's one right here. Again, when you finish this cycle, you're only halfway through on the sine graph cycle. And then you're going to do another cycle. And at that point right there, when you get to 8 pi, well, now they're both going to start again. So we're using that concept of the LCM to figure out, again, how far out do I need to go to capture solutions? And then once I've done that, how often are they going to repeat? Let me get rid of this. And I just want to note this in case you're a little bit lost about this. You can always list these if you want to find the LCM that way. So you can go 2 pi like this, and you can say, okay, well, this is 2 pi, and then 4 pi, and then 6 pi, and then 8 pi. And that lines up with where you're finishing these cycles for the cosine graph. 2 pi, 4 pi, 6 pi, 8 pi, so on and so forth. Then you can go out and put 4 pi, and you can say, okay, well, this is 4 pi, and then 8 pi, and then 12 pi, and then 16 pi, and so on and so forth. And again, that's where you're going to be finishing for this sine graph. So 4 pi, 8 pi, 12 pi, 16 pi. And again, if you look for the least common multiple there, where you're going to find that it's going to be 4 pi. Right? So you have 4 pi there and 4 pi there. Again, other common multiples, you'd have 8 pi and 8 pi, and then 12 pi and 12 pi. So it's every 4 pi, but you want the least common multiple here to make this work. All right, so that tells me that if I'm looking for solutions to capture them initially, I'm going to start here at 0, and I'm going to go to 4 pi. I'm actually going to end up excluding 4 pi, but let's just keep it in for right now. And I'm going to look for all these solutions in this first interval right here from 0 to 4 pi. So this is what I'm going to look for. So you're going to see that you have a solution here at 0, here at 2 pi, here at 7 pi over 3, and then here at 11 pi over 3. Now you have this solution at 4 pi, but basically what that's going to come from is me taking 0 and adding 4 pi to get to that. So that's how I'm going to list it. So let me go ahead and exclude that right now, and we'll put that back in a moment when we show the second cycle. So notice that if I go through this second cycle here, so now I'm going to include this 4 pi, and I'm going to actually exclude this 8 pi here. What you're going to have is this solution here is coming from this guy right here, plus 4 pi. So 0 plus 4 pi is 4 pi. Then this solution right here is coming from 2 pi plus 4 pi. So that gives me the 6 pi. Then this solution right here, this 7 pi over 3, if I add 4 pi to that, I'm going to get to 19 pi over 3. And I'm running out of room here, so I don't know where I'm going to write this. But if you did 7 pi over 3 plus, let's write 4 pi as 12 pi over 3. And of course, this would be, let me put this down here, 19 pi over 3. So you can see that, and I covered it up. So let me uncircle that real quick. This would be, let me undo that real quick, 19 pi over 3. So this is 7 pi over 3 plus 4 pi. And then this 11 pi over 3, just plus 4 pi to get to this guy right here, which is 23 pi over 3. So this would be 11 pi over 3 plus 12 pi over 3, which is going to give me this 23 pi over 3 that we see right there. And I know this is kind of covered up, so maybe you can't see it. So let me arrow to this again, and let me do that like that so that you can see everything. So what's going to happen is I'm going to capture these first solutions of 0, 2 pi, 7 pi over 3, and 11 pi over 3 just by working in the interval where theta is greater than or equal to 0 and less than 4 pi. And then all I have to do is take those solutions and add 4 pi n to that, where n is any integer, and then basically I would have my general solution. So let me erase all of this, and let me slide this over. So I'm just going to write here that I want my general solution. And you're going to see that you can condense two of the solutions into one, but I'll do that in a moment. So again, we start with this guy right here, which is 0, and then add 4 pi n. Again, this would turn into this solution here, which would turn into this solution here, so on and so forth. Then you have this other guy at 2 pi. So let's put 2 pi plus 4 pi n. So again, this would turn into this solution here, and so on and so forth. And then we would have these other ones, and this is not going to fit on the screen. So let me actually slide this over here, and this is just going to overlap. And then basically you have this solution here, which is 7 pi over 3. So 7 pi over 3 plus 4 pi n. So this guy, again, plus 4 pi would get me here. And then you add another 4 pi, you get to another solution, so on and so forth. Let me get rid of that one. And then lastly, you have this 11 pi. So 11 pi over 3, and then plus 4 pi n. So that's this one. Adding 4 pi would get me here. And then you keep adding 4 pi, you'll keep getting to additional solutions. So let me close this down. Now, you would notice that, well, first off, 0 plus 4 pi n, I could just write that as 4 pi n. But you would notice that this solution right here and this solution right here, well, you can really make that simpler. You can list it this way if you want. It's not wrong, but you can make that simpler because if you really look at it, we have this, and then this, and then this, and then the other one, when you look at that, you have this, and then this, and of course you would have 10 pi, but that's off the screen for right now because we don't have that on this graph. So what you would say is that, well, these solutions, if you put those together, they're just happening every 2 pi. So I could really say that's 2 pi n. So 2 pi n, and of course you could include 0 by just making n equal to 0. So let's just put 2 pi n, where n is any integer, so that would cover those two solutions. Let me move this down here. So this is my general solution here. So 2 pi n, where n is any integer, 7 pi over 3 plus 4 pi n, where n is any integer, and then 11 pi over 3 plus 4 pi n, where n is any integer. Because this is such a difficult concept to wrap your head around the first time you see it, I want to rearrange things and show you a different graph. So this is another way that you can obtain the solution graphically. So let's say we start again with the cosine of theta minus 1 is equal to the sine of theta over 2. Well, you could subtract cosine of theta away from each side, and you could add 1 to each side, and that would give you the sine of theta over 2, and then minus the cosine of theta, and then plus 1, and this would be equal to 0. So again, I just subtracted cosine of theta away from each side, and I added 1 to each side, so that gives me this equation here. Now, what I'll do to produce this graph is I'll say y equals the sine of x over 2 minus the cosine of x plus 1. Now, if this is equal to 0, you're basically just plugging in a 0 for y there, and you're saying, where are my x-intercepts, or where's the graph going to cross the x-axis where y is equal to 0? Those are going to be the solutions for the equation. So let's get rid of this. We know where this is coming from now. And you'll see that this is exactly matching our general solution. You have a solution here at 0. And again, if you add 4 pi to that, you see your solution at 4 pi. You have a solution at 2 pi, add 4 pi to that, you get a solution at 6 pi. You have your 7 pi over 3, add 4 pi to that. You have your solution at 19 pi over 3, and then you have 11 pi over 3, add 4 pi to that. You get your solution at 23 pi over 3. And of course, this 0, 2 pi, 4 pi, 6 pi, 8 pi that we've seen before, those can be condensed into this 2 pi n. So we know that at this point. But I want you to notice that on this graph, it is crystal clear that the period is going to be 4 pi. So you can see that visually pretty easily. So let's start at 0 and go to 4 pi. Let's just trace this out. So you have this big guy right here. So notice that that's from 0 to 2 pi. And then right now, from 2 pi to 4 pi, you see this right here. And this is exactly going to be matched if you go from 4 pi to 8 pi. So you have this from 4 pi to 6 pi, this big guy here, that is exactly matching what happened from 0 to 2 pi. And then when you go to the next part, from 6 pi to 8 pi, to finish things up, you're going to match what we did from 2 pi to 4 pi previously. So this is one cycle, and then this is one cycle. So we can see clearly the period is going to be 4 pi, and so that leads to this general solution. So if you're ever looking at something like this and you're trying to figure out, well, what's the period? Again, find the period of each guy individually. The period of this we know is 4 pi, and then the period for this we know is 2 pi, and then find the LCM, so what is the least common multiple of 2 pi and 4 pi, and the answer there is going to be 4 pi. And again, we showed that by listing it out. So we can see that's how we get our period of 4 pi, and so that's how we can get our general solution of 2 pi n, 7 pi over 3 plus 4 pi n, and then 11 pi over 3 plus 4 pi n, where n is any integer. All right, so let's come back to the starting point here. We know how to solve this graphically, but obviously we need to do this in a different way. So we need to do this algebraically. So if you're in this section of your book, you're probably going to use a half angle formula. So we'll do that for the first problem. For the next problem, I'll show you a substitution technique that's actually a little bit faster. So let me copy the problem. So we have the cosine of theta minus 1 is equal to the sine of theta over 2. So let me grab this real quick, and let me come down here and paste this in. So again, we're just going to use the half angle formula. So earlier in the course, we learned that the sine of theta over 2 is equal to plus or minus the square root of 1 minus the cosine of theta over 2. So because this is the sine of theta over 2, and this is the sine of theta over 2, I can just plug this in for this. And the reason we would want to do that is, right now we have cosine of theta and sine of theta over 2. When I plug this in, I'll have cosine of theta and then cosine of theta, so I'll be able to do some basic algebra and get cosine of theta equals some number. So let's slide down here a little bit, and I'll just put the cosine of theta minus 1 is equal to, again, this is being plugged in for this, so plus or minus the square root of 1 minus the cosine of theta over 2. Now, the first thing I notice here is I have this square root guy. If you want to get rid of that, you can square both sides of the equation. But remember, if you square both sides of an equation, you introduce the possibility of extraneous solutions. So one reason I don't like using this formula here is because now I have to go through and check my solutions. So you're going to see that that's kind of going to add a lot of time to this problem. In the next problem, I'll show you a way around that using a substitution technique. So on the left, if you square this, you have to expand it. So you're going to take the first guy and square it. So this is the cosine squared theta. And then minus, because this is a minus, you have 2 times cosine of theta times 1. So this is 2 cosine of theta. And then plus 1 being squared, which is 1. Let me slide this down so it all fits. This would be equal to, with this plus or minus, because it's being squared, you can just get rid of it. If you have a positive and you square it, it's going to stay a positive. If you square a negative, you get a positive. So just forget about the plus or minus. The square root is going to cancel with the exponent of 2, and you're left with the radicand. So we just have 1 minus the cosine of theta over 2. So at this point, again, I'm trying to get cosine of theta equal some number. I would clear this denominator. So let's multiply both sides of the equation by 2. So this needs to be distributed to each guy inside. And so 2 times cosine squared theta is 2 cosine squared theta. And then minus 2 times 2 is 4. And then you'll have cosine of theta. And then plus 2 times 1 is 2. Let me slide this over a little bit so this fits. This 2 we cancel with this 2. And you're just left with 1 minus the cosine of theta. So let's stop and think about what we have. Again, we're trying to get cosine of theta equals some number. What you would notice here is, again, you have this guy that's squared here. So when you see this in a trigonometry course, you should be thinking that, okay, this guy is quadratic in form, so I can either solve it using factoring, which is usually the case, or in a harder example, you'll have to use the quadratic formula. But either way, let's get everything to the left and make the right into 0 and see if we can factor. So I'm going to subtract 1 away from each side. This cancels and gives me a 0 there. Let me add cosine of theta to both sides. Let me write 1 cosine of theta. Just for clarity, that's going to cancel, and let's put a 0 over here on the right. So now what I would have is 2 cosine squared theta, negative 4 cosine of theta plus 1 cosine of theta is negative 3 cosine of theta. And then 2 minus 1 is going to be 1. So plus 1, and this equals 0. Okay, what I want to do now is try to factor the left. I'm just going to tell you in advance that you can factor this. And so this right here is a 2, so that's a prime number. So you can just say this is 2 cosine of theta, and this is cosine of theta. So 2 cosine of theta times cosine of theta is 2 cosine squared theta. So that's pretty easy. In this position, you think about this final guy here is a positive 1. So that can only come from 1 times 1 or negative 1 times negative 1. So we're going to put a negative 1 here and a negative 1 here because this middle guy here is negative. If you check this, your outer is going to be negative 2 cosine of theta. Your inner is going to be negative cosine of theta. So negative 2 cosine of theta minus cosine of theta is negative 3 cosine of theta. What you would do at this point is use the zero products property. Let me actually cut this away and just come to a fresh sheet so we have a lot of room. You're going to take each factor, set it equal to 0, and solve. So you're going to take 2 cosine of theta minus 1, set that equal to 0. Let's just solve that real quick. So add 1 to both sides. This cancels. And then let me actually just erase it and put this as a 1 over here. You have 2 that's multiplying the cosine of theta. So just divide both sides of the equation by 2. And so this is going to cancel. And you're going to get cosine of theta equals 1/2. So that is cosine of theta equals 1/2. Then I'm going to put or here. I'm going to have this cosine of theta minus 1 is equal to 0. We'll just add 1 to both sides. And we get cosine of theta is equal to 1. All right, let's come down here. This is the tricky part. So depending on the interval you're given, most teachers will just ask you to find theta being greater than or equal to 0 and less than 2 pi. But because we want to find the general solution, again, we know that we actually have to make this out to 4 pi. So what we're going to do here is we're going to look for everywhere that cosine of theta equals 1/2 or cosine of theta equals 1 in this interval. So first, let's go with the standard result from the unit circle. Cosine of theta equals 1/2. Well, we know we find an x-coordinate of 1/2 right there at pi over 3. And then also, it's going to be 1/2 right there at 5 pi over 3. But what you're going to have to do, since you're going out to 4 pi, and I know that's not included, but since you're going out there, you have to swing around by an additional 2 pi. So in other words, I'm right here, I've got to add another 2 pi. I'm right here, I've got to add another 2 pi. So you're going to go, okay, pi over 3 plus 2 pi, that's 6 pi over 3. That gives us that 7 pi over 3 that we saw earlier. If you did 5 pi over 3 plus 6 pi over 3, that's that 11 pi over 3 that we saw earlier. So let's go ahead and write those solutions out. I'm going to put theta is equal to, let's go pi over 3. Let's go 5 pi over 3. Let's go 7 pi over 3. And then 11 pi over 3. Now we saw the general solution from the graph, and you would note that we didn't see pi over 3 and we didn't see 5 pi over 3. Those are going to be extraneous solutions. Those happen because we squared both sides of the equation. I'll show you that we're going to check, and those are going to be rejected. Okay, so the other guy we have to look at this one. So where cosine of theta equals 1, so that's right there at 0. So you're going to put 0, and then again, to get in this interval here, you've got to add 2 pi, so 0 and then 2 pi as well. So let's put 0 and then 2 pi. Now here's the downside of this type of problem and solving it in this way. If you square both sides of the equation, you have to check your solutions. And so that's going to slow you down a lot because this is time consuming to go through and check things. So again, in the next problem, I'll show you a better way. Okay, let me come back up here and let me paste these, what I call proposed solutions in here. And so this is just from 0 to 4 pi, 0 included, 4 pi not being included. And we're just going to check some things. So let's go the cosine of, let me make that a little bit better. So the cosine of, let's start with 0 and 2 pi. Those are both going to work. So if I plugged in a 0 there, and then minus 1 equals the sine of, let's write this as 1/2 times, in this case, it would be 0. So we know that cosine of 0 is 1. So this would be 1 minus 1, which is 0. Over here, I know that 1/2 times 0 is 0. So this is the sine of 0, which is 0. So this right here is going to be a true statement. We already know that because we looked at the graph. So this is going to work. When you go to 2 pi, it works as well. So if I plugged in, let me get rid of this and this, 2 pi here, and then a 2 pi here, Well, this is exactly going to be the same thing. The only difference is over here, this would be the sine of pi, because 2 pi times a half is pi, and the sine of pi is also 0, and over here the cosine of 2 pi is also 1, so it's the exact same thing, so this works. Okay, let's get rid of this and get rid of this. Let me put my parentheses back in there. So now let's start with the ones that don't work. So you can work with pi over 3 or 5 pi over 3. It's going to be the exact same thing in terms of the math going down. So we know cosine of pi over 3 is a half. So you get 1/2 over here, minus 1, which is 2 over 2. So this is negative 1/2. The problem is the right is going to end up being positive 1/2. So you have sine of 1/2 times pi over 3. That becomes the sine of pi over 6. Now the sine of pi over 6 is 1/2, but positive 1/2, so this right here is false. This is a false statement. That means this solution here of pi over 3 is extraneous, and we didn't see it when we did this graphically, so we know it doesn't work. Now the other guy is going to be basically the same thing. If you put a 5 pi over 3, nothing's going to change here. If you put a 5 pi over 3 here, this would become 5 pi over 6, and the sine of 5 pi over 6, again, that's in quadrant 2 with a pi over 6 reference angle, it's still going to be positive 1/2, so this is still false. So that is going to get knocked out. Now when you change things up to 7 pi over 3, so if you put 7 pi over 3 here, or if you put 11 pi over 3 here, what's going to happen is, let me actually erase these, and let me put 7 pi over 3 here, and 7 pi over 6 here. This is going to end up working out. You're going to end up with negative 1/2 equals negative 1/2, and that's because the sine of 7 pi over 6, now you're going to be in quadrant 3, you have a pi over 6 reference angle, so it's still a half, but because you're in quadrant 3 and sine is negative, it's negative 1/2. This over here, 7 pi over 3 is coterminal with pi over 3, so we don't have to worry about this side, it's not going to change. So this is a true statement, so we're going to accept this solution, and we already saw that 7 pi over 3 was a solution. If you punched in 11 pi over 3 here, and then also here, this would become 11 pi over 6. So again, no change to this side. 11 pi over 3 is coterminal with 5 pi over 3, and so you don't have to worry about this side. On this side, again, it's the same thing. Now you're looking at the sine of 11 pi over 6 reference angle. You're in quadrant 4 where sine is negative, so you get negative 1/2. So this works as a solution. So that was a lot of work. Again, I'll show you how to do this in a more efficient way in the next problem. These problems, because you have to check them, whenever you use the half angle formula and you square both sides, it just turns into a lot of tedious work. So let me just take this information here and make a little solution. So first, let's go with theta being greater than or equal to 0 and less than 2 pi. So if you look at the solutions you have, again, this is rejected and this is rejected. This is going to be greater than 2 pi, this is greater than 2 pi, and this is 2 pi, and again, that's excluded here. So really, it's just going to be 0. So we're going to say that theta is equal to 0. Now, of course, if you want to write this one right here more cleanly, you could say theta is greater than or equal to 0 and less than 4 pi. We could say theta is equal to, again, this is excluded and this is excluded. Let's just put 0 and then 2 pi, and then we can go 7 pi over 3, and then 11 pi over 3. And then, of course, if you want the general solution, let me get rid of this. And you're basically just going to add 4 pi n to each guy. And we know that we can condense this one and this one when we do that. We'll see that in a moment. So let me write out the general solution. And let me set this up so you have 0 plus 4 pi n, which of course is just 4 pi n. So let me just write that like that now. And then we're going to have 2 pi plus 4 pi n. And then we're going to have 7 pi over 3 plus 4 pi n. This is not going to fit. Let me move this over here. And then we have 11 pi over 3 plus 4 pi n. Now again, we know from the graph that these two can be combined into one solution because it's going to happen every 2 pi. But if you didn't know that, if you didn't have a graph or you didn't feel like making one, you could just think about, can I combine these in such a way that I can make a single solution out of them? Yeah. If I started off with 4 pi n and I plugged in a 0 for n, well, that's just going to be 0. If I plugged in a 1, it would be 4 pi. So this would become 8 pi, and then 12 pi, and then 16 pi, and so on and so forth. So then for this one, let's say you plugged in a 0 for n, so you would start out with 2 pi, so you go to 6 pi, and then you go to 10 pi, and then you go to 14 pi, and you get the point. Well, let's just do one more. So you go out to 18 pi, and this would continue forever. So when we look at this, you see that solutions happen every 2 pi. So 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, so on and so forth. So you can combine those two and just really make it into one solution by saying that this is 2 pi n. So if you look at what we did here, we solved this in a different way than using the graphical approach, and we got the same answer, right? So all we really have to do is figure out, well, what is the period of this and what is the period of this? That gives me the two periods that I'm going to work with, and so I want the LCM of that. In this case, it was 4 pi. So you're going to find the solutions for your equation from theta being greater than or equal to 0 and less than 4 pi. So that gives you your initial run of solutions, and then you're going to find additional solutions by taking each solution and adding that 4 pi n, and then of course in some cases you can condense your solutions and come up with something that's a little bit simpler. So we get 2 pi n, we get 7 pi over 3 plus 4 pi n, and 11 pi over 3 plus 4 pi n, where n is any integer. All right, let's take a look at problem 2. So here we have the cosine of theta over 2, and then plus the sine of theta, and this equals 0. So what I'm going to do for this problem is use a little substitution technique. Now, generally speaking, in your textbook, they're going to use the half angle formula, but I find the substitution technique is a little bit faster. You may not like it, so you can use the half angle formula if you need to. So all I'm going to do here is I'm just going to let something like u be equal to this theta over 2. So theta over 2. So from this, I can then say that if I multiply both sides by 2, then 2u is equal to theta. So I established that u is equal to theta over 2, and then by multiplying both sides by 2, I will get that 2u is equal to theta. So I'm just going to use this to plug in, and I'll say that the cosine of, again, theta over 2 is equal to u. So cosine of u now, plus the sine of, we know that theta is 2u. So the sine of 2u, and this equals 0. So let me come down here and paste this in. And I'm going to make a little change to this formula here. I have my little double angle formula for sine. Let me write this as sine of 2u is equal to 2 times the sine of u, and then times your cosine of u. So all you're going to do, since you have the sine of 2u and the sine of 2u, you're just going to plug in this guy right here in for this guy right here. So that's all you're going to do. So let's say that we have the cosine of u, and then plus this guy right here. So 2 sine of u, and then cosine of u. And of course, this is equal to 0. All right, so now you're going to see that you can immediately just factor. Okay, so you have cosine of u and cosine of u. So we can pull that out in front of some parentheses. Of course, you could put times 1 here if you want to. So let's go ahead and say that this is going to be the cosine of u, and then times the quantity. Inside you'd have that 1, and then plus here you'd have the 2 times your sine of u. Close that down, and this equals 0. So at this point, we're already ready to use our zero product property. So let's go ahead and say that we have the cosine of u is equal to 0, and then or you have 1 plus 2 sine of u is equal to 0. Now for this one, let's subtract 1 away from each side. Let me just erase it from over here and write this as -1. Get rid of this plus sign here. 2 is multiplying the sine of u, so let's divide both sides of the equation by 2 so we can cancel this away. And so you get the sine of u equals -1/2. Maybe I could write that a little bit more cleanly. Okay, let me drag this over here, and let's go to the unit circle. All right, let's paste this in. I think probably you don't need a unit circle at this point, but let's just write it out. So all I'm going to do right now is work from 0 to 2 pi. So I'm just going to say we're in the interval where u is greater than or equal to 0 and less than 2 pi. And I'll show you where that's coming from in a moment. I'm going to go to a graph, and I'm going to explain that we're still going to use that same technique where we think about the LCM of the periods. But let's just get this in terms of the solutions first, and then I'll explain that. So if I want cosine of u being equal to 0, where is that going to happen? So that's going to happen here. You have an x-coordinate of 0, so pi over 2. And then here, you have an x-coordinate of 0, so 3 pi over 2. So let me list those solutions. So let's say u is equal to, we're going to have pi over 2, and then we're going to have 3 pi over 2. Now, we're going to see later on that this is basically happening every pi, so we'll be able to condense that, but for right now, let's just list it out. Then additionally, when we think about sine of u is equal to -1/2, so sine is negative in quadrants 3 and 4, so I'm looking for a y-coordinate of -1/2, so that's right there at 7 pi over 6, and then right here, at 11 pi over 6. So let's write those solutions in. So you have 7 pi over 6, and then you have 11 pi over 6. All right, so let's come to the graph and really think about this. I know these graphs take a long time to go through, but if you're struggling with where these solutions are coming from, and especially how to find the general solution, it's really good to spend some time with a few graphs, especially in your first few problems, so you can just develop the concept very deeply. And then as you move forward, you don't need a graph anymore. You'll understand what to do. So I have graphed y equals the cosine of x plus the sine of 2x. Where did that come from? Remember, after we made our substitution, we came up with the cosine of u plus the sine of 2u, and we said that was equal to 0. Well, I'm just using x in the place of u for the purposes of graphing this guy. And basically, if you plugged in a 0 for y, all you're doing is you're saying, well, what are my x-intercepts? So those x values are going to be the solutions for my equation. Let me get rid of this, and let's think about, first off, what is the period for this graph, and where does that come from? If you visually inspect this, you're going to be able to see that the period is going to be 2 pi. And the way you can look at this, let's say we start out right here with an x value of 0 and a y value of 1. If you go out to 2 pi, which is about 6.28, so let's say that's going to be about right there. So that point would be 2 pi, comma 1. So let me trace out this cycle here, and then I'm going to show you another cycle. And you're going to see it's exactly the same thing. So this right here is a cycle, and we're going from 0 to 2 pi. So we're going to go from 0 to 2 pi. We're just going to trace that out. And we're going to stop right there at 2 pi, comma 1. So that's going to be the end of that cycle. The next cycle can be found by just going from 2 pi to 4 pi. So 4 pi is about 12.57. So I'm going to the right of 12 here. So let me look about right here. So let's say this is 4 pi, comma 1. And again, all I have to do is trace this out, and this will become crystal clear for you. So let me trace this as best as I can. And you're going to see that this is another cycle for this graph right here. And let's finish that up. So things that happen in this cycle from 0 to 2 pi will happen in the next cycle from 2 pi to 4 pi, and then from 4 pi to 6 pi, 6 pi to 8 pi, so on and so forth. Now, again, you don't want to have to pull out a graph each time and say, well, what's the period, and go through all this stuff. So what you would want to do, again, is use the concept of the least common multiple. You just look at the period of each guy inside. So the period of the cosine of x, we know that that's 2 pi. What about the period of the sine of 2x? Again, when you think about something like y equals the sine of bx, well, the period is going to be what? It's 2 pi over b. Well, b here is 2, so 2 pi over 2 is going to just be pi. So now if I think about the least common multiple of pi and 2 pi, that's going to be 2 pi. So the LCM of pi and 2 pi is going to be 2 pi. And again, if this is confusing for you, just think about if I had the LCM of 1 and 2, that would be 2. Well, now I have the LCM of 1 pi and 2 pi, so it's just 2 pi. It's very easy when you relate it like that to just having plain integers. You could also list it out. You could just say, okay, well, pi is pi, and then 2 pi, and then 3 pi, and then 4 pi, and so on and so forth. And then for 2 pi, it's going to be 2 pi, and then 4 pi, and then 6 pi, and then 8 pi, again, so on and so forth. So the least common multiple is going to be 2 pi, right? So that's going to be one cycle for this graph here. So from 0 to 2 pi to 4 pi, 4 pi to 6 pi, again, so on and so forth. So let me get rid of this now that we understand that. So if we look in that interval from 0 to 2 pi, I'm going to include 0 and exclude 2 pi, you're going to see you have this solution right here, which is pi over 2. So that's your pi over 2 here. Now, the way these things are stacked up, it's really hard to read. But basically, this guy right here is going to be 7 pi over 6. So this guy right here. So this right here, let me actually arrow to that and say this is 7 pi over 6. So this is crystal clear. I'll arrow to this and say this is pi over 2. And then this guy right here is 3 pi over 2. Let me arrow to that. Or actually, let me do this one above like this. So this one is going to be 3 pi over 2. Extremely hard to read, I know. And then this right here, so this is your 11 pi over 6. So again, when I think about this happens in this cycle, when I get to the next cycle, well, those solutions are going to repeat. All I have to do is add 2 pi to get there. So pi over 2 plus 2 pi gets me to 5 pi over 2. Then 7 pi over 6 plus 2 pi gets me to 19 pi over 6. Then 3 pi over 2 plus 2 pi is going to get me to 7 pi over 2. And then 11 pi over 6 plus 2 pi is going to get me to 23 pi over 6. Okay, let me get rid of this. Now, we talked about this earlier, but this solution and this solution can be condensed into one single solution. If you notice that starting at this pi over 2, basically you can just add pi to get to additional solutions. So if I add pi, which is 2 pi over 2, I would get to 3 pi over 2, and then I would get to 5 pi over 2, and then 7 pi over 2, and then 9 pi over 2, and then 11 pi over 2. You could also subtract pi away. That would put you at this negative pi over 2, and then negative 3 pi over 2, and then negative 5 pi over 2. Again, so on and so forth. So when you write the solution out for this, you could put u is equal to, let's start with pi over 2, and then you can go plus pi n, where n is any integer. If this was 0, you'd just have your pi over 2. If it was negative 1, you'd have negative pi over 2. If it was positive 1, you'd have 3 pi over 2. And you could make it anything you want in terms of these solutions. Okay, let me put a comma here. And then I'm going to go to this 7 pi over 6. And then plus, this is going to repeat every 2 pi. So 2 pi n. Let me slide this down. And then we have our 11 pi over 6 plus 2 pi n. So this is repeating every 2 pi as well. So we're going to take this now and grab this. And I'm going to come to a fresh sheet. Now, remember that originally we said that u was equal to theta over 2. So all you really have to do is replace this u with theta over 2. So how do I get theta by itself? Let me make this 2 a little bit better. You just multiply everything by 2, right? So that would cancel the denominator here. And so everything on this side would have to be multiplied by 2. So you would say theta is equal to 2 times pi over 2 would be pi. So this would end up being pi. And then plus, you've got to multiply by this part 2. So you're going to say 2 pi n. And then you'd have 7 pi over 6 times 2. So this would cancel with this and give me a 3 down here. So this would be 7 pi over 3 plus 2 times 2 would be 4. So 4 pi n. And then here, 11 pi over 6 times 2. This would cancel with this and give me a 3 down here. So this is 11 pi over 3. And then plus 2 times 2 is 4. So 4 pi n. So again, I'm just multiplying everything by 2. So multiply this by 2, I get theta. Multiply this by 2, 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 and this by 2. So everything needs to be multiplied by 2 so I can have this in terms of theta. So this right here is actually the general solution. So let me actually erase this and put that this right here is the general solution. So the general solution. And you also might want theta being greater than or equal to 0 and less than 2 pi, like we talked about at the beginning. And this is really easy to get. You would just plug in a 0 here, and you would just have pi. So theta is equal to pi. And then this guy right here, if you plugged in a 0, and if you plugged in a 0, 7 pi over 3 and 11 pi over 3, those are greater than 2 pi, so those would not be in this interval. All right, before we move on, let me just verify this with you with a graph. So I just graphed y equals the cosine of x over 2 plus the sine of x. Again, the original problem was the cosine of theta over 2 plus the sine of theta equals 0. So again, I just put an x in the place of theta for graphing. And if you plugged in a 0 for y, again, you're just asking where are you crossing the x-axis or where are you having x-intercepts. Those x values are going to satisfy your equation. So let's go ahead and get rid of this. And basically, if you look at the general solution, you're going to see it matches up. If you start with this one, which is at pi, and you add 2 pi, you get to the next solution. So you get to 3 pi, and then you get to 5 pi, and then you get to 7 pi, and then you get to 9 pi. If you started at pi and you subtracted away 2 pi, you'd be at negative pi, and then negative 3 pi, and then negative 5 pi, so on and so forth. So you can see that works visually. Then you have your 7 pi over 3. So that's going to be this guy right here. And I know the way I've labeled things is a little bit tricky to read. Again, you can always go to Desmos and make your own graph if you're having trouble with this, but this is the 7 pi over 3. If you add 4 pi to that, you're adding 12 pi over 3, so that puts you right here at 19 pi over 3. And then let's say we go to the other one, 11 pi over 3, so that's going to be right here. So right here, if you added 4 pi or 12 pi over 3, that's going to put you right here at 23 pi over 3. So you can visually see that our general solution would work and how things are repeating. And again, if you're confused about the period for this graph, you can always go back to the LCM. Okay, so that's what I want to drill right now. This right here has a period of what? The period is, this is cosine of 1/2 times x. So the period is 4 pi. It's 2 pi divided by 1/2, or actually, let me write this more cleanly as 2 pi times 2 over 1. I'm just multiplying by the reciprocal. So this becomes 4 pi like this. And so that's your period. So this is 4 pi. And this has the regular period of 2 pi. So the least common multiple of 2 pi and 4 pi is 4 pi. So when you look at one cycle of this graph, again, starting here, you're going to need to go to 4 pi for that. So that's going to be, let's say, right there. So this is 0, 1. This is 4 pi, 1. So that's one cycle. One cycle. Let me show you this real quick. So this is crystal clear for you because you're going to need this as you move forward and you solve a lot more difficult problems. You need to understand how often these solutions are going to repeat. So that's one cycle from 0 to 4 pi. Now, if you go from 4 pi to 8 pi, and 4 pi, in case you're interested, is about 12.57. We talked about that earlier. 8 pi is about 25 point, let's say 13. So you'd be coming to, let's say, about right there. So that would be 8 pi, 1. So let me trace this out, and you'll see that this guy right here is your next cycle. So what happened in that other cycle is just going to repeat in this cycle right here. So again, that's how you figure this out. You always use the concept of the least common multiple. So your period for this guy is 4 pi. So that's one cycle, that's another cycle. And so this is going to continue forever and ever and ever. So this gives us our general solution of pi plus 2 pi n, 7 pi over 3 plus 4 pi n, and then 11 pi over 3 plus 4 pi n, where n is any integer. All right, let's take a look at problem 3. So here we have -1 plus sine of theta over 2 plus the cosine of theta, and this equals 0. So you could use a half angle formula here and plug in for the sine of theta over 2. Again, the downside to that is you're going to end up squaring both sides of your equation that you set up, and so you have to check for extraneous solutions. So that can be time consuming depending on your situation. So what I'm going to do is use an alternative approach. So I'm first going to let u be equal to this theta over 2. So theta over 2. And then what we can do is multiply both sides by 2. So we would say 2u is equal to theta. So I'm just going to use that to plug in for theta over 2 and theta. So we'll have -1 plus the sine of u, and that's theta over 2 there, so I'm just plugging in a u. And then plus, you're going to have the cosine of, for theta, I'm plugging in a 2u, and this equals 0. So right now, we're going to get a solution in terms of u. Now, when you think about this equation right here, again, in terms of u, you have a period for this guy right here of 2 pi. And then when you think about the period for this guy right here, it's pi. So if I think about how often solutions are going to repeat, it's going to be every 2 pi. Again, the LCM of 2 pi and pi is going to be 2 pi. So that's where that's coming from. So let's go ahead and grab this and come down here. So I'm going to write this in terms of u. So that'll make it a little bit more clear. So the cosine of 2u is equal to 1 minus 2 sine squared u. Now, hopefully you know this from your identities. This is one of your double angle identities for cosine. You have 3 ones that you can pick from. This is the one I'm going to choose for this particular problem. So you have cosine of 2u and cosine of 2u. So all I'm going to do is plug in this right here for this right here. So we're going to have -1 plus the sine of u plus this guy right here. So 1 minus 2 sine squared u. And of course, this equals 0. So let's go ahead now and solve this for the sine of u. Here you have -1 plus 1. So those are going to cancel. And you have the sine of u minus 2 sine squared u. And this equals 0. So what I can do is just pull out a sine of u. So I'm going to say this is the sine of u. And then inside the parentheses, you'd have a 1 and then minus. This would be 2 sine of u. And then this is equal to 0. Okay, so now I'm going to use my zero products property. I'm going to say that the sine of u is equal to 0, and then or 1 minus 2 sine of u is equal to 0. So this one is pretty straightforward. We'll go to the unit circle in a moment. For this one, let's go ahead and subtract 1 away from each side. Let me just erase this and write this as a -1. We'll divide both sides by -2 so that we can isolate the sine of u. So this is going to cancel with this. And you're going to have the sine of u is equal to, we know negative over negative is positive, so just positive 1/2. All right, so we're going to set up our solution for u right now. And what I'm going to do is write things in terms of the general solution. It's going to make it a little bit quicker. So first off, if I think about sine of u equals 0, let's go ahead and look for a y coordinate of 0. So that's going to be right here at 0, and then right here at pi. So I'm going to start by just saying that this is equal to, let me make this a little bit better here. 0 plus, again, for u, things repeat every 2 pi. So I'm going to put 2 pi n, and then I'm going to put pi plus 2 pi n. Now, we'll be able to combine those in a moment. For right now, let's just leave it. The next one is going to be sine of u equals 1/2. So we're looking for a y-coordinate of 1/2 in quadrants 1 or 2 where sine is positive. So that's right here at pi over 6, and then right here at 5 pi over 6. So let's go ahead and write that we have pi over 6 plus 2 pi n, and then we also have 5 pi over 6 plus 2 pi n. So this is just how I'm going to set up the general solution. Of course, 0 plus 2 pi n is just 2 pi n, so you can make that a little bit simpler. And let me just slide this down a little bit so it fits a little bit better. Now, when I think about this solution right here and this solution right here, those are going to happen every pi. So in other words, if I start here and I add pi, I get here, add pi, I get here, add pi, I get here. And so what you can do is actually take this and condense it into just pi n. So pi n. So in other words, if I plug in a 0, I get 0. If I plug in a 1, I get pi. If I plug in a 2, I get 2 pi, so I'm back here again. If I plug in a 3, I get 3 pi, so I'm back here again, so on and so forth. So let me go ahead and grab this real quick, and let's paste this in. I'm just going to drag this up here. Now here's where you have to substitute one more time. So remember that u is equal to theta over 2. So instead of this u, I can just plug in a theta over 2. And now I'm just going to multiply everything by 2, and I'll have my solution. That's it. So basically it's theta is equal to 2 pi n, and then it would be 2 times pi over 6. Let me show this. So 2 times pi over 6. The 2 cancels with the 6 and gives me a 3 down there. So this would be pi over 3. So pi over 3, and then plus 2 times 2 is 4, and then pi n. And then over here, if you have 5 pi over 6 times 2, so we have a common factor of 2 between 2 and 6. So let's cancel that away and put a 3 down here. So this is 5 pi over 3, and then plus 2 times 2 is 4. So this is 4 pi. Let me get rid of this border here, and then n. So this is going to be your general solution. You can write it like this if you want. Let me put some set braces in there. So this is the general solution. And if you want to solve for theta being greater than or equal to 0 and less than 2 pi, well, basically you would just plug in a 0 for n everywhere and see what you have. So if you plugged in a 0 here, you would basically have 0. So let's put theta is equal to 0. If you plugged in a 0 here, you'd have pi over 3. So pi over 3. And then if you plugged in a 0 here, you would have 5 pi over 3. So this is 5 pi over 3. So this is your general solution, 2 pi n. Pi over 3 plus 4 pi n, and then 5 pi over 3 plus 4 pi n, where n is any integer. And then if you want to go from theta being greater than or equal to 0 and less than 2 pi, it's going to be 0, pi over 3, and 5 pi over 3 only. All right, let's take a look at problem 4. So here we have sine of theta equals square root of 3 sine of theta over 2. So again, I'm just going to use my substitution technique. So we're just going to let u be equal to theta over 2. And then we know if we multiply both sides by 2, we get 2u is equal to theta. So right now, if I look at this guy, I know that solutions will repeat every 4 pi. If I look at the guy that I'm going to produce in a moment, which is in terms of u, solutions will repeat every 2 pi. Okay, so you have to keep that straight. So what I'm going to do is put that this is the sine of, again, theta is 2u. So 2u is equal to the square root of 3 times the sine of theta over 2. So theta over 2 is u. So the sine of u. And let's come down here. Now, when you look at the double angle formula for sine, there's only one of them that they give you. So basically, you're going to plug this in for this right here. But let me write this in terms of u so nobody's lost. You have the sine of 2u is equal to 2 sine of u, and then cosine of u. So I'm just replacing theta with u here. This, again, is the double angle identity that we talked about earlier. So here you have sine of 2u and sine of 2u. So I'm just going to take this right here and plug in for this right here. So this is 2 sine of u, and then cosine of u is equal to the square root of 3 and then sine of u. Now, what you want to do is subtract this away from each side of the equation. So actually, let me put minus the square root of 3 sine of u, and then minus the square root of 3 sine of u like that. Maybe that 3 could be a little bit better. So let's cancel that away from over here and put a 0. So we're going to have 2 sine of u, and then cosine of u and then minus the square root of 3 sine of u. So let's say that this is equal to 0 now, and basically you have sine of u and sine of u. So what are we going to do? We're going to factor that out. So we're going to factor that out. So we'll have the sine of u, and then inside the parentheses, you're going to have 2 cosine of u minus the square root of 3, and then this equals 0. All right, so using the zero products property, we're going to say we have the sine of u is equal to 0, and then or 2 cosine of u minus the square root of 3 is equal to 0. So let me clean this one up. I'm going to add the square root of 3 to each side of the equation. Let me just put this over here like this. So this would cancel away. I'm just going to erase it. And then we're going to divide both sides of the equation by 2. And so you're going to get cosine of u is equal to square root of 3 over 2. Okay, so let's come down here. Again, this is in terms of u right now. And solutions are going to repeat every 2 pi, again, in terms of u. If you're working with theta, solutions are going to repeat every 4 pi. So with u, we're going to come through and say sine of u equals 0. So again, that's going to happen here at 0 and then here at pi. And then for cosine of u being equal to square root of 3 over 2, again, cosine is positive in quadrants 1 and 4. Look for an x-coordinate of square root of 3 over 2. So that's right there at pi over 6. And then that's also going to be right here at 11 pi over 6. Again, you're in quadrant 4 with a pi over 6 reference angle. So let's go ahead and write this out. And again, I'm going to put this in terms of the general solution. So I'm going to put 0 plus 2 pi n. And then I'm going to put pi plus 2 pi n. And then I'm going to put pi over 6 plus 2 pi n. And then I'm going to put 11 pi over 6 plus 2 pi n. Now again, this one and this one, you can combine those if you want. You don't have to, but I think it's a little bit nicer to list it as 1 versus these 2 different guys. Of course, you can get rid of the 0 plus if you want. But basically, you would notice that, let's say I start right here. Every time I swing around by pi, I get to another solution. So here's a solution, there's a solution, there's a solution, so on and so forth. So I would combine these and just say that it's going to be pi n. So this right here is going to be pi n. Just like in the last problem, again, if I put in a 0 for n, you'd be right there. If I put in a 1, I'd be right there. If I put in a 2, then I'm at 2 pi. If I put in a 3, I'm at 3 pi. So it'd be right back there. So that's how you can make that a little bit more concise. And let me put a little border here. And I'm going to say that u is equal to theta over 2. So here's u, here's theta over 2. So I want this in terms of theta when I get my final solution. So let's put this as theta over 2. Again, to get theta, just multiply everything by 2. That's all you have to do. So this would be theta is equal to 2 pi n, so 2 pi n. And then you're going to have pi over 6 times 2. We know that we would basically get pi over 3. So pi over 3. And then plus 2 times 2 is 4, so 4 pi n. And then 11 pi over 6 times 2 is 11 pi over 3. And then plus 2 pi n times 2 is 4 pi n. So once again, this is the general solution. So let me put this as the general solution. And if you want the solution in that interval from theta being greater than or equal to 0 and less than 2 pi, I would plug in a 0 here, here, and here, and see what's in this interval. So if you plug in a 0 here, you're going to get 0. So let's say theta is equal to 0. And then if you plug in a 0 here, you're going to get pi over 3. So pi over 3. And then if you plug in a 0 here, you're going to get 11 pi over 3, which is not in this interval, right? So if you think about it as 2 pi being 6 pi over 3, well, 11 pi over 3, that's going to be greater than this. So you could say 6 pi over 3 is less than 11 pi over 3. So this guy right here will not be in this interval. So you're not going to put that in if you list your solution from 0 and 0 being included going out to 2 pi, where 2 pi is excluded. So in this interval, you're just going to have 0 and pi over 3. For the general solution, it's 2 pi n, pi over 3 plus 4 pi n, and 11 pi over 3 plus 4 pi n, where n is any integer. All right, let's take a look at problem 5. Here we have square root of 3 cosine of theta over 2 plus cosine of theta plus 1 equals 0. So again, I'm just going to use my substitution technique. Let's let u be equal to theta over 2, and then we will multiply both sides by 2 and say 2u is equal to theta. So we will have the square root of 3 and then times the cosine of, for theta over 2, we're plugging in a u, and then plus the cosine of, for theta, we're plugging in a 2u, and then plus 1, and this equals 0. So once again, in terms of this guy right here, we're working with u right now. The period for this, or how often the solutions are going to repeat, this one is 2 pi. This one originally with theta is 4 pi. So it's important to understand the difference between the two. So let me go ahead and grab this. And I'm going to come here to, again, a double angle identity for cosine. So I'm going to choose this one to plug in here for the cosine of 2u. So let me write this out again so nobody's lost. This can be the cosine of 2u is equal to 2 cosine squared u minus 1. So this matches this. So I'm just going to take this right here, and I'm going to plug that in right there. So let's go ahead and say we have the square root of 3, and then cosine of u, and then plus, instead of this, I'm going to use this. So 2 cosine squared u minus 1, and then you have this plus 1, and this equals 0. So this right here, minus 1 plus 1, you can get rid of that. That's going to cancel. So you just have square root of 3, and then cosine of u plus 2 cosine squared u is equal to 0. So let's pull out a cosine of u. And inside the parentheses, you'd have the square root of 3. And then plus, this would be 2 cosine of u. And this would be equal to 0. So now I can use my zero product property. We'd have the cosine of u equals 0. And then you could say or 2 cosine of u plus the square root of 3 equals 0. So I just rearranged this. I'm going to subtract the square root of 3 away from each side. Let me just erase it from over here and just write this as negative square root of 3. And then just divide both sides by 2. We'll get rid of that from over here. And if we think about u, again, solutions are going to repeat here every 2 pi. So where does the cosine of u equal 0? Well, that's going to be right here at pi over 2, and then right here at 3 pi over 2. Let me write this out. Of course, we can combine that into one solution, but let me start by saying that this is pi over 2 plus 2 pi n, and then you would have 3 pi over 2 plus 2 pi n. Now, how can we combine that? If I start at pi over 2 and I add pi, I'm to another solution. Add pi, I'm at another solution, so on and so forth. So I can just take pi over 2 and then plus pi n. Let me get rid of that to make this a little bit more concise. Again, if you want to list it the other way, it's not wrong. That's really up to you. And then the other guy that we're going to look at is cosine of u equals negative square root of 3 over 2. So I'm looking for negative square root of 3 over 2 for the x-coordinate. Cosine is negative in quadrants 2 and 3. So I'm looking for that right there. And that's going to be at 5 pi over 6. So pi over 6 reference angle in quadrant 2. And then pi over 6 reference angle in quadrant 3. That's 7 pi over 6. Or again, you could just look for the x-coordinate of negative square root of 3 over 2. So let's go ahead and write that we have 5 pi over 6 plus 2 pi n. And then 7 pi over 6 plus 2 pi n. Okay, let me just paste this in. I had to arrange this to where it would fit. So let's go ahead and say that u, again, is going to be theta over 2. And you can plug that in over here and say this is theta over 2. Multiply both sides by 2, and you're going to get theta is equal to, again, everything here needs to be multiplied by 2. So pi over 2 times 2 is just going to be pi. And then plus pi n times 2 is 2 pi n. 5 pi over 6 times 2 would be 5 pi over 3. And then plus 2 pi n times 2 would be 4 pi n. And then 7 pi over 6 times 2 would be 7 pi over 3. And then plus 2 pi n times 2 is 4 pi n. So this is your general solution here. So let me put this like this and just say this is the general solution. If you want theta to be greater than or equal to 0 and less than 2 pi, well, in this particular case, you could just plug in a 0 everywhere for n. So if you plug in a 0 here, this is going to go away. And so you could say theta is equal to pi. And then if you plugged in a 0 here, you'd have 5 pi over 3. So that would be okay. So 5 pi over 3. But then this one right here is not going to make it, right? If you plug in a 0 there, you'd have 7 pi over 3. And 7 pi over 3 is greater than 6 pi over 3. And 6 pi over 3 is 2 pi, just written with a common denominator. So that is not going to make it in the solution in this interval. So for theta being greater than or equal to 0 and less than 2 pi, you just get pi and 5 pi over 3. And then the general solution is pi plus 2 pi n, 5 pi over 3 plus 4 pi n, and then 7 pi over 3 plus 4 pi n, where n is any integer. All right, let's take a look at problem 6. Here we have cosine of theta plus 1 is equal to 2 cosine of theta over 2. So we're going to let u be equal to theta over 2. And then if we multiply both sides by 2, 2u is equal to theta. So we'll have the cosine of, instead of theta, I'm going to plug in a 2u, and then plus 1 is equal to 2 cosine of, instead of theta over 2, I'm going to plug in a u. So again, the solutions here in terms of u are going to repeat every 2 pi, whereas the solutions for theta would repeat every 4 pi. So again, I'm going to use this little double angle identity for cosine. Let me write this as cosine of 2u is equal to 2 cosine squared u minus 1. So looking at this guy right here and this guy right here, those are an exact match. So I'm going to take this right here and plug it in for this right here. So we're going to have 2 cosine squared u minus 1 and then plus 1 is equal to 2 cosine of u. So here, minus 1 plus 1, you can get rid of that. And you can subtract 2 cosine of u away from each side of the equation. So that cancels and you get 0. And now I'm going to say 2 cosine squared u minus 2 cosine of u is equal to 0. Let's go ahead and factor. I can pull out a 2 cosine of u. So if I pull that out, I have 2 cosine of u. And then inside the parentheses right here, you just have the cosine of u. And then minus, I'm going to pull this out. So I'm just going to have a 1. And so let's put this as equal to 0. So now what you're going to say is that 2 cosine of u is equal to 0, or cosine of u minus 1 equals 0. For this one, you could divide both sides by 2. So this 2 would go away from over here, and 0 divided by 2 is 0. So this is cosine of u equals 0. Then over here, if you add 1 to both sides, you would get cosine of u is equal to 1. So this is what we're looking for. So let's grab this. So let's put u is equal to cosine of u equals 0. So again, that's going to happen here at pi over 2, and then here at 3 pi over 2. We know we can combine those and just say that this is pi over 2 plus pi n. So in other words, here, plus pi gets me here, plus pi gets me here, plus pi gets me here, so on and so forth. So let's put pi over 2 plus pi n. Then the other guy is cosine of u is equal to 1. So when I'm thinking about an x-coordinate of 1, it's just going to be right here. And this solution is going to repeat every 2 pi. So let's go ahead and say that that's going to be 0 plus 2 pi n, which of course is just 2 pi n. And let me move this up here and put a little border here and say that u again is equal to theta over 2. And so let me replace this with a theta over 2. And so I can multiply everything by 2 and say that theta is equal to pi over 2 times 2 is just pi. So this is pi. And then plus pi n times 2 is 2 pi n. And then 2 pi n times 2 is 4 pi n. So if you want the general solution, that's going to be it. Let's go ahead and say that this is going to be the general solution. And then for theta being greater than or equal to 0 and less than 2 pi, we're going to say that theta is equal to, if I plug in a 0 here, I would just have pi. And then if I plug in a 0 here, I would have 0. Plugging in a 1 either here or here, you're going to be not in this interval. So your only solutions, and you could really write this as 0 and then pi like that if you wanted to, it's going to be 0 and pi for theta being greater than or equal to 0 and less than 2 pi. And then for the general solution, it's pi plus 2 pi n, and then 4 pi n, where n is any integer. All right, let's take a look at problem 7. So here we have the negative of cosine of theta plus square root of 3 sine of theta over 2 is equal to negative 1. So again, what I'm going to do is let u be equal to theta over 2. And then we'll say that 2u is equal to theta. Again, just multiplying both sides here by 2. So let's say we have negative cosine of, again, for theta, that's going to be 2u. So 2u, and then plus the square root of 3, and then times the sine of, for theta over 2, I'm plugging in a u, and then this equals negative 1. Again, solutions here in this first equation with theta, you're going to say that they repeat every 4 pi. And then when you come down here, in terms of u, these solutions are going to repeat every 2 pi. So let's go ahead and grab this. All right, so again, I have a little double angle formula. So we have the cosine of, let's just write 2u is equal to 1 minus 2 sine squared u. So this right here matches this right here. You have to be really, really careful because you have this negative right here. So you're going to plug this in for this right here, but the negative is out in front. So what you're going to have to do to not make sign mistakes, you're going to put negative, and then in parentheses, you're going to plug this in. So 1 minus 2 sine squared u, close that down, then plus the square root of 3, and then sine of u, and this equals negative 1. All right, this negative is going to be distributed to each guy inside. You can drop the parentheses if you want. So this would be negative 1, and this would be plus 2 sine squared u. So just make sure that gets distributed. So at this point, I'm going to notice that I have negative 1 here and negative 1 here. So again, you could just add 1 to both sides. That cancels, that cancels. Let's put a 0. So you're going to have 2 sine squared u plus the square root of 3 sine of u is equal to 0. So now I'm going to pull out a sine of u. So if I do that, I'll have the sine of u. And then inside the parentheses, you can have 2 sine of u plus you'll just have the square root of 3. And this equals 0. So using the zero product property, I'm going to say that the sine of u is equal to 0. Then or you're going to have 2 sine of u plus the square root of 3 is equal to 0. So this one, you don't have to mess with it. For this one, let's subtract the square root of 3 away from each side of the equation. So over here, this is going to cancel. Let me just actually rewrite this and say 2 sine of u is equal to the negative of the square root of 3. And then we'll divide both sides of the equation by 2. And so this would cancel. So you have sine of u equals negative square root of 3 over 2. Okay, so let's come down to our unit circle. So we have the sine of u is equal to 0. So again, that's going to happen here at 0 and then also here at pi. So let's write that we have u is equal to, you're going to have 0 plus 2 pi n. Remember, solutions repeat every 2 pi in terms of u. And then we're going to have this pi plus 2 pi n. Now, of course, you could just write this as 2 pi n. When you look at these two, again, you can combine them by just saying, okay, I could just do pi n. So in other words, I could just write this as pi n, because if I plug in a 0 for n, well, I'm just going to get 0, right? Pi times 0 is 0, so I'm at this solution right here. If I plug in a 1, I'm going to be at pi. If I plug in a 2, I'm going to be at 2 pi. If I plug in 3, I'm going to be at 3 pi. So on and so forth. You'll keep getting additional solutions. So let me go ahead and then go to the sine of u equals negative square root of 3 over 2. We know sine is negative in quadrants 3 and 4. And I'm looking for a y-coordinate of negative square root of 3 over 2. That's going to be right here at 5 pi over 3. And then also right here at 4 pi over 3. So a reference angle of pi over 3 in quadrants 3 and 4. Again, 4 pi over 3 and 5 pi over 3. That's what you're looking for. So let's put 4 pi over 3 plus 2 pi n. And then let's put 5 pi over 3 plus 2 pi n. And let's pull this up here. And let's go ahead and say that theta over 2 is equal to u. So this u here, I'm just going to plug in a theta over 2. And now to get theta, which is what we want, you just multiply everything by 2. So this would give me theta is equal to 2 pi n. And then 4 pi over 3 times 2 is 8 pi over 3. And then plus 2 pi n times 2 is 4 pi n. And then 5 pi over 3 times 2 is 10 pi over 3. Plus 2 pi n times 2 is 4. Let me get rid of this right here. So then pi n. So that's your general solution. Let me go ahead and put some set braces there and say this is the general solution. If you want where theta is greater than or equal to 0 and less than 2 pi, you could plug in a 0 for n everywhere. So this would give me 0. So let's say theta is equal to 0. And then if you plugged in a 0 there, you're going to get 8 pi over 3. So that's larger than 2 pi, because if you write 2 pi as 6 pi over 3, well, 8 pi over 3 is obviously greater than 6 pi over 3, so this would not be in this interval. And then 10 pi over 3, again, plugging in a 0 for n, that's not in the interval as well. So really your only solution here, if you're looking for theta being greater than or equal to 0 and less than 2 pi, is just going to be theta equals 0. But for the general solution, it's 2 pi n, 8 pi over 3 plus 4 pi n, and then 10 pi over 3 plus 4 pi n, where n is any integer. All right, for problem 8, we have cosine of theta plus cosine of theta over 2 is equal to 0. So let's go ahead and say that, again, we're going to let u be equal to theta over 2. And then we can say that 2u is equal to theta. Again, this just comes from me multiplying both sides over here by 2. So let's plug in cosine of theta. Again, theta is 2u. So I'm going to say this is the cosine of 2u. And then plus the cosine of For theta over 2, I'm going to plug in a u, and then this equals 0. So solutions here are going to repeat every 4 pi. Solutions here are going to repeat every 2 pi. So let's grab this. And again, we're just going to plug in. So let me write this as the cosine of 2u is equal to 2 cosine squared u minus 1. So this right here and this right here, those match. So I can take this right here and plug it in for this right here. So you're going to have 2 cosine squared u minus 1 plus cosine of u is equal to 0. So what I notice here is that I have something that is quadratic in form. So I'm going to try to factor it. Let's just rearrange this and say it's 2 cosine squared u, and then plus cosine of u, and then minus 1 equals 0. This is actually really easy to factor. So we're going to put 2 cosine of u, and then cosine of u, because 2 is a prime number. So 2 cosine of u times cosine of u is 2 cosine squared u. Then when we think about this negative 1, again, that's coming from this times this. So a negative 1 is only coming from a positive 1 times a negative 1. We just need to figure out the order. Now this guy right here is a positive, so it looks like what I want to do is have a plus 1 here and then a minus 1 here, so that the outer would be 2 cosine of u and the inner would be minus cosine of u. So 2 cosine of u minus cosine of u is cosine of u. So now what we can do is use the zero product property. So let me slide down here a little bit, and I'll say 2 cosine of u minus 1 is equal to 0, and then or the cosine of u plus 1 is equal to 0. So over here I'm going to add 1 to both sides of the equation. This cancels. You get 2 cosine of u is equal to 1. At this point I'm going to divide both sides of the equation by 2, and so this cancels, and you get cosine of u is equal to 1/2. Over here, just subtract 1 away from each side. So this cancels, and you're going to get, let's just write this here, or cosine of u is equal to, this would be negative 1. Okay, coming down here, if you want to see where the cosine of u is going to be 1/2, again, cosine is positive in quadrants 1 and 4, so I'm looking for an x-coordinate of 1/2, so that's going to be right here, and that's at pi over 3. And then also in quadrant 4, that's going to be right here at 5 pi over 3. And then for cosine of u being equal to negative 1, well, that's only going to happen right here at pi. So I want you to notice before we do anything that to get from this solution here to this solution here, it's going to be me adding another 2 pi over 3. If you want to think about this in degrees, if you're a little bit stuck with the fractions, you can just say, okay, I'm adding 120 degrees. So from 60 degrees, adding 120 degrees, I get to 180 degrees. If I add 120 degrees, I get to 300 degrees. And then if I add 120 degrees, I'm going to be at 420 degrees, which is coterminal with 60 degrees. So realize that the solutions repeat every 2 pi over 3. So all I'm going to do here is put u is equal to, I'm just going to start with pi over 3, and then I'm going to add 2 pi over 3 times n. Now, if you want to list all of these out, so if you want to go pi over 3 plus 2 pi n, and then pi plus 2 pi n, and then 5 pi over 3 plus 2 pi n, you can do it that way. It's not wrong. This is just going to make it a lot more concise. So let me go ahead and grab this, and let me paste this in here. So obviously, this is going to be really quick because u is equal to theta over 2. So let me replace this with my theta over 2, and then just multiply both sides by 2. You're going to get that theta is equal to pi over 3 times 2 is 2 pi over 3. And then plus 2 pi over 3 times 2 is 4 pi over 3. And then times n, where n is any integer. Of course, you could just write this like this and say that it's the general solution. So this is your general solution. And then if you want to go where theta is greater than or equal to 0 and less than 2 pi, plug in a 0 there, and you're going to see that theta is equal to 2 pi over 3. And really, there's nothing else you can do. If you plugged in a 1 there, you're going to get 2 pi over 3 plus 4 pi over 3, and that's going to be 2 pi, right? That would be 6 pi over 3, which is 2 pi, and that's not in this interval. So we'll just say that theta is equal to 2 pi over 3 for this interval where theta is greater than or equal to 0 and less than 2 pi. And then for the general solution, it's 2 pi over 3 plus 4 pi over 3 times n, where n is any integer. All right, for problem 9, we have cosine of theta equals cosine of theta over 2 minus 1. So again, I'm just going to stick with my substitution technique. So let u be equal to, we're going to go theta over 2. And then you can say that if I multiply both sides by 2, 2u is equal to theta. So this one right here, again, in terms of the original equation, the solutions repeat every 4 pi. In terms of this equation I'm going to set up here, it's going to be every 2 pi. So I'm going to go cosine of, for theta, I'm plugging in a 2u. And this equals, we have the cosine of, for theta over 2, I'm plugging in a u. Then we have minus 1. I have my little double angle identity set up. So you have the cosine of 2u is equal to 2 cosine squared u minus 1. So this guy right here matches this guy right here. So I'm just going to take this right here and plug it in for this right here. So we're going to have 2 cosine squared u, then minus 1 is equal to cosine of u minus 1. So I'm going to add 1 to both sides of the equation. So that's gone and that's gone. Let's subtract the cosine of u away from each side of the equation. That's gone. Let's put the right side as 0. So you have 2 cosine squared u minus cosine of u is equal to 0. On the left side, you have cosine of u that's common. So you have cosine of u, and then inside the parentheses, you're going to have 2 cosine of u, and then minus 1. Close that down, and this equals 0. All right, so we can use our zero product property and just say the cosine of u equals 0. And then or, you have 2 cosine of u minus 1 equals 0. So add 1 to each side, and you're going to get 2 cosine of u is equal to 1. Divide both sides by 2, and you're going to get cosine of u is equal to 1/2. All right, so cosine of u equals 0. So again, we know that's going to happen here at pi over 2, and then here at 3 pi over 2. So we've already seen that we can basically say that u is equal to pi over 2 plus pi n. Because you could start here and add pi, add pi, add pi, add pi, so on and so forth. And then for cosine of u equals 1/2, we should know already because we've done this multiple times. Here's 1/2 at pi over 3, and then here's 1/2 at 5 pi over 3. So let's go ahead and say that it's going to be pi over 3. Again, plus 2 pi n, and then 5 pi over 3 plus 2 pi n. All right, so coming back, once again, theta over 2 is equal to u. So I'm just going to erase this and put this as theta over 2. If I want theta, multiply both sides by 2. So you can have theta is equal to pi over 2 times 2 is pi, plus pi n times 2 is 2 pi n. And then you have pi over 3 times 2. So that's 2 pi over 3. And then plus 2 times 2 pi n would be 4 pi n. And then 5 pi over 3 times 2 is 10. Let me get rid of this. So 10 pi over 3. And then plus 2 pi n times 2 is 4 pi n. All right, so this is the general solution. So the general solution. And if you want, from theta is greater than or equal to 0 and less than 2 pi, again, you could just plug in a 0 for n. So that would give me pi. And then that would give me 2 pi over 3. So 2 pi over 3. And then over here, if you plugged in a 0, you'd have 10 pi over 3. So that's greater than 2 pi. Remember, 2 pi is 6 pi over 3. So 10 pi over 3 is greater. So it's not in this interval. So really, let me get rid of this comma here. I'm going to write this as theta being equal to 2 pi over 3 and then pi. So my solution here in this interval where theta is greater than or equal to 0 and less than 2 pi is going to be 2 pi over 3 and pi only. And then for the general solution, you have pi plus 2 pi n, 2 pi over 3 plus 4 pi n, 10 pi over 3 plus 4 pi n, where n is any integer. All right, let's take a look at problem 10. So here we have negative 2 minus cosine of theta plus 3 cosine of theta over 2 equals 0. All right, so let's let u be equal to theta over 2. And then we'll say that 2u, again, multiplying both sides by 2, would be equal to theta. So we'll say negative 2 minus cosine of, again, for theta, I'm plugging in a 2u, and then plus 3 cosine of, for theta over 2, I'm plugging in a u, and this equals 0. So once again, the period for this guy is going to be 4 pi, whereas the period for this guy, when I'm thinking about this in terms of u, it's going to be 2 pi. So let me go ahead and grab this, and let's paste this in here. And so let me rewrite this identity. I'm going to say this is the cosine of 2u is equal to 2 cosine squared u minus 1. So this right here matches this right here. But you have to be really careful because you have a negative sign there. That negative needs to multiply whatever this is. I'm going to plug this in right there. So make sure you use parentheses. So we're going to have negative 2 and then minus. I'm going to wrap this in parentheses. So 2 cosine squared u and then minus 1 and then plus 3 cosine of u, and this equals 0. All right, so this is going to get distributed to each guy. So basically you can erase this, and this would be a negative, and this would be a positive. So now what I'm looking at here, I have negative 2 plus 1, that's negative 1. So let's write this as negative 2 cosine squared u, and then plus 3 cosine of u, and then we're going to have minus 1, and this equals 0. Again, this minus 1 is coming from negative 2 plus 1. So I would multiply everything by negative 1 just to make it easier to factor. So that becomes positive, negative, positive, and no change to 0. So let's set up some parentheses here, and we're going to say this is 2 cosine of u, and then cosine of u. So 2 cosine of u times cosine of u, that's 2 cosine squared u. Then this right here is a positive 1 that comes from this times this. So it's either negative 1 times negative 1 or positive 1 times positive 1. And again, because this is a negative in the middle, I know this is negative 1 and negative 1. If you check, you get negative 2 cosine of u, and then you get negative cosine of u. And so if you add those together, negative 2 cosine of u plus negative cosine of u, you get negative 3 cosine of u. So this is what we're looking for. And let's go ahead and say we have 2 cosine of u minus 1 is equal to 0. Then or you have cosine of u minus 1 is equal to 0. So for this one right here, you would add 1 to each side. So let me erase that from here and put this as a 1 here, and then divide both sides by 2. So you're going to get cosine of u is equal to 1/2. So cosine of u is equal to 1/2. Here you would add 1 to both sides. So cosine of u would be equal to 1. So let's grab this and let's come down here and just paste this in. Let me go through and say the cosine of u equals 1/2. So again, we've seen that a lot. So this right here is going to be at pi over 3 in quadrant 1. And then in quadrant 4, where cosine is also positive, that's going to be right here at 5 pi over 3. And then for cosine of u equals 1, well, that's only going to happen right here at 0. Now again, when we think about solutions repeating in terms of u, it's going to be every 2 pi. So all I can do here is just say u is equal to 0 plus 2 pi n, which of course is just 2 pi n. So let me just write it that way. So 2 pi n, and then you're going to have pi over 3 plus 2 pi n, and then you're going to have 5 pi over 3 plus 2 pi n. Okay, so once again, when we think about theta over 2, this is equal to u. So I'm just going to replace this u here with theta over 2. And to get theta by itself, I'm just going to multiply both sides by 2. So theta is equal to, this would be 4 pi n. Again, 2 times 2 pi n is 4 pi n. And then here, 2 times pi over 3 is 2 pi over 3. And then plus 2 times 2 pi n is 4 pi n. And then 5 pi over 3 times 2 is 10 pi over 3. And then plus 2 pi n times 2 is 4 pi n. So this is your general solution. This right here is your general solution. And then if you want, let me make this a little bit cleaner here. If you want for theta being greater than or equal to 0 and less than 2 pi, again, just plug in a 0 for every n and see what you have. If I plug in a 0 here, I'd have 0. 4 pi times 0 is 0. Let's put theta is equal to 0. And then if I plug in a 0 here, I would have 2 pi over 3. So 2 pi over 3. And then if I plug in a 0 here, I'm going to have 10 pi over 3. And again, that's outside of this interval. So these are the only solutions for theta is greater than or equal to 0 and less than 2 pi. It's just 0 and 2 pi over 3. And then the general solution is 4 pi n, 2 pi over 3 plus 4 pi n, and then 10 pi over 3 plus 4 pi n, where n is any integer. All right, now let's look at some problems that involve tangent. So we have for problem 11, 2 times square root of 3, tangent of theta over 2, minus 4 is equal to the square root of 3, tangent of theta over 2, minus 5. Now, before I do anything here, I want you to remember that if you're graphing something like y is equal to the tangent of x, the standard period there is going to be pi. Remember, if you work with cosine or sine, the standard period is 2 pi, but with tangent, it's going to be pi. So if you see something like y is equal to the tangent of bx, something like this, well, now you take that standard period, which is pi, and you divide it by b. So if I had something like, let's say, the tangent of 1/2 times x, just representing this tangent of theta over 2, again, I'm just swapping out the theta with the x. Well, if I want the period for something like that, let's say that the period is going to be pi over b. Now, b is 1/2, so let's go pi over 1 times the reciprocal of 1/2, which is 2 over 1, so this is 2 pi. So before we start this problem, it's important to know that when we look at this, you see tangent of theta over 2, and you see tangent of theta over 2. So the period here is going to be 2 pi. In other words, your solutions are going to repeat every 2 pi. So that's really important if you're trying to find the general solution. Okay, let's get rid of this. And right now, I want to put this in terms of u. I'm just going to use my same substitution technique. Nothing's going to change for me there. So I'm just going to say we're going to let u be equal to this theta over 2. Now, you don't have an issue here where you have to go 2u equals theta. You just have theta over 2 and theta over 2. So we're just going to say this is 2 times square root of 3, and then tangent of u, and then minus 4 equals the square root of 3, and then tangent of u, and then minus 5. I'm going to get tangent of u equals some number. So to do that, I'm going to subtract the square root of 3, and then tangent of u away from each side of the equation. So this right here is going to cancel, and I'm going to add 4 to both sides of the equation. So this is going to cancel. 2 times square root of 3 tangent of u minus square root of 3 tangent of u would just be the square root of 3 tangent of u. And this equals, over here you have negative 5 plus 4. That's going to be negative 1. Okay, at this point, again, I want tangent of u by itself. So realize that the square root of 3 is multiplying the tangent of u. So I'm just going to divide both sides of the equation by the square root of 3. So this would cancel with this. And now you have the tangent of u is equal to negative 1 over the square root of 3. Of course, if you wanted to, you could write this as negative square root of 3 over 3. And that's just rationalizing the denominator if you want to. That's just multiplying the numerator and denominator by the square root of 3. Okay, let's grab this real quick. Okay, coming to the unit circle, again, you can't directly get the tangent values from the unit circle. Pretty much you need to know these or just use your inverse tangent function. If I look at something like the inverse tangent of, let's make this positive. So you can go 1 over square root of 3, or you could just go square root of 3 over 3. Let's type in square root of 3 over 3 like this. You're going to get pi over 6 or 30 degrees, depending on how your calculator's set, if you key that in. Now, another way you could have gotten this, again, you can't directly get it from the unit circle, but you can always say, okay, well, the tangent of pi over 6 is equal to the sine of pi over 6 divided by the cosine of pi over 6. So this would be 1/2, that's your sine value, times the reciprocal of your cosine value. So the cosine value is square root of 3 over 2, so you're going to do 2 over the square root of 3. Again, if you're dividing fractions, you multiply the first fraction by the reciprocal of the second. So this guy is going to cancel with this guy, and you get your 1 over the square root of 3, or you could say the square root of 3 over 3. So this would be my reference angle in any quadrant where tangent is negative, because again, this is negative here. So I want to go into quadrant 2 and then quadrant 4 and find an angle with a reference angle of pi over 6. Well, of course, you can just say, well, that's going to be 5 pi over 6. And then over here, it's going to be 11 pi over 6. But if you don't have the unit circle handy, you can always say, well, in quadrant 2, I could start with pi, and I'm going to write this as 6 pi over 6. So I have a common denominator, and I'm just going to subtract away that reference angle of pi over 6, and that's 5 pi over 6. If you're in quadrant 4, you can go 12 pi over 6, which is 2 pi, then minus pi over 6, that's going to be a reference angle, and that's 11 pi over 6. So lots of different ways to do this. These would be the two solutions if you're looking for u, and basically where u is greater than or equal to 0 and less than 2 pi. When we think about these solutions, they basically repeat every pi. So here and then here. So if I start here and I add pi, add pi, add pi, I keep getting to solutions. I'll say that u is equal to 5 pi over 6, and then plus, I want to go pi n. So that's my general solution for u. Now again, we want things in terms of theta. So if we think about theta, theta over 2 is equal to u. So all you have to do is plug in a theta over 2 here. And if you want theta, multiply both sides by 2. That's all you have to do. So we're going to say that theta is equal to, you would have 5 pi over 6 times 2. Of course, this 2 would cancel with the 6 and give me a 3 down here. And so this would become 5 pi over 3. And then don't forget to multiply this part here by 2. So this would be 2 pi n. So this is my solution in terms of theta. Remember, initially we said that because of that theta over 2, as the argument for those tangent functions involved, you would have a period of 2 pi, and so solutions would repeat every 2 pi. So that's what we get. This is the general solution here. So 5 pi over 3 plus 2 pi n. So this is the general solution. And then for theta being greater than or equal to 0 and less than 2 pi, well, basically you're only going to get that 5 pi over 3 solution. So that's all you're going to get in that interval. And so let's go ahead and say that theta would be equal to 5 pi over 3. Now, if you want to look at the graph, I went ahead and sketched that for you. So if you clean up that equation, you could set it to y equals square root of 3, tangent of x over 2 plus 1. Again, the period here, because of this x over 2, is going to be 2 pi. So you'll see that we have a solution right here, which is at 5 pi over 3. And then again, the solutions happen every 2 pi. So you could write 2 pi as 6 pi over 3. So 5 pi over 3 plus 6 pi over 3 is 11 pi over 3. Then plus 6 pi over 3 is 17 pi over 3, and so on and so forth. So if you want to graph this on Desmos and take a closer look, that's up to you. But clearly you can see that these solutions are going to happen every 2 pi. And that's coming from this x over 2. That's the argument for tangent. All right, let's take a look at problem 12 now. So here we have 2 tangent of theta over 4 plus the square root of 3 equals 2 times square root of 3 plus 3 tangent of theta over 4. Now you have theta over 4 here, and generally speaking, we've been working with theta over 2. So when you get something like theta over 4, now I want to think about the period. So y equals the tangent of something like, let's say, x over 4. Well, let me actually write this as 1/4 times x like that so it's more clear. Again, the standard period for something like y equals the tangent of x is just pi. So you would want to say here that the period is, again, pi divided by b, where 1/4 is your b. So it's going to be pi, let's say, over 1 times the reciprocal of 1/4, which is 4 over 1. So this is going to be 4 pi. So that's going to be your period here. And that's going to be how often these solutions repeat if you're thinking about the general solution. So every 4 pi. And again, for this problem, you can just use your substitution technique. You can just let something like u be equal to theta over 4. It's the same thing. You're just going to end up multiplying both sides by 4 in the end versus what we've been doing, which is multiplying both sides by 2. So here I'm going to say this is 2 tangent of u plus the square root of 3 is equal to 2 times square root of 3 plus 3 tangent of u. Okay, so the idea again is to get tangent of u equals some number. And let's go ahead and subtract 3 tangent of u away from each side of the equation. So this right here is going to cancel. And I'm going to subtract the square root of 3 away from each side of the equation. So let's say this is going to cancel. So 2 tangent of u minus 3 tangent of u is negative tangent of u. And this equals 2 times square root of 3 minus the square root of 3 is just going to be the square root of 3. And to get tangent of u by itself, you could just multiply both sides by -1, or you could divide both sides by -1. Let me actually show this so nobody's lost. Let me just divide both sides by -1. And this right here is going to cancel, and we'll have the tangent of u is equal to, this would be the negative of the square root of 3. And you can come to the unit circle if you want it as a little visual aid. For this one, I think a lot of you know, again, if you use your inverse tangent function, so the inverse tangent with, let's go positive square root of 3 as the argument, you're going to get pi over 3. Again, you could always say tangent of, let's go pi over 3. This is coming from the sine of pi over 3, which is square root of 3 over 2. So square root of 3 over 2 divided by the cosine of pi over 3, which is 1/2. Again, you're going to multiply by the reciprocal here. So that's going to be 2 over 1. The 2's cancel, and you just get the square root of 3. So pi over 3 would be your reference angle anywhere where tangent is going to be negative. So in quadrants 2 and 4. Again, you can look at the unit circle if you have it and say, okay, well, that's going to be 2 pi over 3 and then 5 pi over 3. And again, if you don't know that, you can just say, well, in quadrant 2, I can say I have 3 pi over 3, which is just pi, and then minus that reference angle of pi over 3. So that gives me my solution of 2 pi over 3. In quadrant 4, you can go 6 pi over 3, which is 2 pi, and then minus your reference angle of pi over 3, which gives me 5 pi over 3. So that's how you can find those solutions. Now, in terms of u, remember the tangent of something like u is just going to have a normal period of pi. So we see that this solution's here and here, so every pi. So for the general solution for u, you can say u is equal to 2 pi over 3 plus pi n. Now let me get rid of this, and let's put this in terms of theta now. So remember that u is equal to theta over 4. So let me replace u with theta over 4. So if you want theta, we're just going to multiply both sides by 4. And so that would give me theta is equal to 2 pi over 3 times 4 is 8 pi over 3. And then plus, you need to multiply this by 4, so 4 pi n. So this right here would be your general solution. So this is the general solution. But in the interval from theta being greater than or equal to 0 and less than 2 pi, you're not going to have a solution. If you plug in a 0 for n, you're going to get 8 pi over 3, which is greater than this 2 pi. So for this interval, you're going to say no solution. So that's just for this interval right here. This right here is the general solution. So you do have solutions, but just not in this interval. If you want to look at the graph, again, you can clean up that equation I gave you and say y equals the tangent of x over 4 plus the square root of 3. And you're just looking for, again, these x-intercepts. So you see you have one here at 8 pi over 3. And then these guys are going to occur every 4 pi. So the next one you see here is going to be at 20 pi over 3. So if you take 4 pi and you say it's 12 pi over 3, well, 8 pi over 3 plus 12 pi over 3, that's 20 pi over 3. Then 20 pi over 3 plus 12 pi over 3, that's going to be 32 pi over 3. So there's your other solution there. And of course, this continues in the same pattern forever. All right, let's take a look at problem 13. So we have 2 tangent of theta over 2 minus 5 sine of theta. This equals tangent of theta over 2 minus 4 sine of theta. So before we begin, I just want to tell you that depending on which strategy you use to solve this, you might end up with a little issue because of the domain of the particular identity that you're working with. So what I'm going to do is start off with my normal substitution technique, and then I'm going to show you if you end up using a half angle formula here, you might run into a little problem. So I'll show you how to fix that. Let's start off with what we normally do, and that's to use a substitution technique. Now, first off, I'm going to note that because you have tangent of theta over 2, again, the normal period for tangent is pi. But here you're going to have pi divided by that 1/2, which ends up being pi times 2, which is 2 pi. So the period there is 2 pi. And when you work with the sine of theta, the period is 2 pi. And then here, again, this is 2 pi. And then this is 2 pi. So for this original equation that we're working with, we expect these solutions to repeat every 2 pi. Now, of course, in this particular situation, you're going to be able to condense things, but when you get a solution, it will repeat every 2 pi. Now, let me get rid of this, and let me put up our little substitution. So let's say we're going to let u be equal to, let's go theta over 2, and then again, we can multiply both sides of this by 2, and we're going to get 2u is equal to theta. Okay, so we're just going to plug in. We have 2 tangent of, for theta over 2, we're going to plug in a u, and then minus 5 sine of, for theta, we're going to plug in a 2u, and then this equals the tangent of, again, this would just be u, and then minus 4 sine of 2u. Now, if we think about this equation right here, now you have tangent of u, and again, the period for that would just be pi, and you have sine of 2u, the period for that is going to be pi as well. And again, tangent of u and sine of 2u, it's the same. So if you wanted to arrow to this and say, okay, the period is pi, and then it's pi, and then it's pi, and then it's pi. So when you think about solutions in terms of u, they're going to repeat every pi. Okay, let's get rid of this. Now that we know that, and let's go through and solve this. So I'm going to subtract tangent of u away from each side of the equation. And so this right here is going to cancel away. And then I'm going to add 4 sine of 2u to both sides of the equation. And I'm going to use my double angle identity to plug in for sine of 2u in a moment. Let me get rid of this right here. So the right side is 0. So let's go ahead and say that 2 tangent of u minus tangent of u is just the tangent of u. And then negative 5 sine of 2u plus 4 sine of 2u, that's negative sine of 2u, and of course this equals 0. All right, at this point, again, I'm going to use my little identity. I think we know at this point that the sine of 2u is equal to 2 sine of u cosine of u. So again, this matches this, so I'm just going to plug this right here in for this right here. So that's what I'm going to do. So down here, I'm going to put the tangent of u, and then minus, I'm going to plug this in. So 2 sine of u cosine of u, and then this equals 0. All right, at this point, what I'm going to do is right tangent of u in terms of sine and cosine. So we know that this is the sine of u over the cosine of u, and then minus 2 sine of u cosine of u, and this equals 0. Now what I would do here is get a common denominator. So to do that, I would multiply the numerator and denominator here by the cosine of u. And so this is going to give me the sine of u, and then minus 2 sine of u, and then cosine of u times cosine of u would be cosine squared u. Let me put this over 1 so this is more clear. Down here, you would have cosine of u and cosine of u, so you'd have a common denominator of the cosine of u, and this equals 0. Let me put this on another page so we have a lot of room. Now we know if a fraction equals 0, then the numerator equals 0, and the denominator has to be non-zero, because you can't divide by 0. So I would first say that the domain is going to be the set of all u such that u is not equal to, well, what would I plug in for u there that would make the cosine of u 0? Well, think about pi over 2 or 3 pi over 2 or 5 pi over 2 or something like that. So basically, let's just put pi over 2 plus pi n, where n is any integer. So that's my domain. So what I'm going to do is set the numerator equal to 0. I'm going to solve that. If I get anything that violates the domain, I'll have to reject it. So what I'll do is I'll say that we have the sine of u minus 2 sine of u cosine squared u is equal to 0. And I have sine of u, and then I have sine of u. So we're going to pull that out in front of some parentheses. And so that's going to give me the sine of u, and then times the quantity. This would be 1 minus 2 cosine squared u. Close that down, and we'll say this equals 0. Okay, so using the zero product property, we're going to get that the sine of u is equal to 0. So that's pretty straightforward. Then over here, let's go ahead and say or. We have 1 minus 2 cosine squared u is equal to 0. Let's subtract 1 away from each side of the equation. Let me actually erase it from over there. I'll just clean it up as I go. Then we're going to divide both sides by negative 2. So this is going to cancel. So you get cosine squared u is equal to positive 1/2. How do we solve this? Basically, you would use your square root property and say that the cosine of u is equal to plus or minus the square root. So let me actually erase this. So the square root of 1/2, which of course is the square root of 1, which is 1, over the square root of 2. Now, if you rationalize the denominator there, this is the square root of 2. So the square root of 2 over 2. So you could really write this as the sine of u equals 0, or the cosine of u equals square root of 2 over 2. Then I'll put or. The cosine of u is equal to negative square root of 2 over 2. So where's the sine of u equal to 0? So we know that that's going to be right here at 0, and then also right here at pi. So what you could do is just say it's 0 plus pi n, which is just pi n. So let me put u is equal to just pi n. And then the next guy, let me actually erase these as I go. You're going to have cosine of u equals square root of 2 over 2. Okay, so that's going to be right here at pi over 4. Here's your square root of 2 over 2 for your x coordinate. Again, go into quadrant 4 where cosine is positive. Here's your square root of 2 over 2. That's at 7 pi over 4. And then for cosine of u equals negative square root of 2 over 2, well, that's going to be right here at 3 pi over 4. Again, negative square root of 2 over 2 for the x coordinate. And then also right here at 5 pi over 4. Again, negative square root of 2 over 2 for the x coordinate. You could do the pi over 4 plus pi n. In other words, from here to here, you're adding pi each time. And then the other one would be 3 pi over 4 plus pi n. So from here, go to here, you're adding pi each time. Now notice that what you could do here is just jump by pi over 2 each time. So from pi over 4, if I add pi over 2, I'm going to be at 3 pi over 4. And then at 3 pi over 4, if I add pi over 2, I'm going to be at 5 pi over 4. And then at 5 pi over 4, if I add pi over 2, I'm going to be at 7 pi over 4, and that would just continue forever and ever and ever. So you can make that a lot simpler by just saying that this is pi over 4, and then plus pi over 2 times n. Now notice that none of the solutions we listed here would violate that domain that we set up, so we're good to go in terms of this problem. So remember that we said that u is equal to theta over 2. So again, like we've been doing, just put in a theta over 2 here, and multiply both sides by 2, and you'll have your solution. So theta would be equal to 2 pi n, and then 2 times pi over 4 is pi over 2, so this is pi over 2, and then plus 2 times pi over 2 would be pi, so this is pi n. So this would be your general solution. So this right here is the general solution. And then if you want theta is greater than or equal to 0 and less than 2 pi, well, if you plugged in a 0 here, you would get 0. So let me put theta equals 0. If you plugged in a 1, then you get 2 pi, so that's not in this interval. Over here, if you plugged in a 0, you would get pi over 2. And then if you plugged in a 1, you would get pi over 2 plus pi. So let's say pi over 2 plus 2 pi over 2. That's going to give me 3 pi over 2. So these are your solutions in this interval where theta is greater than or equal to 0 and less than 2 pi. And then this is your general solution. All right, let's just come down here and verify this with the graph real quick. So we have y equals tangent of x over 2 minus the sine of x. So again, the period of this is 2 pi and the period of this is 2 pi. So solutions will repeat every 2 pi. With our general solution, we were able to combine things. So we found that we had 2 pi n, and then we had pi over 2 plus pi n. So if you look at the 2 pi n one, that's pretty easy. So something like 0, and then 2 pi, and then 4 pi, and then 6 pi. You could also go to the left of 0. So here's negative 2 pi. You'd have negative 4 pi, negative 6 pi, so on and so forth. The other guy is pi over 2 plus pi n. And of course, you could start at pi over 2, and then you could just keep adding pi to get to additional solutions. So if I added 2 pi over 2, which is just pi, I'd be at 3 pi over 2, then 5 pi over 2, then 7 pi over 2, then 9 pi over 2, then 11 pi over 2, then 13 pi over 2, so on and so forth. All right, for those of you that are interested, I'm going to go back through this problem, and I'm going to solve it using a half angle formula. And I'm actually going to do that twice so that you can see on the second time through, the formula that I'm going to choose is actually going to have a little bit of a problem. And this problem is going to involve division by 0. So something that doesn't work in the equation that we set up will actually solve this equation. So I'll talk about why that happens and basically what to do if it happens. So let's start off with the one that's going to work. So I have 2 tangent of theta over 2 minus 5 sine of theta equals tangent of theta over 2 minus 4 sine of theta. So if you wanted to solve this with a half angle identity, the first thing you would do if you're looking for the general solution is figure out, well, how often are the solutions going to repeat? Again, you think about tangent of theta over 2. The period there is 2 pi. So the normal pi that you get for tangent of theta, and then divide that by 1/2, so you get 2 pi. Then for sine of theta, that's 2 pi. It's just the standard period. Then tangent of theta over 2, so that's 2 pi. And then this sine of theta, that's 2 pi. So I know solutions would repeat every 2 pi. So I got that out of the way. Now, the next thing I would think about here is getting everything to the left and basically having the right being 0. So I'm just going to subtract the tangent of theta over 2 away from each side of the equation. And then I'm going to add 4 sine of theta to both sides of the equation. So the right side here is going to be 0. So this is canceled and this is canceled. So this is 0. On the left, you basically have 2 tangent of theta over 2 minus tangent of theta over 2. That is the tangent of theta over 2. And then negative 5 sine of theta plus 4 sine of theta. That's negative sine of theta. And this equals 0. So let me grab this real quick. And the idea is we're going to plug in for the tangent of theta over 2. Now you have 3 formulas that we talked about. So this is the first one you could use. So tangent of theta over 2 is equal to plus or minus the square root of 1 minus the cosine of theta over 1 plus the cosine of theta. I'm not going to mess with this one, although it works fine if you want to use it. I'm going to work with these two. So I'm going to start with this one right here. And then later on, I'll tell you about the problem that occurs if you use this one. This one is derived from this one. You might remember that from earlier in the course. Let me slide down here. We're just going to start with that one from the top. And to basically, you have this right here that matches this right here. So I'm just going to plug this right here in for this right here. So that would give me the sine of theta over 1 plus the cosine of theta. And then you have a minus. I'm just going to write the sine of theta over 1 for right now because we are going to get a common denominator. So this equals 0. Okay, so let's get our common denominator. Let me actually erase this and move it way down here. And I'm just going to multiply this by the quantity 1 plus the cosine of theta over the quantity 1 plus the cosine of theta. Let me make this a little bit better here. And so you would have the sine of theta and then minus, this would need to be distributed to each guy. So let me actually put some brackets here because we're subtracting away the whole thing. So sine of theta times 1 is the sine of theta. And then sine of theta times cosine of theta is just going to be plus sine of theta, cosine, let me make that a little bit better. So cosine of theta, close down these brackets. Now that negative needs to be distributed to each guy. So this would be a minus, and then this would be a minus. So let me erase that. Let me put this over your common denominator, which is 1 plus the cosine of theta. And of course, this equals 0. Now, if you look at this, you have sine of theta minus sine of theta. I'm just going to line that out. Those would cancel away. So basically, you have negative, let me write negative 1 times sine of theta times cosine of theta over 1 plus the cosine of theta, and this equals 0. The numerator needs to be 0, and the denominator needs to not be 0. So this is really important when you solve these types of problems to remember about the domain. So for the domain here, we would say it's the set of all theta such that theta, let me make that a little bit better there, is not going to be equal to what? Well, you would set 1 plus cosine of theta equal to 0. You would get cosine of theta is equal to negative 1. So here, theta would be equal to pi plus 2 pi n, where n is any integer. So at pi, 3 pi, 5 pi, 7 pi, so on and so forth, the cosine of that would be negative 1, and 1 plus negative 1 would be 0. So let's put in pi plus 2 pi n, and let me close that down. So if we were solving this equation on its own, so in other words, somebody just gave you this equation to solve, let's say you get something that violates the domain as the solution, you need to reject that and report your answer. But if you're solving something where you plugged in using an identity, well, then it's not so straightforward. What you actually need to do is check that in the original equation you were trying to solve, because it could be true that through the process of deriving the identity, we introduced a restriction that would actually work in the original equation. So if you get something that doesn't work because of this domain, just go ahead and check it. You'll see that sometimes it'll work. So what I'll do here is just set the numerator equal to 0. So I'm going to say we have basically, you could multiply both sides by negative 1, and you're going to have the sine of theta times the cosine of theta equals 0. So again, if you had negative 1 times this, you could multiply both sides by negative 1, and this would go away. So now what you're going to do is say, I'm going to use the zero product property and say the sine of theta equals 0, or the cosine of theta equals 0. So let me grab this real quick, come back to my unit circle. So where's the sine of theta equal to 0? Well, right here at 0, and then right here at pi. Well, we know that pi violates the domain, so we're going to restrict that for right now. And then for cosine of theta being equal to 0, again, that's going to be pi over 2, and then also 3 pi over 2. So let me actually put these solutions together. So this first one would be 2 pi n basically. We know that solutions are repeating every 2 pi. So let's put 2 pi n. And then you have pi over 2 plus 2 pi n, and then 3 pi over 2 plus 2 pi n. But again, we know we can combine those and say this is pi over 2 plus pi n. Now this solution right here, which is pi, you're going to reject that. But my suggestion, again, let me go ahead and grab this and let me paste this in here. I would actually check this. So if you said something like pi plus 2 pi n, well, it violates the domain of this guy right here. Again, if I plugged in a pi right there, 1 plus the cosine of pi is 1 plus negative 1, which is 0. So from this right here, it would need to be rejected because it would violate the domain. But I would go ahead and check it and see if it works. So something like the tangent of, again, you could just use pi, so pi over 2, and then you would say minus the sine of pi, is that equal to 0? Well, the tangent of pi over 2 is actually undefined because it's the sine of pi over 2, which is 1, over the cosine of pi over 2, which is 0. So this is undefined, so it does not work in this original equation. So it's rejected here, and it's going to be rejected here. So go ahead and get rid of this. It's not going to work when you consider this for your solution. So get rid of this and come down here. You could check the other ones. They obviously work. You can grab this, and again, come back to the graph. Let me paste this in here. And you could write this in solution set notation if you want. you have this 2 pi n, which again, we looked at this already, but we can do it again. Again, those are solutions like 0, and then 2 pi, and then 4 pi, and then 6 pi. And of course, you can go to the left of 0, you would have your negative 2 pi, negative 4 pi, so on and so forth. Now, the other solutions were combined together. So you see pi over 2 plus pi n, that's coming from the fact that you have a solution at pi over 2, and then if you add 2 pi to that, or 4 pi over 2, you're going to get to this 5 pi over 2. Then if you add 4 pi over 2, you'd be at 9 pi over 2. Then if you add 4 pi over 2, you'd be at 13 pi over 2. Now the other guy, we found 3 pi over 2. If you add 4 pi over 2, you'd be at 7 pi over 2. Then at 11 pi over 2. And we're just taking these solutions here and we're combining them and saying, well, hey, that's happening every pi. So pi over 2 plus pi is 3 pi over 2, then 5 pi over 2, then 7 pi over 2, then 9 pi over 2, then 11 pi over 2, then 13 pi over 2, so on and so forth. So we can see that that solution is going to be correct. It's 2 pi n and then pi over 2 plus pi n. All right, let's come back to this point right here. And I'm going to derive that other identity. I think a lot of you remember this from earlier in the course, but maybe you forgot. So I'm going to start with sine of theta over 1 plus cosine of theta. And I'm going to multiply by 1 minus the cosine of theta over 1 minus the cosine of theta. Now let me stop for a moment. We already know that for this one right here, we cannot have theta being equal to pi plus 2 pi n where n is any integer. But what did I introduce by multiplying by 1 minus the cosine of theta over 1 minus the cosine of theta? Well, here, 1 minus the cosine of theta can't be equal to 0. And so that becomes cosine of theta equals 1. So that's basically going to be at 0 plus 2 pi n or 2 pi n. Now we know that 2 pi n is a solution for the equation that we're going to work on, so that's going to create the issue. So if you try to solve it with this identity that I'm setting up, this is the problem that you're probably going to run up against. So for this one, let's write the sine of theta times the quantity 1 minus the cosine of theta. And then this would be over, this right here would be 1 squared minus cosine squared theta, which we would change into sine squared theta, and then you would cancel this with one of these. So this becomes 1 minus the cosine of theta over the sine of theta. So that's the other form of this guy. So let me go ahead and grab this, and let me just paste this in here. I just wrote tangent of theta over 2 is equal to 1 minus the cosine of theta over the sine of theta. So if we go back to that point where we had the tangent of theta over 2 minus the sine of theta equals 0. Well, again, this matches this. So you're just going to plug this right here in for this right here. So that gives me 1 minus the cosine of theta over the sine of theta. Then minus, let's go sine squared theta over the sine of theta. All I did was I multiplied the sine of theta by the sine of theta over the sine of theta so I could have a common denominator, and this equals 0. Now what you could do is write this sine squared theta as 1 minus cosine squared theta, and now I would have a common denominator, so I'd say 1 minus the cosine of theta. Be very careful because this minus here is going to apply to this whole thing. So basically I would wrap this in some parentheses, so 1 minus the cosine squared theta. And if you want to drop those, then change the sign of each sign inside. So this is a -1 and a positive cosine squared theta. And of course, before we do anything else, this 1 and this -1 would cancel away. Let me just rearrange this as cosine squared theta minus the cosine of theta. And we can just erase this. We know where it comes from. So let me move this up here. This is over the common denominator of this sine of theta, and this equals 0. So let's think about this. When we solve this equation, again, the numerator needs to be 0 and the denominator needs to be not 0. A lot of people just multiply both sides by the sine of theta and they get rid of this. But again, you're starting with this form right here. You can't just ignore the fact that the sine of theta can't be equal to 0. So I would think about the domain here. So the domain, and basically it would be the set of all theta such that theta is not equal to, let me slide this down a little bit. Well, where is the sine of theta equal to 0? Well, it's equal to 0 at 0 plus 2 pi n, which is 2 pi n. But also, you have that other guy, which is at pi, then plus 2 pi n. So let me put pi plus 2 pi n. So these two places, basically. Now let's go ahead and solve this guy right here. So we're going to go the cosine squared theta, and then minus the cosine of theta, and this equals 0. So I'm just going to say cosine of theta is outside of some parentheses. Inside you'd have the cosine of theta minus 1, and this equals 0. So the cosine of theta equals 0, or you'd have cosine of theta equals 1. So cosine of theta minus 1 equals 0. Add 1 to both sides, you get cosine of theta equals 1. So let me grab this. So let's come back, and let me make that a little bit cleaner there. You can have a better theta. So cosine of theta equals 0. So again, we know that that's at pi over 2, and that's at 3 pi over 2. Cosine of theta equals 1, well, that's going to be right here at 0. Now, again, we don't have to worry about this guy right here. Remember that that was restricted from the domain because you have a 0 there for the sine value of pi, but that doesn't come up in this set of solutions. What you get here is 0 plus 2 pi n, where n is any integer. So let's say theta is equal to 2 pi n. And then you also get the pi over 2 plus 2 pi n and the 3 pi over 2 plus 2 pi n, which of course we just say is pi over 2 plus pi n. So let me come down here and paste this in, and let me think about this with you. I can actually erase this right here. If you look at what we came up with, you see that this part right here is a violation of this domain. If you go back to this equation, if you plug in a 0 or 2 pi or 4 pi or something like that, well, sine of 0 or sine of 2 pi or 4 pi, that's 0. So this gives me division by 0, which is undefined. So if I was just solving this equation right here, I would need to reject this solution right here. But in this particular case, what I would do, again, because of how these identities are derived, I would just stop and say, okay, well, does it work in the original equation? So I just start with tangent of, again, theta over 2 minus the sine of theta. Is this equal to 0? Well, if I plugged in the tangent of, let's say, 0 over 2, or you could use 2 pi over 2, whatever you want to do. Well, the tangent of 0 over 2 would be the tangent of 0. So let's say the tangent of 0 minus the sine of, let me make this theta more legible. So let me make that into a clear theta. So the sine of 0, does that equal 0? Yeah, the tangent of 0 is the sine of 0, which is 0, over the cosine of 0, which is 1. So this is 0. And then minus the sine of 0 is 0. Does this equal 0? Yeah, 0 equals 0. So this actually does work as a solution in the original equation we were trying to solve. So if you're solving something with tangent involved, this could be an issue. You just need to be aware of it. So I would reject this from this equation. But again, I would always check in the original equation that you were trying to solve. So although it's rejected from this particular equation, it does work as a solution for the equation you're trying to solve. So I would just go back to solving this equation. Let's just say tangent of theta over 2 minus sine of theta equals 0. Well, this right here would be my general solution for that equation. 2 pi n, where n is any integer, and then pi over 2 plus pi n, where n is any integer. All right, now let's look at problem 14. So we have the square root of 2 tangent of theta over 2 minus the tangent of theta over 2 over the square root of 2. This equals the cosecant of theta over the square root of 2. So again, if you're trying to find the general solution, I would first think about how often are these solutions going to repeat. So I'm thinking about the tangent of theta over 2, and you have the tangent of theta over 2 again. In each case, again, the period for the tangent of theta over 2 is going to be 2 pi. So it's the standard period of pi, and then divided by 1/2, and so that gives you the 2 pi. Then the cosecant of theta, that's just the standard 2 pi. So if I look at 2 pi, 2 pi, and 2 pi, well, that tells me the solutions are going to repeat every 2 pi because the least common multiple of 2 pi, 2 pi, and 2 pi is just 2 pi. So let's get rid of this. And now let's think about how we can solve this guy. So I notice I have a denominator of square root of 2 and a denominator of square root of 2. So I'm just going to multiply both sides by the square root of 2. Let me slide down here a little bit and do that. So I'm going to put the square root of 2 outside of some parentheses. Or actually, let me just multiply everything by the square root of 2 individually. So square root of 2 times the square root of 2, and then tangent of theta over 2, and then minus, let's go square root of 2, times, you have your tangent of theta over 2, and then over the square root of 2, and this equals the cosecant of theta over the square root of 2, and then times the square root of 2. So we can see that square root of 2 times square root of 2 would be 2. So this is 2 tangent of theta over 2. And then minus square root of 2 over square root of 2 is 1, so that's going to cancel. And then you just have the tangent of theta over 2. And this equals, here square root of 2 and square root of 2 would cancel, so you get the cosecant of theta. Okay, let me come to a fresh page here so we have some room. So 2 tangent of theta over 2 minus the tangent of theta over 2, that is just going to give me the tangent of theta over 2. And then this is equal to the cosecant of theta. what I'm going to do is actually just subtract the cosecant of theta away from each side. So I'd have minus the cosecant of theta, and this would be equal to 0. Now, what I'm going to do is put this in terms of sine. So remember, the cosecant of theta is equal to 1 over the sine of theta. So let me actually just come down here and do that. I'll just say that the tangent of theta over 2 minus, again, the cosecant of theta is 1 over the sine of theta, and this equals 0. So what I'm going to do is use a little half angle identity to plug in for the tangent of theta over 2. And you have one where the denominator is sine of theta. We just talked about it in the last problem where we saw that it caused an issue for us. So let's come down here. I have the identity written up. I'm going to paste this in. The reason I'm choosing this identity is because if I plug this right here in for this right here, I'm already going to have a common denominator of sine of theta. So I think this is the best one to choose. So this guy right here matches this guy right here. And again, what I'm going to do is just plug this right here in for this right here. So you would have 1 minus the cosine of theta over the sine of theta. And let me slide down. This is going to go off the screen. So then minus, you have this 1 over the sine of theta, and this equals 0. So because of the identity I chose, I already have a common denominator, so it makes it a lot easier. And I'm just going to say that I have 1 minus the cosine of theta, then minus this 1 here, over the common denominator of the sine of theta, and this equals 0. Okay, so pretty straightforward at this point. 1 minus 1 would be 0, so let me actually just mark that out. And you'd have the negative of the cosine of theta over the sine of theta equals 0. You could really put this as negative 1 times this, and then you could multiply both sides by negative 1 and get rid of this, because the negative 1 would go away from there. Negative 1 times negative 1 is positive 1, and then over here, 0 times negative 1 is still 0. So you can write this as the cosine of theta over the sine of theta equals 0, which of course is the same thing as saying, where's the cotangent of theta being equal to 0? Because by definition, this is the cotangent of theta. So you need to make the numerator 0 and the denominator non-zero. So basically, you're going to say that you want cosine of theta to be equal to 0. So where does that happen? Again, you can come to the unit circle. I think we know this at this point, that this is going to happen at pi over 2 and then 3 pi over 2. Now, we said that the solutions would repeat every 2 pi, and of course they will. You could look at this pi over 2, and you could add 2 pi to that and get to 5 pi over 2, and then 9 pi over 2, so on and so forth. You could go to 3 pi over 2, and then add 2 pi to that, and that will put you at 7 pi over 2, and then 11 pi over 2, so on and so forth. But again, with these solutions, a lot of times you can just combine them, and I'll just say that theta is equal to, let's just go with pi over 2, plus, again, to go from here to here is pi, right? So plus pi, plus pi, plus pi. You'll keep hitting solutions. So I'm just going to put pi n, where n is any integer. So this would be your general solution. And notice that this would not violate the domain of the equation you were solving. You basically had the cosine of theta over the sine of theta, which remember is nothing more than just the cotangent of theta. This is equal to 0. So this, again, the sine of theta, if you look at the sine of pi over 2, that's 1, and the sine of 3 pi over 2, that's negative 1, so you won't have any issues here in terms of violating your domain of that equation you were working with. So this would be my general solution. So this is the general solution. And if you wanted the solution where theta is greater than or equal to 0 and less than 2 pi, well, you can just grab it from the unit circle, or you could plug in a 0 here and then a 1 here. If you plug in a 0 here, you just get pi over 2. So let me put theta is equal to pi over 2. And then if you plug in a 1 there, you'd have pi over 2 plus pi. So pi over 2 plus 2 pi over 2. And that's going to give me 3 pi over 2. And obviously you can see that from the unit circle, but maybe you don't have that handy, so it's not always available. Okay, so these are our solutions. We can go through and verify this with a graph if you want to. Again, you can type this into Desmos. So you can get this to y equals the tangent of x over 2 minus the cosecant of x. You could have also written this as y equals the tangent of x over 2 minus 1 over the sine of x. You're going to get the same graph. It's really up to you how you want to key it in. But again, we set our solution. Let me just write the general solution. So it was pi over 2 plus pi n. So this is the general solution. So here's your pi over 2. Let me use a different color. And then if you add pi, you get to 3 pi over 2. And then if you keep doing that, you get to 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2. But again, these solutions, if you think about it, it came from pi over 2 plus 2 pi n. So adding 2 pi gets me to this solution, and then this solution, and so on and so forth. Whereas the other solution that we found was 3 pi over 2, If you add 2 pi to that, you're getting to 7 pi over 2, then 11 pi over 2, so on and so forth. So when you think about those solutions together, you can combine it into this nice little statement and say that you have pi over 2 plus pi n. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So basically increasing by pi each time, or you could write that as 2 pi over 2 if you want to do this quickly in your head. All right, let's take a look at problem 15. So now we have the cosine of theta plus 4 times square root of 2 sine of theta over 2 equals 5 times square root of 2 sine of theta over 2 plus the sine of theta. So the idea here is that if we want to find the general solution, we're first going to think about how often the solutions are going to repeat. So I think about the period of something like cosine of theta. Well, that's the standard 2 pi. And then for the sine of theta, that's the standard 2 pi. But again, if you get to something like the sine of theta over 2, and you have sine of theta over 2 again, well, that now is going to be 4 pi. And where's that 4 pi coming from? Like we've talked about a lot, it becomes 2 pi, which is your standard period, divided by that 1/2. And so 2 pi divided by 1/2 is 2 pi times 2, which is 4 pi. So we know that at this point, and if we look at 2 pi, 4 pi, 4 pi, and 2 pi, well, the least common multiple there is going to be 4 pi. So that tells me if I'm trying to find the general solution, I'm going to see that my solutions are going to repeat every 4 pi. So in other words, I want to capture all the solutions from 0, and 0 being included, going up to and excluding 4 pi, and then any solutions in that interval are going to repeat every 4 pi. So that's the strategy here. Now we're going to end up using a half angle identity and squaring both sides. So this problem is extremely tedious if you're trying to get the general solution. If you're just going to use the standard from 0 to 2 pi where 0 is included and 2 pi is not, well then it's not that bad because you don't have that many solutions to check. So for this one, I'm going to start out by subtracting the sine of theta away from each side of the equation. And then I'm going to subtract 4 times square root of 2 and then sine of theta over 2 away from each side of the equation. And let's see where that puts us. This is going to cancel, and then this is going to cancel. So you would have the cosine of theta minus the sine of theta, and then this would be equal to 5 times square root of 2 sine of theta over 2 minus 4 times square root of 2 sine of theta over 2 is going to be just the square root of 2, and then sine of theta over 2. Now at this point, I'm actually going to square both sides of the equation. So let me slide down a little bit and do that. And I'm just going to make another line so nobody's lost. So cosine of theta minus the sine of theta. So this is going to be squared. And then we're going to square this side. So we have the square root of 2. And then times the sine of theta over 2. And this is going to be squared. Okay, on the left, we're going to use our little formula. So we're going to have cosine squared theta. And then minus 2 times this guy times this guy. So cosine of theta, sine of theta. And then plus this last guy squared, so that's sine squared theta. Let me actually slide this down so it fits. So this equals, remember this right here inside is multiplication. Square root of 2 times sine of theta over 2. So this exponent is going to be applied to each guy. So in other words, this is the square root of 2 being squared, and then times your sine of theta over 2 being squared. So over here, what I'm going to do is rearrange this. I think maybe it's not that obvious, but you have cosine squared theta plus sine squared theta, and by definition, that's 1. So I'm going to make this crystal clear. So this is cosine squared theta plus sine squared theta, and then minus 2 cosine of theta sine of theta, and this equals the square root of 2 squared is 2, and then times, normally we would write this as sine squared theta over 2, but I'm actually going to keep it like this because we're going to plug in, and I want it to be crystal clear what's going to happen. So I'm going to write this as sine of theta over 2, and I'm just going to wrap this and square this like this. Again, this will make more sense later on. So right now, I want you to notice that cosine squared theta plus sine squared theta is 1. So this, by definition, is 1. So you have 1 minus 2 cosine of theta sine of theta is equal to, again, I'm just going to write this as 2 times the sine of theta over 2, and I'm going to square this like this. So let me grab this, and let me come down here. So we have a little half angle identity that we talked about earlier on in the course, and we've seen this throughout the practice test. So sine of theta over 2 equals plus or minus the square root of 1 minus the cosine of theta over 2. So again, this matches this. So I'm going to plug this right here in for this right here. So I don't know if I can fit this all on the screen. I think parts of it are going to go off, but I'll do my best. So we have 1 minus 2 cosine of theta sine of theta equals 2 times. Again, I'm plugging this right here in for this right here. You have this guy wrapped and it's squared. So I'm going to keep that. So I'm just going to wrap this and square it. So you can have your plus or minus the square root of 1 minus the cosine of theta, and this is over 2. Okay, so on the left, you have 1 minus 2 cosine of theta sine of theta is equal to, you have your 2 times, again, if I square this guy right here, the plus or minus goes away, the square root guy goes away, and I'm just left with the radicand. So this is 1 minus the cosine of theta over 2. So 2 over 2 is 1. And so what I'm left with now is 1 minus 2 cosine of theta sine of theta is equal to 1 minus the cosine of theta. Now you have 1 over here and 1 over here. So I'm going to subtract 1 away from each side of the equation. And this is going to cancel, and this is going to cancel. So you have negative 2 cosine of theta sine of theta. And this equals the negative of cosine of theta. I'm going to add the cosine of theta to both sides of the equation. So let's go ahead and do that. So this would cancel. Over here on the right, you now have 0. So let me put plus the cosine of theta equals 0. Now, if you want to, you don't have to. You can multiply both sides by negative 1 and change this sign and this sign. And of course, there's no change to 0. You could leave it like it was. It's up to you. I like what I have out in front to be positive. It just makes it easier for me to factor when I'm thinking about it. So I'm going to pull out the cosine of theta now. You have that here and you have that here. So that's going to get pulled out in front of some parentheses. So you have the cosine of theta times the quantity. Inside here, you'd have 2 sine of theta. And then minus, if I pull this out, you would have a 1. Okay, close that down and let's say this equals 0. Okay, at this point, I'm going to use my zero product property and say that cosine of theta equals 0. And then or, you're going to have 2 sine of theta minus 1 equals 0. Add 1 to both sides. So this would be 2 sine of theta is equal to 1. Divide both sides by 2, and you're going to get sine of theta equals 1/2. So let me write this more cleanly. And let me grab this real quick. Okay, so coming down here, remember at the start of this problem, we said that solutions would repeat every 4 pi. So we will look at theta is greater than or equal to 0 and less than 4 pi. So using the unit circle, you're going to find values, and then you're going to add 2 pi to those to get everything in this interval. So let's start with cosine of theta equals 0. So again, we've done this a million times. So pi over 2 and then 3 pi over 2. But what I would do here is basically say that you have pi over 2, and then you have 3 pi over 2, and then you have pi over 2 plus 2 pi. So that's me adding 4 pi over 2, so that's going to be 5 pi over 2. And then you have 3 pi over 2 plus 2 pi, so adding 4 pi over 2, so that's going to be 7 pi over 2. Now at this point, you don't want to combine things like we've done in the past, because these are proposed solutions. We squared both sides of an equation, so we don't know what works yet. We need to capture things and then check. So I'm just going to say theta is equal to this, but again, a lot of these are actually going to be rejected, and I'll show you that in a moment. So then we want to look at the sine of theta equals 1/2. Let me actually get rid of this. So we know that it's going to be at pi over 6, and it's also going to be at 5 pi over 6. So let me write those in there. So you have pi over 6, and then you have 5 pi over 6. But then again, to capture all the solutions in this interval, you've got to add 2 pi to each one of those. So pi over 6 plus 2 pi, you're adding 12 pi over 6, so that's 13 pi over 6. And then 5 pi over 6 plus 12 pi over 6, which again is 2 pi, that's going to be 17 pi over 6. So you can see that if this was theta is greater than or equal to 0 and less than 2 pi, you would have pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. You would just check those to see which ones work, and then basically you'd have your solution. So it's not that bad if you're just doing the standard interval that's given in most textbooks. But if you want to find the general solution, you have to go through these and see which ones are going to work and which ones are not going to work. And then anything that works, you just add 4 pi n to that, where n is any integer. All right, so the most tedious part of this problem is actually just checking the solutions. So we squared both sides of our equation, and when that happens, you introduce the possibility of extraneous solutions or solutions that do not work in the original equation. So first off, let me write the original equation in this form here. So we're going to go cosine of theta minus the sine of theta, then minus the square root of 2, and then times the sine of, for theta over 2, I'm going to write 1/2 times theta, and this is equal to 0. So I'm just changing the original equation into something that's more easy to work with. I'm actually going to graph this in a little while and show you the solutions that way as well. So first off, you would need to plug in each solution here and see if it works. See if it gives you a true statement. So I would start with this pi over 2 solution, and basically you'd have cosine of pi over 2 minus sine of pi over 2 minus the square root of 2 times the sine of pi over 4. Does that equal 0? So the reason you're getting pi over 4 here is coming from 1/2 times that pi over 2, which is pi over 4. I'm just going to go through the first one with you. You see I already have the answer here. -2 is not equal to 0. So obviously this one is not going to work. But let me just go through it with you the first time. So the cosine of pi over 2 is 0. And then minus the sine of pi over 2, that's 1. And then minus the square root of 2 times the sine of pi over 4, that is the square root of 2 over 2. Does that equal 0? So square root of 2 times square root of 2 is going to be 2. And then 2 over 2 is 1. So basically you have 0 minus 1 minus 1. So this is just -1 minus 1, which is -2. So you get -2 is equal to 0. And of course, this is a false statement. -2 is not equal to 0. So that's why I have -2 is not equal to 0 here. So this solution is extraneous, and so we would reject it. Okay, for the rest of the guys in the top row, you're going to be able to get them from the unit circle. Remember that 5 pi over 2 is coterminal with pi over 2, and 7 pi over 2 is coterminal with 3 pi over 2. So you'll be able to get everything from the unit circle, so it's really not that bad. So for this one, if you plug in a 3 pi over 2 for theta, you're going to get 0 equals 0. So this is going to be a valid solution. So we're going to accept that. Okay, the next one is 5 pi over 2. If you plug that in, you're going to get 0 equals 0. So this is a valid solution. For the last one in the top row, 7 pi over 2, this is not going to work. So this solution is extraneous. You're going to get 2 on the left side. So the result of this is equal to 0 on the right. And of course, those are not equal. So you'd say 2 is not equal to 0. So this is an extraneous solution. It is rejected. Okay, now let's work on the proposed solutions on the bottom row here. These are going to take a lot longer to figure out if they work or not. So if you're self-studying, you might want to just use a computer and just check it that way. There's really no harm in that as long as you understand how you could go about doing it. I think it would be a time saver. Now, if you're on a timed exam, then you really can't do that. So what I would first start off with is the sine of pi over 12. Let me come down here and write the sine of pi over 12. Earlier in the course, we talked about how we could get the exact value for something like that. And basically, you would use identities. Now, there's different identities you could use. What I would use is the sum or difference identity for sine. I think that's the easiest way to do it. So I would just break this up. Remember, pi over 12 is just 15 degrees. So you could say that's 45 degrees minus 30 degrees. So I would break this up and say it's the sine of 45 degrees is pi over 4. And then minus 30 degrees, that's going to be pi over 6. Hopefully you remember this identity. It's going to be the sine of the first guy. So the sine of pi over 4. And I'm going to write these out as I go. So this is the square root of 2 over 2. And then times the cosine of the second guy. So the cosine of pi over 6. So this is the square root of 3 over 2. And let me just go ahead and say that that would be the square root of 2. So the square root of 2 times the square root of 3 over 2 times 2, which would be 4. And then you have minus. This sign right here and this sign right here are the same. So minus and minus. You have the cosine of the first guy. So that's pi over 4. So let me put minus. That's going to be the square root of 2 over 2. You're going to have times the sine of the last guy or the second guy. So we say pi over 6. So then this is going to be times the sine of pi over 6 is 1/2. So let me write this as square root of 2 over 4. Let me put equals and equals. So I'm going to go square root of 2 times square root of 3. I would not put that as the square root of 6 because you're going to see in a little while you're going to have to break it back up. So I'm just going to leave it like that. And then minus the square root of 2, and this is over 4. This is going to be obvious why I'm doing this in a moment. I'm going to factor out the square root of 2 now. So I'm going to put that out in front of some parentheses. So square root of 2 comes out. You would have the square root of 3 minus 1 inside the parentheses, and this is over 4. So let me grab this. Let me come back up here. I think I wrote that too big. So let me write the sine of pi over 12 is equal to the square root of 2, and then times the quantity, the square root of 3 minus 1, and this is over 4. Okay, so that's one way that you could get it. There's other ways and there's other forms of this. Again, it's just up to you. This is what works for me when I did it on my own. Okay, so let's start off with a cosine of pi over 6. We know that is, let me put a little border in here. We know that is the square root of 3 over 2. And then minus the sine of pi over 6, that is 1/2. So you could write this with a common denominator and say it's the square root of 3 minus 1 over the common denominator of 2. Then you have minus the square root of 2 times this sine of pi over 12, which we have right here. So we're going to have the square root of 2 times the square root of 3 minus 1. So this is inside of parentheses like that. And then this is over 4. So if you look at what I'm going to do here, square root of 2 times square root of 2 is going to be 2. So this right here would be 2. And then when you think about 2 and 4, we can cancel a common factor of 2. So this would go away, and this would be a 2. So now you can just drop these parentheses, and let me slide this over here. This should be equal to 0, and of course it is. You have square root of 3 minus 1 over 2 minus square root of 3 minus 1 over 2. Well, basically you're going to end up with 0 equals 0, so this is a valid solution. So come over here and check this one off. So this one is very tedious to check, and these guys right here are tedious as well. So let's go ahead and grab this real quick. Okay, let's come down here. So now we're going to work with 5 pi over 6. Again, when you think about the sine of 5 pi over 12, you can use identities to do that. You're going to end up with something like -1 minus the square root of 3 on the left, and then 0 on the right. So these are not equal. So this is an extraneous solution. Okay, now we're going to check 13 pi over 6. And remember, that's going to be coterminal with pi over 6. So you can get the cosine of 13 pi over 6 and the sine of 13 pi over 6. Those can come from the unit circle. But the sine of 13 pi over 12, you need an identity for that. Okay, so again, that's where it makes it a little bit more challenging. So if you go through and crank this out, you're going to get -1 plus square root of 3 on the left, and then 0 on the right. So those are not equal. So this is an extraneous solution. Okay, last one. So you have 17 pi over 6. Remember that is going to be coterminal with 5 pi over 6. So cosine of 17 pi over 6 and sine of 17 pi over 6, again, you can get those from the unit circle. But if you want sine of 17 pi over 12, you got to use identities for that. You're going to find that this is going to work. You're going to get 0 equals 0. So this is a valid solution. All right, now let's come up with a little solution here. So the first thing is you might want to just work in the interval where theta is greater than or equal to 0 and less than 2 pi. So most teachers will just give you this interval to work in. So in this case, you're only going to have pi over 6 and 3 pi over 2. That's it. 5 pi over 2 is greater than 2 pi, and 17 pi over 6 is greater than 2 pi. So that's not going to work. So we'll say that for this interval, theta is equal to, let's go pi over 6, and then let's also go, let me make that 6 a little bit better. You have 3 pi over 2. So those two solutions only. Then for the general solution, we're going to take each valid solution here. This is from the interval, theta is greater than or equal to 0 and less than 4 pi. So we're going to add 4 pi n to that, where n is any integer. So I'm going to start with pi over 6 and just add 4 pi n. And then I'm going to go to 3 pi over 2 and then plus 4 pi n. And then I'm going to go to 5 pi, so 5 pi over 2, and then plus 4 pi n. And then lastly, I'm going to put 17 pi over 6 plus 4 pi n. So let me close that down, and that's your general solution. So pi over 6 plus 4 pi n, 3 pi over 2 plus 4 pi n, 5 pi over 2 plus 4 pi n, and then 17 pi over 6 plus 4 pi n, where n is any integer. Okay, so let's come to the graph and just verify our solutions. You can follow along on Desmos and just do this on your own. So y equals the cosine of x minus the sine of x minus the square root of 2 times your sine of x over 2. Let me go ahead and paste in the general solution, and let's think about this for a moment. So first off, we said that the period for this guy is going to be 4 pi. So let's say we start right here. You would go out to 4 pi, which is about 12.57. Let's come here. So right there. So that would be your interval from 0 to 4 pi. Now again, you could trace along this if you want to really see how this pattern is going to repeat. So here's your pattern here. So that's your cycle right there. So then when you go from 4 pi to 8 pi, the same things are going to repeat. Okay, so let's go ahead and trace this out, and then I'll come back and label things and show you how this happens. So if you think about 8 pi, that's about 25.13. Let's come about right there. So that's about 8 pi. So let's just trace this out. So all the solutions that happened in that other cycle will repeat in this cycle right here. So let's trace this out, and then let's go through it one by one. So you have this solution of pi over 6, and then we have plus 4 pi n. So here's pi over 6. And then if you add 4 pi to that, you're going to get to that solution in this guy right here. And this is the solution of 25 pi over 6. So pi over 6 plus 24 pi over 6, which is 4 pi, written with a common denominator, is 25 pi over 6. So this plus 4 pi gets me here. If I added 4 pi, I'd go right there at 49 pi over 6. So 25 pi over 6 plus 24 pi over 6, that's 49 pi over 6. So that would jump right there. So this would be your next cycle. Now, let's erase this and go to the next one. So you have 3 pi over 2 plus 4 pi n. So here's 3 pi over 2. And again, if I add 4 pi to that, well, I'm adding 8 pi over 2. So that's going to be at 11 pi over 2. So that's this one right here. So this one right here plus 4 pi gets me there. If I add another 8 pi over 2, that's going to put me right there at 19 pi over 2. So notice it's the same thing repeating every 4 pi. Let's go to the next one. So we have 5 pi over 2. So that's going to be right here. And maybe this is covered up too much. So let me get rid of it temporarily. So that's 5 pi over 2. So you can see that. And I'll put it back in. And then that's going to repeat every 4 pi. So 5 pi over 2 plus 8 pi over 2. That's going to be this 13 pi over 2 right here, which is covered up. So let me erase that so you can see it's 13 pi over 2. And then I'll put it back in. So this is me adding 4 pi to get to that solution. And if I added another 8 pi over 2, I'd be right here at that 21 pi over 2. So every 4 pi, those solutions are going to repeat. Then we look at the last one here, which is 17 pi over 6. So that's right there. And again, if I add 4 pi to that, I'm going to be adding 24 pi over 6. So 17 pi over 6 plus 24 pi over 6 is going to give me this 41 pi over 6 here. So again, me adding 4 pi gets me there. If I add another 24 pi over 6, I'm going to go right there to that solution of 65 pi over 6. So you can see, based on our graph, that again, the solutions are going to repeat every 4 pi. And we obtain that by just looking at the equation and saying, well, all the periods, when I think about the least common multiple, it's 4 pi. So when I graph this guy, I can visually see that the solutions repeat every 4 pi. So our general solution here is pi over 6 plus 4 pi n, 3 pi over 2 plus 4 pi n, 5 pi over 2 plus 4 pi n, and then 17 pi over 6 plus 4 pi n, where n is any integer. All right, let's take a look at the practice test. For the instructions, we're asked to solve each for theta is greater than or equal to 0 and less than 2 pi, and for all solutions. All right, for the first problem, we have 2 cosine of theta is equal to sine of 2 theta. So you see this sine of 2 theta here. We're going to use a little double angle identity to make a little replacement here. Let me just copy this. So we have 2 cosine of theta is equal to the sine of 2 theta. And let me come down here. So I have my little identity here. So sine of 2 theta is equal to 2 sine of theta cosine of theta. So again, this right here matches this right here. So I'm just going to take this right here and I'm going to plug it in for this right here. So that's all I'm doing. So I'm going to say that I have 2 cosine of theta is equal to, again, this right here is getting plugged in here. So we're going to put 2 sine of theta and then cosine of theta. All right, so this is something I would solve using factoring. So what you could do is subtract 2 sine of theta, cosine of theta away from each side of the equation. So let me just show that. So minus 2 sine of theta, cosine of theta. And then over here, minus 2 sine of theta, cosine of theta. So on the right side now, this is canceled. I'm going to put 0. And let me rewrite this left side. You could put 2 cosine of theta and then minus 2 sine of theta, cosine of theta. And of course, this equals 0. So think about what's common here. You have a 2 and you have a 2. And then you have a cosine of theta and a cosine of theta. So 2 cosine of theta is going to be pulled out. So let's put 2 cosine of theta outside of some parentheses. So inside you would have a 1 and then minus. If the 2 and the cosine of theta are pulled out, you're just going to have the sine of theta left. So the sine of theta, close that down and set that equal to 0. All right, so now we're ready to use our zero product property. We're going to take 2 cosine of theta, so 2 cosine of theta, and set that equal to 0. And we're going to solve that. And basically, you would just divide both sides by 2. So divide both sides by 2. And you're going to get that the cosine of theta is equal to 0. So that's one of them. Then we're going to put or. You're going to have this factor here. 1 minus the sine of theta is equal to 0. We would subtract 1 away from each side. Let me just write this as negative 1 over here. I'm just going to erase it here. And then because this is a negative sine of theta, you can multiply both sides by negative 1 or divide both sides by negative 1. So we can do it like this just to show it. So this would cancel with this, and you're going to get sine of theta is equal to positive 1. Let me slide this over like this. Okay, let me paste this in here. And let's look at the first one. So we have the cosine of theta equals 0. So you're looking for an x-coordinate of 0. So that's going to happen right here at pi over 2. And then right here at 3 pi over 2. And then for sine of theta equals 1, well, that's going to be at pi over 2. When you think about the first part, you could put theta is equal to pi over 2, and then plus 2 pi n, where n is any integer. And then you would put 3 pi over 2, and then plus 2 pi n, where n is any integer. And then for the second guy here, again, it's just going to be pi over 2 plus 2 pi n. Now, of course, because you have a solution that happens here and then here, well, this is happening every pi. So in other words, if I add pi, I get here, add pi, I get here, so on and so forth. So really, you can make this a lot better and just say that it's pi over 2 plus pi n. So this right here would be the general solution. Let me slide this down a little bit. So this is the general solution if you're looking for that. And then if you want the solution where theta is greater than or equal to 0 and less than 2 pi, well, you're just going to list these two solutions here. So for that one, we'd say theta is equal to pi over 2 and then 3 pi over 2. All right, let's take a look at problem 2 now. So we have 2 cosine squared theta minus 2 is equal to negative cosine of 2 theta. All right, so once again, we have the cosine of 2 theta and the cosine of 2 theta. So all I'm going to do is use this little identity. So this right here is going to get plugged in for this right here. Now you have to be really, really careful because you have this minus sign that's right here. So what I'm going to do is write 2 cosine squared theta, and then minus 2 is equal to, let me put that minus sign, and then I'm going to wrap this inside of some parentheses so that minus gets distributed to each guy. So we're going to say this is 2 cosine squared theta, and then minus 1. What I would do is actually put this as a negative 1 here, so it's crystal clear that this needs to be distributed to each guy inside of the parentheses. So I'm going to have 2 cosine squared theta, then minus 2 is equal to, this would be negative 2 cosine squared theta, and then this would be plus 1. Okay, so looking at this, what I would do is solve this using the square root property. You could also solve this with factoring if you want to. It's basically up to you, but factoring is going to be a little bit more work. So I'm going to add 2 cosine squared theta to both sides of the equation. And then I'm going to add 2 to both sides of the equation. So this right here is going to cancel, and this is going to cancel. So on the left, you have 2 cosine squared theta plus 2 cosine squared theta. So that is 4 cosine squared theta. And this equals on the right, 1 plus 2 is going to be 3. So this would be 3 here. And so if I want cosine squared theta equals some number, so I can use my square root property, I'm going to divide both sides of the equation by 4. And now this would cancel. So you have cosine squared theta is equal to 3/4. So from the square root property, now you can just say that the cosine of theta is equal to plus or minus the square root of 3/4. Now you can break that up and say it's the plus or minus the square root of 3 over the square root of 4. And of course, the square root of 4 is 2. And so I have cosine of theta is equal to plus or minus the square root of 3 over 2. Okay, so coming to the unit circle, basically what this means is that I want the cosine of theta to be equal to the square root of 3 over 2. Then you could say, or the cosine of theta is equal to the negative of the square root of 3 over 2. Let me make that a little bit better there, and I'll fix this up also. Okay, so I'm going to get rid of this and maybe just slide this up a little bit. So first off, let's think about this one right here. So the cosine of theta equals square root of 3 over 2. So we know in quadrant 1, you're going to have an x-coordinate right there, square root of 3 over 2 at pi over 6. And then cosine is also positive in quadrant 4. So that's going to be right here at 11 pi over 6, again, pi over 6 reference angle. Then for this one, cosine of theta equals negative square root of 3 over 2. I'm looking in quadrants 2 and 3, where cosine is negative. So I want this negative square root of 3 over 2 for the x-coordinate. So that's going to be at 5 pi over 6. Again, notice it has a pi over 6 reference angle. Now you have this negative square root of 3 over 2 for the x-coordinate. Again, that's going to be at 7 pi over 6. That has a pi over 6 reference angle as well. So first off, let's write our solution where theta is greater than or equal to 0 and less than 2 pi. We would say for this, theta is equal to, let's go pi over 6, And then let's go 5 pi over 6. And then we're going to take 7 pi over 6. And then we're going to take 11 pi over 6. Now, in terms of the general solution, so for the general solution, what you can do is actually make this a little bit more concise than saying pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, 7 pi over 6 plus 2 pi n, and then 11 pi over 6 plus 2 pi n. What you can do is look at this solution and this solution, and that's happening every pi. So you could put it as pi over 6 plus pi n, where n is any integer. So you could do it that way. And then let me erase this and this. You could also look at this one, and it's basically the same thing. It's going to happen every pi. So you could say that it's 5 pi over 6, and then plus pi n, where n is any integer. All right, let's take a look at problem 3 now. So we have the cosine of 2 theta equals negative 2 cosine squared theta. So cosine of 2 theta is equal to negative 2 cosine squared theta. So I want you to notice again that you have the cosine of 2 theta, and here's the cosine of 2 theta. So we're going to use the same identity from the last problem. Again, when you look at the cosine of 2 theta, you have 3 identities you can choose from. So this is the one I'm going to use. So I'm going to take this right here, this 2 cosine squared theta minus 1, and I'm going to plug that in right there. So we're going to have 2 cosine squared theta minus 1 is equal to negative 2 cosine squared theta. All right, again, I see something where I think the square root property would be best. You can also solve this using factoring if you want. It's really personal preference. I'm just going to add 2 cosine squared theta to both sides of the equation. And then I'm going to add 1 to both sides of the equation. So this is going to cancel, and this is going to cancel. So I'm looking at 2 cosine squared theta plus 2 cosine squared theta, which is 4 cosine squared theta. Then this equals, over here I just have a 1. So I want to get cosine squared theta is equal to some number, so I can use my square root property. You could, again, solve this using factoring if you want, but I think that's more complicated. So I'm just going to divide both sides by 4, and this would cancel. So you get cosine squared theta is equal to 1/4. Okay, so now I can say, by the square root property, that cosine of theta is equal to plus or minus the square root of 1/4. Now, the square root of 1/4 is going to be 1/2, so let's write that in like that. Okay, so coming down here, again, what I would do is split this up and say this is the cosine of theta is equal to 1/2, then or the cosine of theta is equal to negative 1/2. So let's just go through and look for an x-coordinate of 1/2 or negative 1/2. In quadrant 1, you're going to see that's at pi over 3. If you go into quadrant 2, again, where cosine is negative, you're going to have this negative 1/2 here. That's at 2 pi over 3. And then in quadrant 3, where cosine is negative, you want this negative 1/2 here, which is at 4 pi over 3. And then in quadrant 4, where cosine is positive again, you want this positive 1/2. That's at 5 pi over 3. So you have your pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So let's write that out. So for theta is greater than or equal to 0 and less than 2 pi, let's say that theta is equal to pi over 3, and then you have 2 pi over 3, and then you have 4 pi over 3, and then lastly you have 5 pi over 3. Now, what about the general solution? So the general solution, it seems like you can make things a little bit simpler. Again, you could go through and say pi over 3 plus 2 pi n, 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 2 pi n, and then 5 pi over 3 plus 2 pi n, where n is an integer. But again, just like in the last problem, notice that you have a solution here and then a solution here, so that's every pi. So you could put pi over 3 and then plus pi n, where n is any integer. Let me make that 3 a little bit better. And then you could put this one and this one together, so every pi, right? So 2 pi over 3, 2 pi over 3. Let me get rid of this right here and right here so we can see that. And then plus, it's going to be pi n, where n is any integer. All right, let's take a look at problem 4. So here we have 2 sine of 2 theta is equal to negative square root of 3 sine of theta plus 3 sine of 2 theta. So what I want to do here is use a little identity for the sine of 2 theta. But before I do that, I want to clean this up a little bit. I'm going to subtract 2 sine of 2 theta away from each side of the equation. So over here, this is going to cancel and give me 0. And so let's write that 0 is equal to negative square root of 3, and then sine of theta, and then 3 sine of 2 theta minus 2 sine of 2 theta would be sine of 2 theta. So let's put plus the sine of 2 theta. Now I'm just going to rearrange this and put this as the sine of 2 theta, and then minus the square root of 3 sine of theta, and this equals 0. So let's come down here to our identity. So we have sine of 2 theta and sine of 2 theta. So again, I'm just going to plug this right here in for this right here. So I'm going to have 2 sine of theta cosine of theta minus the square root of 3 sine of theta is equal to 0. Let me make this a little bit better. So this is something we can solve using factoring. So you have the sine of theta and the sine of theta. So I'm just going to pull that out. And so if that comes out in front of some parentheses, you're going to have the sine of theta times the quantity 2 cosine of theta minus, you'd have just the square root of 3 here. And then this equals 0. Okay, so using the zero product property, we're first going to say that the sine of theta is equal to 0. Then we're going to have we're going to have this guy. So 2 cosine of theta minus the square root of 3 is equal to 0. So we would add square root of 3 to both sides of the equation here. So this would cancel away. I'm just going to erase it. And let me write this up here as just the square root of 3. And then to get cosine of theta by itself, let's divide both sides by 2. So this would cancel. Let me just erase it. So you get cosine of theta is equal to square root of 3 over 2. Okay, so sine of theta equals 0. So that's going to be right here. So you have a y-coordinate of 0, so that's at 0. And then right here, you have a y-coordinate of 0 again, so that's at pi. Then for cosine of theta equals square root of 3 over 2, that's going to be in quadrant 1 and 4 where cosine is positive. And you're looking at pi over 6. Here's your x-coordinate of square root of 3 over 2. And then you're looking at 11 pi over 6. Here's your x-coordinate of square root of 3 over 2. So let's write out for theta is greater than or equal to 0 and less than 2 pi. We're going to have that theta is equal to, you're going to have 0. You're going to have pi over 6. You're going to have pi, and then you're going to have 11 pi over 6. All right, for the general solution here, we're going to think about this solution here and this solution here and how we can combine them. So basically, if you think about this solution right here, it's the 0 plus 2 pi n. So in other words, it would be 0, then 2 pi, then 4 pi, then 6 pi, then 8 pi, so on and so forth. If you think about this one right here, it's pi plus 2 pi n. So you'd have pi, then 3 pi, then 5 pi, then 7 pi, so on and so forth. So solutions are happening every pi. So what you could do is just put pi n, where n is an integer. If I plugged in a 0 for n, I'd have 0. If I plugged in a 1, I'd have pi. If I plugged in a 2, I'd have 2 pi. If I plugged in a 3, I'd have 3 pi, so on and so forth. Then you have this pi over 6, and that's just going to repeat every 2 pi. So let's put plus 2 pi n, and then you have your 11 pi, so 11 pi over 6. Let me slide over so this fits, and then plus 2 pi n, where n is any integer. All right, let's take a look at problem 5. So we have 4 cosine squared theta minus sine squared 2 theta equals 0. Let me copy this real quick. So we have 4 cosine squared theta, and then minus for sine squared of this 2 theta here, I'm going to write this a little bit differently. Remember, this is a notation that really means that you have the sine of 2 theta being squared. So let's set this equal to 0. So I'm writing it in this manner so that it's completely obvious when we plug in. So you have your sine of 2 theta and your sine of 2 theta. And again, I'm just going to plug this right here in for this right here. So that's all I'm going to do. So we're going to have 4 cosine squared theta, and then minus, inside the parentheses, I'm going to plug this in. So you have 2 sine of theta, and then cosine of theta. And then this guy right here is going to be squared, and this equals 0. Okay, so now we have 4 cosine squared theta, and then basically minus, this guy right here is squared. Now this is multiplication, so it's 2 times the sine of theta times the cosine of theta. So basically each guy here is going to be raised to the second power or squared. So in other words, you'd have 2 squared, and then times your sine squared theta, and then times your cosine squared theta, and then this just equals 0. Now we know 2 squared is just going to be 4. And what I would actually do here is rearrange this. We're going to solve this by factoring. So to make it crystal clear, let me write 4 cosine squared theta, and then minus 4. I'm just going to write cosine squared theta, and then sine squared theta. So just changing the order here, that's completely legal. And we'll say this equals 0. So you can see that you have this 4 cosine squared theta and 4 cosine squared theta. So I'm just going to pull that out in front of some parentheses. So let's say that we would have 4 cosine squared theta. If I pull that out, I'd have a 1, and then minus, if I pull that out, I'd have sine squared theta, and then this equals 0. You can use your zero product property at this point. So you can say 4 cosine squared theta is equal to 0, and then or 1 minus sine squared theta is equal to 0. For this one, you could divide both sides by 4. So if you divide this side by 4, you get cosine squared theta. If you divide 0 by 4, you're just going to get 0. Then for this one, 1 minus sine squared theta equals 0. You could just change that into cosine squared theta equals 0, because 1 minus sine squared theta is by definition cosine squared theta. So you don't need this or here. You're just going to solve one of these. So just cosine squared theta is equal to 0. So come down here, we have cosine squared theta is equal to 0. And of course, that gives me that the cosine of theta is equal to 0. And let's think about where this happens. So you have a 0 here at pi over 2, and then a 0 here at 3 pi over 2. So for theta being greater than or equal to 0 and less than 2 pi, we're going to say that theta is equal to pi over 2, and then 3 pi over 2. And then for the general solution, we're going to say that you have pi over 2, so pi over 2. And again, you could go plus 2 pi n and then list 3 pi over 2 plus 2 pi n, but things are going to happen every pi. So in other words, if you start here and you add pi, you get here, then back to here, then back to here. So you can just put plus pi n where n is any integer. All right, let's take a look at problem 6 now. So let me just copy this again. So 2 cosine squared theta is equal to 1 minus cosine of 2 theta. So once again, you have cosine of 2 theta and cosine of 2 theta. So I'm just going to take this right here and plug in for this right here. So we're going to have 2 cosine squared theta is equal to 1, and then you got to be really careful about that minus there. So minus, I'm going to plug this in inside of some parentheses. So 2 cosine squared theta, and then minus 1. Now again, you've got to remember to distribute this minus to each guy. A lot of times I'll just put plus a negative 1 here and then distribute it like this so that it's not something you're going to forget. So let me go ahead and slide down here and just say we have 2 cosine squared theta is equal to 1, and then each sign here would change. So this would be minus 2 cosine squared theta, and this would now be plus 1. Okay, so this is something, again, that I would use the square root property for. You can solve it using factoring, but as I've told you in previous problems, I think that's a little bit more work for this situation. So I would just add 2 cosine squared theta to both sides of the equation. And so this would cancel. And 1 plus 1 is going to be 2. So let's go ahead and say that this is 2 on this side. On this side, 2 cosine squared theta plus 2 cosine squared theta is going to be 4 cosine squared theta. If you want to use the square root property, you need cosine squared theta equals some number. So what I'll do here is divide both sides of the equation by 4. This would cancel. We'll say that we have the cosine squared theta is equal to 2 over 4 is 1/2. So now I can use my square root property, and I'm going to say that the cosine of theta is equal to plus or minus the square root of 1/2. Now what I would do is write that as the square root of 1 over the square root of 2. And the square root of 1 is 1, and then over the square root of 2. Now to match what you see on the unit circle, what you'd want to do is rationalize the denominator. So let's go ahead and multiply this by the square root of 2 over the square root of 2. So this would be plus or minus the square root of 2 over 2. So plus or minus the square root of 2 over 2. Okay, so let's come down here. I would rewrite this and say this is cosine of theta is equal to the square root of 2 over 2, then or the cosine of theta is equal to the negative of the square root of 2 over 2. Okay, let's get rid of this, and maybe we could slide this up just a little bit so everything fits. So first off, we know that cosine is positive in quadrants 1 and 4. So I'm looking for an x-coordinate of square root of 2 over 2. So that's going to be right there at pi over 4. And then also if I come into quadrant 4, that's going to be right here at 7 pi over 4. Again, notice the reference angle would be pi over 4 for that angle. So now I'm going to go into quadrants 2 and 3. Again, you can just look for an angle with a reference angle of pi over 4, or you can just look for an x-coordinate of negative square root of 2 over 2, whatever you want to do. Most of you know already, it's going to be right here at 3 pi over 4, and then right here at 5 pi over 4. So let's write the solution where theta is greater than or equal to 0 and less than 2 pi. So we'll say that theta is equal to, let's start with pi over 4, and then let's go to 3 pi over 4, and then let's go to 5 pi over 4, and then lastly 7 pi over 4. Now when you go to find the general solution, you can do a lot better than just saying that you have pi over 4 plus 2 pi n, and then 3 pi over 4 plus 2 pi n, and then 5 pi over 4 plus 2 pi n, and then 7 pi over 4 plus 2 pi n. What you can do is actually just look at the consistent jump. So to go from here to here, I'm just adding pi over 2. Then I'm going to add another pi over 2 to get to here, then another pi over 2 to get to here, and so on and so forth. So really what I could do for the general solution, I can just start out by saying that I have pi over 4, and then plus, I would just add pi over 2, and then times n, where n is any integer. Let me make that n a little bit better. All right, for problem 7, we have negative 1/5 cosecant of, you have this theta plus pi over 2, and then this equals 2/5. So there are quite a few ways that you could solve this type of problem. It's really up to you which way you want to use, but I think the strategy that is the easiest to understand is to use a little substitution. So I'm going to let something like u be equal to this guy right here. So this theta plus pi over 2. And so now I can write this equation as negative 1/5 cosecant of, instead of this right here, since again u is equal to that, I could just put u. So then this equals 2/5. The first thing I'm going to do is get this in terms of cosecant of u equals some number. So I'm just going to multiply both sides by the reciprocal of negative 1/5. So let's multiply this by 5 over negative 1, and then times 5 over negative 1. So of course, this right here would cancel and give me a 1. So on the left, I have the cosecant of u. And this equals, if I think about on the right, the 5s would cancel. Let me put a 1 here and a 1 here. So basically you have 2 over 1, which is 2, times 1 over negative 1, which is negative 1. So 2 times negative 1 is negative 2. In order to use the unit circle, I would put this in terms of sign. So remember that the sine of, let's say, u is equal to 1 over the cosecant of u. Well, the cosecant of u is negative 2. So this is 1 over negative 2, or you could write this as negative 1/2. So the sine of u equals negative 1/2. Let's grab this real quick, and let's come down here. And so sine is negative in quadrants 3 and 4. So I'm looking for a y-coordinate of negative 1/2, and that's going to be right here. So that's at 7 pi over 6. And that's going to also be right here. So that's at 11 pi over 6. So in each case, you have a reference angle of pi over 6. So let me write here that u, and I'm just going to put this in terms of the general solution for right now, and then we're going to fix it in a moment. So u is equal to, I'm going to go 7 pi over 6 plus 2 pi n, where n is any integer, and then you have 11 pi over 6 plus 2 pi n, where n is any integer. Now let me grab this. I'm just going to paste this in here and move this over here. I'm actually just going to put this like this, maybe a little border. So we're going to know we're going to solve these two. So let me put u is equal to this. What you're going to do is now plug back in for u. So you're going to replace that with theta plus pi over 2. So this is theta plus pi over 2. Let me do that over here as well. So this is theta plus, let me slide this over. So this is pi over 2. This equals this. Okay, so the first thing I would do is subtract pi over 2 away from each side of the equation. So this gives me theta is equal to, you'll have 7 pi over 6 minus pi over 2. So minus pi over 2. I would write this with a common denominator by multiplying by 3 over 3. So this is 3 pi over 6. So 3 pi over 6. And then you have plus this 2 pi n, where again, n is any integer. So for this one, 7 pi minus 3 pi is 4 pi. So this would be 4 pi over 6. So 4 pi over 6, which you could simplify to 2 pi over 3. So 2 pi over 3, and then plus 2 pi n. So plus 2 pi n. Okay, over here we're going to do the same thing. So I'm going to subtract pi over 2 away from each side of the equation. So this right here is going to cancel away. So you'd have theta is equal to 11 pi over 6, and then minus for pi over 2. Again, I'd multiply this by 3 over 3. So you'd have 3 pi over 6. So 3 pi over 6, and then plus 2 pi n. Now 11 pi over 6 minus 3 pi over 6, that's going to be 8 pi over 6. So this would be 8 pi over 6. And of course, that's going to simplify to 4 pi over 3. So this becomes 4 pi over 3 plus 2 pi n. So plus 2 pi n. For the general solution, you're just going to have this. So you're going to say that this is 2 pi over 3 plus 2 pi n, again, where n is any integer, and then 4 pi over 3 plus 2 pi n, where n is any integer. Now, in terms of the interval, where theta is greater than or equal to 0 and less than 2 pi, where you're just going to take 2 pi over 3 and 4 pi over 3. In other words, you'd plug in a 0 for n in each case. So we're going to say that we have theta is equal to 2 pi over 3 and then 4 pi over 3. All right, let's take a look at problem 8. So here we have a negative cosine of, you have 3 theta plus 3 pi over 2, and this equals negative square root of 2 over 2. Okay, the first thing you could do here is make a substitution. I'm going to let u be equal to 3 theta plus 3 pi over 2. Again, you don't have to do it that way. There's lots of ways to solve this, but I think this is the easiest way to understand. So what I'm going to do is say we have the negative of cosine of u is equal to negative square root of 2 over 2. You can multiply both sides by negative 1, and so you would get that the cosine of u is equal to the square root of 2 over 2. Just going to come to this sheet right here. You're going to need quite a bit of room to go through this. So first, let's just visit the unit circle with this part right here. Now, where is the cosine of u equal to square root of 2 over 2? So when we think about square root of 2 over 2, we're going to have that as the x-coordinate here at pi over 4, and then also here at 7 pi over 4. And so you could say that u is equal to, we're going to put pi over 4. In terms of this right now, solutions would repeat every 2 pi because you just have cosine of u equals square root of 2 over 2. So this would be plus 2 pi n. And then for this one right here, you have 7 pi over 4 plus, again, 2 pi n. So solutions right now are repeating every 2 pi. And I'm going to split this up. It's quite a bit of work, so let me just put this off to the side for right now. And let me erase this and put this sort of in the middle because there's quite a bit of work that we need to do. So we're going to put u as 3 theta plus 3 pi over 2. So let me slide this down because we have to have some room here. And basically, the first thing you would do is subtract 3 pi over 2 away from each side of the equation. So this right here would cancel away. And let me slide down. We'll come back up in a little while. We would have that 3 theta is equal to, for this one, you would want to get a common denominator. So let's multiply this by 2 over 2. This is pi over 4 minus, this would be 6 pi over 4, and then plus your 2 pi n. Now, pi minus 6 pi would be negative 5 pi. So this becomes negative 5 pi over 4. So negative 5 pi over 4. Now, we have 3 theta, not theta. If you want to get rid of this 3 here that's multiplying theta, you can divide everything by 3, or you can multiply everything by 1/3. I think that's easier if you're working with fractions, but it's up to you. So basically, I'm going to cancel this with this and say I have theta is equal to, you would have negative 5 pi over 3 times 4 is 12, and then plus 2 pi n times 1/3 is going to be 2 pi over 3 times n. Okay, let me erase all this, and let me put this up here for right now. Now I'm going to change this really quickly. Notice that you can add 2 pi over 3 to this solution to get to another solution because I could just plug in a 1 for n. So you could say negative 5 pi over 12 plus 2 pi over 3 to get to another solution. I'm going to multiply this by 4 over 4. So this would be 8 pi over 12. Negative 5 pi plus 8 pi, that would be 3 pi over 12, which reduces to pi over 4. Okay, so I'm going to write this as theta is equal to pi over 4 plus 2 pi over 3 times n. We have this other one to deal with. We're going to do the same process. It's just time consuming. It's not really that bad. So we're going to have 3 theta plus 3 pi over 2 is equal to this 7 pi over 4 and then plus 2 pi n. Okay, let me get rid of this and we'll just slide down. So again, I'm going to subtract 3 pi over 2 away from each side of the equation. Again, we know that this would cancel. 3 pi over 2, if I multiplied by 2 over 2, this would be 6 pi over 4. So 6 pi over 4. And so 7 pi minus 6 pi would be pi. So this right here would be pi over 4. So let's write this as pi over 4. And let's just erase this, save ourselves another line. We know that if we want to get rid of this 3, that is multiplying the theta there, we can just multiply both sides by a third. So multiply both sides by a third, or you could divide both sides by 3, whatever you want to do. So basically this would cancel with this, and you have theta is equal to, you would have pi over 12 plus, this again would be 2 pi over 3 times n. And let me actually just drag this up here like this and put a little comma. Now this is your general solution. So you could erase this and use some set braces if you want. It's up to you. So let me actually label this. I'll bring this down here and just say, this is the general solution. If you want theta to be greater than or equal to 0 and less than 2 pi, you have some additional work to do. So basically, you would say theta is equal to, let's start with the fact that we have pi over 4. Now I could add pi over 4 and 2 pi over 3. So again, I got to get a common denominator, so it's a little bit of work. So let's go ahead and say that this right here, if I multiply by 3 over 3, and this right here, if I multiply by 4 over 4, well, that would give me 3 pi plus 8 pi, which would be 11 pi over 12. So this would be 11 pi over 12. Okay, I could try to do that again. So let's go 11 pi over 12, and I'm going to add another 2 pi over 3. So if I multiply this by 4 over 4, this would be 8 pi. So 8 pi over 12, and that would give me 19 pi over 12. So 19 pi over 12. So let's put that down as a solution. And that's as good as I can do in terms of in this interval. If I try to add another 2 pi over 3, I'm going to go outside of this interval. You could try that on your own if you want. Then I'm going to go to this pi over 12. And again, let me slide this down. I'm going to add pi over 12 and 2 pi over 3. Well, I'm going to multiply this by 4 over 4. And so again, this is going to be 8 pi over 12. So 8 pi over 12. So this would give me 9 pi over 12. So this right here would be 9 pi over 12. Each is divisible by 3, so this would be 3 pi over 4. So 3 pi over 4. Now, let's go back with the 9 pi over 12 form, and let's add this 2 pi over 3, which we know is 8 pi. So 8 pi over 12, just by multiplying 2 pi over 3 by 4 over 4. And this would give me 17 pi over 12. So this would be 17 pi over 12. And again, that's as good as you can do, because if you take 17 pi over 12 and you add another 2 pi over 3, you're not going to be in this interval. So this is your general solution, pi over 4 plus 2 pi over 3n. And then pi over 12 plus 2 pi over 3n, where n is any integer. And then if you wanted the interval from theta being greater than or equal to 0 and less than 2 pi, well, then you say theta is pi over 4, 11 pi over 12, 19 pi over 12, pi over 12, 3 pi over 4, and then 17 pi over 12. All right, let's take a look at problem 9. So here we have the square root of 3 is equal to 2 cosine of, we have this theta over 4 plus 5 pi over 3. Again, the way I would solve this, I'm just going to let u be equal to this theta over 4, and then plus 5 pi over 3. So now I'm just solving square root of 3 is equal to 2 cosine of u. So let me grab this and come down here. And basically you could divide both sides of the equation by 2. And so this would cancel. You'd have the cosine of u is equal to square root of 3 over 2. We could just come down here and write it. So cosine of u is equal to square root of 3 over 2. So again, in terms of u, things are going to repeat every 2 pi. So let's go through and find this solution here, square root of 3 over 2. That's your x-coordinate, that's at pi over 6. And then square root of 3 over 2, that's your x-coordinate at 11 pi over 6. So let's say that we have u is equal to pi over 6 plus 2 pi n. And then we're going to have 11 pi over 6 plus 2 pi n. Okay, let's say u is equal to this, or we have u is equal to this. Now, I think we could probably speed the process up a little bit, but I might lose some people, so I think I'm just going to go slowly. So we're going to say that theta over 4 plus 5 pi over 3, so that's my u, is equal to 11 pi over 6. And then you have your plus 2 pi n. Let me scooch this down. So plus 2 pi n. So I'm going to subtract 5 pi over 3 away from each side of the equation. So this right here is going to cancel. You would have theta over 4 is equal to 11 pi over 6 minus, for 5 pi over 3, let's multiply this by 2 over 2. This would give me 10 pi over 6, and then plus your 2 pi n. So 11 pi minus 10 pi, that's going to be pi. So this right here is going to become pi over 6. So this is pi over 6. Now you have theta over 4. If you want theta by itself, just multiply everything by 4. And basically, you're going to see that this is going to cancel. So you have theta is equal to pi over 6 times 4. Well, this 4 and this 6 have a common factor of 2. So 4 divided by 2 is 2. 6 divided by 2 is 3. So this would be 2 pi over 3. And then plus 2 times 4 is 8. So this would be 8 pi n. Let me just put this like this. Okay, so we did this one. Let's get rid of that. And let's work on this one. So for u, I'm plugging this in. So theta over 4 plus 5 pi over 3. And this is equal to pi over 6. Leave a space, and I'm going to put plus 2 pi n. Okay, let's get rid of this. We don't need this information anymore. So we know that we're going to subtract 5 pi over 3 away from each side of the equation. And we know that 5 pi over 3, again, if you multiply by 2 over 2, this is 10 pi over 6. So minus 10 pi over 6. Let's just erase it from over here. Keep it simple. So pi minus 10 pi is going to be negative 9 pi. So this becomes negative 9 pi over 6. So you can simplify this. 9 and 6 are each divisible by 3. So this would be negative 3 pi over 2. At this point, you want theta. So let's multiply everything by 4 and see where that gets us. So we know that this would cancel. So now you have theta is equal to, you would have 4 divided by 2 is 2. 2 times negative 3 is negative 6. So negative 6 pi. And then basically you're going to have plus 2 times 4 is 8. So this is 8 pi n. So what I would do here is go ahead and add 8 pi to this solution. So negative 6 pi plus 8 pi would be 2 pi. So let's go ahead and say that this is theta is equal to 2 pi plus 8 pi n, where n is any integer. So let's put 2 pi plus 8 pi n. Okay, so thinking about this, it's the general solution. So this is your general solution. And then if you want for theta to be greater than or equal to 0 and less than 2 pi, well, essentially what you have to do is plug in a 0 here, and that would give you 2 pi over 3. So 2 pi over 3. If you plug in a 0 here, you're going to get 2 pi, and that's not in this interval. 2 pi is excluded. So you really can't get anything from this part. So really you can only say that for theta being greater than or equal to 0 and less than 2 pi, you just have theta is equal to 2 pi over 3. But for the general solution, you have 2 pi over 3 plus 8 pi n, and then 2 pi plus 8 pi n, where n is any integer. All right, now we're going to change things up. We're going to look at some problems that deal with the sum to product identities that we talked about earlier in the course. So typically when you answer problems of this type, you do it in terms of the general solution, because if you work over a specific interval, let's just say theta is greater than or equal to 0 and less than 2 pi, you get so many solutions in some cases that it's not practical to list them. So I'm going to have for the instructions to just solve each for all solutions. All right, let's take a look at problem 10. So here we have negative sine of x minus the cosine of 4x. This equals the negative of the cosine of 6x. So when I see something like the negative cosine of 4x and the negative cosine of 6x, I am thinking that I can use the sum to product identities. So I would add the cosine of 6x to both sides of the equation. And let's go ahead and cancel this away and put a 0 here. Let me slide down a little bit. So I'm just going to write that we have the negative of the sine of x. And then I'm going to put minus the cosine of 4x. And then plus the cosine of 6x. And this equals 0. So let me grab this. All right, so coming here, right now, the way I've written the equation, I have cosine of 4x plus cosine of 6x. So I can use this identity here and just basically say that I'm going to have a 4x in the place of x and a 6x in the place of y. But if I was to do that, notice that you'd have cosine and cosine, and then over here I have sine. So what I'd want to do is actually change this up so that I can use this guy right here, so I would have sine and sine. So I'm actually going to delete this one. I'm not going to use it. Let me move this up a little bit so we have more room. And the way I'm going to do this, of course, you could just switch the order of this and say that this is negative sine of x and then plus the cosine of 6x and then minus the cosine of 4x. So you could do it that way. So negative sine of x and then say plus the cosine of 6x. And then you can go minus the cosine of 4x and this equals 0. So you could do it that way. Or you could multiply everything here by -1. I'm actually going to do it that way. I prefer that. So let's change this to a positive, this to a positive, this to a negative, and no change to 0. So whatever you want to do, you're going to get the same answer either way. So now what I'm going to do is use this little identity. So if we had the cosine of 4x and then minus the cosine of 6x, so basically I'm working with this right here. That's going to match this right here. This is equal to, just match the formula. Here, x is going to be 4x and y is going to be 6x. So this would be -2 times the sine of, you're going to add these guys together. So 4x plus 6x, that's 10x, and this is over 2. Now, you can simplify this. 10 over 2 is 5. So this would be 5x, like this. And maybe I can make that a little bit smaller there, so it's more consistent. And then times the sine of, now you're going to subtract. So you want x minus y over 2. So 4x minus 6x, that's -2x. So -2x over 2. Of course, -2 over 2 is -1. So we can put this as the sine of -x. Now, we know from earlier in the course that we have the even-odd identities. And basically, the sine of -x is the negative of the sine of x. So in other words, the sine of -x is equal to -1 times the sine of x. So you can take this and pull it out as a -1 and say it's -1 times this -2, which would be +2. So I'm going to make that positive, and I'm going to get rid of that. And basically, this is the form we're going to use. Okay, so because this matches this, we're going to take this right here and plug it in for that right there. So that's all we're going to do. So we're going to have that the sine of x plus this right here is 2 sine of 5x, and then sine of x is equal to 0. Now notice that you have the sine of x and the sine of x. So I can pull that out. I can say this comes out in front of some parentheses here, and we're going to have the sine of x times the quantity. This getting pulled out would give me a 1, and then plus, if this gets pulled out, you have 2 sine of 5x, and then this equals 0. Okay, so we're going to have the sine of x is equal to 0. I'm going to stop for a moment and solve that real quick, and then I'm going to do the other one because the other one is a little bit more complicated. So let's come down to the unit circle. Again, if I had something like the sine of x is equal to 0, well, where is that going to happen? Well, here at 0, and then here at pi. Remember, we're working in terms of the general solution, so I'm just going to say that x is equal to pi n, because this is happening every pi. So here, add pi, add pi, add pi. If you want 0, just plug in a 0 for n. Then if you want pi, just plug in a 1. If you want 2 pi, plug in a 2, so on and so forth. So x is pi n for that particular one. So for this one, let me put that x is equal to pi n, where n is any integer. Then let's go or. The next one's a little bit complicated. So we have 1 plus 2 sine of 5x, and this would be set equal to 0. So let me actually subtract 1 away from each side of the equation. This would cancel. So you put a -1 over here and erase that from over here. Let me divide both sides of the equation by 2. So this would get erased here. So this is the sine of 5x. So the sine of 5x is equal to -1/2. So equal to -1/2. Okay, let me write this in. So the sine of 5x is equal to -1/2. Now, you can work with this without using a substitution, but I think it's a little bit helpful if you use a substitution. So let me actually erase these previous answers here. And let's think about something like the sine of u is equal to negative 1/2. So if I asked you for the general solution for this, just in terms of the sine of u, the regular period is 2 pi. So if I find a solution, it's going to repeat every 2 pi. So here I'm looking in quadrants 3 and 4, where sine is negative, and I want a y-coordinate of negative 1/2. So that's right here at 7 pi over 6. Notice the pi over 6 reference angle. And then right here at 11 pi over 6, again, pi over 6 reference angle. So we would say that u is equal to, you would have 7 pi over 6 plus 2 pi n, where n is any integer. And then you would have 11 pi over 6 plus 2 pi n, where n is any integer. So let me grab this real quick and come back up here and paste this in. And we probably need a new sheet. Let me actually grab this and go somewhere else. So the idea here is that u was equal to 5x. So now I can plug in a 5x for u here. And of course, we don't have it over here, but we'll set it up. So let's go ahead and say that we have 5x is equal to 7 pi over 6. I'm going to leave some space. So plus 2 pi n. Let me put or. 5x is equal to this right here. So 11 pi over 6. And then plus 2 pi n. Okay, so we want x by itself. And to do that, right now you have 5 that's multiplying x, so you could divide everything by 5. But since we have fractions involved, I think it's easier to actually multiply everything by 1/5. So let's go ahead and do that. I'm going to multiply this by 1/5, multiply this by 1/5, multiply this by 1/5. Okay, let me slide this out of the way. We'll do this one in a moment. So 1/5 times 5 is going to be 1. So basically you have x is equal to 7 pi over 6 times 1/5 is 7 pi over 30. And then plus 2 pi n times 1/5 is 2 pi over 5 times n. Let me actually cut this away and move this over here. And I'm going to paste this in now. Let me put that as one of them. And let me work on this one. So I'm going to multiply everything by 1/5. Let me move this down so it fits. And so this cancels. You get x is equal to 11 pi over 6 times 1/5 is going to be 11 pi over 30. And then plus 2 pi n times 1/5 is 2 pi over 5 times n. So let me grab this and come back down here and just put a comma here and get rid of this. So now I just want to put my general solution together, basically just combining all these parts that I have. Let me slide down a little bit. So first I have this pi n. So let me set this up as the general solution here. So you have pi n, where n is any integer. Then you have this part right here. So the 7 pi over 30. And then plus, you're going to have 2 pi over 5 times n, where n is any integer. And then you're going to have 11 pi over 30. Let me slide this a little bit further down so it fits. So plus 2 pi over 5 times n, where n is any integer. All right, let's take a look at problem 11. So we have the sine of 2x plus the cosine of 7x is equal to the cosine of 3x. So what I'm going to do is subtract the cosine of 3x away from each side of the equation. So this would cancel and give me a 0 over here. Let me slide down a little bit. So now I'm going to have the sine of 2x and then plus the cosine of 7x and then minus the cosine of 3x, and this equals 0. So if we look at this identity, the one we used in the last example, it's going to work out for us here. You have the cosine of 7x minus the cosine of 3x. Well, here you have the cosine of x minus the cosine of y. So 7x is x and 3x is y. So if you use this, you're going to end up with a sine and then a sine, and here you have a sine. So we're going to be good to go with this formula here. Let me slide this out of the way just a little bit so we can plug in. So if I had the cosine of 7x and then minus the cosine of 3x, this is equal to negative 2 sine of, I'm just going to add 7x and 3x together. That's going to give me 10x and then divide that by 2. That would be 5x. And then we'd have the sine of, now you're going to subtract 7x minus 3x. That's going to be 4x over 2. And 4x over 2 is going to be 2x. Okay, so let me highlight this. And essentially, what you're going to do, just like we've been doing before, we're going to take this right here and we're going to plug it in for this right here. So we're going to say we have the sine of 2x, and then basically you have this right here that's getting plugged in for this right here. So let's go minus 2 sine of 5x, and then sine of 2x, and this equals 0. Okay, so looking at what we have, you have the sine of 2x and the sine of 2x. So I can pull that out in front of some parentheses. So we're going to have the sine of 2x and then times the quantity. If this gets pulled out, you have a 1, and then minus, you're going to have 2 sine of 5x, and then close that down, and this equals 0. We're going to use our zero products property here. So first you're going to take the sine of 2x, and you're going to set that equal to 0. And then you're going to say, or, we're going to have 1 minus 2 sine of 5x, and we're going to set that equal to 0. So for this one, let's subtract 1 away from each side. This would cancel. So you're going to have negative 2 sine of 5x is equal to negative 1. We get rid of this and slide this up here. I would divide each side by negative 2. And so basically this would cancel away. And you're going to get that the sine of 5x is equal to negative 1 over negative 2 is going to be 1/2. All right, let's start off with sine of 2x equals 0. Basically, you could say that u is equal to 2x. And then you could say, well, I want the sine of u being equal to 0. And of course, that's going to happen right here at 0. And it's going to happen right here at pi. So let's go ahead and say that u is equal to, let's go pi n, where n is any integer. So what you would do is come back and say, well, u is 2x. So you would put 2x like this. And then now you would divide both sides of the equation by 2. So this would cancel. And you're going to get x is equal to pi over 2 times n. So x would be equal to pi over 2 times n, where n is any integer. And I'm going to come back here and just paste this in. So that's that part. Now this part, you have sine of 5x equals 1/2. So let me write sine of 5x equals 1/2. So again, you can use the substitution or not. It's really up to you. I like to do it. So I'm just going to let u be equal to 5x. And then we have the sine of u is equal to 1/2. So of course, I'm looking for a y coordinate of 1/2. So right there at pi over 6, and then right there at 5 pi over 6. So u is equal to pi over 6 plus, if I'm looking at the sine of u, again, right now, sine of u equals 1/2. Well, the solutions are going to repeat every 2 pi. So just put plus 2 pi n, and then I'm going to come over here and say we have 5 pi over 6 plus 2 pi n. Now, we let u equal 5x. So I'm going to get rid of this and just put a 5x is equal to this. Let me grab this real quick. So essentially, what you can do, if you want x by itself, is just multiply everything by 1/5. Let me split this up so it's more clear. Let me bring this down here and say 5x is equal to this as well. So let me move this down here so this fits. I'm going to multiply this by 1/5, and this by 1/5, and then this by 1/5. So this would cancel. You get x is equal to pi over 30 plus 2 pi n times 1/5 is 2 pi over 5 times n. So that's for this one up here. Okay, for this one down here, again, you're just going to do the same thing. So you're going to multiply everything by 1/5. Let me move this over so this fits. And so this is going to cancel. And so you have x is equal to, you'll have 5 pi over 6 times 1/5. Well, this 5 will cancel with this 5. So you can have pi over 6 plus 2 pi n times 1/5 is 2 pi over 5 times n. So let me put a comma here and just put this up here. So pi over 6 plus 2 pi over 5 times n. So this is for this part right here. Okay, let me slide down a little bit and let me give you a general solution. So I'm just going to put these together. So here is your general solution. So I'm going to start with the pi over 2 and then times n. And then I'm going to go with the pi over 30 plus 2 pi over 5 times n. And then I'm going to go with pi over 6 plus 2 pi over 5 times n. So n here is just any integer. All right, for problem 12, we're going to have the cosine of 4x plus the sine of 3x is equal to the sine of 5x. All right, what I'm going to do is subtract the sine of 5x away from each side of the equation. So that would cancel and give me a 0 on the right. So we would write this as the cosine of 4x. and then plus the sine of 3x, and then minus the sine of 5x, and this equals 0. So let me grab this real quick and come down here and paste this in. So I'm going to use this little identity here. Notice that you have the sine of 3x minus the sine of 5x. So let's set this up. We have the sine of 3x and then minus the sine of 5x. So this would be equal to, let me make this 5 a little bit clearer there. And let me slide this down just a little bit. So this is 2 cosine of, I'm going to add these guys together. So 3x plus 5x, that's 8x, and then divide by 2, that's going to be 4x. And then times your sine of, I'm going to subtract 3x minus 5x, that's negative 2x, and then divide by 2. So negative 2x over 2 would be negative x. So this right here would be negative x. Again, the sine of negative x is equal to, you can go negative 1 times the sine of x. So you can take this and pull it out as a negative 1 and basically put it out in front here. Let me actually slide this down like this and put the 2 there. So I'm going to put that negative there and get rid of it from there. So let me make this a little bit cleaner here. This right here matches this right here. So all I have to do is plug this right here in for this right here. That's it. So we're going to have the cosine of 4x, and then basically you're going to plug this in, so minus 2 cosine of 4x, and then sine of x, and this equals 0. So we're going to factor out the cosine of 4x. That's going to be common. So let's go ahead and pull that out. We have the cosine of 4x outside of some parentheses. Inside, if you pull that out, you're going to have a 1, and then minus, you're going to have a 2, and then the sine of x. Okay, so this equals 0. So using the zero product property, we're going to say the cosine of 4x is equal to 0. Then or 1 minus 2 sine of x is equal to 0. For this one, you really don't have to do anything with it. For this one, I would subtract 1 away from each side. Let's get rid of that and put this as a negative 1, and then divide both sides by negative 2. And so this would go away. And so you have the sine of x is equal to positive 1/2. Okay, let me move this over here. I think we know this one is going to be pi over 6 plus 2 pi n, where n is any integer, and then 5 pi over 6 plus 2 pi n, where n is any integer. But again, you can always go to the unit circle, and you would find 1/2 for the y-coordinate here at pi over 6, and then 1/2 for the y-coordinate at 5 pi over 6. So let me just write this one in. So this is sine of x, so the regular 2 pi period. So I'm just going to say that it's pi over 6 plus 2 pi n, and then we have 5 pi over 6 plus 2 pi n. If I come back down here, and let's just say I say that cosine of u is equal to 0, where we're going to let u be equal to 4x. So basically, we know that this guy is going to happen at pi over 2, and then 3 pi over 2. So that's going to be your 0 for the x-coordinate there, and 0 for your x-coordinate there. Now, when I think about this, again, normally you would write, if it's just cosine of u is equal to 0, or cosine of x is equal to 0, or whatever you're working with, if it's a regular cosine function, well, things are repeating every 2 pi. But here, you're able to condense those two solutions into one, and let's just say that u is equal to pi over 2 plus pi n, where n is any integer. So let me actually grab all of this, come back up here, and let's think about this for a moment. So we let u be equal to 4x. And so all I'm going to do, let me just put a little border here. I'm going to say that we have 4x is equal to pi over 2 plus pi n. And then basically all I'm going to do is multiply both sides by a fourth, or we can divide both sides by 4, whatever you want to do. So basically, let me move this down here, and I'm going to multiply this by 1/4. And this should probably be up here a little bit more. So times 1/4, and then times 1/4. So you're going to end up with this canceling with this, and you're going to have x is equal to, this would be pi over 8, so pi over 8, and this is really hard to fit. So then plus, this is pi over 4 times n, so pi over 4 times n. And I'm just going to arrow over like this and move this up. All right, so we have the general solution. So let's go ahead and set this up and say this is my general solution. So let me just start with this. I'll go pi over 8 plus pi over 4 times n, where n is any integer. And then you're going to have pi over 6 plus 2 pi n, where n is any integer, and then 5 pi over 6 plus 2 pi n, where n is any integer. All right, let's take a look at problem 13. So we have the cosine of 2x is equal to the sine of 7x plus the sine of 3x. So what I'm going to do is subtract the cosine of 2x away from each side of the equation. So over here, this would cancel, give me 0. And I'm going to write this with this guy on the left and 0 on the right. So let's just say we have the sine of 7x and then plus the sine of 3x and then minus the cosine of 2x, and this equals 0. I have a little identity set up for us. So the sine of x plus the sine of y. Here you have the sine of 7x plus the sine of 3x. So we would say that the sine of 7x plus the sine of 3x is equal to, let's say it's 2. Let me slide this down so it actually fits. So you're going to have sine of, you're going to add this. So 7x plus 3x is 10x, and then 10x divided by 2 is 5x. So 5x, maybe that s could be a little bit better, and maybe the n could be a little bit better there as well. And then we're going to have cosine of, so you can have 7x minus 3x, which is 4x, divided by 2, which is 2x. Okay, so this right here matches this right here. So this and this, those are going to match. So I'm just going to take this right here and plug it in for that right there. That's it. Let's slide down and say we have 2 sine of 5x and then cosine of 2x and then minus the cosine of 2x, and this equals 0. When we look at this, we have the cosine of 2x and the cosine of 2x. So I'm going to pull that out in front of some parentheses and say I have the cosine of 2x, and then inside the parentheses, I'm pulling that out, so I'd have 2 sine of 5x, and then minus, if I pull this out, I'm going to have a 1, close that down, and this equals 0. I'm going to say that I have the cosine of 2x is equal to 0, then or you have 2 sine of 5x minus 1 is equal to 0. So for this one, let's add 1 to both sides. And so this would be a 1 over here, and then divide both sides by 2. So let's get rid of this. Okay, so let's write out that the cosine of 2x is equal to 0. Again, I like to use substitution for this. So I would just let something like u be equal to 2x. Again, you don't have to do this. I think it's a little bit easier. So I'm just going to say the cosine of u is equal to 0. And of course, we've done this a million times. We know that's right here at pi over 2 and right here at 3 pi over 2. So you could say that it's u is equal to pi over 2 plus 2 pi n, and then 3 pi over 2 plus 2 pi n. But again, you can combine those because this is happening every pi. So you can get rid of this, and you can make this into pi over 2 plus pi n. Now, we know that u is equal to 2x, so we're just going to plug in a 2x there, and then get rid of all this. You don't need it anymore. Essentially, if I want x by itself, I would divide everything by 2 or multiply everything by a half. So you would have x is equal to pi over 4, and then plus pi over 2 times n. So I just multiplied everything by a half. So 2x basically times 1/2. And then let me slide this down so I can show this. Pi over 2 times 1/2, and then pi n times 1/2. So that gives me this x is equal to pi over 4 plus pi over 2 times n, where n is any integer. Okay, let's come over here, and I'll arrow to that. And now I have the sine of 5x equals 1/2. So again, you don't need the unit circle, but let's just go down there. So the sine of, again, 5x is equal to 1/2. So once again, this right here is a bit complicated to think about. That's why I use the substitution. So I just let u be equal to 5x. And then you could just solve sine of u is equal to 1/2. And basically, you know that you're going to have solutions here at pi over 6, where the y-coordinate is 1/2, and then 5 pi over 6, where the y-coordinate is again 1/2. And then things in terms of u repeat every 2 pi. So it's very straightforward. So we would say that u is equal to, we're going to have pi over 6 plus 2 pi n. And then we're going to have 5 pi over 6 plus 2 pi n. Okay, well, since I let u be equal to 5x, you could just plug in a 5x there. And then let me just grab this. And essentially, all you have to do, let me just write this separately. So let me put 5x is equal to this, put a little border. Just multiply everything by 1/5 to get x by itself. Messed up my border there. Just trying to slide this down so I have enough room. So multiply this by 1/5, multiply this by 1/5, multiply this by 1/5. So this is going to cancel. You get x is equal to pi over 30, and then plus 2 pi over 5 times n. Then over here, you can do the same thing. So multiply everything by 1/5. Let me slide this out of the way so I have enough room. And essentially, this would cancel. You get x is equal to, you're going to have these 5s canceling. So pi over 6, and then plus, you'd have 2 pi over 5 times n. And I'm just going to arrow down like this. And let's just write a little general solution. So a general solution for this. So first, you have this pi over 4 plus pi over 2 times n, where n is any integer. Then you have this pi over 30 plus 2 pi over 5 times n, where n is any integer. And then you have pi over 6 plus 2 pi over 5 times n. Let me make the n a little bit better, where n is any integer. All right, let's take a look at problem 14 now. So we have the cosine of 5x plus the cosine of 3x is equal to the cosine of x. So let me just subtract the cosine of x away from each side of the equation. This is going to cancel, give me 0 over here. Let's write this as the cosine of 5x, and then plus the cosine of 3x, and then minus the cosine of x, and this equals 0. All right, let me paste this in here. And now we're going to use this little identity, cosine of x plus cosine of y. Let me slide this down so it fits. Let me just write what we want to do. So the cosine of this 5x, and then plus the cosine of this 3x. This would be equal to, we're going to go 2 cosine of, this is not going to fit, so let me slide it down some more. And then inside the parentheses, you have this plus this. So 5x plus 3x, that's 8x over 2. So 8x over 2 is going to be 4x. And then times the cosine of, now you're going to go this minus this. So 5x minus 3x, that's 2x, and then over 2, so that's going to be x. So let's close that down. Okay, so we can see that this right here matches this right here. So all we're going to do is we're going to take this right here, and we're going to plug it in for that right there. That's all we're going to do. So we're going to have 2 cosine of 4x, and then cosine of x, and then minus the cosine of x, and this equals 0. Okay, at this point, it's very straightforward. You have the cosine of x and the cosine of x. So we're just going to pull that out in front of some parentheses. So let's say we have the cosine of x, and then inside the parentheses, we're going to have 2 cosine of 4x, and then minus, if this gets pulled out, you're going to have a 1. Close that down, and this equals 0. Okay, so at this point, we have the cosine of x is equal to 0. A lot of you know, again, that's pi over 2 plus 2 pi n, and then 3 pi over 2 plus 2 pi n, which you can combine into pi over 2 plus pi n. We'll go to the unit circle, and we'll do it there, just in case you are lost. Let me go or. We're going to go 2 cosine of 4x, then minus 1 equals 0. Let's add 1 to both sides. We'll cancel that away, and we'll say that this is 2 cosine of 4x is equal to 1. Divide both sides by 2. This will cancel. So you have cosine of 4x equals 1/2. Let me rewrite that. So cosine of 4x is equal to 1/2. Again, cosine of x equals 0. A lot of you know this already. So here's 0 and here's 0. So that's pi over 2 and 3 pi over 2. So of course, these solutions do repeat every 2 pi. So you could say pi over 2 plus 2 pi n, and then 3 pi over 2 plus 2 pi n. That's fine. But you can condense that and say it's pi over 2 plus pi n, because solutions are happening every pi. So let's just say that x is equal to pi over 2 plus pi n, where n is any integer. And let's come up here, and I'm just going to arrow to that. So that's for this one. Then for this one, again, it's a little bit complicated to think about. So the cosine of 4x equals 1/2. Let's come down here and say cosine of 4x is equal to 1/2. Again, I'm going to stick to the substitution technique. You don't have to use that, but I like to do it. So I'm just going to let u be equal to 4x, and then just say, okay, I'm looking for cosine of u to be equal to 1/2. And again, because this is just cosine of u, my solutions are going to repeat every 2 pi. So it's just the standard period that we're working with here in terms of u. So I'm looking for a 1/2 for the x coordinate. So that's right here at pi over 3. And then that's going to be right here at 5 pi over 3. So we're going to say that u is equal to pi over 3 plus you're going to have 2 pi n. And then you're going to have this one down here, which is 5 pi over 3. Let me make that 3 a little bit better. And then plus 2 pi n. So u is 4x, so let's replace this u with 4x here. And let's come back and just paste this in. Just put a little border here for right now. So 4x is equal to this, and then you have 4x is equal to, again, the 5 pi over 3. Let me make that a little bit better. And then plus 2 pi n. So how do we get x by itself? Well, we divide everything by 4, or you can multiply by a fourth. I think that's easier because you are working with fractions here. Let me slide this over so I have some room to do this. So I'm going to multiply this by 1/4, multiply this by 1/4, and multiply this by 1/4. So that's going to give me, this would cancel. X is equal to 1/4 times pi over 3 is pi over 12. And then plus 2 over 4 is 1/2. So basically this is pi over 2. So pi over 2. And then times n, where n is any integer. Let me make this a little bit better. And then this other one, again, I'm just going to multiply everything by 1/4 and see what that gives me. So this again is going to cancel. You're going to get x is equal to 1/4 times 5 pi over 3 would be 5 pi over 12. And then plus, you're going to have this 2 pi over 4, that's pi over 2. So pi over 2, and then times n, where n is any integer. And move this up here like that, or actually I'll just stick it right there. That's fine. And then basically you just want to write the general solution. So I'm just going to combine these two different solutions here. So let's go ahead and start with this one. We have pi over 2 plus pi n, where n is any integer. And then we have pi over 12 plus pi over 2 times n, where n is any integer. And then we have 5 pi over 12 plus pi over 2 times n, where n is any integer. All right, let's take a look at problem 15 now. So we have the negative of the cosine of 3x is equal to the cosine of 5x plus the cosine of x. All right, so what I'm going to do is actually add the cosine of 3x to both sides of the equation. So this would cancel and give me a 0. Let me flip this around. I'll put this on the left and put 0 on the right. So I'm just going to write this as the cosine of 3x plus the cosine of 5x, and then plus the cosine of x is equal to 0. Okay, let's grab this, and let's come down here. We have our little identity set up. So I'm just going to write cosine of 3x plus the cosine of 5x is equal to 2 cosine of, you have your 3x plus 5x, that's 8x, again, over 2. So 8x over 2 would be 4x. And then times your cosine of, you have your 3x minus 5x, that's negative 2x. And negative 2x, let me write this out. So negative 2x over 2, that's going to be negative x. So this right here would be negative x. Now, we know that the cosine of negative x is equal to the cosine of x. That's your, what we call even odd identities, or some people call these the negative angle identities. So you can actually just erase that and say it's the cosine of x. And so now we have this guy right here matching this guy right here. And so I'm just going to take this right here and plug it in for this right here. So that's all I'm doing. I'm going to have 2 cosine of 4x cosine of x plus cosine of x is equal to 0. So we know that we have cosine of x and cosine of x, so I can factor that out. So I'm just going to pull it out in front of some parentheses. So the cosine of x times the quantity. Here you would have 2 cosine of 4x, and then plus, if I pull this out, you would have a 1. So close that down, and this is going to be equal to 0. Let me go ahead and grab this, and let me come to a fresh sheet. So we're going to use our zero products property. So we're going to have the cosine of x is equal to 0. And then, or, we're going to have this guy right here. So 2 cosine of 4x plus 1 is equal to 0. Again, we've solved this so many times. You should know at this point that it's x is going to be equal to pi over 2 plus 2 pi n, and then 3 pi over 2 plus 2 pi n, and that can be condensed into x equals pi over 2 plus pi n, where n is any integer. But again, I'll go to the unit circle and show you that in a moment. For this one, let's subtract 1 away from each side. We'll cancel that away. We'll say this equals negative 1, and then we'll divide both sides by 2, and then we'll cancel this away. So the cosine of 4x equals negative 1/2. So the cosine of 4x is equal to negative 1/2. Okay, let me make this a little bit better there. So let me paste this in here. So the cosine of x equals 0. Again, if I'm looking at this, I know that basically I have a solution here at pi over 2, and then here at 3 pi over 2, and I can go pi over 2 plus 2 pi n, and then 3 pi over 2 plus 2 pi n. But again, since things are happening every pi, you could just say this is pi over 2 plus pi n. So let me put x is equal to that. Okay, let me come back up here and just paste this one in. So this is for this one. And then you have the cosine of 4x is equal to negative 1/2. So let me write the cosine of 4x is equal to negative 1/2. Again, I like to use the substitution technique. You don't have to, but I find it to be helpful. So let u be equal to, we're going to say this 4x here. So now when I have the cosine of u is equal to negative 1/2, I could just think about these things in terms of repeating every 2 pi. I don't have to think about anything. And basically, when I go back and substitute again and I solve for x, it'll take care of all that for me. I can just say that u is going to be what? Well, where do we have an x-coordinate of negative 1/2? I'm going into quadrants 2 and 3, where cosine is negative, and so that's going to be right here at 2 pi over 3. Again, I would have a pi over 3 reference angle, and then right here at 4 pi over 3, I would have a pi over 3 reference angle. So we can say that u is equal to 2 pi over 3, and then plus 2 pi n, and then you would have your 4 pi, so 4 pi over 3, plus 2 pi n. So again, this is nice because I don't have to think about the period, right? That's going to be taken care of for me when I make my substitution. So I'm going to come back over here, and I'm going to plug in a 4x. Now notice if you think about the cosine of 4x, well, this is 2 pi over 4, right? So this is going to end up being pi over 2 for the period of this guy. So you would expect for the solutions to repeat every pi over 2. And you're going to see that because, again, you have this 2 pi here that's going to be divided by this 4. That's going to give you pi over 2 and then times that n. So that's what's going to happen. Let's go ahead and grab this real quick. And let's come back here and paste this in. And I don't know if I have enough room to work. So let me slide down a little bit. And let me just start with this one. So 4x is equal to 2 pi over 3. And then plus 2 pi n. So if I want x by itself, just divide everything by 4 or multiply everything by 1/4. I think that's a little bit easier to do if you have fractions involved. So this cancels. You get x is equal to, you think about 2 and 4. 2 divided by 2 is 1, and 4 divided by 2 is 2. So this is going to be pi over 6, so pi over 6. And then plus, this 2 would cancel with this 4 and give me a 2. So this is pi over 2 times n. So again, if you think about this guy right here, again, the period is pi over 2, right? If I had y equals the cosine of 4x, the period is going to be pi over 2. So you would expect for solutions that you find for this to repeat every pi over 2. Like this, and we'll arrow to that. And we'll just work on this one. So this one would have been 4x is equal to this. Again, I'm just going to multiply everything by 1/4 to get x by itself. So times 1/4. Times 1/4 and times 1/4. Okay, so this is going to cancel. You have x is equal to, you have this 4 would cancel with this 4 and give me pi over 3. And then plus this 2 and this 4 have a common factor of 2. Let me just put a 1 there and put a 2 down here. So again, this is pi over 2 times n, where n is any integer. I think this color really does not show up very well. So let me move this out of the way, and I'll rewrite it in something that's a little bit better. So let's go ahead and say that this is pi over 3, and then plus pi over 2 times n, where n is any integer. Okay, let me get rid of that comma and put one in a different color. And let's make our general solution, so the general solution. So let's start with this one. We have pi over 2 plus pi n, and then we have pi over 6 plus pi over 2 times n, and then we have pi over 3 plus pi over 2 times n, again, where n is any integer. All right, let's take a look at the practice test. For the instructions, we're asked to find the exact value. All right, let's take a look at the first problem. So here we have the inverse tangent of the tangent of 7 pi over 3. Remember, if you're working this type of problem, we go back to what we talked about in the lesson. So the inverse tangent of the tangent of x would be equal to x for x being greater than negative pi over 2 and less than pi over 2. In other words, I have to plug something in for x that's in the domain of the restricted tangent function for these guys to undo each other. You could also think about it as the range from the inverse tangent function, which is pretty easy to think about on the unit circle. Remember, that's from negative pi over 2 to pi over 2, with both being excluded. So I'm going to stop a little bit short there. So from negative pi over 2 to pi over 2, again, with those guys being excluded. So when you think about your problem, the inverse tangent of the tangent of 7 pi over 3, you could just look at your unit circle and say, well, is 7 pi over 3 in the range of the inverse tangent function? No. So it's impossible for me to take the inverse tangent of this and get 7 pi over 3 out. I've got to get something in this interval right here, again, from negative pi over 2 to pi over 2, with both being excluded. So what you could do here is find the tangent of 7 pi over 3. That's one strategy. So that's going to be coterminal with pi over 3. Let me just show that real quick. So 7 pi over 3 minus 2 pi. Let's write that as 6 pi over 3. So this would be pi over 3. So if we think about what the tangent of 7 pi over 3 is, let's put this as the inverse tangent of the tangent of pi over 3. So that's the coterminal angle. So the shortcut here is just to say, okay, well now pi over 3, which is right here, that's in the interval from negative pi over 2 to pi over 2, with both being excluded. So these guys would undo each other. So you could just say that this is pi over 3 and be done with it. The other way, or the longer way here, would be to say that, again, I have the inverse tangent. So the inverse tangent of the tangent of 7 pi over 3. And I could just evaluate the tangent of 7 pi over 3. Again, it's coterminal with pi over 3. So I could say that the tangent of 7 pi over 3 is equal to the tangent of pi over 3. And most of you know that square root of 3, and that's coming from the sine value, which is square root of 3 over 2, divided by the cosine value, which is 1/2. So I'm going to multiply by the reciprocal. So this is times 2 over 1. These cancel, and you get the square root of 3. So if I know that the tangent of 7 pi over 3 is square root of 3, then all I'm going to do is say this is equal to the inverse tangent of the square root of 3. And again, now I'm just looking in that interval for an angle with a tangent value of square root of 3, and I know that's going to occur at pi over 3. So this is a bit of a longer approach, but if you get this situation, just look at your angle and say, is it in the domain of the restricted tangent function or the range of the inverse tangent function? And if it is, you could just take that as the answer. If it's not, you have to do additional work. All right, let's take a look at problem 2. So here we have the inverse sine of the sine of negative 17 pi over 6. So remember that the inverse sine of the sine of x is equal to x for x being greater than or equal to negative pi over 2 and less than or equal to pi over 2. Now, where does this come from? Again, this x here has to be in the domain of the restricted sine function, or you could say the range of the inverse sine function. In other words, if I come to the unit circle, my range for the inverse sine function is from negative pi over 2 to pi over 2. So this is what I'm going to get out. So if I write my problem, so the inverse sine of the sine of a negative 17 pi over 6, well, I can't get negative 17 pi over 6 out from the inverse sine function. It's got to be from negative pi over 2 to pi over 2, with both being included. So what you'd have to do is either figure out what is the sine of negative 17 pi over 6, and then take the inverse sine of that. You could do it that way. Or you could put this in terms of an angle that's in this interval that has the same sine value of negative 17 pi over 6, and then you could do the cancellation property with that. So let's just go ahead and do both ways. So the first thing is I'm going to find the coterminal angle. So here's negative 17 pi over 6. If I added 2 pi, that would be 12 pi over 6. That would give me negative 5 pi over 6. So what I'm going to actually do is add 4 pi. So I'm going to add 24 pi over 6. And so now negative 17 pi plus 24 pi, that's 7 pi. So over the common denominator of 6. So I get 7 pi over 6. That's the coterminal angle. So that's going to be right here. Now, this is, again, not in the interval from negative pi over 2 to pi over 2. So what you could do at this point is just say, well, the sine of 7 pi over 6 is going to be negative 1/2. So you could say that this is equal to the inverse sine of, and let me write this out as the sine of 7 pi over 6. So nobody's lost in terms of where this is coming from. We know the sine of 7 pi over 6 is negative 1/2. So this is the inverse sine of negative 1/2. And of course, if I'm looking for the inverse sine of negative 1/2, again, I'm looking from negative pi over 2 to pi over 2, with both being included, for where I have a sine value of negative 1/2. So that's going to be right here. We see that it's 11 pi over 6, but again, in this situation, I want to rotate clockwise. So I want to rotate clockwise like this. So I don't want 11 pi over 6. I want negative pi over 6. So this right here would be equal to negative pi over 6. So that's one way to do it. The other way to do it, an alternative approach, once you realize that the sine of negative 17 pi over 6 is equal to the sine of 7 pi over 6, well, these guys are both going to be in quadrant 3, right? So we know that they're going to be right there. I can find an angle in quadrant 4 where sine is also negative, to where it's going to be in this interval here and then I can use my cancellation property. And let me just put that this equals the sine of 11 pi over 6. So I'm in quadrant 4 where sine is negative, and I have a pi over 6 reference angle, so the sine value would be the same. But again, because this guy right here is not in the interval, I would need to subtract away 2 pi from this. So subtract away 12 pi over 6. So this would be equal to the sine of negative pi over 6. So all of these have the same sine value. So what you could do is say that the inverse sine of the sine of negative 17 pi over 6 is equal to the inverse sine of the sine of a negative pi over 6. Again, the sine of negative 17 pi over 6 and the sine of negative pi over 6 are the same. In each case, you get negative 1/2. Once I put it in terms of this guy right here, that's in the interval from negative pi over 2 to pi over 2 with both being included, now I can just take the angle there as the answer. So now this would just be negative pi over 6. So 2 different ways to do it. It's really up to you what you want to do. All right, let's take a look at problem 3. So here we have the inverse cosine of the cosine of negative 7 pi over 5. Again, we use the rule from the lesson. So the inverse cosine of the cosine of x is equal to x for x is greater than or equal to 0 and less than or equal to pi. So again, this x right here would have to be in the domain of the restricted cosine function, or you could also think about it as being in the range of the inverse cosine function. So what I'm going to do is come to the unit circle again. I think it's a good way to visualize this. So the range again is going to be from 0 to pi, with both being included. So let's think about the inverse cosine of the cosine of negative 7 pi over 5. So this angle right here is not on the unit circle. I had to actually draw this in right here. So let me draw this in a different color here so you can see this. So first off, if I look at this rotation right here, this is going to be 3 pi over 5. And the way I'm getting that is I have negative 7 pi over 5, and then plus, I'm going to add 2 pi to that, so 10 pi over 5, and that's going to be 3 pi over 5. So that's this rotation here. The original angle, the negative 7 pi over 5, that's basically me taking a clockwise rotation, so this guy right there, so that angle would be negative 7 pi over 5. But again, this is not in the interval from 0 to pi with both being included, so you really want to put it in terms of this coterminal angle, the 3 pi over 5. So let me get rid of this. And in case you're curious, you can put this in terms of degrees. It's going to give you 108 degrees. Let me go ahead and show that real quick in case you're curious. So 3 pi over 5, you can always multiply this by 180 degrees over pi. And so the pi's would cancel. 180 divided by 5 is 36, and 3 times 36 is 108. So this would be 108 degrees. And you can see we're in quadrant 2, so that's consistent with what we found. Let me get rid of that. And so let's say this is equal to the inverse cosine of the cosine of, again, the coterminal angle here is going to be 3 pi over 5. And now because the 3 pi over 5 is in the interval from 0 to pi, with both being included, these guys would undo each other. And you could just say that it's going to be 3 pi over 5. All right, let's change things up in terms of the instructions. So now we want to solve each equation for x is greater than or equal to 0 and less than 2 pi. Okay, let's take a look at problem 4. So we have negative 2 cosecant of, you have x over 3 plus 3 pi over 4, and this equals negative 4. Now, we've looked at different strategies for solving this in this section. What I'm going to do here is use the inverse cosecant function. Sometimes you have to do this because you'll get a problem where you can't use the unit circle, and you have to approximate things with your calculator. So the first thing I'm going to do is isolate the cosecant of this guy right here. So the cosecant of this x over 3 plus 3 pi over 4, we want that to be equal to some number. Now what I see is that negative 2 is multiplying this guy. So I'm just going to divide both sides of the equation by negative 2 just to get things started. So of course this would cancel with this. And so you would have the cosecant of this x over 3 and then plus 3 pi over 4. This would be equal to negative 4 over negative 2 is 2. Let me make that a little bit cleaner there. So this over here would be 2. Now, let me go ahead and grab this, and let me come to a fresh sheet and paste this in. In the past, you'd make a little substitution here, and you'd solve it that way. But what I'm going to do is actually just take the inverse cosecant of each side. So I'm going to take the inverse cosecant of the cosecant of this x over 3 plus 3 pi over 4. And then this equals the inverse cosecant of 2. Now the problem is that you're only going to get one answer here, because if you think about the inverse cosecant of 2, again coming to the unit circle, if you look at the inverse cosecant function, you're getting something from negative pi over 2 to pi over 2. Those guys are included. Remember, 0 is excluded from that. You could also convert this over and say that the inverse cosecant of 2 is equal to the inverse sine of the reciprocal of this, which is 1/2. You know that that's going to be pi over 6. Let me actually highlight from negative pi over 2 to pi over 2. So that's where we're looking here. Again, both would be included. And so with this one, again, a sine value of 1/2 is going to occur right there at pi over 6. So this is pi over 6. Here's the problem. You also have a sine value of 1/2 over here at 5 pi over 6, and this is not going to get returned to you by your calculator as an answer. So you have to know that it would be pi over 6 and then 5 pi over 6. Also, if you're trying to find the general solution, remember things in terms of cosecant or sine, they repeat every 2 pi. So you could put pi over 6 plus 2 pi n and then 5 pi over 6 plus 2 pi n. So coming back, let me go ahead and set this up. I'm going to show this as canceling with this, and I'm going to say that I have x over 3 plus 3 pi over 4 is equal to, again, from the calculator, I'm going to get pi over 6. And if you want the general solution, you could just put plus 2 pi n. I'll just give that even though we weren't asked for it. And then the other one you'd have to do is x over 3 plus 3 pi over 4 is equal to, again, I have a cosecant value of 2 at 5 pi over 6 as well. So I'm going to say 5 pi over 6 and then plus 2 pi n. So let me actually grab these real quick. So I'm going to actually split things up and just work on each one at a time. So we want to solve for x. That's the goal. So the first thing is go ahead and subtract 3 pi over 4 away from each side of the equation. And this is going to cancel. You're going to have x over 3 is equal to, you'll have pi over 6 and then minus 3 pi over 4, and then you have plus 2 pi n. Now you need a common denominator here. You have 6 and you have 4. So 6 is 3 times 2, 4 is 2 times 2. So what you want is 2 times 2 times 3, or 12. So I'm going to multiply this by 2 over 2, and this by 3 over 3. So this would be 2 pi over 12. So 2 pi over 12. And then over here, this would be 9 pi over 12. So 9 pi over 12. And so 2 pi over 12 minus 9 pi over 12, that's going to be negative 7 pi over 12. So this is negative 7 pi over 12. And then you have this plus 2 pi n. Now, I want x by itself. So I'm going to multiply both sides by 3. So just multiply everything here by 3. Let me slide down a little bit. So of course, this is going to cancel with this. So now I have x is equal to, if you think about 3 and 12, 12 divided by 3 is 4. So this becomes negative 7 pi over 4, and then plus 2 pi n times 3 would be 6 pi n. So this is one solution in terms of the general solution. Let me go ahead and grab this real quick. So let me bring this down here to this little sheet, and now I'm going to come back up here and work on this one. So I'm going to subtract 3 pi over 4 away from each side of the equation. So of course, this right here is going to cancel. You're going to have x over 3 is equal to 5 pi over 6, and then minus 3 pi over 4, and then plus the 2 pi n. Now, when I look at this, again, the common denominator, or the least common denominator, is going to be 12. So multiply this by 2 over 2, multiply this by 3 over 3, and so this would be 10 pi over 12. So 10 pi over 12. And then this right here would be 9 pi over 12. So 9 pi over 12. And of course, 10 pi minus 9 pi is pi. So this is pi over 12. So this right here is pi over 12. Now, I want to get x by itself, so I'm going to multiply everything here by 3. So just multiply both sides by 3. This cancels. You get x is equal to, with 12, if you divide that by 3, you get 4. So this is pi over 4 plus 2 pi n times 3 is going to be 6 pi n. So let me go ahead and grab this. Let me come down here and paste this in. So I'm just going to put a comma and then just move this in here. So if you wanted the general solution, you could list it like this. So you could put pi over 4 plus 6 pi n, where n is any integer. And then this one, what I would prefer to do is actually put this in terms of something that's positive. So just take negative 7 pi over 4 and add 6 pi to that. So that's going to be 24 pi over 4. So this would give me 17 pi over 4 and then plus 6 pi n. So you don't have to do this step. It's up to you. You could actually list negative 7 pi over 4 plus 6 pi n. Perfectly valid. This is just something that's personal preference for me. Now, in terms of the interval we were given, we said that x was greater than or equal to 0 and less than 2 pi. Well, in this case, x is just going to be pi over 4 and that's it. Okay, so to wrap up this problem, I'm just going to look at the graph with you real quick. This is completely optional, but if you want to go to Desmos, you could type in y equals -2 cosecant of x over 3 plus 3 pi over 4. Make sure to wrap that in parentheses, and then plus 4. So where did this come from? Again, we started with -4 is equal to -2 cosecant of x over 3 plus 3 pi over 4. If you add 4 to both sides, you could say this is 0, and this is plus 4 over here. So now this matches this. And all you're doing is you're taking this 0 and you're plugging it in for y. And you're saying, okay, when that happens, for which x values am I going to get a y value of 0? In other words, where are the x-intercepts? So those guys, those x values would actually satisfy the equation. So here you have that -7 pi over 4 that we found. And here you have that pi over 4 that we found as well. And we know that the period for this guy is going to be 6 pi. So things repeat every 6 pi. So if you take -7 pi over 4 and you add 6 pi, you get that, and this is covered up here. Let me actually erase this so you can see this more clearly. You get this solution here, which is 17 pi over 4. Again, we saw that earlier when we were listing our solution. And then you could take the pi over 4, add 6 pi, you would get to that 25 pi over 4. You could do this in your head, pi over 4 plus 24 pi over 4. That would be 25 pi over 4. All right, let's take a look at problem 5. So here we have 4 cosine of x over 2 plus pi over 4. This equals -2 times the square root of 3. So again, if you get a problem like this, you would first isolate the cosine of whatever it is. In this case, it's x over 2 plus pi over 4. So you want that on one side and a number on the other. So this right here is what I want to isolate. So to do that, I'm just going to divide both sides of the equation by 4. So this right here is going to cancel with this right here. Let me slide down. We'll say that the cosine of this x over 2 plus pi over 4. Let me make this s a little bit better there. This is equal to, now looking at the 2 and the 4 here, 4 divided by 2 is 2, and 2 divided by 2 is 1. So this would be negative square root of 3 over 2. So let me grab this real quick, and let me come down here and just paste this in. Now again, this is something we already know how to solve. You could use a substitution technique if you want, but what I'm going to do here is just take the inverse cosine of both sides. So let's say we have the inverse cosine of this guy right here. So the cosine of x over 2, then plus pi over 4. So close that down. And this equals, again, I've got to do this over here as well. So the inverse cosine of the negative of the square root of 3 over 2. When you think about the inverse cosine, again, I'm getting something from 0 to pi where 0 and pi are both included. So I want the inverse cosine of the negative of the square root of 3 over 2. So because this is negative here, I want to look in quadrant 2. So where is the cosine value, negative square root of 3 over 2? So right there, and the associated angle is 5 pi over 6. So this right here would be 5 pi over 6. You also have in quadrant 3 an angle, which is going to be 7 pi over 6, that also has a cosine value of negative square root of 3 over 2. So that's for 7 pi over 6. So you got to keep these two things in mind. So you have 5 pi over 6, and then if you're finding the general solution, you'd say plus 2 pi n, where n is any integer, and then 7 pi over 6, again, plus 2 pi n, where n is any integer. So let's come back up, and let's set this up. So I'm going to come down here, and I'm going to cancel this with this, and I'm going to say I have x over 2 plus pi over 4, and then this equals, again, from the calculator, you could get the 5 pi over 6, and then you could say plus 2 pi n, where n is any integer. Then the other one, again, you can't get this from the calculator. You have to go into quadrant 3 and say what angle also has a cosine value of negative square root of 3 over 2. Again, I'm looking for an angle in quadrant 3 with a reference angle of pi over 6. It's going to be 7 pi over 6. So it's going to be x over 2 plus pi over 4 is equal to, again, the 7 pi over 6 plus 2 pi n. You don't need the plus 2 pi n if you're not trying to find the general solution. I'm just doing it for completeness. So let me go ahead and grab this real quick. And let's just, again, do this one at a time. So my goal is to isolate x. So I'm going to start by just subtracting pi over 4 away from each side of the equation. So that cancels. You get x over 2 is equal to, you're going to have 5 pi over 6, and then basically minus pi over 4, and then plus 2 pi n. So in the last problem, we had a denominator of 6 and a denominator of 4, and we found that the least common denominator was 12. 6 is 3 times 2, 4 is 2 times 2, so the LCD is 2 times 2 times 3, or 12. So here times 2 over 2, and then here times 3 over 3. So this would end up giving me x over 2 is equal to, this would be 10 pi over 12, and then minus this would be 3 pi over 12, and then plus 2 pi n. And let me just slide this up here. So I'm going to say that I have x over 2 is equal to 10 pi minus 3 pi is 7 pi. So this would be 7 pi over 12, and then plus your 2 pi n. Now to get x by itself, I'm going to multiply both sides of the equation by 2. And so now this is going to cancel, and I'm going to get that x is equal to 12 divided by 2 is 6, 2 divided by 2 is 1. So this is 7 pi over 6 plus 2 pi n times 2 would be 4 pi n. So that's one solution. Let's go ahead and grab this real quick. Okay, let me just bring this here and I'm going to drop this off. And now let me go to the other side. And I'm just going to, again, solve for x. So I'm going to subtract pi over 4 away from each side of the equation. This cancels. You get x over 2 is equal to, you'd have 7 pi over 6, and then minus pi over 4, and then plus your 2 pi n. So here again, the least common denominator would be 12. So I'm going to multiply this by 2 over 2, and I'm going to multiply this by 3 over 3. So let's say this is x over 2 is equal to, the 7 pi times 2 would be 14 pi, and this is over 12, and then minus 3 times pi is 3 pi, and then this is over 12, and then plus your 2 pi n. So let's say that we have x over 2 is equal to 14 pi minus 3 pi would be 11 pi. So this is 11 pi over 12, and then plus 2 pi n. Now again, if I want to solve for x, I'm just going to multiply both sides of the equation by 2. And so this is going to cancel. You get x is equal to 12 divided by 2 is 6. And so this is 11 pi over 6. And then plus 2 pi n times 2 is just going to be 4 pi n. Okay, let me come down here and paste this in. And I'm just going to merge these two. So bring this up here. Again, if you want the general solution, you could list this. We weren't asked for that, but let's just put this in. So 7 pi over 6 plus 4 pi n, where n is in the integer, and then 11 pi over 6 plus 4 pi n, where n is in the integer. So this is your general solution. If you want what we were asked for, which is x is greater than or equal to 0 and less than 2 pi, what are we going to have? Well, 7 pi over 6 is in this interval. So let's say x is equal to 7 pi over 6. And then 11 pi over 6 is also in this interval. So let's put 11 pi over 6. So that's the solution we're looking for in terms of the practice test. All right, so what I want to do is just look at the graph with you. Again, this is completely optional, but you can go to Desmos and just type in y equals 4 cosine of this x over 2 plus pi over 4. Make sure to wrap that in parentheses and then plus 2 times square root of 3. Again, where does this come from? We started with negative 2 times the square root of 3 is equal to 4 cosine of this x over 2 plus pi over 4. If I add 2 times square root of 3 to both sides, well, over here I would have 0, and over here I would have plus 2 times square root of 3. Now this matches this. The only difference is I have a 0 here, whereas here I have a y. So if I plugged in a 0 for that y there, I'm just asking for which x values am I going to get a y value of 0. So I'm trying to find the x-intercepts. So those x values are going to satisfy the equation. Now, let me get rid of this, and let's just look at what we have. So we have 7 pi over 6, and we have 11 pi over 6. Those are what we found from solving the equation. We also found that the period was 4 pi. And you can look at this guy, and you see you have that x over 2 there, so that's going to lead to a period of 4 pi. So things repeat every 4 pi. So if I took 7 pi over 6 and I added 4 pi, well, I'd be at that 31 pi over 6. If I took 11 pi over 6 and I added 4 pi, I'd be at this 35 pi over 6. All right, let's take a look at problem 6. So here we have 6 cosecant of 3x plus 5 pi over 6, and this equals negative 4 times the square root of 3. Again, if I'm going to try to solve this with the inverse cosecant function, first I want to isolate the cosecant of this 3x plus 5 pi over 6. So let's go ahead and divide both sides of the equation by 6. Just to get things started. So this will cancel. So sliding down here, we have the cosecant of 3x plus 5 pi over 6. And this equals, over here, if I think about 4 and 6, there's a common factor of 2. 4 divided by 2 is 2. 6 divided by 2 is 3. So this is the negative of 2 times the square root of 3 over 3. So now what I'll do is take the inverse cosecant of each side. So let's say we have the inverse cosecant of the cosecant of 3x plus 5 pi over 6. And this equals the inverse cosecant of the negative of 2 times the square root of 3 over 3. Now for this, I would convert it over and say that we want the inverse cosecant of this, again, negative 2 times square root of 3 over 3. I would say this is equal to the inverse sine of, again, you could just take the reciprocal of this. So negative 3 over 2 times the square root of 3. And 3 you could write as the square root of 3 times the square root of 3. And so now I can cancel this square root of 3 with this square root of 3. So this becomes the negative of the square root of 3 over 2. So let me actually just grab this real quick and come down here and paste this in. Let me put that in there. Again, if I'm working with the inverse sine function, I'm looking from negative pi over 2 to pi over 2 with both being included. If you want to work with the inverse cosecant function, if you're more comfortable with that, remember it's negative pi over 2 to pi over 2. Both of those are included, but 0 would be excluded there. Now for this one, I'm just looking for an angle, and this is going to be in quadrant 4, where the sine value is negative square root of 3 over 2. Well, here is my negative square root of 3 over 2. And again, do I take 5 pi over 3? No, because I need to rotate clockwise. So I want to rotate like this clockwise. The reference angle there is pi over 3. So this is negative pi over 3. Again, you can also get that by going 5 pi over 3 minus 2 pi. So you can always go 5 pi over 3 minus, let's go 6 pi over 3. And again, that's another way to get negative pi over 3. So whatever you want to do there. So let me put here that this is negative pi over 3. When we look in quadrant 3, where sine is also negative, where do I have a sine value of negative square root of 3 over 2? Well, it's going to be right here. And that's at 4 pi over 3, again, where I have a reference angle of pi over 3 as well. So let's go back up and let's fill this in. So this right here is going to cancel with this right here. And you're going to have 3x plus 5 pi over 6 is equal to. So for this one, you can use the answer from the calculator. You're going to have to think about things because this is going to end up giving you something that's negative. So you could put 5 pi over 3 plus 2 pi n here, and you'll end up with something that's positive. Or you can go with the calculator, which is negative pi over 3 like this. In either situation, as long as you're putting the plus 2 pi in for this particular problem, you'll be good to go. You'll be able to adjust things and get it into the interval that you want. But it's a little bit easier if we start with this one. So I'll let you do the negative pi over 3 on your own if you want. I'm just going to use the coterminal angle in this particular case. Now you also need the guy in quadrant 3, again, where the cosecant value is negative 2 times square root of 3 over 3, where the sine value is negative square root of 3 over 2. So that's going to be the 4 pi over 3 that we found. So let's go 3x plus 5 pi over 6 is equal to 4 pi over 3, and then plus 2 pi n. All right, so let me go one at a time. And actually, I'm going to do this both ways so you can see what I'm talking about. So 3x plus 5 pi over 6 is equal to, again, you can use 5 pi over 3, or you can use negative pi over 3. At the end of the day, it's going to be the same thing. You have that plus 2 pi n there, so you can adjust things to put it in the interval that you want. So in each case, I'm going to subtract 5 pi over 6 away from each side of the equation. Let me actually just move this down. I'll do this separately. So this would cancel. You're going to have 3x is equal to 5 pi over 3 minus 5 pi over 6, and then plus 2 pi n. So here I need a common denominator. So I'd multiply this by 2 over 2. So this would be 10 pi over 6. So this is 10 pi over 6. So 10 pi over 6 minus 5 pi over 6 is 5 pi over 6. So this right here would be 5 pi over 6. So at this point I have 3 that's multiplying x. So to get rid of that, I'm just going to divide both sides by 3, or you can just multiply both sides by a third. I think that's a little bit easier because you have a fraction involved. So let's go ahead and do that. So we can see that this would cancel. So you get x is equal to, if I think about 5 pi over 6 times a third, that's going to be 5 pi over 18. And then plus here, 2 pi n times a third is 2 pi over 3 times n. And just in case you're a little bit lost in terms of why we're able to use 5 pi over 3 or negative pi over 3, again, if I go ahead and solve this, I'm going to get something different in this position. It's going to be negative. But again, because I know that I can add 2 pi over 3 times n, where n is any integer, I can adjust things to get it in the interval that I want. So what I want to do here is just subtract 5 pi over 6 away from each side of the equation. So that would cancel. You get 3x is equal to, so you have negative pi over 3. And then again, if I'm subtracting away 5 pi over 6, let me just multiply this by 2 over 2 now, and then minus 5 pi over 6, and then plus 2 pi n. So you're going to have 3x is equal to negative 2 pi minus 5 pi over 6, and then plus 2 pi n. Well, negative 2 pi minus 5 pi is negative 7 pi, so this becomes negative 7 pi over 6. And at this point, I'm going to multiply everything by a third. So multiply this by a third, multiply this by a third, and multiply this by a third. So this cancels, and you're going to get x is equal to, so negative 7 pi over 6 times a third is negative 7 pi over 18. And then plus, again, you get the 2 pi over 3 times n. If you started with the negative pi over 3, So what comes from your calculator, you're going to get this. If you change it into the coterminal angle, the 5 pi over 3, you're going to get this. Again, because you have this part right here, this 2 pi over 3 times n, you can adjust this to get into this. So I can say negative 7 pi over 18 plus, for 2 pi over 3, if I multiply by 6 over 6, I would have 12 pi over 18. So this equals what? Well, 12 pi minus 7 pi is 5 pi. So this is 5 pi over 18. So you can see that these solutions are going to match up. Again, because you have this 2 pi over 3 times n, where n is any integer, you can achieve this 5 pi over 18, and then anything else that you could get from this solution. And we're going to deal with this one now. So I'm going to subtract 5 pi over 6 away from each side of the equation. So that cancels. You have 3x is equal to, you have 4 pi over 3. I'm just going to multiply this by 2 over 2 now. So we have a common denominator, and then minus 5 pi over 6, and then plus 2 pi n. Okay, let me get rid of this and put a 5 here. All right, so looking at this, we know that 4 pi times 2 is 8 pi. So this would be 8 pi over 6. So 8 pi over 6. And then you're subtracting away 5 pi over 6. So that would be 3 pi over 6. So 3 pi over 6, which of course is going to be pi over 2. So this is pi over 2. I want to get rid of this 3. So let's multiply everything by a third, or you could divide everything by 3, whatever you want to do. And so we're going to end up with this canceling, and you get x is equal to, your pi over 2 times a third is pi over 6, and then plus 2 pi n times a third is 2 pi over 3 times n. So let's grab this. Let me come back up here. Let me get rid of this, put a little comma, and throw this in here. This would be for the general solution. You could list it this way. So you could say that for the general solution, you're going to have pi over 6 plus 2 pi over 3 times n. And then you have 5 pi over 18 plus 2 pi over 3, and make that 3 a little bit better, times n. Now, when it comes to finding the solution in the interval, for this particular one, there's a lot of work you have to do. So we're going to say that x is greater than or equal to 0 and less than 2 pi. Well, what's going to happen is I'm going to start by saying x is equal to pi over 6. And then I've got to take pi over 6, and I've got to add 2 pi over 3. So let's do that as 4 pi over 6. I'm just multiplying this by 2 over 2. That's it. So that would be 4 pi over 6. So this becomes 5 pi over 6. So this becomes 5 pi over 6. And then the other one, you would take 5 pi over 6, and you would add 4 pi over 6. So 4 pi over 6. And that would give me 9 pi over 6. So 9 pi over 6. And of course, you can simplify that. So 9 divided by 3 is 3, and 6 divided by 3 is 2. So that's 3 pi over 2. Now, if you take 3 pi over 2 and you add another 2 pi over 3, you're going to be outside of this interval. So we're going to stop on that one. Now you need to come over to this one, and you want to go 5 pi over 18, and you want to add 2 pi over 3. So I'm just going to multiply this by 6 over 6. So I'm going to say this is 12 pi over 18. So that would be 17 pi over 18. So this is, first let me list the 5 pi over 18, and then I'm going to list 17 pi over 18. And then we're going to do this once more. So you're going to take your 17 pi over 18, and you're going to add another 12 pi over 18. Again, I'm just taking 2 pi over 3 and I'm multiplying it by 6 over 6. So that would be 12 pi over 18. So 17 pi plus 12 pi, that's going to be 29 pi over that common denominator of 18. So this is 29 pi over 18. So a lot of solutions there. If you add another 2 pi over 3 to that one, you're going to be outside of this interval. So these are your solutions. You could rearrange them in order if you want. Some teachers want you to do that. I would just list it like this and be done with it. We are going to look at the graph, so let's go there now. All right, so once again, you can go to Desmos and make your own graph. So this is something I suggest you do when you first start, but it's completely optional. So if you start with negative 4 times the square root of 3 is equal to 6 cosecant of 3x plus 5 pi over 6. Again, if you add 4 times square root of 3 to both sides, this would be plus 4 times square root of 3 over here, and over here this would be 0. So essentially you're just plugging in a 0 for that y there, and you're saying for which x values am I going to get a y value of 0? So those are your x-intercepts, and the x values there would satisfy that equation. So just looking at the solutions first in the interval from 0 to 2 pi, you have your pi over 6, your 5 pi over 18, your 5 pi over 6, your 17 pi over 18, your 3 pi over 2, and then your 29 pi over 18. Again, when you think about the period of this guy, it's coming from the fact that you have that 3 that's multiplying x. So the normal period for cosecant is 2 pi, but now it's going to be 2 pi over 3. So if you take something like this solution here of pi over 6 and you add 2 pi over 3, you get to this 5 pi over 6. Then you add 2 pi over 3, you get to 3 pi over 2, and so on and so forth. If you take this solution here of 5 pi over 18, again, if you add 2 pi over 3, you get to 17 pi over 18. Add 2 pi over 3, you get to 29 pi over 18, so on and so forth. And again, thinking about this one going this way, remember that if we use that calculator answer of negative pi over 3, we ended up with this right here, this negative 7 pi over 18. So if you get this as a solution, again, if you want to be in this interval here, you just need to realize your period is 2 pi over 3, and then add 2 pi over 3 to push yourself into this interval that you want. So then you can get your 5 pi over 18, your 17 pi over 18, and your 29 pi over 18. So just keep that in mind if you're solving this type of problem. All right, now let's change things up a little bit. So for the instructions, we're asked to solve each equation for exact solutions. Okay, let's look at problem 7. So here we have 4 inverse sine of x is equal to pi. And basically for this type of problem, you want to isolate the inverse sine of x first. So to do that, I'm just going to divide both sides of the equation by 4. So this right here is going to cancel. We're going to have the inverse sine of x is equal to pi over 4. Now at this point, how do you get a solution for x? Well, you could take the sine of each side if you want to. You could also just use the definition of the inverse sine function. In other words, if the inverse sine of x is equal to pi over 4, that tells me that the sine of pi over 4 is equal to x. Let me actually just move this over here, and I'm going to put a little border, and I'll do this the long way as well. So you could just take the sine of each side. So you could say the sine of the inverse sine of x, like this, is equal to the sine of pi over 4. You'll get the same thing. So basically, these guys will undo each other or cancel away as long as x is in the domain of the inverse sine function. So for the inverse sine function, again, the domain is from -1 to +1, with both being included. So this right here would be x is equal to the sine of pi over 4. So an exact match of what we have over here. So however you want to do that. Now, pretty much everyone knows at this point, if you go to pi over 4, the sine value is square root of 2 over 2. So coming back, I'm just going to replace this sine of pi over 4 with square root of 2 over 2. So we'll say x is equal to the square root of 2 over 2. Okay, let me come back up here and just check this with you. So x equals the square root of 2 over 2. So I'm just going to plug this right here in for x right there. See if we get a true statement. So we have 4 times the inverse sine of the square root of 2 over 2. Does that equal pi? The inverse sine of square root of 2 over 2 we know is pi over 4. So this right here would be 4 times pi over 4. Let me make that a little bit better there. Is equal to pi. And of course, this is going to cancel with this. And you're going to get that pi is equal to pi, which of course is a true statement. So we can say this solution here, x equals square root of 2 over 2, is valid. All right, so once again, I'm going to show you a graph for each one of these guys, just so we can get some visual confirmation of what's going on. So all I did was I took my 4 inverse sine of x is equal to pi, and I just rewrote it by subtracting pi away from each side. So again, if y was 0, I'm just asking for which x value am I going to get a y value of 0? And so that's going to be right here at this x-intercept. So your x value is square root of 2 over 2. Again, that's what we found as our solution. And the y value, of course, is 0. All right, let's take a look at number 8 now. So here we have the inverse sine of x minus pi over 3 is equal to pi over 6. So again, I want to isolate the inverse sine function first. Here that's already done for me. So the next thing you want to do, you could just take the sine of each side, or you could just use the definition of the inverse sine function. So if the inverse sine of x minus pi over 3 is equal to pi over 6, well then the sine of pi over 6 is going to be equal to this right here, this x minus pi over 3. Again, if it's more clear for you or easier to understand, then you can just say you have the sine of the inverse sine of this guy right here. So this x minus pi over 3, close that down, and this would be equal to the sine of pi over 6. So you might want to just take the sine of each side. Maybe that makes more sense. So this right here would cancel with this right here. So those guys will undo each other, and you're going to basically have the same thing as above. So x minus pi over 3 is equal to the sine of pi over 6. Okay, let me bring this to a fresh sheet. So I'm trying to isolate x and figure out what that's going to be. And basically, I'm going to add pi over 3 to each side of the equation. So that would cancel. So you get x is equal to the sine of pi over 6, which again, if you go to the unit circle, I know pretty much everyone knows this, but here's pi over 6. The sine value is 1/2. So coming back up, again, sine of pi over 6 would be 1/2, and then plus pi over 3. So it's just that simple. That's going to be your solution. Let's go ahead and grab this real quick. And I'm going to come back up here And I'm just going to check this with you. We'll also see this solution graphically, but I'm going to have to approximate this. And let me just do this now. So this is approximately. I'm just going to key this into my calculator, and I get about, let's say, 1.547. So I'm just going to stop there. Now, if you check this, you plug this guy right here. So this guy right here in for x right there. You're going to see this works out. So you have the inverse sine of, again, let's plug in 1/2 plus pi over 3 minus pi over 3. And that should be equal to pi over 6. And of course, this is going to be true because the pi over 3 minus pi over 3, that's going to cancel away. So you're going to have the inverse sine of 1/2 is equal to pi over 6. And so you get pi over 6 is equal to pi over 6. So that is a true statement. Let me make this a little bit better here. So this solution here, which is x equals 1/2 plus pi over 3, is correct. Okay, so once again, if you want to look at this graphically, you can go to Desmos, and we had pi over 6 was equal to the inverse sine of x minus pi over 3. So we just subtract pi over 6 away from each side. So again, if I replace y with 0, then I'm trying to find the x value for which the y value is 0, or I'm trying to find this x-intercept right here. And this is an approximation, so it's about 1.547. But again, if you wanted the exact answer, it's going to be pi over 3 plus 1/2. All right, let's take a look at problem 9. So here we have 4/7 times the inverse cosine of x over 4, and this equals pi. So for the first thing here, I'm going to isolate the inverse cosine of x over 4. So I'm going to just write this out. So 4/7 times the inverse cosine of x over 4, and this equals pi. So if I want to isolate this right here, what would I do? Well, I need to get rid of this 4/7 that's multiplying the inverse cosine of x over 4. So let me multiply both sides by the reciprocal of 4/7, which is 7/4. And so this right here is going to cancel. You multiply reciprocals together, and you're going to get 1. And so you're going to have the inverse cosine of x over 4 is equal to 7 pi over 4. And let me paste this in here. And I want you to think about this on the unit circle, pause the video, and just tell me if this is possible or not. So hopefully you thought about it and you realize that there's really nothing you can plug in for x that would satisfy this equation. The inverse cosine is going to have a range from 0 to pi. So where 0 and pi are both included. If you think about 7 pi over 4, that is right here. So it's impossible to plug in something for x there and get something out of that inverse cosine function that's 7 pi over 4. You're not going to be able to do it. So for this guy, you're going to say there's no solution. So coming back up, you can erase this and just say that there's no solution. Now, if you didn't realize that and you went through and you kept solving the problem, if you plug in for x, your proposed solution, it's going to get rejected. You'll end up with a false statement. Now here, you can look at the graph. All I did was subtract pi away from our equation on each side. And essentially, if you plugged in a 0 for y there, you're looking for where you have an x value such that the y value would be 0. So where do I cross the x-axis, or where are my x-intercepts? And you don't have any. Right, so you can see that the graph goes from here to here. There are no x-intercepts, so that equation that we looked at has no solution. All right, let's take a look at problem 10 now. So here we have the inverse tangent of x is equal to the inverse cosine of 5 over 13. So for these types of problems, you're going to take this guy right here. You have this known 5 over 13. You're going to let some variable be equal to this. Remember that the inverse cosine of this guy right here is an angle, and because this is positive, it's going to be in quadrant 1. So I'm just going to let something like, let's say, theta be equal to the inverse cosine of 5 over 13. And once you set that up, you can say then, based on the definition of inverse cosine, that the cosine of this theta is going to be 5 over 13. So in other words, the cosine of theta is 5 over 13. Well, then the inverse cosine of 5 over 13 is going to be theta. Additionally, I know if this argument here is positive, I'm going to be in quadrant 1. So let's say that theta is in quadrant 1. Now that we know that, we're ready to approach the problem. Essentially, you're going to take the tangent of each side. So I'm going to say that I have the tangent of the inverse tangent of x, and this equals, so I'm going to say that I want the tangent of, again, instead of the inverse cosine of 5 over 13, because that's equal to theta, I'm going to say I want the tangent of theta. We will say that this will undo this, and I have x is equal to the tangent of theta. So all I have to do is figure out what is the tangent of theta, and I've solved this problem. So what do we know? We know that the cosine of theta is, again, 5 over 13, and this right here is your adjacent, or we would say the x, you could say it like that. And this right here is your hypotenuse, or you can say your r. So if we want the tangent of theta, so the tangent of theta, again, this is your opposite, or your y, over your adjacent, or your x. Now we know the adjacent is 5. So let's go ahead and plug that in. I'll just put that right there. And that's coming from this right here. In terms of finding the opposite or the y value here, you're just going to use your Pythagorean theorem. You can make a sketch if you want. So I have a little simple sketch. So this is your adjacent. It's going to be 5. And then your hypotenuse is 13. Again, the cosine of theta is 5 over 13. So again, this is your adjacent. So that's where this guy comes from. And then this right here is your hypotenuse. Let me make that a little bit cleaner here. So this is the hypotenuse. That's where this is coming from. So we know a 5, 12, 13 right triangle, and basically that's what you're going to have. But if you just had the 5 and the 13 there, well, you would need to say, okay, x squared plus y squared equals r squared. So x is 5, r is 13, and y is going to be 12. Right, so x is 5, 5 squared plus, we don't know what y is yet, so y squared equals r is 13, so 13 squared. Let me make this 3 a little bit better. So this becomes y squared is equal to, this is 169 minus 5 squared is 25. So 169 minus 25 is 144. And here, because I'm going to be in quadrant 1, I know that y is the principal square root of 144, which is 12. So that's how I get this right here. So the opposite is 12. So coming back, I can just erase this and put 12. So x equals the tangent of theta, and the tangent of theta is 12 fifths. So x is going to be 12 fifths. All right, for problem 11, we have the inverse cosine of x is equal to the inverse sine of 8 over 17. So just like the last problem, you take this one with the known ratio in it, and you let something like theta be equal to this. So we're going to let's say theta be equal to the inverse sine of 8 over 17. And again, then we can say that the sine of theta is equal to 8 over 17. And I want to label this now. We know where we're going with this. This right here is the opposite, and this right here is the hypotenuse, or you could say the y over the r. Now, if I take the cosine of each side, I would say that I have the cosine of the inverse cosine of x is equal to the cosine of, again, the inverse sine of 8 over 17. I said that was theta, so this is the cosine of theta. So let me slide down a little bit. I'm just going to show that we're going to cancel this away and say that what we want to find, let me put a little border here, is x is equal to the cosine of theta. So what is the cosine of theta? The cosine of theta is equal to the adjacent over the hypotenuse. So I know the hypotenuse is 17 already. What's the adjacent? Again, you could just use the Pythagorean theorem. You can make a sketch. You need to know that theta is in what quadrant. Again, if this is positive and you plug it into the inverse sine function, you're going to get an angle in quadrant 1. So theta is in quadrant 1. So not necessary, but you can always make a sketch. So we know that this right here is the y value or the opposite. We know that this right here is the r value or the hypotenuse. And so basically this right here, the adjacent, which is your x, is unknown, right? So you just say x squared plus y squared is equal to r squared. And we know that y is 8, so that would be 8 squared or 64. And we know that r is 17, so 17 squared, that's going to be 289. So let me write that out. So this is 289. And so if we subtract 64 away from each side, so minus 64 over here and minus 64 over here, you're going to get that x squared is equal to 289 minus 64 is 225. And then basically, because we're in quadrant 1, the x values are positive here. And so we want to say that x is the principal square root of 225, which is 15. So that's where that's coming from. Again, a lot of you know this is a special right triangle, so 8, 15, 17, but you can always make a sketch if you need it. So the adjacent here is going to be 15. So the cosine of theta is 15 over 17. And again, you could just say that x is equal to, again, the cosine of theta, which is 15 over 17. All right, let's look at one more of these. So for problem 12, we have the inverse cotangent of x is equal to the inverse secant of 13 over 12. So coming down here, we have the inverse cotangent of x is equal to, I'm going to let, again, something like theta be equal to the inverse secant of 13 over 12. So let's let theta be equal to the inverse secant of 13 over 12. So this right here, we could say it's equal to theta. Now let me slide down here a little bit, and I'm just going to come over here and say then we know that the secant of theta is equal to 13 over 12. And basically, I know with secant, it's going to be hypotenuse over adjacent. So again, it's the reciprocal of the cosine function. So it's hypotenuse over adjacent. So now let's just take our inverse cotangent of x is equal to theta, and let's take the cotangent of each side. So I'm going to say that I want the cotangent of this, and that will be equal to the cotangent of theta. So let's say that this is going to undo this, and we have x is equal to the cotangent of theta. Okay, let me erase this. We don't really need it anymore. So what is the cotangent of theta? The cotangent of theta is equal to, again, it's the reciprocal of the tangent of theta. And with the tangent of theta, you have your opposite over adjacent. So the cotangent of theta is your adjacent over your opposite. Now we know the adjacent at this point is going to be 12. So let's just write that in there. So this would be 12. But what's the opposite? Well, again, you know you're working with a 5, 12, 13 right triangle. So the opposite is going to be 5. But I'll go ahead and show you that with a little sketch in a moment. Again, you also want to note, let me put this down here, that because this guy is positive, the inverse secant function is going to give you something in quadrant 1. So let's say that theta is in quadrant 1. That way you can sketch your triangle. So once again, you have a 5, 12, 13 right triangle. So we know that the adjacent is 12. Again, that's your x, or you could say your adjacent. We know the hypotenuse, which we'll call that r, is 13. This is the one we need to find. That's your opposite or your y. And so basically, you just say x squared plus y squared is equal to r squared. So x here is 12. 12 squared is 144. And then plus, we don't know what y is, so let's just say y squared is equal to r is 13. So 13 squared is 169. If you subtract the 144 away from each side, you're going to get y squared is equal to 169 minus 144 is 25. And then again, I'm in quadrant 1, so y values are positive. So y equals the principal square root of 25, which is 5. So that's how you get this opposite here of 5, or a y value of 5. So coming back, again, we've already filled this in. 12 is your adjacent and 5 is your opposite. So x equals the cotangent of theta. Again, this is going to be 12 fifths. So that's going to be your answer. All right, let's take a look at problem 13. So for this problem, we have the inverse cosine of x minus the inverse sine of x, and this equals 7 pi over 6. So generally speaking, when you see a problem like this in your textbook, you can do it the longer way, and that's generally where they're going to guide you through it. Or you can do this using a little shortcut with an identity. So let's do it that way first, so we'll know what the answer is, and then I'll go through it with you the longer way, and I'll actually do that twice, so you can fully understand what's going on. So coming down here, we have a little identity that we can use for this problem. So we have the inverse sine of x plus the inverse cosine of x is equal to pi over 2. All you want to do is solve this identity for one of these guys. So you could solve it for the inverse sine of x, or you could solve it for the inverse cosine of x. In this particular case, it's a little bit easier to solve for the inverse sine of x. I would just subtract the inverse cosine of x away from each side of the equation. So that would give you the inverse sine of x is equal to, you'd have pi over 2 minus the inverse cosine of x. So the idea is that this right here matches this right here. So I'm going to take this guy right here, which the inverse sine of x is equal to, and I'm going to plug it in for this guy right here. If I do that, I'm going to have an inverse cosine of x and an inverse cosine of x, and I'll be able to get my solution really quickly. To set this up, we're going to keep the inverse cosine of x here, and then minus, here's where you have to be careful. I'm subtracting this whole thing away. So go ahead and put some parentheses there. You can even write this right now as plus and then -1 times this to make it clear that you need to distribute the -1 to remove the parentheses. And then I'm going to put this pi over 2 minus the inverse cosine of x inside those parentheses. And then this equals 7 pi over 6. And let's just come to a fresh sheet so we can work. So I'm going to copy the inverse cosine of x. And then basically you have this -1 that's going to get distributed to each guy inside of the parentheses. So -1 times pi over 2 is negative pi over 2. And then -1 times negative inverse cosine of x would be plus inverse cosine of x. And this equals 7 pi over 6. So you have inverse cosine of x plus inverse cosine of x. That is going to be 2 inverse cosine of x. And then here, let me actually slide this down so we can see this. I would add pi over 2 to both sides of the equation. So over here, I need a common denominator. So let me multiply this by 3 over 3. So basically, you would have 2 inverse cosine of x is equal to, let me show this is canceling. You would have 7 pi plus 3 times pi is 3 pi over the common denominator of 6. 7 pi plus 3 pi is 10 pi. So this right here is 10 pi over 6. Now, what we're going to do is simplify this. 10 divided by 2 is going to be 5, and 6 divided by 2 is going to be 3. So this right now is 2 inverse cosine of x is equal to 5 pi over 3. Let me just erase that and fix that. And then basically, what you'd want to do is isolate this right here. So you could divide both sides by 2, or since you have a fraction involved, it's probably easier to multiply both sides by 1/2 to show it that way. So this is going to cancel. So now I have the inverse cosine of x is equal to, you would have 5 pi over 3 times 1/2, which is 5 pi over 6. So again, throughout this practice test, we've already seen how to solve something like this. You could take the cosine of each side. If you're more comfortable with that, you can do it that way. Or again, you could just use the definition of the inverse cosine function and just say that if the inverse cosine of x equals 5 pi over 6, well then the cosine of 5 pi over 6 is equal to x. Again, if you want to see it the long way, you can always go cosine of the inverse cosine of x, like this, is equal to the cosine of 5 pi over 6. It's the same thing. In other words, this and this, those are going to cancel, and you're going to be left with that x there, and that equals the cosine of 5 pi over 6. Now, the cosine of 5 pi over 6, hopefully you know that at this point. Here's your 5 pi over 6, and the cosine value is negative square root of 3 over 2. So I can finish up this problem and say that x is equal to negative square root of 3 over 2. If I plug in a negative square root of 3 over 2 here, so in other words, if I have the inverse cosine of the negative of the square root of 3 over 2, I already know, let me move this out of the way, I already know that this is going to be 5 pi over 6. So this becomes 5 pi over 6, and then minus here, this is the inverse sign of the negative of the square root of 3 over 2. So most of you know this is going to be negative pi over 3. So you'd have minus a negative pi over 3. Let me show that. That will end up being plus pi over 3. And this would be equal to 7 pi over 6. Now, let me show you this real quick. Again, when we think about the inverse sine function, so it's from negative pi over 2 to pi over 2, with both being included. And again, where's the sine value? Negative square root of 3 over 2. Well, that's going to be right there. But again, I do not want 5 pi over 3. I need to rotate clockwise. So I need to rotate clockwise like this. So I want to put that as negative pi over 3. Okay, so coming back, we know this is negative pi over 3. And now let's just check it. This seems to be getting in the way. So let me move this over here and put a little border here. And so we would have 5 pi over 6 minus the negative is plus a positive, so plus pi over 3. I need a common denominator, so let me multiply this by 2 over 2. So this would be plus 2 pi over 6. So 2 pi over 6. Does that equal 7 pi over 6? Yes, it does. You get 7 pi over 6 is equal to 7 pi over 6. So this x equals negative square root of 3 over 2 is a valid solution. Okay, if you want to go to Desmos and look at the graph, you can type in y equals the inverse cosine of x minus the inverse sine of x minus 7 pi over 6. So I just started with my equation and I subtracted 7 pi over 6 away from each side. So of course that would give you a 0 over here. So if you plugged in a 0 for y, you're just asking for which x value. Am I getting a y value of 0? So where is the x-intercept? And that's going to be right there. So your x-coordinate there is negative square root of 3 over 2. And of course, the y-coordinate is 0. So that's another way you can verify your solution. All right, let's take a look at this problem using a different approach. So now we're going to use the more tedious method, the method you'll probably see in your textbook where we don't use an identity. I'm just going to tell you if you're on a test, don't use this method. Just use the identity and solve the problem. And then for self-study, or if you're trying to really figure out where stuff is coming from, that's where you want to turn to this approach. We know that x is equal to negative square root of 3 over 2. We should also know that the inverse cosine of x, again, negative square root of 3 over 2 is our x, that's 5 pi over 6. So this is an angle in quadrant 2. We know that. So let me put that this is going to be beta, and this is going to be in quadrant 2. We're just going to use this for reference as we work through the problem. And then the inverse sine of x, again, x is negative square root of 3 over 2. That is negative pi over 3. So I'm going to end up calling this theta. And this is going to be in quadrant 4, rotating clockwise. Now, with that being said, let's go ahead and start the problem. So the very first thing you're going to do is isolate one of these guys. So I'm going to start by isolating the inverse cosine of x. Then I'm going to come back after I solve the problem, and I'm going to show you how to do it by isolating the inverse sine of x. It's two different approaches, and you go down a different path, but you end up with the same answer either way. So to isolate the inverse cosine of x, I would add the inverse sine of x to both sides of the equation. So I would have the inverse cosine of x is equal to the inverse sine of x, and then basically plus 7 pi over 6. Now at this point, what I'm going to do is make a little substitution. You saw a moment ago that I said that I'm going to represent this inverse sine of x with theta. So let's go ahead and do that. We're going to let the inverse sine of x be equal to theta. And of course, we already know that x is negative square root of 3 over 2, and theta is negative pi over 3. So theta is in quadrant 4, rotating clockwise. And we're going to say then that the sine of theta is equal to, I'm going to write this as x over 1. It's just x, but x over 1, just so that we can say that x is your opposite. So this is your opposite. Let me make that a little bit better there. And then your 1 is going to be your hypotenuse. So we're going to use this information to sketch a triangle in a little while. But one thing that we need to know, if we're going to sketch the triangle, we need to know where's theta. Of course, we already know that it's in quadrant 4, but how could we get that information if we didn't know it? Well, basically what you would do is rewrite this. Let's say we have the inverse cosine of x is equal to, instead of the inverse sine of x, I'm just going to put theta and then plus 7 pi over 6. There's two things here, and you're going to put them together with the keyword and. So basically, the first piece of information you're going to use is you're going to take this right here. So the inverse cosine of x, remember the range of the inverse cosine function is from 0 to pi, with both being included. So that means that this right here, this theta plus 7 pi over 6, has to be from 0 to pi, with 0 and pi both being included. So in other words, I would say that you have theta plus 7 pi over 6 is greater than or equal to 0, and less than or equal to pi. So that's the first piece of information. You would subtract 7 pi over 6 away from each part. So this would be negative 7 pi over 6. This would go away from here. And then if I subtract this away from over here, let's go ahead and write this as 6 pi over 6. So 6 pi over 6 minus 7 pi over 6 is negative pi over 6. So this is negative pi over 6. So that's the first piece of information. Theta is greater than or equal to negative 7 pi over 6 and less than or equal to negative pi over 6. But that's not enough to tell me where theta is. So I need another piece of information. So I'm going to use the keyword and. And then for the second piece of information, I'm going to look at this right here. I let theta be equal to the inverse sine of x. And so theta has to be from negative pi over 2 to pi over 2, with both being included, because that's the range of the inverse sine function. So I'm going to say that theta is greater than or equal to negative pi over 2 and less than or equal to pi over 2. Writing this a little bit more neatly, this is what we have right now. So we basically want the intersection of these two to figure out where theta is going to be. And basically, if you set up the intersection, if you think about the left guy here, you want the guy that's larger. So negative 7 pi over 6 and negative pi over 2, negative pi over 2 is going to be larger, so you want to use that. So this is going to be negative pi over 2. And then you're going to say is less than or equal to your theta, and that's going to be less than or equal to. Over here, you actually want to use the smaller value. That's what's going to go on the right. So you have negative pi over 6 and pi over 2. So negative pi over 6 is less than pi over 2. So you're going to use negative pi over 6. So this would be the intersection of these two. So that tells me that theta is greater than or equal to negative pi over 2 and less than or equal to negative pi over 6. And if you look at the unit circle, this right here, if you rotate it clockwise, would be negative pi over 6, and this would be negative pi over 2. So this piece right here, we're saying that our angle is somewhere in there, so it's going to be in quadrant 4. Now, we already know that that is accurate because we end up with an angle that is negative pi over 3. Again, this is rotating clockwise. So we have that negative pi over 3. So that is consistent with what we found. Your negative pi over 3 is greater than or equal to negative pi over 2 and less than or equal to negative pi over 6. So we're good to go there. So coming back here, I would just note that now we know that theta is in quadrant 4, rotating clockwise. All right, so returning to the problem, now we have the inverse cosine of x is equal to theta plus 7 pi over 6. So what you want to do is just take the cosine of each side. So I'm going to say the cosine of the inverse cosine of x is equal to the cosine of theta plus 7 pi over 6. So of course, these are going to cancel, and you're going to have that x is equal to the cosine of theta plus 7 pi over 6. Now, we know we can't just distribute cosine to each part there. We need to use our sum identity for cosine. So I have that set up for us in case you forgot. So the cosine of a plus b is the cosine of a times the cosine of b minus the sine of a times the sine of b. So we can say that x is equal to the cosine of the first guy, which is theta, and then times the cosine of the second guy, which is 7 pi over 6, and then minus the sine of the first guy, which is theta, and then times the sine of the second guy, which is 7 pi over 6. Now going to the unit circle, here's 7 pi over 6, so the cosine value is negative square root of 3 over 2, and the sine value is negative 1/2. So coming back, I'm just going to replace some things. So this right here is negative square root of 3 over 2. This right here is negative 1/2. And of course, we already know, let me put this off to the side, that the sine of theta, again, is going to be x, or you could say x over 1. This is the opposite, and this right here is the hypotenuse. Let me make that a lot better there. And then basically, we also know that theta is in quadrant 4. Just going to copy that down. And of course, that's rotating clockwise. So this right here, I'm going to plug in an x. You get x is equal to the cosine of theta times the negative of the square root of 3 over 2. I don't know what the cosine of theta is. Then minus, here for the sine of theta, that is x. And then times, for the sine of 7 pi over 6, that's negative 1/2. Well, negative x times negative 1/2, that's going to be plus x over 2. So this right here is plus x over 2. And then at this point, I'm going to just multiply everything by 2. So I'm going to multiply over here by 2, over here by 2, and over here by 2. So this would cancel, and this would cancel. So you're going to get 2x is equal to, so let's put the negative of the square root of 3 times the cosine of theta, and then plus over here I just have x. So now I'm going to subtract x away from each side of the equation. So this cancels, and I end up with 2x minus x, that's x, and this equals the negative of the square root of 3 times the cosine of theta. So here's why we put in all that work earlier. We need to figure out what is the cosine of theta. So that's stopping us from getting a solution. So the first thing is, we know, and I've copied this a few times, but that the sine of theta is equal to x over 1. So this x right here is going to be the opposite, and this 1 right here is going to be the hypotenuse. We know it ends up being negative square root of 3 over 2. And we know this angle right here, theta, is negative pi over 3, because again, we've looked at this earlier. But again, if you don't know that, how do you figure out what is the cosine of theta? The cosine of theta is your adjacent over your hypotenuse. Well, I know the hypotenuse is 1. So let me just go ahead and say this is 1 down here. Well, what is the adjacent? Well, it's going to end up being this right here, the square root of 1 minus x squared. I don't know if I can fit that. So let me actually erase this border here. Move myself back over. And let me put this in as the square root of 1 minus x squared like that. So the cosine of theta, let me just erase this. I'm just going to put times the square root of 1 minus x squared. Now let me pause for a minute and address something that's probably going to be very confusing for you. When you look at things in trigonometry, generally speaking, we call the adjacent x, we call the opposite y, and then we call the hypotenuse r. So generally you say x squared plus y squared equals r squared. We're using x to represent our opposite here. So it gets a little bit confusing in this particular case, but you just have to keep this straight in your mind that this x right here is actually the opposite, or what we would normally say is the y. And then this right here, this square root of 1 minus x squared, that is what we would normally say is the x, but it's just going to be the adjacent here. So you really have to keep that straight, because in a moment, I'm going to say that the x here is negative, and a lot of you are going to say, no, 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 no. The x values are positive in quadrant 4, so that's wrong, but it's actually right, because this right here, again, is not an x value, it is a y value. It is an opposite here. So here's your negative pi over 3. Again, basically what you're doing is you're making yourself this triangle here. So here's your right angle here, and this is your angle theta, which we know. Let me just arrow to that. That's going to be negative pi over 3. Well, what is this opposite right here, which is represented by x in the problem? Well, it's actually going to be this y value right here, which is negative square root of 3 over 2. So this is negative square root of 3 over 2. And then this right here is your adjacent, so that's going to be 1/2. Again, you can even plug this stuff in if you want to be crystal clear about what's going on. If I have a negative, so if I have a negative square root of 3 over 2 here, if I plug that in there for x, I'm going to get positive 1/2. You can do that right here. So this is the square root of 1 minus. If I plug this in and squared it, so negative square root of 3 over 2 squared would be positive 3/4. So this would be 3/4. You could write 1 as 4/4. So this becomes the square root of 1/4. So the square root of 1/4, and of course that's 1/2. So that's completely consistent with what we know. This would be positive 1/2, and this would be negative square root of 3 over 2. So when I say that this x is going to be negative, I don't want you to be confused. This is where this is coming from. It's going to be for this opposite here, not the traditional x that we're talking about here. Okay, so hopefully that's straight for you. And now we're basically home free. What I would do is write this as x is equal to, again, using my rule, square root of a times square root of b is equal to the square root of ab, you can basically just multiply these guys together. So you can say this is the negative of the square root of 3 times this quantity. So 3 times the quantity 1 minus x squared. So that would be 3 minus 3x squared. So 3 minus 3x squared. Square both sides. So square both sides. And this is where you need to know that x is negative. So you're going to have x squared is equal to, the negative goes away, and you're just left with the radicand here. So you have 3 minus 3x squared. Add 3x squared to both sides of the equation. And you're going to have 4x squared is equal to, this cancels, you're going to get 3. Divide both sides of the equation by 4. So this is going to cancel, and you're going to get x squared is equal to 3/4. Now again, let me write this off so nobody's lost. We know that the sine of theta is equal to x over 1. And I know that the sine of theta is going to be negative, again, in quadrant 4. This x right here represents that opposite. Again, you can look at it on the unit circle, or you can come back to the sketch. This is the x that I'm talking about. It's for this opposite. I'm not talking about this x right here, this x right here. It's going to end up being negative square root of 3 over 2. So I know it's negative because it's the opposite, or it's the sine value in quadrant 4 where sine is negative. So I'm going to say here that x is less than 0. So if you have by the square root property x squared equals 3/4, then x equals plus or minus the square root of 3 over the square root of 4, which is 2, but I don't need the positive here. That won't work. That's going to be extraneous. I just want the negative. So here we get x equals the negative of the square root of 3 over 2. Again, we've already checked this. We know this is the solution. So that is one way you could solve it. Okay, I'm going to do this the other way. So basically, if you wanted to solve this for the inverse sine of x, you could subtract the inverse cosine of x away from each side. So you'd have the negative of the inverse sine of x is equal to the negative of the inverse cosine of x, and then plus 7 pi over 6. Multiply both sides by -1. So this becomes positive, positive, and then negative. So again, just like we did before, you're going to make a little substitution. I'm going to call this right here beta. So I'm going to let beta be equal to the inverse cosine of x. And then basically you'd have the inverse sine of x is equal to beta minus 7 pi over 6. So now what you have to do again is figure out where is beta. We know that beta is 5 pi over 6 because we already solved the problem. That means we're in quadrant 2. But if we don't know that, how do we figure it out? Again, you've got to set up 2 different restrictions. So for one, you could take this one and say, well, I know the inverse cosine is giving me something from 0 to pi. So that means that this beta is greater than or equal to 0 and less than or equal to pi. And from this one right here, you know that the inverse sine function is going to give you something from negative pi over 2 to pi over 2, with both being included. So you would say that negative pi over 2 is less than or equal to this beta minus 7 pi over 6, which is less than or equal to this pi over 2. Now, what I'm going to do is just speed this up a little bit. So you'd end up with that other one, beta is greater than or equal to 2 pi over 3 and less than or equal to 5 pi over 3. And then, of course, you have your and beta is greater than or equal to 0 and less than or equal to pi. If you look at the intersection of these guys, you're going to get that beta is greater than or equal to 2 pi over 3 and less than or equal to pi. So it would look like this. So coming to the unit circle, you're looking right here. So here's 2 pi over 3 to pi. So that tells me for sure I'm going to be in quadrant 2. Of course, we know the angle is 5 pi over 6, but we wouldn't know that. So we just need to know we're going to sketch the triangle in quadrant 2. Okay, let me come back up here and let me grab this. I also want to write here that the cosine of beta is equal to x. So this would be x over 1. So now this is the adjacent and this is the hypotenuse. Okay, so let me bring this down here. Again, I'm going to go a little bit more quickly. We're going to take the sine of each side. So that's going to give me x is equal to the sine of this beta minus 7 pi over 6. And you need to use your difference identity for sine here. So this is going to be x is equal to the sine of the first guy, so the sine of beta, times the cosine of the second guy. So this would be the cosine of 7 pi over 6. So this is negative square root of 3 over 2. And then I'm going to write my first guy there, which was the sine of beta, and then minus the cosine of the first guy. So the cosine of beta, we know that's x, and then times the sine of the second guy. The sine of 7 pi over 6 is negative 1/2. So again, this would be negative x times negative 1/2. That's x over 2. So this is plus x over 2. So basically, you multiply everything by 2. You're going to get 2x is equal to negative square root of 3 sine of beta, and then plus x. You know that you're going to subtract x away from each side. So get rid of this over here, and now you have x over here. So really the holdup is I need to figure out what is the sine of beta. And we're going to figure that out because we know that the cosine of beta in this case is going to be x. Again, you could write that as x over 1. So this is now the adjacent, and this is the hypotenuse. Okay, so let me grab this and let me paste this in. So this is my angle beta, and I'm trying to figure out the sine of that. Again, I already know that beta is 5 pi over 6. Now remember, sketching this triangle, we're looking at the reference angle here. This is going to be pi minus your beta. So in this case, it would be pi, or 6 pi over 6 minus 5 pi over 6, which is going to be pi over 6. That's your reference angle. So then we just think about, okay, this right here is going to be negative because I'm in quadrant 2, and this is going to be positive. Again, this is negative square root of 3 over 2, and this is 1/2. So what is the sine of beta? So the sine of beta, again, this is the opposite over the hypotenuse. Again, this right here, because I'm in quadrant 2, the y values would be positive, right? Or your opposite's going to be positive. So this is the square root of 1 minus x squared, and the hypotenuse is 1, so you can write over 1 if you want. It's up to you. But basically, you end up with the same thing. You're going to plug this in right there, and you're going to have x is equal to the negative of the square root of 3 times the square root of 1 minus x squared. Now, notice that x here, again, this guy right here is the adjacent, and you're in quadrant 2, so this is negative. It's not as confusing because with this one, at least x is in line with what we normally think of as x values. So it's for the adjacent in this case. With the other one, a lot of people get tripped up on that. But basically, you would say x is equal to the negative of, just like we did last time, the square root of 3 minus 3x squared, just multiplying this by this quantity. And then basically square both sides, so x squared is equal to, you're going to have 3 minus 3x squared, and then add 3x squared to both sides. You're going to have 4x squared is equal to 3. Divide both sides by 4, and you're going to get x squared is equal to 3/4. And then by the square root property, x is equal to plus or minus the square root of 3 over 2. And of course, we know that x is negative. Once again, so this is crystal clear, this is my x here. So it's for the adjacent. You can even go to the unit circle and look at your 5 pi over 6. That's right there. So this right here is going to be negative. Again, you can drop this like this if you want, and make yourself a little right triangle if you're confused. So it's going to be this right here. So this right here is going to be negative square root of 3 over 2, and this right here is going to be positive 1/2. So I know because I'm in quadrant 2, this is going to be negative. So coming back, I don't need the plus or minus, I just want the negative. So that's another way you can solve this. So once again, we find that x is equal to negative square root of 3 over 2. All right, for problem 14, we have the inverse cosine of x plus the inverse tangent of x is equal to pi over 2. Now again, for this one, you can use your identities. That's going to greatly speed up your work, or you can do it the long way. It's really up to you. Again, if you're on a test, always use the identities. It's just much faster. So we have this one that we talked about in the previous problem. The inverse cosine of x plus the inverse sine of x is equal to pi over 2. You're going to find that when you're solving these problems, this one is going to be very, very helpful. Comes up all the time. And then this one's going to come up. So the inverse tangent of x is equal to the inverse sine of x over the square root of x squared plus 1. Okay, let me start with this one. And I'm going to come up here and I'm going to plug in for the inverse cosine of x. So let me write here that the inverse cosine of x plus the inverse sine of x is equal to pi over 2. So what you could do is subtract the inverse sine of x away from each side of the equation there. Let me slide this down here. So now that identity can be rewritten as the inverse cosine of x is equal to pi over 2 minus the inverse sine of x. So all I'm going to do is take this right here, that matches this right here, and I'm going to plug this right here in for this right here. So I'll have pi over 2 minus the inverse sine of x, and then plus, so in the place of the inverse tangent of x, I'm going to plug in the inverse sine of this x over the square root of x squared plus 1. Close that down, and this equals pi over 2. So you'll notice that you have pi over 2 over here and pi over 2 over here. So you can just cancel it away from each side. If you want to do this the long way, just subtract pi over 2 away from each side of the equation. So I'm going to say that this is going to cancel, and this is going to cancel, so you have 0 over here. And then I'm just going to add the inverse sine of x to both sides. So the inverse sine of x, and then I'll add the inverse sine of x over here. So of course, this is going to cancel. So what you have on the left is just the inverse sine of this x over the square root of x squared plus 1. And then this would be equal to, over here, you have the inverse sine of x. Let me make that a little bit better there. All right, so a very easy equation to solve, actually. If the inverse sine of x over the square root of x squared plus 1 is equal to the inverse sine of x, well, then it must be true that this right here, this argument, must be equal to this argument. You could also just take the sine of each side if you want. I think that's a slower approach, but you can do that if you want to see it. So I'm just going to say that x over the square root of x squared plus 1, again, the argument here for the inverse sine function, is equal to the argument here for the inverse sine function, so just x. All right, so how are we going to solve this? There's a lot of approaches. I think the easiest one to understand is just to cross multiply. So I'm going to say that this times this, that would be x times the square root of x squared plus 1 is equal to 1 times x, which would be x. Okay, so at this point, I'm just going to subtract x away from each side. Let me just erase this and put minus x, and this equals 0, and make that x a little bit better, and maybe the 0 could be a little bit better. And at this point, notice that you have an x here and an x here. So what do you do when that happens? You basically factor it out. So you're going to pull that out in front of some parentheses and say that x times the quantity, here you would have the square root of x squared plus 1. And then if I pull that out from here, you're going to have a 1. You can put times 1 if you need that. Let's go ahead and say this is minus 1 here, close that down, and this equals 0. So now what you would want to do is use your zero product property. Basically, you would say that x is equal to 0, or this guy right here, so the square root of x squared plus 1 minus 1 is equal to 0. With this, I would just add 1 to both sides. So this equals 1. And this one, you would square both sides of the equation. So let me show that. So I'm going to square this and square this. And so you get x squared plus 1 is equal to 1 squared is 1. Subtract 1 away from each side of the equation, and you get x squared is equal to 0. So x squared equals 0. Let me get rid of this and just put this up here as x squared equals 0. Of course, that's going to be x is equal to 0. So you get x equals 0 or x equals 0, which is just x equals 0. Let me come to the unit circle real quick and fill this out with you. So if you have the inverse cosine of 0, what is that? Again, that's pi over 2. If we look, again, from 0 to pi, with 0 and pi both being included, where do I have a cosine value of 0? That's going to be right there, and that's going to occur at pi over 2. If I think about the other guy that's involved, so we had the inverse tangent. So the inverse tangent, and that's going to be of 0. So what is that going to be? With the inverse tangent, you're working from negative pi over 2 to pi over 2, with both being excluded. So I'm going to stop a little bit short there. So where am I going to have a tangent value of 0? Well, it's going to be at 0 right there. Let me change my color up. So it's going to be right there because the sine value is 0 and the cosine value is not 0, it's 1. So 0 divided by something that's not 0 is 0. So we know the inverse tangent of 0, again, this is the tangent value, gives me that angle of 0. So coming back, again, if I'm plugging in a 0 here, I get pi over 2, and I'm plugging in a 0 here, I get 0. So this becomes pi over 2 plus 0 equals pi over 2. And of course, this is a true statement. You get pi over 2 equals pi over 2. So x equals 0 is a valid solution. Okay, once again, if you want to go to Desmos and see this graphically, you can. I'm just going to rearrange this equation. So all I did was I subtracted pi over 2 away from each side. And of course, that would give me 0 over here. So if y is 0, what is the x value that makes y 0? I'm looking for the x-intercept, and that's going to be right there at 0, 0. All right, for those of you that want to see this, I'm going to go about this the longer way, so we're not going to use any identities to help us. And I just want to note here that the inverse cosine of 0 is pi over 2, and the inverse tangent of, again, this is the tangent value of 0, that's going to be equal to the angle 0. So this is the one that you're going to want to write down. We're going to use it as we're solving this problem, at least the way that I'm doing it. Maybe you would do it a different way, so you would need this one, but just write that down and you could check things every so often to make sure you're on the right track. All right, so inverse cosine of x plus inverse tangent of x equals pi over 2. Not using any identities, what do we do? Well, you pick one of these to isolate, and I'm going to isolate the inverse cosine of x. So that means I have the inverse cosine of x is equal to, I would subtract the inverse tangent of x away from each side of the equation. So that's pi over 2 minus the inverse tangent of x, and make that a little bit better. Now at this point, what I like to do, you don't have to do this, I like to make a substitution for this because this guy is an angle. We know it's 0 in terms of the angle because x, the tangent value there, is going to be 0. So what I would do is I would say that I'm going to let theta be equal to the inverse tangent of x. And then of course you can say that the tangent of theta is equal to x. Let me make this e a little bit better. Okay, so once we've established this, now we can rewrite this as the inverse cosine of x is equal to pi over 2 minus, in this case, I'm going to put in theta, because again, the inverse tangent of x, I've said that's going to be theta. Now we need to try to figure out where is theta. So what I'm going to do is say, for the first guy here, I know that the inverse cosine of x is going to give me something from 0 to pi with both being included. So you're going to have pi over 2 minus theta is greater than or equal to 0 and less than or equal to pi. Then the other thing to think about is that the inverse tangent of x is theta. And so from the range of the inverse tangent function, we would say that theta is strictly greater than negative pi over 2 and strictly less than pi over 2. So keep these two in mind. I'm going to say and here. I'm actually just going to grab this real quick. What's going to happen, we're going to end up with just this one, but I want to show that to you in case you're a little bit lost about how to solve something like this. So you have a three-part inequality, and you want to isolate this theta right here. And right now you have a negative theta, so that's going to be an issue. So there's lots of ways to deal with that. What I would do is actually multiply everything by -1. Remember, if you're working with an inequality and you're multiplying by -1, you've got to flip the direction of the inequality symbol. Here you have inequality symbol, so you've got to do it to both. So here you would have 0 times -1. This would flip to a greater than or equal to. Then you would have negative pi over 2. Then you would have plus theta. This would flip to a greater than or equal to, and this would become negative pi. Now, -1 times 0 is still 0. And this right here, you typically don't write things like this. You want to put in the order of the number line. So you want to reorder this and say it's negative pi is less than or equal to theta plus negative pi over 2, which is less than or equal to 0. Once you do this little step here, it's not that bad. You're just going to add pi over 2 to each part. So let me do that over here. So we know that this would cancel. Just going to erase it. Let me move this down here like this. So 0 plus pi over 2 is, of course, just pi over 2, like that. And then over here, you have pi over 2 minus pi. So let's go minus 2 pi over 2. So this is negative pi over 2. Let's get rid of this and say this is negative pi over 2. Now, if we look at the intersection here, really, I'm just going to go with number 2, because the only difference between these two is here I have a non-strict inequality, and here I have a strict one. Here I have a non-strict inequality, and here I have a strict one. So it's got to work in both. When I think about theta, I'm going to choose this one and say that it has to be from negative pi over 2 to pi over 2, with both being excluded. So the normal range for the inverse tangent function. So all that tells me is that I'm going to be in quadrant 1 or quadrant 4, rotating clockwise. So just so this is clear, let's come to the unit circle. And we already know that we're going to be at 0. And 0 is a quadrantal angle, so it's really not in any quadrant. But for the sake of talking here, let's say we're going to be from negative pi over 2 to pi over 2, with both of those guys being excluded, so I'm going to stop a little bit short. Again, we know that the answer is 0, but if we're solving this for the first time, we don't know that yet. So that means when we sketch our triangle, we're going to sketch something in quadrant 1 and quadrant 4. I know that the x values here, and this is where it gets confusing, so let's just say the adjacent here would be positive, because that's going to be positive in quadrants 1 and 4. So keep that in mind, and let's go back up. And let me just put this here, that theta is greater than negative pi over 2 and less than pi over 2. What I'm going to do at this point is just take the cosine of each side. So again, you could write this out if you need to. You could also just use the definition of the inverse cosine function, which just means that if the inverse cosine of x is equal to pi over 2 minus theta, well then x is equal to the cosine of this pi over 2 minus theta. So let's just go ahead and grab this and come down here. I have my little difference identity for cosine if you want to pause the video and use that. So basically x would be equal to, you want the cosine of the first guy, so you want the cosine of pi over 2, and then times the cosine of the second guy, so that's theta, and then plus we want the sine of the first guy, so the sine of pi over 2, and then times the sine of the second guy, so the sine of theta. Now, what is the cosine of pi over 2 and the sine of pi over 2? Most of you know that the cosine of pi over 2 is 0 and the sine of pi over 2 is 1. Again, so nobody's confused. In case you don't have a unit circle, here's pi over 2. So the cosine value is 0, the sine value is 1. So I'm going to plug in a 0 there, and I'm going to plug in a 1 there. So what does that give me? X is equal to 0 times anything is 0. So you don't have to write that. So then you would have a 1 here. So basically, x is just the sine of theta. Okay, so x is the sine of theta. What do we know about theta at this point? We know that the tangent of theta, which is by definition the opposite over the adjacent, is equal to x, and you could say over 1. The adjacent here is positive. That's why I can put positive 1, because I know that theta is greater than negative pi over 2 and less than pi over 2. Not this x, but when we think about the x values, so the traditional x values on the coordinate plane, those guys are positive in quadrants 1 and 4. This x right here is referring to the opposite for that side. This would be a y value traditionally. Again, when I go to the sketch, that's going to make more sense if you're still confused. So we know that this is positive 1 and this is x here. Now this x could actually be positive if you're in quadrant 1, and it could be negative if we're rotating clockwise in quadrant 4. Of course, we know it ends up being 0 because we've already solved the problem. So at this point, what you would want to do is figure out what is the sine of theta. So the sine of theta is equal to the opposite over the hypotenuse. Well, I know the opposite is x, so now I just need to figure out what is the hypotenuse. Let me actually just move this over here and come down to a little basic sketch. So again, let me write this out. So the tangent of theta is equal to your opposite over your adjacent. And I know that I'm either in quadrant 1 or quadrant 4, rotating clockwise. And so I know that the, again, traditional x values, so the adjacent here is going to be positive. So I know this is positive 1. Then for the opposite, all I know about it is it's x. So if I'm in quadrant 1, again, x is positive. Again, that's for the opposite here, not this x right here, this x right here. Then this x right here, again, if I'm in quadrant 4, rotating clockwise, well, now this would be negative. So I don't have any more information about that, so I'm just going to write x. The goal at this point with this sketch is just to figure out, well, what is the hypotenuse going to be? In either case, that's going to be positive because the hypotenuse is always positive. So the sine of theta is going to be, if you use your Pythagorean theorem, the hypotenuse is square root of x squared plus 1. So this is going to be your opposite over your hypotenuse. And so this right here would be x over the square root of x squared plus 1. X is equal to the sine of theta. Well, the sine of theta is x over the square root of x squared plus 1. Does that look familiar? Yeah, that's exactly what we found earlier with way fewer steps using our identities. So basically, we're right back to that point. And all you would do here, again, you could just cross multiply. You could say this is x over 1. So x over 1. And so basically 1 times x is x. And this equals, this would be x times the square root of x squared plus 1. So all you would have to do here again is subtract away x from each side. Let me get rid of it from over there. And actually, let me just move this over here. And again, we've already solved this. So we know we're going to factor out the x and have x times a quantity, square root of x squared plus 1, and then minus 1 like this. Close that down and that equals 0. At this point, you would use your zero product property. So either x is equal to 0 or this guy right here, the square root of x squared plus 1 minus 1 equals 0. So again, we know that this is going to be 0 in each case. Let me move the 1 over here by adding 1 to both sides. Square both sides, you get x squared plus 1 is equal to 1 squared would still be 1. Subtract 1 away from each side, you get x squared is equal to 0. And of course, x is just going to be 0. So x equals 0 or x equals 0. Again, you get x equals 0, which we know is a valid solution. All right, let's take a look at one more of these. So for problem 15, we have 2 inverse sine of x plus the inverse cosine of x equals pi. So again, let's start by using our little identity. Again, the inverse cosine of x plus the inverse sine of x equals pi over 2. So I'm going to go ahead and solve that for the inverse cosine of x. So you could say the inverse cosine of x is equal to, let's go pi over 2 minus the inverse sine of x. So again, this right here matches this right here. So all I'm going to do is plug this right here in for this right here. So that's going to give me inverse sine of x and inverse sine of x. So that'll make the problem really, really easy. So let's come down here and basically I'll have 2 inverse sine of x. And then I'm going to plug this in. So plus pi over 2 minus inverse sine of x. And this equals pi. You have 2 inverse sine of x minus inverse sine of x. So that's just going to be the inverse sine of x, and then I'm just going to subtract pi over 2 away from each side of the equation. So this would be equal to, if you have pi minus pi over 2, you could write this as 2 pi over 2 to get a common denominator. So this would end up being just pi over 2. Then we could say that the sine of pi over 2 is equal to x. Again, if you want, you could take the sine of each side a little bit slower, but some people like to do that. But basically, we know the sine of pi over 2 is 1. Again, coming back to the unit circle, here's pi over 2. Your sine value is 1. So this right here would be 1. So we would say x is equal to 1. Okay, let's see if x equals 1 works. So we have 2 times the inverse sine of 1 plus the inverse cosine of 1. This should be equal to pi. So let's figure out what the inverse sine of 1 is and the inverse cosine of 1 is. A lot of you know, without going to the unit circle, that this right here is 0, and then this right here is pi over 2, But again, I always want to go to the unit circle so you can see it for yourself. So let's start with the inverse sine of 1. Of course, this is pi over 2 because you're working from negative pi over 2 to pi over 2. So both of those are actually included. And basically, you're looking for a sine value of 1. So that's going to be right there. So of course, the inverse sine of 1 is pi over 2. Then when we think about the other guy, so the inverse cosine of 1, and this is going to be 0. So we're working here from 0 to pi, with both being included, and you're looking for a cosine value that's going to be 1. So that's right there. So your angle is 0. Okay, so coming back, we've confirmed this. So let's set this up as 2 times pi over 2. And then you can go plus 0 or leave it off. So this just equals pi. And basically, let me erase this. I'm just going to slide this up so this can all fit on the screen at once. Move this up here. You'll see that the 2's would cancel, and you get pi is equal to pi. So that tells me x equals 1 is a valid solution. Now again, if you want to look at the graph, you can go to Desmos. I have y equals 2 inverse sine of x plus inverse cosine of x and then minus pi. So again, all I did was I took my equation and I subtracted pi away from each side, and that would give me a 0 over here. So if you plug in a 0 for y, what's the x value that makes that true, or where's the x-intercept? Well, that's going to be at 1, 0. So your x value there is 1. All right, for anybody that wants to stick around, I'll do this one the long way as well, just so you can get some practice. So basically, we start with 2 inverse sine of x plus inverse cosine of x equals pi. Again, just pick one of these to isolate. It's going to be a lot easier to isolate the inverse cosine of x. So I'm just going to say the inverse cosine of x is equal to negative 2 inverse sine of x and then plus pi. So all I did was subtract 2 inverse sine of x away from each side of the equation. And at this point, I like to make a little substitution. So we're going to let theta be equal to this right here. So this inverse sine of x, we know the inverse sine of 1, which is what x ends up being, is going to be pi over 2. So this angle theta is pi over 2. Just keep that in mind as you're solving the problem if you want to check things as you go. So this would be the inverse sine of x. And of course, then we can say that the sine of this theta would be equal to x. Let's go ahead and rewrite this now and say that we have the inverse cosine of x is equal to negative 2 theta plus pi. All right, so in terms of the restrictions, we know that the inverse cosine function gives me something from 0 to pi. We also know that the inverse sine function gives me something from negative pi over 2 to pi over 2. So in each case, both of those guys are included, so the 0 and the pi, and then the negative pi over 2 and the pi over 2. So let's go ahead and set up number 1 here. I'll say that pi minus 2 theta is going to be greater than or equal to 0 and less than or equal to pi. Again, that's coming from the range of the inverse cosine function. And then I'm going to put and. Remember that theta is equal to inverse sine of x. So that means that this guy right here is going to be greater than or equal to negative pi over 2 and less than or equal to pi over 2. And of course, we already know it's pi over 2, so it's within something we can get from the range of the inverse sine function. Let me grab this real quick and come down here. So this is what we can do. Again, if we haven't solved the problem and we need to know, well, where is theta? What quadrant is it in? We can't always get an exact quadrant, but a lot of times you can get it down to the point where you can figure out is stuff positive or negative, things like that. So for this one, it's very straightforward. But for the top one, again, you've got to think about how you can manipulate that. And I think the easiest approach here is just to multiply everything by negative 1. So let's put negative 1 times 0, and I'm going to flip all the signs. So that would be a greater than or equal to, and then this is going to be negative pi, and then plus 2 theta. I'm going to flip the sign here. So this will become a greater than or equal to, and this would become negative 1 times pi. So of course, negative 1 times 0 is 0, and negative 1 times pi is negative pi. And all you want to do at this point is just rewrite this in the order of the number line. I would put this as negative pi is less than or equal to your 2 theta, and then basically you would have minus pi, and this is less than or equal to 0. So I'm going to go ahead and add pi to each part here, and let's see what that gives me. So this is going to cancel. Negative pi plus pi is going to be 0, and then 0 plus pi is pi. So basically you have 2 theta is greater than or equal to 0 and less than or equal to pi. If you divide each part by 2 here, you're going to get that theta is greater than or equal to 0 and less than or equal to pi over 2. So if I combine this with this, you're going to end up with theta being greater than or equal to 0 again, with this one, you want to choose the one that's more restrictive. So in terms of the leftmost guy, you want the guy that's going to be larger. So 0 is greater than negative pi over 2, so you pick that one. And then in terms of this right value here, we have pi over 2 and pi over 2, so it's just going to be the same thing. So you're going to put and less than or equal to pi over 2. So what does that tell me? Again, 0 is a quadrantal angle and pi over 2 is a quadrantal angle, but for talking, we would say that theta is in quadrant 1. Now, we know we're going to end up getting pi over 2, and pi over 2 is not in quadrant 1, it's a quadrantal angle. But when you sketch your triangle, you would sketch it in quadrant 1 and just see what you get. And what you want to do now is just take the cosine of each side, or again, you can use the definition of inverse cosine function, and just say that x would be equal to the cosine of, let me write this as pi minus 2 theta like that. And let's come down here. Again, let me put that theta is greater than or equal to 0 and less than or equal to pi over 2. So again, in quadrant 1 is where we're going to sketch the triangle. So using this difference identity for cosine, you're going to say x is equal to the cosine of the first guy, which is pi, and then times the cosine of the second guy, which is 2 theta, and then plus the sine of the first guy, which is pi, and then times the sine of the second guy, which is 2 theta. Now, in terms of pi, that's right here, and your cosine value is -1, your sine value is 0. So for this, I'm plugging in a -1, and then for this, I'm plugging in a 0. So you might as well say that this is going to go away, because 0 times anything is just 0, and then adding 0 to something doesn't change it. So basically, you would have x is equal to the negative of the cosine of 2 theta. So basically, let me write that x is equal to the negative of, again, if you have the cosine of 2 theta, you can put this as, and you need parentheses here, 2 cosine squared theta minus 1. We're going to distribute the negative to each guy, so that becomes a minus, and this becomes a plus. And I'm just going to come back here and paste this in and move this here, put a little border. So basically, we need to figure out what is the cosine of theta. We have cosine squared theta there, but that doesn't matter. We could just square it. So what is the cosine of theta? So that equals what? Again, this is the adjacent over the hypotenuse. Well, what do we know? Again, we know that the sine of theta is x. So the sine of theta is equal to x over 1. So this right here would be the opposite, and this right here would be the hypotenuse. We know the hypotenuse is always going to be positive. And again, I'm sketching the triangle in quadrant 1. So let me just put that I'm going to sketch it in quadrant 1. Even though the angle ends up being pi over 2, which is quadrantal, we're still going to sketch it in quadrant 1. So let's go ahead and say that the hypotenuse is 1, and I just need to figure out what is the adjacent. Again, you can just do the Pythagorean theorem here if you want. So you come down to your little sketch here, and you set this up. So this right here is your opposite. So this right here is your opposite. And then this right here is your hypotenuse. So this is the hypotenuse. And then basically this right here is what you're going to figure out with the Pythagorean theorem. So this is going to be your adjacent. Again, you've got to keep this straight in your head. I know somebody's still confused. This right here is the traditional x. And when we think about that, that's going to represent your adjacent in most cases. But now because we have x involved in the problem, the x here that I'm talking about when we solve this equation, that's actually going to be for this opposite right here, which is what we think of as a y value. I know this is super hard to get straight the first few times you see it, but this is your adjacent, square root of 1 minus x squared. Your opposite is x, and then your hypotenuse is 1. All right, so coming back, if we fill this in for the adjacent as the square root of 1 minus x squared, now we're good to go in terms of the problem. So here you have x equals -2 cosine squared theta plus 1. I'm going to first write this as the cosine of theta like this being squared. I think it's easier to think about. And for the cosine of theta, I'm just going to plug in the square root of 1 minus x squared. So this is going to get cut off. Let me come down here a little bit. And basically, you're going to have x is equal to -2 times, again, for the cosine of theta, that's the square root of 1 minus x squared. And this would be squared and then plus 1. Let me go ahead and grab this real quick and come down to a fresh sheet, and let's just think about this. So this right here, if I'm squaring the square root of 1 minus x squared, you could say that this squaring would undo the square root operation. And so what I'm going to have is x is equal to -2 times this radicand here. Make sure to wrap it in parentheses. So 1 minus x squared, and then plus 1. So this guy right here needs to be distributed to each guy inside of the parentheses. So we're going to have x is equal to -2 times 1 is -2, and then -2 times -x squared is plus 2x squared, and then plus 1. So -2 plus 1 is -1. Let's just write this as -1 like this. And because we have a quadratic, let's go ahead and write this as 2x squared. I'm going to subtract x away from each side. So let me actually write -x here and 0 here. So I'm going to have 2x squared minus x minus 1 is equal to 0. Okay, so this is something you can factor. Of course, you could use the quadratic formula if you're more comfortable with that. It's really up to you. So this is a 2 here. So I'm going to put 2x here and x here. And because this last guy is a negative 1, that can only come from negative 1 times positive 1. And of course, because this is a negative 1 here, what you would want is a negative 1 here and a plus 1 here, so that your outer is negative 2x and your inner is plus x. So negative 2x plus x, that's negative x. So at this point, you'd use your zero product property, and you would say that 2x plus 1 is equal to 0, or x minus 1 equals 0. Let's start with this one right here. So subtract 1 away from each side. This cancels. You get 2x is equal to negative 1. Divide both sides by 2. This cancels. And you get x is equal to negative 1/2. Let me actually erase this so I can fit this on the screen. I'm just going to write that x is equal to negative 1/2. Now, is this a valid solution? No. Again, just going back to the sketch, what does x represent? It represents the opposite. And we know that at the end of the day, we've already solved this problem, x is going to be 1 and theta is pi over 2. But again, if you don't know that, we just go back to the fact that theta is greater than or equal to 0 and less than or equal to pi over 2. So we established that earlier. So we know that the x here, again, this is the opposite, not this x here, but this x that's for this opposite, that is not going to be negative based on this information right here. So you can reject that, or again, if you're more comfortable with it, you can plug it in for x in the original problem, and you'll see that it's extraneous. It will not work as a solution. So I'm just going to mark this out. Then here we have or x minus 1 equals 0. So I'm just going to add 1 to both sides of the equation. This cancels, and you get x equals 1. Of course, we know that this is our solution. I'm just going to erase these right here, so it's crystal clear that this is the only valid solution. So x equals 1, which we verified already graphically and also by plugging in. All right, let's take a look at the practice test. For the instructions, we're asked to solve each for all solutions. All right, let's take a look at the first problem. So here we have 1 plus the sine of x is greater than, we have 2 minus the square root of 2 over 2. So this type of problem is an easier problem. You can just solve it by isolating the sine of x on one side and putting a number on the other. You could also use the test point method, which we're going to see later on, but I wouldn't recommend that in this situation because it's just so easy. So the first thing I'm going to do is multiply both sides of the inequality by 2. That's going to clear this denominator right here. So I'm going to go 2 times 1 plus 2 times the sine of x, and this is greater than, you have 2 minus the square root of 2 over 2, and then times 2. So 2 times 1 is obviously 2, and then plus you just have 2 sine of x, and this is greater than, here the 2's would cancel, so you just have your numerator, so 2 minus the square root of 2. Now at this point, notice you have a 2 here and a 2 here, so you can subtract 2 away from each side of the inequality. So basically this is going to cancel, and this is going to cancel, and what you're left with is 2 sine of x is greater than the negative of the square root of 2. All right, so I'm going to divide both sides of the inequality by 2 so I can completely isolate the sine of x. So this cancels, and you're going to get that the sine of x is greater than the negative of the square root of 2 over 2. Okay, let me come down here and paste this in. When you solve an inequality like this, the first thing I would do is think about the period for what you're working with. So if you just have something like the sine of x, remember, if I was solving, let's say, the sine of x equals the negative of the square root of 2 over 2. This is just the standard period of 2 pi, so solutions repeat every 2 pi. So if I solve this equation here to see where the sine of x is equal to the negative of the square root of 2 over 2, I'm going to go into quadrants 3 and 4, where sine is going to be negative, and I'm looking for a reference angle of pi over 4. So at 5 pi over 4, I'm going to have that reference angle of pi over 4. Notice your sine value here is negative square root of 2 over 2, and then at 7 pi over 4, I'm going to have a reference angle of pi over 4, and so your sine value is negative square root of 2 over 2. Now, if you look between these values here, this inequality is not going to be satisfied. In other words, it would produce a false statement. So if I look at the sine values between 5 pi over 4 and 7 pi over 4, you notice you get negative square root of 3 over 2, negative 1, negative square root of 3 over 2. So obviously that is not greater than negative square root of 2 over 2. So this would not work. So what you want to focus on is the part of the unit circle where it would work. So where the sine values would be greater than the negative of the square root of 2 over 2. So that's going to be right here. Now, the way you're going to write this is going to be a little bit tricky. So let me go ahead and highlight all of this first, and then let's talk about it. So basically, when you look at this, you would start, or you could start, I would say, because there's different ways to write it. Let me erase this. You could start by saying that x is strictly greater than, let's put our 7 pi over 4 here. So 7 pi over 4. And I'm going to add that 2 pi n, so 2 pi n, that we put when we work with the general solution. So let me put that like that. And I'm going to say it's less than. Now here's where it's tricky. If you're just looking at the unit circle, you might be tempted to put 5 pi over 4 there. So really you have to think about it as I'm starting at 7 pi over 4. So I've already rotated like this. So in other words, this is not 5 pi over 4. It's 5 pi over 4 plus 2 pi, which is 8 pi over 4 if you want a common denominator. So that's 13 pi over 4. So that's how you have to treat that right there. So let's go ahead and say that this part is going to be 13 pi over 4 and then plus 2 pi n. Now, this is one way to write it. You don't have to write it that way. When you go to the graph in a moment with me, I'll show you that there's obviously going to be lots and lots of ways that you could write this general solution. So what you could also choose to do is rotate clockwise here. So we all know that if we rotate clockwise here, this would be negative pi over 4. And basically we know that the sign of negative pi over 4 and the sign of 7 pi over 4, that's going to be the same. You're going to get that negative square root of 2 over 2 in each case. And so what you could do is say that x is greater than this negative pi over 4 and then plus your, I don't think I can fit this. So let me put the 2 pi in there. So 2 pi n. And then I'll put that back in. And less than, well, now if I'm starting here and I've rotated clockwise here, so this is negative pi over 4, well, now I can just do this rotation here, and that would be 5 pi over 4. So let's put 5 pi over 4 and then plus 2 pi n. And if this is a little bit confusing for you, don't worry about it. The first few times you do this, it is a little bit confusing to get your general solution. When we look at the graph in a moment, it'll make more sense. Let me get rid of this one. This is the one I'm going to go with because this is what I used in the practice test. Now, if you want to look at the graph of this, what you would do is think about this as an equation. So let's just say I had the sine of x is equal to the negative of the square root of 2 over 2. So let's say you had the sine of x plus the square root of 2 over 2. And basically, at this point, that would be equal to 0. And so a lot of times what we'll do is we'll say y is equal to this. Let me move this up here. And if you wanted to solve that equation that way, you're looking for where y is 0. So those are your x-intercepts. So you're going to see those at negative pi over 4. You're going to see 5 pi over 4. You're going to see 7 pi over 4. You're going to see 13 pi over 4. So basically, you can think about it as 5 pi over 4 plus 2 pi n and 7 pi over 4 plus 2 pi n, where n is any integer, if you're looking for the x-intercepts. But essentially, we're trying to solve the inequality. So we're trying to say, well, in this particular case, it would be where are the y values greater than 0? So let me grab this real quick. I already have the equation written, so we don't need to take that. And let's come down to the graph. So let's put this like this, just out of the way. And again, you can go to Desmos or any online graphing calculator and just type this in. Y equals the sine of x plus the square root of 2 over 2. Again, the x-intercepts, if you want to look at those, here's your negative pi over 4. Here's your 5 pi over 4. Here's your 7 pi over 4. Here's your 13 pi over 4, so on and so forth. So basically 5 pi over 4 plus 2 pi n and 7 pi over 4 plus 2 pi n, where n is any integer. Now, if we're trying to figure out where the y values are greater than 0, again, if you look at this piece right here, so between negative pi over 4 and 5 pi over 4, you're going to see that that inequality would be satisfied. So the y values are greater than 0. Again, if you look at this one right here, this is how we're listing the solution. So between 7 pi over 4 and 13 pi over 4, again, we're going to be greater than 0 in terms of the y values. So you have this piece and this piece and this piece, and that continues forever and ever and ever. So that's one way that you could write it like this. Or again, if you wanted to say that x is greater than your negative pi over 4, so this right here, plus 2 pi n, and less than your 5 pi over 4, so this right here, plus 2 pi n, where n is any integer, that's fine as well. Because again, if you take negative pi over 4 and you add 2 pi, you get to 7 pi over 4. If you add 2 pi, you get to 15 pi over 4, so on and so forth. If you take your 5 pi over 4 and you add 2 pi, you get to 13 pi over 4. Again, if you add 2 pi again, you're going to get to 21 pi over 4, so on and so forth. All right, let's move on and look at problem 2. So here we have 2 tangent of x is less than negative 2 times the square root of 3. So you can solve this just like the last problem, isolate the tangent of x on one side, have a number on the other, and then go to the unit circle and put your solution together. The problem with that is it's not as straightforward because the tangent values are not on the unit circle. So if you're somebody that has them memorized, you can do it like that. But what I'm actually going to do is use a table. So let me go ahead and slide down a little bit. I'm just going to divide both sides of the inequality by 2 to get things started. That would cancel. And you get that the tangent of x is less than, these 2's would cancel. So you get the negative of the square root of 3. Again, I'll come to the unit circle. You can't directly get the values for tangent from the unit circle, but what you could do is use your calculator And I think all of you know that if you typed in the inverse tangent of, let's just make this positive. So let's go positive square root of 3. You're going to get pi over 3. And of course, that's coming from the fact that the tangent of pi over 3 is equal to the sine of pi over 3, which is the square root of 3 over 2, divided by the cosine of pi over 3, which is a half. So I'm just going to multiply by the reciprocal, so times 2 over 1. And so, of course, these 2's would cancel, and you're going to get the square root of 3. So where do I have a tangent value of negative square root of 3? Well, that's going to be in quadrants 2 and 4, where tangent is negative, and where I have a reference angle of pi over 3. So that's going to be at 2 pi over 3, and then also it's going to be at 5 pi over 3. So just keep that in mind. So if I was to ask you the tangent of x, where is that equal to the negative of the square root of 3? Again, if you want to solve this from 0 to 2 pi, like this, you would say x is equal to 2 pi over 3, and then 5 pi over 3. Now for this one, you have to consider that the period for tangent is pi. In other words, I have this solution here. I rotate by pi, and I get to another solution. I rotate by pi, I get to another solution, and so on and so forth. So really for this problem, if I'm setting up a table or something like that, I don't want to go between 0 and 2 pi. I want to go between 0 and pi. That's all I need to do because the solutions are repeating every pi. So get rid of this and get rid of this. So I'm just going to consider that right there. Now, when I talk about making a table, essentially what you're doing is you're going to split this guy up into different intervals, and you're just going to test. So you don't have to do it this way. I just find it to be the easiest in this particular situation. So I'm going to go between 0 and pi, and I'm going to think about the intervals that I'm going to set up. So this right here would be a critical value. So that's basically where the tangent of x is equal to the negative of the square root of 3. But you also have to consider where the tangent of x would be undefined. So at pi over 2, in this guy right here, working from 0 to pi, well, basically it's going to be undefined there because the tangent of pi over 2 is equal to the sine of pi over 2 divided by the cosine of pi over 2. And the cosine of pi over 2 is 0. So division by 0 is undefined. So this becomes 1 over 0, which is, by definition, undefined. So this is undefined. Now, we have to include that in when we test. So let me get rid of this. And basically, let me line this out. So you're going to have an interval between 0 and pi over 2. So you're going to test in there and see if things work. And then you're going to have an interval between pi over 2 and 2 pi over 3. So you're going to test in there and see if it works. And then you're going to have an interval between 2 pi over 3 and pi, test in there and see if it works. So when I set these tables up, I don't include anything. I just include things if I need to at the end. I've already got the table set up. So I wrote this in a different way. It was the tangent of x is less than the negative of the square root of 3. I just added the square root of 3 to both sides of the inequality. So it produces this right here. And essentially, here are the intervals. And I've already picked out something in each interval. And I've plugged it into the calculator to speed things up. Essentially, you're just trying to figure out, is it positive or is it negative? Basically, if it's negative, it's going to work. It's going to be less than 0. And if it's positive, it's not going to work because it's not going to be less than 0. So in this interval between 0 and pi over 2, I chose pi over 6. And if you plug that into your calculator, you're going to get about 2.31. So this is positive. So this is not going to work. Then in this interval between pi over 2 and 2 pi over 3, I picked 7 pi over 12, which is going to be 105 degrees, in case you're curious. So basically, if you plug that in, you're going to get exactly -2. So this is negative, so this is going to work. And then between 2 pi over 3 and pi, in this interval here, I picked 5 pi over 6. If you plug that in, you get about 1.15. So this is positive, so this is not going to work. So if you want to put your solution together, again, you could do it here. I prefer to go to the unit circle. So just coming back here, let me erase this and this. So basically, this right here is where it's going to work. So this right here is where it's going to work. So between pi over 2 and 2 pi over 3, 2 pi over 3 will not be included because it's a strict inequality, and pi over 2 will not be included because that's where it's undefined. Because the period is pi, you're going to say that x is going to be greater than your pi over 2, so pi over 2. And now you got to put plus, what's the period for tangent? It's pi, so pi n. Don't make the mistake of putting 2 pi n because, again, the period for tangent is pi. Then we're going to say, and it's less than, you're going to use 2 pi over 3. So 2 pi over 3, and then plus pi n. Now, if you wanted to look at this, again, when we get to the graph, you're going to see this more obviously. If you take pi over 2 and you add pi, where you're adding 2 pi over 2, so that's 3 pi over 2. If you take 2 pi over 3 and you add pi, again, you're adding 3 pi over 3, so that's going to be 5 pi over 3. So you'd see that you have this piece that works, and then you have this piece that works between there. And again, you just keep adding this period here to each part, and you'll keep getting additional solutions. Now for the graph, what I'm going to do again is write this as the tangent of x, I'm going to add square root of 3 to each side, so plus the square root of 3. We'll say that's less than 0. So essentially, I'm going to graph this right here as y equals the tangent of x plus the square root of 3. And I'm going to say, well, where are the y values less than 0? That's going to satisfy this inequality. So let's grab this real quick. And let's come down here and paste this in, put the solution out of the way. Essentially, if you go to this graph, again, y equals tangent of x plus square root of 3, if you want to type that into Desmos, you're going to see that you have these vertical asymptotes, and that's everywhere where this guy's undefined. Remember, it's undefined at pi over 2 plus pi n, where n is any integer. That's everywhere where cosine is going to have a value of 0. So this right here, if you look at it, this is going to be pi over 2. Then this guy right here, this would be 3 pi over 2. Then this right here would be 5 pi over 2. Then this right here would be 7 pi over 2. So on and so forth. I'm actually going to get rid of these because I think they're going to be in the way. So let me get rid of that. I'm just going to keep that one. So essentially, if you look at this, you have your vertical asymptote here, and you're trying to see where the y values are less than 0. Well, anything that's greater than pi over 2, it can't be pi over 2 itself. And then anything that's less than 2 pi over 3, right there, that's going to be where it is 0. That's an x-intercept. So this part of the graph right here is where it's going to work. That's where the y values are going to be less than 0. Again, if you take this pi over 2 and you add pi, you're going to get to the 3 pi over 2. Let me write this back in. So this is 3 pi over 2. And then if you take 2 pi over 3 and you add pi, so this is 5 pi over 3. Again, let me arrow to this so you can see this. This is 3 pi over 2. So basically, again, it's going to work. So right here, that's your 5 pi over 3. And then basically, if you follow this part of the graph right here, that's again where the y values are going to be less than 0. So you can keep adding pi to each part right here to get additional solutions. So this piece and this piece, so on and so forth. All right, let's take a look at problem 3. So here we have 2 cosine of, and then inside the parentheses, you have 2x minus pi over 6, and this is less than or equal to 1. So what I'm going to do for this problem is use a substitution technique. You can do this in different ways, but I find the substitution technique is easiest. So if you have something with a bunch of stuff going on inside, what I'm going to do is say we're going to let something like u, you could use w, whatever you want to do, be equal to this right here. So 2x minus pi over 6. So that's going to do a lot for us. It's going to make the problem a lot simpler. I'm just going to say we have 2 cosine of u is less than or equal to 1. So here, when we find solutions in terms of u, things are going to repeat every 2 pi. Okay, so that's a little bit easier to work with than to try to figure this out. If you look at this, you have this 2 right here that's multiplying x. When we look at the graph at the end, you're going to again see that that is changing your standard period for cosine. Normally it's 2 pi, but because you have the 2 that's multiplying the x there, now it's going to be pi. And again, I'll show you that later on. So let me just grab this real quick. Let me come to a fresh sheet. We're just going to solve this, and then we'll go back up in a moment. So all you have to do for this problem is isolate the cosine of u on one side. And to do that, I'm just going to divide both sides of the inequality by 2. Cancel this. And we'll say that the cosine of u is less than or equal to 1/2. Okay, let's go to the unit circle, and let's paste this in. So again, I would just ask the question, where is the cosine of u equal to 1/2. Now the period for this, or how often the solutions are going to repeat, is going to be 2 pi. So I would solve this from 0 to 2 pi and see what we get. So u would be equal to, where is the cosine value 1/2? Well, it's going to be at pi over 3. There's your cosine value of 1/2. And then also, cosine is positive in quadrant 4. So where do I have a pi over 3 reference angle? So that 5 pi over 3, again, the cosine value is 1/2. So let me circle that as well. So let's put pi over 3 and then 5 pi over 3. Now, because this is a non-strict inequality, these will actually work as a solution. So you got to keep that in mind. So where's the cosine value less than 1/2? We know where it's equal to 1/2. If I look between these guys, you'll notice that the cosine value is actually greater than 1/2. You have square root of 2 over 2, square root of 3 over 2. You have 1, square root of 3 over 2, square root of 2 over 2. So this is not going to work. What you're going to want is this part right here. So basically between pi over 3 and your 5 pi over 3, that's what you want to put down as your solution. Now again, this is in terms of u. Let me get rid of this. Just keep in mind that these work. And I'm going to write this out. So we're going to say u, so not x yet, but u is greater than or equal to, let's start with pi over 3. So pi over 3. Again, the period here, because it's in terms of u, this is going to be 2 pi, so 2 pi n, where n is any integer. And less than or equal to, let's go 5 pi over 3. So 5 pi over 3. And again, plus 2 pi n, where n is any integer. Now let me go ahead and grab this real quick, and let's come back up here and paste this in. All right, so because we let u be equal to this, what we're going to do is make another substitution here. So basically, let me say that we have 2x minus pi over 6. So that's going to be in the middle. And this is greater than or equal to this pi over 3 plus 2 pi n. And it's less than or equal to 5 pi over 3 plus 2 pi n. So now all we have to do is solve this for x and we're good to go. So basically what I would do first is add pi over 6 to each part. So we're going to add pi over 6 to each part. So let's do that like that. So this is going to cancel. And essentially if I do pi over 3 plus pi over 6, let's multiply this by 2 over 2. This would be 2 pi plus pi over the common denominator of 6. So that would be 3 pi over 6. 3 divided by 3 is 1, and 6 divided by 3 is going to be 2. So this would end up being pi over 2. So let me get rid of this. I'm just going to rewrite it on another line so nobody gets lost. So this right here, if we add, we would get pi over 2, and then plus your 2 pi n. And this is less than or equal to. This is canceled, so let me put 2x, which is less than or equal to. So now you've got to do 5 pi over 3. I need a common denominator, so let me multiply this by 2 over 2. So that'd be 10 pi over 6. So let's say this is 10 pi over 6. And then basically plus your pi over 6. So 10 pi plus pi would be 11 pi. So this would be 11 pi over 6. So 11 pi over 6. And then basically plus 2 pi n. And now I just want x by itself. So I'm multiplying here by 2. So what you need to do is divide each part by 2. A good way to do this, because you have fractions involved, is just to multiply everything by a half. And let me show that so nobody gets lost. So let me come down here and say you're going to have 1/2 times pi over 2 plus 2 pi n times 1/2 less than or equal to 1/2 times 2x, which is less than or equal to 11 pi over 6 times 1/2 plus 2 pi n times 1/2. Maybe that n could be a little bit better there. Okay, let me grab this real quick and slide it over so it fits. 1/2 times pi over 2, that's going to be pi over 4. And then plus, the 2's would cancel. So notice that you get pi n here. Remember when I first introduced the problem, I said the period would be pi. So now you're seeing you get pi n. And then we have this is less than or equal to, the 2's would cancel, so your x, which is less than or equal to. This here would end up being 11 pi over, 6 times 2 is 12. And then plus, again, the 2's would cancel, so you're going to have your pi n, where n is an integer. So this is one way to get the solution. There's obviously other ways to do it, but I think this is the easiest way to do it, especially if you're first starting out. So let's go ahead and grab this real quick. I want to quickly come back up and remind you what the original problem was. What I'm going to end up doing is graphing this by subtracting 1 away from each side. And we're going to look for where the y values are less than or equal to 0. So here's our little graph. Let me go ahead and paste this in. Put that right there. Again, this 2 that's multiplying this x here, that's creating a period that is pi, right? Remember, if you have the standard period of 2 pi, you're going to divide by this guy that's multiplying x here. So 2 pi divided by 2 gives you pi. So that's where that period's coming from. So when we look at the x-intercepts, or where this guy is 0, you'll see that you have a pi over 4, so that's going to be right here. And then you have 11 pi over 12, so that's going to be right here. So where is it less than or equal to 0? Well, these would be included because, again, you have a non-strict inequality, and then all of this right here. So this right here is where we're less than or equal to 0, so this whole thing. So that's those guys right there. And again, you can add pi to each part and get additional solutions. So pi over 4, if you added pi to that, you add 4 pi over 4, that would give me this 5 pi over 4. 11 pi over 12, if I added pi to that, that's 12 pi over 12, and so that would be 23 pi over 12, so that's this right here. And again, anywhere between that would be less than 0, so there's your solution there. And again, you can keep doing this to get this part and this part. Anywhere where the y values are going to be less than or equal to 0, you would satisfy that inequality. All right, for problem 4, we have -3 plus 2/5 sine of 2x minus 5 pi over 6, which is less than -16/5. All right, let me slide down here just a little bit. The idea, again, just like in the last problem, I'm going to let something like u be equal to this inside part right here. This is going to make it a lot easier to solve. So 2x minus 5 pi over 6. And then you could say this is -3 plus 2/5. And then sine of u is less than -16/5. So let's solve this in terms of u, and then basically we'll come back and substitute like we did in the last problem. Okay, let's paste this in on a new sheet. Essentially, I want to isolate the sine of u on one side and have a number on the other. So let's go ahead and add 3 to both sides of the inequality. So you could write 3 as 15 over 5, just so that you would have a common denominator. And basically, this would cancel over here. You would have 2/5, and then sine of u is less than -16 plus 15, that's going to be -1. So this right here would be -1/5. Now what I would do, because I have 2/5 that's multiplying the sine of u, I would go ahead and multiply both sides by 5 halves, so the reciprocal there. And let's see what that does. So basically, these are all going to cancel. So you're just going to have a 1 there. So 1 times the sine of u is just the sine of u. So the sine of u is less than. The 5s would cancel. So this is negative 1/2. Okay, let's come down here and paste this in. So again, you would ask the question, where is the sine of u equal to negative 1/2? And because in terms of this u right now, the period is 2 pi, so I can say I'm just going to solve this over the interval from 0 to 2 pi and see what that produces for me. So I want to look in quadrants 3 and 4, where sine is negative, and I want a reference angle of pi over 6. So that's going to be 7 pi over 6, there's your sine value of negative 1/2, and then 11 pi over 6, there's your sine value of negative 1/2. Okay, so let's go ahead and say that we're going to look between 7 pi over 6 and 11 pi over 6 and see, are the sine values less than negative 1/2? Yes. You can see that basically this is negative square root of 2 over 2, negative square root of 3 over 2, negative 1, negative square root of 3 over 2, negative square root of 2 over 2. So basically this right here is what we want. So this right here is what we want. We don't want values on the other part because, again, that's where you would be actually greater than negative 1/2 for the sine values. So to write our solution, we're going to say that u is strictly greater than. We're going to have this 7 pi over 6. And again, things are going to repeat every 2 pi here. So I'm going to put plus 2 pi n. And less than, we're going to go 11 pi over 6. So 11 pi over 6. And then plus 2 pi n. And let's go ahead and paste this in here. So again, u is equal to this. So I'm just going to plug this in here for u. So we're going to say that we have 2x minus 5 pi over 6 is greater than. We have 7 pi over 6 plus 2 pi n. And less than, we have 11 pi over 6 plus 2 pi n. And let me come down here to a little fresh sheet. Just like in the last problem, you need to isolate x in the middle. So I'm going to add 5 pi over 6 to each part here. And let's see what that does. So add 5 pi over 6. So essentially here you already have a common denominator. If you did 7 pi over 6 plus 5 pi over 6, that would give you 12 pi, which is coming from 7 pi plus 5 pi over 6, which is going to be equal to 2 pi. So this right here on the left is 2 pi. And then plus, don't forget this part right here, so 2 pi n. Then this is less than, this would cancel, your 2x, which is less than, you have your 11 pi over 6 plus 5 pi over 6. So 11 pi plus 5 pi is going to be 16 pi. So this right here would be 16 pi over 6. And each here is divisible by 2. 16 divided by 2 is 8. 6 divided by 2 is 3. So this ends up becoming 8 pi over 3. So 8 pi over 3. And then plus, don't forget your 2 pi n. All right, the next step, again, if you want x by itself, since you have 2 that's multiplying x, you could divide everything by 2, or you can multiply everything by 1/2, which I think is a little bit easier because you have a fraction involved. So let's go through and say we have 2 pi times 1/2 plus 2 pi n times 1/2, which is less than 2x times 1/2. Let me actually do this in a different order. So 1/2 times 2x like that, which is less than, you have your 8 pi over 3 times 1/2. And then plus, let me slide this over so it fits, you have your 2 pi n times 1/2. All right, so let's go through and say the 2's would cancel, so you have pi. And then plus these 2's would cancel, so you have pi n. So this is going to be less than. The 2's would cancel, so this is x, which is less than. So 8 divided by 2 is 4. So this is 4 pi over 3. And then plus the 2's here would cancel, so you get pi n. So that is your solution in terms of x. So x is greater than pi plus pi n, and less than 4 pi over 3 plus pi n. Let me grab this real quick. So coming back to the original inequality, when I graph it, it's going to be cleaned up a little bit. I just want you to remember this was a less than. So we're going to be looking for y values that are less than 0. All right, let's look at the graph. Again, we just cleaned this up a little bit, and we're looking for where the y values are less than 0. Now, on the practice test, I did give a different answer, but I'm going to explain where that's coming from and why it doesn't matter. So first off, you'll notice that you have this plus pi n and plus pi n. Again, I want you to know that that's coming from this 2 that is multiplying this x here. Again, the standard period, if you had y equals the sine of x, that's 2 pi. But if you have this 2x here, this 2 that's multiplying x, you're taking your standard period of 2 pi, you're dividing by 2, and you're getting pi for the period. So that's why this guy right here is plus pi n and plus pi n. Now, in terms of looking at the x-intercepts, we have these right here that we can start with. So we have pi. So basically, that's where this guy is going to be 0 in terms of the y value, and then 4 pi over 3. So where is it less than 0? Well, between those guys. So between these guys, so between pi and 4 pi over 3. So you can write your solution like this. It works just fine. Again, if you added pi to pi, you would get to 2 pi. If you added pi to 4 pi over 3, you're adding 3 pi over 3. So that would give you this 7 pi over 3 right here. And again, if you go between those guys, you're going to have y values that are less than 0. So you can get this piece, and of course this piece, and so on and so forth. Now, the way I wrote the solution, I actually used this one and this one to start things off. And I said, okay, between 0 and your pi over 3. So if you started with pi and you subtracted away pi, you would have 0. If you started with 4 pi over 3 and you subtracted away pi, or 3 pi over 3, you would have pi over 3. And if you use those guys to write it, what you could do is say that x is greater than, you could go 0 plus pi n, which is just pi n, and less than, you can go pi over 3 plus pi n. So another way to write it, this way is fine, this way is fine, whatever you want to do. I'll probably just stick with this one because that's how I wrote it on the practice test. So let's just go ahead and say that x is greater than pi n and less than pi over 3 plus pi n, where n is any integer. All right, let's take a look at problem 5. So here we have 1 minus the cosine of x is greater than the sine of x. So for this problem, I'm going to use the test point approach. So you'll remember this is what we used when we solved quadratic inequalities, rational inequalities. It's basically the same concept. I would write this as 1 minus the cosine of x, subtract the sine of x away from each side. So minus the sine of x, we're going to say, where is that greater than 0? Let me go ahead and grab this real quick, comment down here. And essentially, you're going to replace this inequality symbol with equals. You're just going to solve that related equation. So 1 minus the cosine of x, then minus the sine of x. Where's that equal to 0? Well, because we have cosine of x and sine of x, let me add the sine of x to each side. So let me say we have 1 minus the cosine of x is equal to the sine of x. And essentially, I'm going to square both sides. So you're going to have 1 minus the cosine of x squared is equal to sine squared x. Here's where you have to be careful. When you square both sides of an equation, you have to check your solutions. There's a possibility of extraneous solutions, so you have to be real careful here. So let me slide down. We're going to come back up and check in a moment. This you have to expand. So it's 1 squared, which is 1, minus 2 times this guy, so it's just minus 2 cosine of x, and then plus this last guy squared, so cosine squared x. And this equals, instead of sine squared x, I'm going to rewrite this. Remember, you can put that as 1 minus cosine squared x, and that's just coming from sine squared x plus cosine squared x is equal to 1. If you subtract cosine squared x away from each side, you get the identity sine squared x is equal to 1. Let me go ahead and write it. So 1 minus the cosine squared x. And so I'm just plugging in for sine squared x, this 1 minus cosine squared x. Okay, so now that we have this set up, I'm going to subtract 1 away from each side of the equation. That cancels. And then basically I'm going to add cosine squared x to both sides of the equation. So that cancels. This is 0 on the right. Let's say cosine squared x plus cosine squared x is 2 cosine squared x, and then minus 2 cosine of x, and this equals 0. So I'm going to solve this using factoring. I'm going to pull out a 2 cosine of x from each part. So here you would just have the cosine of x, and then minus here you would just have 1, and this equals 0. So what I'm going to do is solve 2 cosine of x is equal to 0, and then or cosine of x minus 1 is equal to 0. So for this one, you would divide both sides by 2. So you're just going to solve cosine of x equals 0. For this one, you would add 1 to both sides. So you're going to see where the cosine of x is equal to 1. Now, in terms of this guy right here, your period, if you were solving this equation, or if you go back to your original equation that you set up, the period's going to be 2 pi. So solutions will repeat every 2 pi. So let me go ahead and grab this real quick. And again, we're going to come to the unit circle, and we're going to think about where the cosine of x is equal to 0. Again, I'm going to solve this from 0 to 2 pi for right now. And so x would be equal to, let's go ahead and say, where's the cosine of x equal to 0? Well, that's going to be at pi over 2, and then also 3 pi over 2. So let me write those in. So you can have pi over 2, and then 3 pi over 2. Now, 3 pi over 2 is going to be an extraneous solution, but I'll show you that in a moment. And then when we think about where the cosine of x is equal to 1, well, that's going to be right here at 0. So there's your cosine value of 1. So let's go ahead and put that down as 0. Okay, let me grab this real quick, and let me come back here and paste this in. So essentially what we're going to do is figure out which solutions work, and you do that by plugging in. We know that the cosine of pi over 2 and the cosine of 3 pi over 2 is 0. So in each case, you would get 1 on the left. On the right, it's going to change. So the sine of pi over 2 is 1, so this works. But the sine of 3 pi over 2 is negative 1, so that wouldn't work. So this one right here, you can just mark it out. Now this one right here with 0, it's going to work. So the cosine of 0 is 1. So 1 minus 1 is 0. And the sine of 0 is 0. So this one works as well. Okay, so basically get rid of this. And essentially you're using these guys to split up the number line. So you have 0 and pi over 2. Let me grab this real quick. And I want to come back up. We're going to see this in a moment. I've already written it into the table. So 1 minus cosine of x minus sine of x is greater than 0. Let me come down and basically let me paste this back in here. And let me get rid of all of this. And I'm just going to show you the intervals we're going to set up here. So basically these are the critical values. So you're going to look at 0 and pi over 2. So you're just going to have an interval between 0 and pi over 2 and an interval between pi over 2 and 2 pi. So again, I've already set everything up for us. We have 1 minus the cosine of x minus the sine of x. Where's that greater than 0? So you're just going to pick something in each interval, plug it into your calculator, and see if it's positive or negative. If it's positive, it's going to satisfy the inequality. If it's negative, then it's not. So between 0 and pi over 2, I'm going to pick pi over 3. Plug that in. You're going to get about negative 0.37. Again, I don't care what the value is. I just want to know if it's positive or negative. Because it's negative, it's not going to work. Then in this interval between pi over 2 and 2 pi, I'm going to pick 2 pi over 3. You plug that in, you get about 0.63. So this is going to work. So if we want to write our solution, you can come back and say, okay, well, between pi over 2 and 2 pi, that is where it's going to work. So let's put that like that. And so essentially, because it's a strict inequality, we're not going to include either of those. And because the period is 2 pi, again, if you go back to this form here, if I graph y equals 1 minus the cosine of x minus the sine of x, the period of this is 2 pi, the period of this is 2 pi, so the least common multiple is 2 pi, so I know things repeat every 2 pi. Okay, so coming back down, let's say that x is greater than pi over 2 plus, again, the 2 pi n, where n is any integer. Let's make that better. And less than, we're going to go 2 pi plus 2 pi n, where n is any integer. So let's go ahead and grab this real quick. Again, when I graph this, I'm going to be looking for where the y values are greater than 0. Okay, let's come down to the graph. I'm going to paste in my solution. So again, where is it equal to 0? Well, we found our pi over 2. We have pi over 2. And we also found at 2 pi, it's going to be equal to 0. So if you look between those guys, we're going to have where the y values are greater than 0. That's what we're looking for. So this right here, this would be a solution. So between pi over 2 and 2 pi. Now again, if you want to add 2 pi to each part, you take pi over 2 and you add 4 pi over 2, that's getting a common denominator, you're going to get to this 5 pi over 2. If you take 2 pi and you add 2 pi, you're going to get to 4 pi. And again, between those values, you'd have y values that are greater than 0. And so again, you would satisfy that inequality. So x here is greater than pi over 2 plus 2 pi n and less than 2 pi plus 2 pi n, where n is any integer. All right, let's take a look at problem 6. So here we have negative cosecant of x plus cotangent of x is greater than or equal to negative 1. So again, for this type of problem, we're going to go back to the test point method. Let me write negative cosecant of x plus cotangent of x. Let me add 1 to both sides. So plus 1, where is this greater than or equal to 0? So that's what we're trying to figure out. So let me go ahead and grab this real quick. And let me come down here. Now I'm just going to warn you in advance, this problem is a little bit tricky because when you think about the cosecant of x and the cotangent of x, you have an issue where it's going to be undefined at certain points. And actually, when you look at the graph, it's going to be a little bit complicated. So I'm going to really take my time and go slow. So first off, if you look at something like y equals negative cosecant of x, plus cotangent of x plus 1, if I asked you for the domain of that, what would it be? Remember that the cosecant of x, by definition, so the cosecant of x is 1 over the sine of x. So this would be undefined anywhere where the sine of x is 0. So that's going to be at 0, pi, 2 pi, 3 pi, so on and so forth. So basically pi n, where n is any integer. Then if you look at the cotangent of x, this is going to be the cosine of x over the sine of x. So again, anywhere where the sine of x is 0. So pi n, where n is any integer. So if I wanted to write the domain for this, so the domain, I would say it's the set of all x such that x is not equal to pi n, where n is any integer. So anything other than that, you'll be good to go for plugging in for x. Let me erase this. We're going to bring this back up later on when we look at the graph. Let's just think about how we could solve this. I'm just going to first replace this with equals. So negative cosecant of x plus cotangent of x plus 1 is equal to 0. The goal here would be to isolate one of these, square both sides, and use an identity. So I'm just going to add cosecant of x to each side of the equation. And so this would cancel. You're going to get that the cotangent of x plus 1 is equal to the cosecant of x. Again, you have to be careful when you square both sides of an equation because you can get extraneous solutions, and in this case, we will. So let's go ahead and square both sides. So cotangent of x plus 1 squared is equal to cosecant squared x. So this right here, if you expand it, you get cotangent squared x, so just squaring the first guy, plus 2 times this guy, so 2 cotangent of x, and then plus this last guy here, 1 squared, which is 1, and this equals cosecant squared x. Okay, I'm just going to erase things as I go. I'm going to move this up here. I want you to recall that when we studied the Pythagorean identities, we had the identity that the cosecant squared x was equal to 1 plus cotangent squared x. So again, if these guys are a match, you can plug in this right here for this right here. So I'm going to say that I have cotangent squared x plus 2 cotangent of x plus 1 is equal to 1 plus cotangent squared x. And essentially, I'm going to subtract 1 away from each side, so that's going to cancel and that's going to cancel. And I'm going to subtract cotangent squared x away from each side of the equation. So that's going to cancel. The right side is 0, and so this is going to cancel. You get 2 cotangent of x is equal to 0. Divide both sides by 2. This cancels, and you're going to get cotangent of x is equal to 0. So let's think about that for a moment. Let's grab this real quick. Let's come down here and paste this in. Again, if I think about the cotangent of x, this is the cosine of x over the sine of x. So where would that be equal to 0? Well, it's where the cosine value is 0 and the sine value is not 0. So you're going to see that that's going to be right here at pi over 2, and then that's also going to be right here at 3 pi over 2. I'm going to go ahead and solve this over the interval from 0 to 2 pi, because again, if I thought about y equals negative cosecant of x plus cotangent of x plus 1, things are going to repeat there every 2 pi. Right? Because the period for this is 2 pi and the period for this is pi. So the least common multiple between 2 pi and pi would be 2 pi. So I know things are going to repeat every 2 pi. So let me come back down and just say that the solutions, or the proposed solutions, because one of these is not going to work, from 0 to 2 pi, basically your x is going to be pi over 2 and then 3 pi over 2. And let's come back up here. So let me paste this in and let me just show you that one of these is not going to work. So the cotangent of pi over 2 and the 3 pi over 2, in each case, that's going to be 0. So the left side is always going to be 1. On the right, though, the cosecant of pi over 2 is going to be positive 1. So this one does work. We're okay. But the cosecant of 3 pi over 2 is a negative 1. So that's negative 1. So that would be false if you do it that way. And so basically this doesn't work. So let me get rid of this and let's get rid of this. So essentially when you split up the number line, you're going to be using pi over 2 as a critical value. But again, you have to also consider where this guy is undefined, right? When we work with this problem. So you have your cosecant of x involved and your cotangent of x involved. And we already said that x cannot be pi n where n is any integer. So we would say 0 and pi there, those are going to have to be excluded because in each case you're going to get division by 0, which is undefined. So that's going to give me an interval between 0 and pi over 2, and then between pi over 2 and pi, and then between pi and 2 pi. So basically I'm just going to set that up and test. Again, I've already set the table up for us. So I have negative cosecant of x plus cotangent of x plus 1. Where is that greater than or equal to 0? So we already know it's equal to 0 at pi over 2. But we're trying to figure out where is it greater than 0. So I'm just going to pick something in each interval and test. So in this first interval between 0 and pi over 2, I'm picking pi over 6. Plug that in, you get about 0.73. So this is positive, so it's going to work. Then here, between pi over 2 and pi, if you work in this interval, let's say we pick 5 pi over 6, we get about negative 2.73. So this is negative, so it's not going to work. Then in the interval between pi and 2 pi, well, basically we're picking 7 pi over 6. You plug that in, you get about 4.73. So this is positive, so this is going to work. Now the solution here is a little bit complicated to put together. Okay, so coming back to the unit circle, let's think about our solution. So we know that things work in this interval right here. And for right now, I'm not going to include anything. So I'm just going to say between 0 and pi over 2. Pi over 2 will be included, but I'll get to that in a moment. And then things are going to work between pi and 2 pi. So basically right there. So you don't want to include this right here. It would be undefined at 0, 2 pi, 4 pi, 6 pi, so on and so forth. And you don't want to include this right here. It would be undefined at pi, 3 pi, 5 pi, 7 pi, so on and so forth. But you do want to include this one right here because that's what makes it 0, and this is a non-strict inequality. So putting the solution together is a little bit tedious. Essentially, you're going to say that x is strictly greater than. You're going to start with 0. So you're going to go 0 plus 2 pi n, because again, things are going to repeat every 2 pi here. But 0 plus 2 pi n is just 2 pi n. So I'm going to put 2 pi n. So that's 0, 2 pi, 4 pi, so on and so forth. Then we'll say, and it's less than this pi over 2, but I want to include that. So let me put less than or equal to. So the pi over 2 and then plus 2 pi n, where n is an integer. Then you're going to use the keyword or. So that's how we're going to join this here. And you're going to think about this part right here. So maybe I can do that in a different color, so it's a little bit more obvious what we're doing. Again, we're breaking this up into two separate parts. So this right here, so I'm going to say that x here is strictly greater than, you don't want to include pi, so you're going to say pi plus 2 pi n, and less than, this would be 2 pi, so 2 pi plus 2 pi n. Okay, let's take a look at the graph. So again, we want to know where negative cosecant of x plus cotangent of x plus 1, where's that greater than or equal to 0? Now, before I move forward with this, I want to explain some differences between the graph I'm giving you here and what you might see on an online graphing calculator like Desmos. We know, because we thought about it earlier, that the domain for this guy right here is going to be the set of all x such that x is not equal to pi n, where n is any integer. So again, if you plugged in something like 0, pi, 2 pi, 3 pi, you're going to get undefined here. Now, if you want to split this up into different cases, you can say that at 0, 2 pi, 4 pi, 6 pi, so I'm going to call that 2 pi n. So at this case right here, you're going to actually get a hole in the graph. So that's why you see these holes here. So here, 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 here. So let's just go with this. This is 0, 2 pi, 4 pi, 6 pi. Now, if you go to Desmos and you mouse over an x value of 0, you're going to get this right here, and it'll actually give you a hole, and it'll say it's undefined. And that's because they're actually plugging in 0, and so that is undefined. But if you go over to what looks like 2 pi, they're going to approximate that. Let's just say they use about 6.28, and you can actually plug that in there because it's not actually 2 pi. You will not get undefined. You will get something that's very, very close to 1. So as you get closer and closer to 2 pi without touching it, you're going to get closer and closer to a y value of 1, but you'll never touch it. So that's something that would come up when we talk about limits, and we'll get to that later on in the course. But for right now, you have to know that at 2 pi or 4 pi or 0 or 6 pi or something like that, basically 2 pi n, you're going to get a hole in the graph because this guy is going to approach a y value of 1, but it won't touch it. Now, the other scenario occurs at pi, and then you have 3 pi, and then 5 pi, so on and so forth. So let's say that's pi plus 2 pi n. Well, basically there, you're getting a vertical asymptote. So let me write v period a period for vertical asymptote. Basically what's happening is, as you approach pi or 3 pi or 5 pi, what's happening is your y values are approaching positive or negative infinity, just depending on which direction you're approaching it from. So basically that's why you're getting a vertical asymptote there. Okay, so now that we understand the graph and why it might be different from what you're going to see, let's think about our solution here. Basically, we're looking for, again, where the y values are going to be greater than or equal to 0. So let me start right here. This right here was 2 pi n. So that's 0, 2 pi, 4 pi. So 0, 2 pi, 4 pi, so on and so forth. So x is greater than 2 pi n and less than or equal to pi over 2 plus 2 pi n. So let's take this piece right here. So this piece right here, and that's going to include this pi over 2 because that's where we're greater than or equal to 0. So you have this part right here. And again, if you're adding 2 pi to each part, well, basically, again, 0 plus 2 pi is 2 pi, and pi over 2 plus 2 pi, that's going to be 5 pi over 2. So you're going to get this piece right here. And if you keep doing that, you're going to get this piece right here, and so on and so forth. When we think about the other part, we have or x is greater than pi plus 2 pi n and less than 2 pi plus 2 pi n. So we're thinking about this guy right here is going to be pi. So let me write that in. So this guy right here is going to be pi. That's your vertical asymptote. So we know we can't actually plug in pi. Well, here we're saying that x is greater than pi, so that's going to be up here, and less than 2 pi. So that's going to be this piece right here. So let me do this in a green color. So this piece right here, well, of course, we're going to be greater than 0 there. So that's going to be right here. But we're going to have to stop right there at that 2 pi because we're undefined. So that's where it's not going to work. Again, because at 2 pi, 4 pi, 6 pi, 8 pi, it's not going to work. So basically, let me draw this in like this. So this piece like this. And basically, you could do this piece right here like this if you wanted to. So you can keep going like that. So basically, you see the solution and how it repeats. So this is one way you could write it. You could say x is greater than 2 pi n and less than or equal to pi over 2 plus 2 pi n. Again, because this is included and this is excluded. Or x is greater than pi plus 2 pi n and less than 2 pi plus 2 pi n, where n is any integer. And again, that's coming from the fact that things like pi and 2 pi are going to be excluded because that's where you're undefined. All right, let's take a look at problem 7 now. So we have the cosine of 2x plus 2 is greater than negative 3 cosine of x. So let me add 3 cosine of x to both sides. And I'm going to solve cosine of 2x plus 3 cosine of x, and then plus 2 is greater than 0. So let me grab this real quick, and we'll just come down here. Again, I'm just going to solve the related equation, get some critical values, and then we're just going to set up some intervals and test. So I'm going to go cosine of 2x plus 3 cosine of x plus 2 is equal to 0. Now again, when you think about the period here, it's going to be 2 pi. The period for this guy right here, this part, is going to be pi. Because if you think about y equals cosine of 2x, well again, that 2 that's multiplying the x, that's going to speed things up. So it's 2 pi divided by 2, which gives you pi. Then when you look at this part here, and it doesn't matter if you think about it as 3 cosine of x or cosine of x, when you think about the period for that, it's going to be 2 pi. So this is just the standard 2 pi. And again, if you graph y equals cosine of 2x plus 3 cosine of x plus 2, which we're going to do in a moment, you'll see the period is 2 pi. So it's just the least common multiple of these two periods. So 2 pi and pi, so the LCM is going to be 2 pi. All right, so now that we know that, let's make a little substitution. So we know that the cosine of 2x, we have 3 different formulas we can use. Because there's a cosine of x here, I'm just going to say this is equal to 2 cosine squared x and then minus 1. So again, since this right here matches this right here, I'm just going to take this right here and plug it in for that right there. All right, so let's say we have 2 cosine squared x minus 1, and then plus 3 cosine of x plus 2, and this equals 0. All right, so we know that negative 1 plus 2 would be positive 1. So I'm just going to erase this and put this like this. And essentially all you need to do is factor the left side. We've factored this particular guy many times throughout this section, so I think a lot of you will know it off the top of your head. It's basically 2 cosine of x and then cosine of x. And again, because this is a plus 1 and this is a plus 3 here, well, basically it's just plus 1 here and plus 1 here. So the outer, if you want to check this, let's say it's plus 2 cosine of x, and then the inner is plus cosine of x. So of course, 2 cosine of x plus cosine of x, that's 3 cosine of x. So that's what I'm looking for. All right, so to solve this with the zero products property, I'm just going to say 2 cosine of x plus 1 is equal to 0. Subtract 1 away from each side. So you have 2 cosine of x is equal to negative 1. Divide both sides by 2. So we have cosine of x equals negative 1/2. Then you have or. For this one, you have cosine of x plus 1 equals 0. So that's going to be cosine of x. Let me make this s a little bit better. We'll say that's equal to, if I subtract 1 away from each side, it'll be negative 1. Okay, let me grab this real quick. Come down to the unit circle here. And basically, again, because when we established earlier that the period would be 2 pi, well, I'm just going to solve this over the interval 0 to 2 pi, like this, and basically see where the critical values are. So for cosine of x equals negative 1/2, we know cosine is negative in quadrants 2 and 3, and I'm looking for where I have a reference angle of pi over 3. So that's 2 pi over 3. There's your cosine value of negative 1/2. And then at 4 pi over 3, there's your cosine value of negative 1/2. Then you also have cosine of x equals negative 1. Well, that's just going to be right here at pi. So essentially, you're going to have an interval from 0 to 2 pi over 3, and then from 2 pi over 3 to pi, and then from pi to 4 pi over 3, and then from 4 pi over 3 to 2 pi. So I have everything set up already. So we have cosine of 2x plus 3 cosine of x plus 2 is greater than 0. So I'm just using this form here. If you want to make the substitution and write it the other way, that's up to you. It's the exact same thing. So basically, we see in each interval that I've already picked a little value and done a test. I'm just trying to figure out where it's greater than 0. So I want the positive guys only. So in this interval, if I plug in pi over 4, I get about 4.12. So this would work, right? Because it's greater than 0. And then in this interval, if I pick 3 pi over 4, I get about negative 0.12. So this is negative. It's not going to work. In this interval, if I pick 5 pi over 4, I get about negative 0.12. So again, it's negative. It's not going to work. And then in this interval, I'm going to pick 7 pi over 4. So again, I get about 4.12. So this is going to work. It's positive. So between 0 and 2 pi over 3, and then between 4 pi over 3 and 2 pi. So let's come back to the unit circle. Again, when you have a solution like this, it can be a little bit complicated. Let me put this like this. So this right here was an artificial boundary that we created because I solved over the interval from 0 to 2 pi. So really, there's nothing stopping me from doing it continuously like this. So if you want to put your solution together here, what I would do is say, let's just start with 4 pi over 3. So x is greater than 4 pi over 3. And then again, you go plus 2 pi n, where n is any integer. Maybe I could slide that down a little bit. And we'll say, and it's less than. Again, this is not 2 pi over 3. I'm starting here. So basically, if I rotate like this, I'm going to add 2 pi to this. So it's 2 pi over 3 plus, I'm going to go 6 pi over 3. That's me putting 2 pi in terms of having a common denominator. So basically, this is 8 pi over 3. So let's say this is 8 pi over 3 and then plus 2 pi n. Again, if you wanted to rotate clockwise here, so that would be 4 pi over 3 minus 6 pi over 3. So this right here, if I rotate it clockwise, let me show this. This right here, like that, that would be negative 2 pi over 3. So if you want, you could write the solution as x is greater than negative 2 pi over 3, and then plus 2 pi n, and I never leave enough room for this. Let me do it like that. And then basically, and it's less than, well, now if you're starting from negative 2 pi over 3 and you're swinging around here, so basically it would be less than this 2 pi over 3. So this is 2 pi over 3 and then plus 2 pi, and let me slide over a little bit so I can fit this, n. So this is what I listed for the practice test answer, so I'll just go with this. When we get to the graph, I'll show you this one as well. So let's go ahead and grab this real quick. And let me come down here to the graph and just paste this in so we can look at this. Again, I'm graphing y equals the cosine of 2x plus 3 cosine of x plus 2. Again, the period is 2 pi because the period for this guy right here is going to be pi. The period for this guy right here is going to be 2 pi. So you want the least common multiple of those periods, and that's going to be 2 pi. So that's going to be the period for the whole thing. All right, so if we look at this answer here, so 4 pi over 3, let's find that. So that's right there. That's where this guy's going to be 0. And then 8 pi over 3, that's going to be right there. So that's where this guy is 0. Now that's not included because we have a strict inequality. We're trying to figure out where it's greater than 0. So basically, if you look at this piece right here, so greater than 4 pi over 3 and less than 8 pi over 3. So that's one way you can put the solution. And again, you can add 2 pi to each part. So 4 pi over 3 plus 2 pi, that's me adding 6 pi over 3, so that's going to be 10 pi over 3, and then 8 pi over 3 plus 6 pi over 3, that's going to be 14 pi over 3, that's going to be right there. And again, you can just go through and say, okay, well, the y values would be greater than 0 between those two guys. So that one there. And then let me show you the other one that I talked about. Remember I said if you rotate clockwise, you get this negative 2 pi over 3. And I got that from taking the 4 pi over 3 and subtracting away 2 pi. So that's going to be right here. So that's down here. So it's negative 2 pi over 3. I know this up here kind of looks like it's over there, but this is in line with this. So this is your negative 2 pi over 3. And then we would go over here to 2 pi over 3. And again, that's where your y values are going to be greater than 0. So that right there. Let me just go back real quick. So this rotating this way clockwise, if I started here and said, well, it was greater than negative 2 pi over 3, and then I could swing around to 2 pi over 3, so it would be less than 2 pi over 3. So greater than negative 2 pi over 3 and less than 2 pi over 3. So that's where I'm getting those guys from. So again, coming back, you could have listed your solution that way. So you could say negative 2 pi over 3 plus 2 pi n is less than x, which is less than 2 pi over 3 plus 2 pi n, where n is any integer. But I'm just going to list it this way. This is what we did on the practice test. So let's say that x is greater than 4 pi over 3 plus 2 pi n and less than 8 pi over 3 plus 2 pi n, where n is any integer. All right, let's take a look at problem number 8. So here we have sine squared of 2x is greater than or equal to 3 cosine squared x. So what I'm going to do to start things off is just subtract 3 cosine squared x away from each side of the inequality. So let's write sine squared. I'm going to wrap this so of 2x like this, and then minus 3 cosine squared x. And of course, now this would be greater than or equal to 0. Again, all I did was subtract 3 cosine squared x away from each side of the inequality. So that gives me this form here. So let's come down here. I think we know the drill at this point. We're just going to replace this inequality symbol with equals. We're going to solve and then generate some intervals, and we're going to test. So here, I'm just going to write sine squared of 2x. I'm going to change that in a moment. Then minus, we have 3 cosine squared x. And I'm going to say, where is this equal to 0? Now, you've seen for most of these problems, we've solved over the interval from 0 to 2 pi. Not every problem. We had one with tangent. We also had one with stuff inside where we made a substitution. But generally speaking, the problems that we've seen, we've solved the equation from 0 to 2 pi. And then basically, we've gone through and set up the intervals, and then we test. In this particular case, we're going to solve from 0 to pi. Now, where are we getting that from? Essentially, we haven't really talked about this yet, but if you looked at the period of something like y equals sine squared of 2x, it's going to be pi over 2. Now, there's a little formula you can use. You can look it up online if you want. This doesn't come up too often, so I'm not going to spend a whole lot of time on where it comes from or anything like that. I'm just going to give it to you, and it's given to you in the practice test as well. So the period for this, whether you look at it as, let's say, y equals 3 cosine squared x, or if you just want to look at y equals cosine squared x, either way, the period for this is going to be pi. And again, you can pause the video, go on Desmos, and look at it. You'll be able to visually see that for each part here, the period that I'm giving you is correct. Now, when you want the period of the whole thing, let's say you graph y equals sine squared of 2x minus 3 cosine squared x, what is that going to be? Again, it's the least common multiple of these periods, so it's going to be pi. So that's why when I solve this equation, I'm going to solve it over the interval from 0 to pi, 0 being included, pi being excluded. All right, so what I'm going to do now is just make a little substitution. I think we all know that the sine of 2x, there's only one formula. It's basically going to be 2 sine of x cosine of x. Now, you have to be careful because you have this squared guy involved. So what I do to not make a mistake, I go ahead and rewrite this as the sine of 2x just being squared like that. So that's basically what this notation means. And then let me write minus 3 cosine squared x, and this equals 0. And again, this right here is going to match this right here. So all I'm going to do now is take this right here and plug it in for that right there. Let me slide down and get a little room going here. And let's go ahead and say that we're going to have this 2 sine of x and then cosine of x. And let me wrap this. This whole thing's going to be squared. So again, just plugging in there, the whole thing squared. Then minus, you have your 3 cosine squared x, and this equals 0. All right, now this is multiplication here. So in other words, if you had a times b times c, and this guy was squared, this is a squared times b squared times c squared. So that's a rule we learned a long time ago in algebra. So I'm just going to apply that here. So everything will be raised to the second power or squared. So you're going to have 2 squared times sine squared x times cosine squared x, and then minus 3 cosine squared x, and this equals 0. Obviously, 2 squared is 4, so you can just put that like that. You can drop the multiplication symbol. You don't really need it. You can keep it if you want. So basically, you're going to solve this with factoring. You'll notice that you have cosine squared x and cosine squared x. So you can just pull that out. So let's pull that out in front of some parentheses. You'll have cosine squared x times the quantity. So inside, you're going to have 4 sine squared x, and then minus 3, close that down, and this equals 0. All right, so using the zero products property, now we can say that cosine squared x is equal to 0, or we have 4 sine squared x minus 3 is equal to 0. Well, this one by the square root property, if cosine squared x equals 0, then the cosine of x you would say is equal to plus or minus the square root of 0, but there is no plus or minus the square root of 0, it's just going to be 0. So you can change this into cosine of x just equals 0. Now moving on to the other one, 4 sine squared x minus 3 equals 0. Add 3 to both sides of the equation. This will go away. And let's say that this equals 3 here. And let's go ahead and divide both sides of the equation by 4. Let's cancel that away. And so basically, again, by the square root property, if sine squared x equals 3/4, then the sine of x, so the sine of x is equal to plus or minus the square root of 3/4. Let me move this up here. So this equals plus or minus the square root of 3/4. Of course, this would be plus or minus the square root of 3 over the square root of 4 is 2. All right, let me grab this real quick. Come down here to our unit circle. I think most of you can do this without it, but we'll just put it here for a visual aid. Again, we want to solve over the interval from 0, with that being included, to pi, again, because of the period of what we're working with. So I only need to solve over this because the solutions you'll see will repeat every pi. So for the cosine of x being equal to 0, again, just working in this interval, it's just going to be right here at pi over 2. You don't need to list the 3 pi over 2 because we just want to work in this interval. Then for the sine of x being equal to plus or minus the square root of 3 over 2, well, again, the square root of 3 over 2, if you look for that as a sine value, you have it right there at pi over 3, and then you're also going to have that right here at 2 pi over 3. Now, again, if you think about this in terms of how solutions repeat, if you look at a solution here, you're also going to have a solution here because you have square root of 3 over 2 here and negative square root of 3 over 2 here. And remember, it's plus or minus the square root of 3 over 2. So you can see that this is going to repeat every pi. So this right here would repeat every pi. So add pi, get there, add pi, you'll keep getting solutions. The other one, this 2 pi over 3, again, if you add pi, you're going to be at 5 pi over 3. So again, add pi, you get to another solution. Add pi, you get to another solution, so on and so forth. Again, this is negative square root of 3 over 2. This is positive square root of 3 over 2. But again, we want either positive or negative square root of 3 over 2. So we're good to go there. Then this one right here and this one right here, again, every pi. You can see your cosine value is 0 there as well. So add pi, add pi, add pi. You keep getting to solutions. All right, so thinking about the intervals you'll have between 0 and pi over 3, then between pi over 3 and pi over 2, between pi over 2 and 2 pi over 3, and then between 2 pi over 3 and pi. So that's all you really need to do. Let's go down to our little table. So I've already set it up. So I'm going to work with it in this form. So sine squared of 2x minus 3 cosine squared x. Where is that greater than 0? We don't care about where it's equal to 0 because we already know that. It's going to be at pi over 3, pi over 2, and 2 pi over 3. We've already established that. So basically looking for where it's greater than 0, we're going to plug in something in that interval and just test, and we'll look at what we get and see if it's positive, we'll accept it. If it's negative, we'll reject it. So I'm going to choose pi over 6 in this interval between 0 and pi over 3, and I get exactly negative 3/2. So this would be rejected, it's negative. And then in the interval between pi over 3 and pi over 2, I'm going to pick 5 pi over 12, which is going to be 75 degrees. And so I get about 0.05. I don't care what the value is, it's positive, so I'm going to accept that. Then in the interval between pi over 2 and 2 pi over 3, I'm going to pick 7 pi over 12, that's 105 degrees. And again, if I plug that in, I get about 0.05, so that's positive, so that's going to work. And then in this interval between 2 pi over 3 and pi, I'm going to pick 5 pi over 6. If I do that, I get exactly negative 3 halves, so that's negative, it's not going to work. Now let's go back down, and let's think about this here. So you have between pi over 3 and pi over 2, so it works there. And then you have between pi over 2 and 2 pi over 3, so it works there. Now, would pi over 2 be included? Yes, this is a non-strict inequality. Would pi over 3 be included? Yes, this is a non-strict inequality. Would 2 pi over 3 be included? Yes, this is a non-strict inequality. So essentially, let me get rid of this circling here. I'm just going to do this like this as one continuous piece here. And again, if you added pi to each part, well, essentially, if you start with pi over 3, again, if you add pi, you're going to get to 4 pi over 3. And then if you took 2 pi over 3 and you added pi, you're going to get to 5 pi over 3. So this piece right here would work as well. And again, you could just continue in that pattern forever. Let me get rid of this and we'll write the solution out. I think it's pretty easy to do. So we're going to say that x is greater than or equal to, let's go pi over 3, so pi over 3, and then plus pi n. Again, the period of what we're working with is going to be pi. Let me put this back in here. We'll say and it's less than or equal to, we're going to go 2 pi over 3. So 2 pi over 3 and then plus pi n. All right, let me paste this solution in here. So again, you can go to Desmos and just type in y equals sine squared of 2x minus 3 cosine squared x. And we're trying to figure out where the y values are either equal to 0 or greater than 0. So basically, if I look at these x-intercepts here, let me just point them out. So we have this pi over 3 here, and then we have this 2 pi over 3 here. Now you'll notice that we also have this x-intercept of pi over 2. Now notice if I go between here, you're going to see that, and this is a little bit hard to make out, but basically everywhere here, starting from pi over 3 and going to 2 pi over 3, I either have a y value of 0 or something that's greater than 0, so this whole thing would work. So from pi over 3 to 2 pi over 3, that would basically all work, and including those end values. Now again, if you add pi to each part, you would get additional solutions. So if I said pi over 3 plus pi, that's adding 3 pi over 3, so that would be 4 pi over 3. If I took 2 pi over 3 plus pi, so plus 3 pi over 3, that's 5 pi over 3. And again, if you want to take that middle guy there, that x-intercept of pi over 2, well, if you add pi, that's going to be plus 2 pi over 2, so that's 3 pi over 2, so that guy right there. And again, everywhere starting from 4 pi over 3 and including that, going up to and including this 5 pi over 3, we're going to have a solution because the y value is either 0 or greater than 0. So basically, you can just keep doing that as much as you want. So you'd have a solution here, and so on and so forth. So let's go ahead and say that x is greater than or equal to pi over 3 plus pi n, and less than or equal to 2 pi over 3 plus pi n, where n is any integer. All right, let's take a look at problem 9. So here we have negative 2 cosecant of x sine of x is less than or equal to negative square root of 2 cosecant of x. All right, for this problem, you can solve it in quite a few different ways. The first thing I'm going to do is just add the square root of 2 cosecant of x to both sides of the inequality, just to get things started. So let me cancel this away and say this is 0. So I'm going to write negative 2 cosecant of x sine of x, and then plus the square root of 2 cosecant of x, and this is less than or equal to 0. So let me grab this real quick. Let's come down here and think about this. So basically, let's say we worked on something like y is equal to negative 2 cosecant of x sine of x plus the square root of 2 cosecant, let me make that c a little bit better, of x. And I asked you, what's the domain? So what am I allowed to plug in for x? Remember that the cosecant of x, so the cosecant of x, by definition, is 1 over the sine of x. So you're thinking about division by 0 here. So where would I have a sine value of 0? So that's at 0, pi, 2 pi, 3 pi. So basically pi n, where n is any integer. So if I ask you for the domain for this, you would say that the domain is the set of all x such that x is not equal to pi n, where n is any integer. So let me erase this. We'll bring this back up when we need it. How do I solve this inequality here? Again, I'm just going to solve the related equation to get things started. So let's say negative 2 cosecant of x sine of x plus the square root of 2 cosecant of x, and let's say this equals 0. So again, a lot of you are going to notice that the cosecant of x times the sine of x, that's going to be 1. So as long as you're not plugging in something to where this is undefined, this is going to be 1. This is going to be 1 over the sine of x times the sine of x. So as long as your sine value is not 0, you're basically good to go. So this would cancel, and you're going to get 1. So you could replace this with 1 and say -2 plus square root of 2 cosecant of x and figure out where's that equal to 0. So you can do that if you want. Basically, what I'm going to do is use a different approach. So I'm going to actually factor this. So I'm going to change this form over. Instead of -2, let me write this as negative square root of 2 times the square root of 2. So basically, if you multiply that together, you get -2. And then I'm going to pull out square root of 2 cosecant of x. What's going to happen is that's basically going to go away. You're going to have a no solution, and you'll have something in terms of sign that we can go to the unit circle and just solve really quickly. Okay, so let me say we pull out the square root of 2 cosecant of x, and then inside you'd have negative square root of 2 sine of x, and then plus, pull this out, you'd have 1, close it down, and this is 0. Okay, so this right here, if you do square root of 2 cosecant of x is equal to 0, divide both sides by the square root of 2, and you just get the cosecant of x equals 0, which has no solution. So that has no solution. Then over here, basically you're going to work on this part. So let me slide down a little bit. You have the negative of the square root of 2 sine of x plus 1 equals 0. Subtract 1 away from each side. You'd have this is equal to -1. Divide both sides by negative square root of 2. Let me just erase it from over here. Negative over negative is positive. And if you rationalize the denominator, you're going to get sine of x is equal to the square root of 2 over 2. Okay, let me grab this real quick. Keep in mind where this guy is also undefined, so we're going to need that. So the solutions here are going to repeat every 2 pi. So let me solve this over the interval from 0 to 2 pi, like this. So x would be equal to, again, square root of 2 over 2. Sine is positive in quadrants 1 and 2. So I want pi over 4. There's your sine value of square root of 2 over 2. And then also where I have a pi over 4 reference angle in quadrant 2. So 3 pi over 4, sine value of square root of 2 over 2. So let's put x equals, we're going to put pi over 4, and then 3 pi over 4. Now, when you set up critical values, you also have to go with where the guy is going to be undefined. Remember, the cosecant of x is undefined where the sine value is 0. So that's going to be right here at 0, and then right here at pi. So this will give us quite a few intervals to set up. I have everything ready on our table on the next page. Let me just show you what's going on here. So between 0 and pi over 4, and then between pi over 4 and 3 pi over 4, between 3 pi over 4 and pi, and then between pi and 2 pi. Okay, so everything's set up. So we have -2 cosecant of x sine of x plus the square root of 2 cosecant of x. Where is that less than or equal to 0? We know it's going to be equal to 0 at the pi over 4 and 3 pi over 4. So those will be included when we set up our solution. But basically right now we need to figure out, well, where is it less than 0? If I go into this interval here and I choose pi over 6, I get about 0.83. So that's not less than 0. That's positive. So let's get rid of that. If I go into this interval and I pick 2 pi over 3, I get about negative 0.37. So that's negative. So this is going to work. And then if I go into this interval here and I pick 5 pi over 6, again, I get about 0.83. So this is not going to work. It's positive. And if I go into this interval here, I pick 4 pi over 3, and I get about negative 3.63. So this is negative, so this is going to work. All right, so putting this solution together, you've got between pi over 4 and 3 pi over 4, and then between pi and 2 pi. So coming back, you have between pi over 4 and 3 pi over 4, and then you have between pi and 2 pi. So you've got to think about what's going to be included and what's not going to be included. Right here, this would be included because this is going to make that inequality true, because pi over 4 and 3 pi over 4, you're going to get 0. So basically, that would be a true statement. But 0, 2 pi, 4 pi, something like that, that's not going to work because it's undefined there. So you cannot put 2 pi in, and you cannot put pi in. Same thing. So pi, 3 pi, 5 pi, basically pi in where n is any integer. You can't include those. You're going to see you have vertical asymptotes when we get to the graph. So let's write that x is greater than or equal to, let's go pi over 4 plus 2 pi n, and it's less than or equal to, let's go 3 pi over 4 plus 2 pi n. Then I'm going to go or, I'm going to take this part right here. So x is greater than, we're going to have pi plus 2 pi n, and it's less than, this right here would be 2 pi. So let's write that as 2 pi plus 2 pi n. Again, these are not included because at pi and 2 pi, it's undefined. So you cannot include that. These are included because at pi over 4 and 3 pi over 4, I would get a value of 0, and 0 is equal to 0, so that would work. Let me go ahead and grab this. Okay. I have everything set up for us. Let me paste this in. Let me get rid of this highlighting. We don't need that. And it's a little bit hard to read, but basically you can go to Desmos and just make your own graph if you want to be able to see it more clearly. Essentially, when we look at this, we're looking for the y values where it's going to be 0 or less. So less than or equal to 0. If you go to pi over 4, so that's going to be right here, that's where it's equal to 0. If you go to 3 pi over 4, again, that's where it's equal to 0. So right here, this is all included. So from pi over 4 to 3 pi over 4. Again, if you add 2 pi to each part there, so pi over 4 plus, let's go 8 pi over 4, that would give you 9 pi over 4. If you go 3 pi over 4 plus 2 pi, that's going to be 3 pi over 4 plus 8 pi over 4. That's 11 pi over 4. So again, that's this piece right here. You can keep getting this piece again and again. So this right here, and then this right here, so on and so forth. So that's all of those. Now, the other part that you need, because again, this is less than or equal to 0, you need these parts right here. So how do you get that? Well, that's where we come in for this one, the OR. So you have pi and 2 pi. So this is pi right here. You have a vertical asymptote. And this is 2 pi. You have a vertical asymptote. So anything that's greater than pi and less than 2 pi, well, here, you're going to be less than 0 in terms of the y values. So that works as well. And again, you can go through and add 2 pi to this. So pi plus 2 pi is 3 pi. So that's going to put you right here. This is 3 pi. And then if you take 2 pi plus 2 pi, that's going to be 4 pi. So this is 4 pi right here. So again, if you look at this piece right here, if you're greater than 3 pi and less than 4 pi, you're going to be good to go again. And you would have this piece right here and so on and so forth. So that's going to be our solution. We're going to go ahead and say that x is greater than or equal to pi over 4 plus 2 pi n and less than or equal to 3 pi over 4 plus 2 pi n. So again, those are included. Then or, and here these are going to be excluded because these are where we're undefined. So we have x is greater than pi plus 2 pi n and less than 2 pi plus 2 pi n. All right, let's take a look at problem number 10. So here we have the cosine of x plus 1 is greater than or equal to negative square root of 3 cosine of x over 2. So the first thing I'm going to do is add square root of 3 cosine of x over 2 to both sides. Let me write that over here. So square root of 3 cosine of x over 2 plus the cosine of x plus 1 is greater than or equal to 0. So let me grab this and come down here and paste this in. So I'm going to solve the related equation first. So let's write out square root of 3 cosine of x over 2 plus the cosine of x plus 1 is equal to 0. Now, you could use a half angle formula for this, but if you follow my videos, you know that I don't like that because you end up squaring both sides of your equation and then you have to check. So that slows you down. So basically, you can make a substitution here. You can let something like u, so let me let u be equal to x over 2. And then what you can do is you can multiply both sides by 2, and you could say 2u is equal to x. So all I'm going to do is in the place of x over 2, I'm going to write a u. And in the place of x, I'm going to write a 2u. So just like this, and come to a fresh sheet. We're just going to work on this. So this is going to be in terms of u. So basically, we know that right now, the period for this is 2 pi, and the period for this is pi. So the least common multiple, if you look at it, again, if you have pi and 2 pi, the least common multiple is going to be 2 pi. So solutions here in terms of u are going to repeat every 2 pi. So just keep that in mind. All right, so I'm going to replace the cosine of 2u with a little identity. So cosine of 2u, again, you have 3 of these you can pick. So I'm going to use 2 cosine squared u and then minus 1. So I'm just going to plug this right here in for this right here. So that's going to go right there. And again, let me show that this is matching this. All right, so let's say we have the square root of 3 cosine of u and then plus 2 cosine squared u and then minus 1. And then you have your plus 1 and this equals 0. All right, so pretty easy to solve this. Negative 1 plus 1, that'll cancel away. So what I'm going to do is just factor out cosine of u. So if I pull that out, inside you'd have the square root of 3 and then plus you'd have 2. Cosine squared u is cosine of u times cosine of u. So you just have cosine of u here, and then this equals 0. All right, so to solve this, we're going to say cosine of u is equal to 0, or you're going to have square root of 3 plus 2 cosine of u is equal to 0. Subtract the square root of 3 away from each side. So minus the square root of 3, and then divide both sides by 2. So this would be divided by 2 here, and divide by 2 here. That's just going to go away. So let me move this over here. So let me grab this real quick. Let me come down here and paste this in. So let me put a little border here. Again, when you think about it in terms of u, things are going to repeat every 2 pi. So I'm just going to solve this over the interval from 0 to 2 pi. So this is in terms of u. So cosine of u equals 0. So again, where's the cosine value 0? So it's going to be at pi over 2 and 3 pi over 2. And then cosine of u equals negative square root of 3 over 2. So I'm going into quadrants 2 and 3, and I'm going to find a reference angle of pi over 6. So 5 pi over 6, there's your cosine value of negative square root of 3 over 2. And then 7 pi over 6, there's your cosine value of negative square root of 3 over 2. So let me write that u is equal to, you've got pi over 2, you've got 5 pi over 6, you've got 7 pi over 6, and then you've got 3 pi over 2. So this is actually going to set up 5 intervals. So you can have between 0 and pi over 2, between pi over 2 and 5 pi over 6, between 5 pi over 6 and 7 pi over 6, between 7 pi over 6 and 3 pi over 2, and then between 3 pi over 2 and 2 pi. All right, so coming down here, I've already set up the table. So we're going to work with the inequality in this form. 2 cosine squared u plus square root of 3 cosine of u is greater than or equal to 0. Of course, we know where it's equal to 0 already. We solved the related equation. So pi over 2, 5 pi over 6, 7 pi over 6, and 3 pi over 2. But where is it greater than 0? Again, in each interval, you can just pick something, plug it in, and you're just worried about is it positive or negative. You don't care about the actual value. So here, if you plug in pi over 4, you get about 2.22. So yeah, this would work. Here, if you plug in 3 pi over 4, you get about negative 0.22. That's negative. That won't work. Here, if you plug in pi, you get about 0.27, so that's positive, so that would work. Here, if you plug in 5 pi over 4, you get about negative 0.22, so that's not going to work. And then here, if you plug in 7 pi over 4, you get about 2.22, so that's going to work. Now, this one and this one, you're going to combine that. Remember that this is just set up this way because we solved over the interval from 0 to 2 pi. And basically what you would do is combine those. So it's just going to be from 3 pi over 2, and then this won't be pi over 2. Let me go to the unit circle. Let me get rid of this, and let me highlight the stuff that works so you can see this. I think this is the trickiest part. So basically we know that this right here, so between 3 pi over 2 and this guy right here, which will not be pi over 2, again, because if I'm starting here and I'm rotating here, this is not pi over 2, it's pi over 2 plus 2 pi, so that's basically going to be 5 pi over 2. Now, these would both be included because it's a non-strict inequality. So remember, this is in terms of u. So let me write u is greater than or equal to, let's go ahead and put our 3 pi over 2 plus 2 pi n, and it's less than or equal to, again, instead of this being pi over 2, you go pi over 2 plus 4 pi over 2. So that's 5 pi over 2. So let's put 5 pi over 2 plus 2 pi n. Okay, let me get rid of this. Now, we've done enough of these problems to know that if you wanted to, you could rotate clockwise here and say this is negative pi over 2. If you wanted to put negative pi over 2 here and pi over 2 here, that's fine. That will work for the solution in terms of u. So let's go ahead and put, or we need the other part, and that's going to be this part right here. So basically, from 5 pi over 6 to 7 pi over 6, and again, those are both going to be included. So I'm going to say that u is greater than or equal to 5 pi over 6 plus 2. Let me scooch this down. So 2 pi n. And then it's going to be and less than or equal to your 7 pi over 6 plus 2 pi n. Okay, let's come back here and let me put a little border. Remember that u is x over 2. So all you have to do is plug in an x over 2 here. So let's put x over 2 and then x over 2. Now, if you want to solve for x, you're going to multiply everything by 2. That's all you have to do. So let me slide down here, and I'm just going to start. So we're going to write out 3 pi over 2 times 2 plus 2 times 2 pi n is less than or equal to, let me make that a lot better there. We'll have x over 2 times 2, which is less than or equal to 5 pi over 2 times 2 plus 2 pi n times 2. So this cancels. You're going to get 3 pi. And then plus this would be 4 pi n. Let me make this 3 a little bit better there. And then this would be less than or equal to, this cancel, so this is x, which is less than or equal to, the 2's cancel, so you're going to get 5 pi plus 2 pi n times 2 is 4 pi n. Okay, let me get rid of this. So that's part of your solution. Let me drag this up here, and then let me put or. So the other one is going to be coming from this right here. Again, you're just going to multiply everything by 2. So you're going to have 5 pi over 6 times 2 plus 2 times 2 pi n. So this is less than or equal to x over 2 times 2, which is less than or equal to, you have 7 pi over 6 times 2 plus 2 pi n times 2. Again, coming through here, so 6 divided by 2 is 3. So that's going to be 5 pi over 3. Let me write this down here. So let me write 5 pi over 3, and then plus 2 times 2 is 4, so this is 4 pi n. So this is going to be less than or equal to, the 2's cancel, so this is just x, which is less than or equal to, 6 divided by 2 again is 3, so this is 7 pi over 3, and then plus 2 times 2 is 4, so this is 4 pi n. Okay, let me get rid of this, and this right here is our final solution. So let me grab this, let me paste this in here. So we're graphing y equals cosine of x plus square root of 3 cosine of x over 2 plus 1. When we think about the period of this guy, it's going to be 4 pi. The period of the cosine of x is 2 pi. The period of the cosine of x over 2 is 4 pi. So you want the least common multiple of that. So the LCM of 2 pi and 4 pi is 4 pi. So that's why you have this plus 4 pi n all over the place here. So we want to figure out where the y values are going to be greater than or equal to 0. So at 3 pi, it's equal to 0. At 5 pi, it's equal to 0. And again, if I look between, my y values are greater than 0. So that's going to work there. Now I'm going to go this way because I don't have enough information this way. The graph is just not long enough for me. You can do this on Desmos if you want. But basically, I'm going to subtract 4 pi away from each part. So 3 pi minus 4 pi is negative pi. So that would be negative pi right there. And then if you do 5 pi minus 4 pi, that's going to be pi. So right there. So that's another piece. So here the y values again are greater than 0. So you could have also written this and said, well, it's negative pi plus 4 pi n, which is less than or equal to x, which is less than or equal to, it would be pi plus 4 pi n. So another way to write that part. Now for the other part, we're looking at 5 pi over 3. So that's right there. And then we have 7 pi over 3. So that's right there. So basically you're 0 at those values. And then between them, your y values are greater than 0. So that would work. Again, if you subtract away 4 pi from each part, well, 5 pi over 3 minus, let's go 12 pi over 3, that would be negative 7 pi over 3. So that's going to put you right here. And then if you go 7 pi over 3 minus 12 pi over 3, that's going to be negative 5 pi over 3. So that's going to put you right there. So again, this piece right here. So you could have written it like that as well. So I'm just going to go with the solution as given. So we have x is greater than or equal to 3 pi plus 4 pi n and less than or equal to 5 pi plus 4 pi n. Then or you have x is greater than or equal to 5 pi over 3 plus 4 pi n and less than or equal to 7 pi over 3 plus 4 pi n, where n is any integer.